Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
So let's start with lecture number 2, that is about stress and strain. That lecture is totally about axial loading. So we will deal this lecture, and this lecture will be about this lecture will tell us about the detail about axial loading and their effects on the material. By effect we means the strain produced in the material. This is the overview, means that what we will cover in this lecture is we will talk about stress and axial loading. Then we will discuss somewhat normal strain, then stress strain test that is performed on universal testing machine. Then we will discuss stress strain diagram for ductile material and then for brittle material. Then we will move toward Hooke's law, and we will see what is Hooke's law and what is modulus of elasticity. We will then cover elastic versus plastic behavior. After covering that, we will move toward fatigue and then deformation under axial loading. We will solve some problem. Then what is static indeterminacy and how to tackle this static indeterminacy. We will have a problem. We will solve this. Then thermal stresses and Poisson ratio. So I will cover all the topic that is tick marked in our today's first lecture. Clear? The rest topics will be covered in the next lecture, that will be at 2 p.m. So I will switch toward the slides that is also open over here, because it will become easier for me to write over here instead of there. So let's start with normal strain. So as you know that whenever a load is applied to any member, for example, if this is a member that is a wait, why I am not able to write anything. So invitation, present, documents, page view. You have to just wait for a few minutes. Okay, so we will move toward this. I have some problem. So basically, whenever you have any object or a member, for example, this is a rod, steel rod, or any member of any material, and that is subjected to load, and that load is given as P. Now we have discussed in our previous lecture that what is normal stress. So we have seen that those loads which are perpendicular to the surface where it is applied, so this load is applied on this surface that is perpendicular to the load, so it will create deformation in this rod. So internal deformations will also be created, and this body will resist the deformation. So we define the normal stress as the internal resistance offered by the material to the per unit area, that is known as normal stress, and that normal stress we have written that is P over A. So this normal stress is actually producing strain, that is known as normal strain. Now what is strain? Whenever you applied a load to the member, just like in this example, so you will see that there will be deformation, there will be increase in the length of this object. So for example, if this was the initial member, clear, and after applying load, just in this, if you applied the load, so its length will increase. So if this is the let's say this is the original length of the rod, that is represented as L. Now after applying load, this much increase has been occurred in this load, and this increase is known as change in length, that is represented as delta. So we define strain as change in length divided by original length. Clear? So strain is represented as epsilon, and that is equal to change in length over original length. And change is length is represented as delta, and original length is L. So this is known as normal strain. Clear? So normal stress exerting on a body will create a normal stress. So if a bar is subjected to a direct load due to stress in the bar, there will be change in length. If bar has original length L and change by amount delta, so this strain will be equal to change in length divided by original length, and this strain is known as normal strain. Now the same is the case that if you have a bar, so in this case you can see that the load is tensile load, so definitely there will be increase in length. Clear? So again, if you have the same scenario and now this same length of bar is subjected to compressive load, that is also P. So in this scenario, if this is the original length, so now its length will decrease and it will be toward this, and this will be the change in length, and this change will be in this upward direction, and there will be a contraction in the length. So again you can find the strain, that is change in length over original length. So in both scenario you have seen whether it is tensile stress or compressive stress, or tensile load or compressive load. So there will be change in length. That change may be positive or change may be negative. By positive means increase in the length of the member or bar, and by negative means decrease in the length of the bar. So that depends on the load. So if you have tensile strain, so its value will be positive, which shows that there is increase in the length. If your value of strain comes out to be negative, so it does not mean that it is going toward negative side. It means that your length is decreasing. Clear?
Yes, sir. Yes.
Okay. So then you can see that there are different scenarios given. The first one, figure 2.1, shows you that there is a bar of length L. Their bar BC of length L is given, and the area of this bar is represented as A. So let me also zoom it so that it may be clearly visible to you. Okay. Little bit. Okay, so this bar BC having area A and original length L, that is fixed at one end at point B. Now this bar is subjected to normal load, that is represented as P, and due to this load there will be a reaction force at point B, and this load is tensile load. So definitely you can see that there will be an increase in length. So this will be the increase in length, that is also given over here as well. So in this case we can see that stress sigma, that is equal to P into perpendicular distance, perpendicular area, or area that is perpendicular to this load P. So sigma will be equal to P by A. And what about the normal strain? Normal strain, as we know that it is equal to change in length divided by original length. So we can, if you know the change in length and you know the original length, so you can divide the change in length by original length, so it will give you the strain. Now in the case B, you can see this bar B dash C dash is now having area 2A, and it is of the same length as that of initial bar BC, and we applied a load that is of 2 times of initial load. So here this area is 2A, means the area is doubled and load is also doubled. So now in this case you can see that stress will be equal to 2P over 2A. Clear? And the strain is again the change in length, that is this much divided by original length. So in this case you have seen that if we increase the load and area, strain remains the same, just like in first scenario as well as in second scenario. But the condition is that if material remains same. If the material is different, so definitely the strain, both strains will be different. So for same material under different loading and different area, their strain will be same, because strain is a material property. Now in the third scenario is that you have the rod that is of double length. Clear? And the load and area is same as in figure 1. So in this scenario you can see if the length is 2L, so definitely the change in length will be also 2 delta. So in this case stress will be equal to P by A and strain will be equal to 2 delta over 2L, and again it will be equal to same change in length divided by original length. So it means that strain is material property. Clear? So if you have same material, so it will give you same strength irrespective of the load. Clear? We will also discuss this in Hooke's law, because according to Hooke's law, stress is directly proportional to strain, but in elastic region. After elastic region, this is not proportional. This strain is not proportional to this. This stress is not proportional to this strain. So we will discuss that in that slide in detail. Any question till now?
No, sir.
Okay. So Hooke's law. Most of you know about Hooke's law, and Hooke's law states that whenever you applied a load to any material, that is, when you applied load to material, there it deforms. It deforms. By deformation means either increase in its length, clear, or if the load is compressive, so there will be decrease in the length. So there will be a deformation. Epsilon. Change in length. Now again that stress will be equal to P over this area A, clear, and the strain or deformation will be equal to change in length divided by original length. So if the total length is L, clear. So according to Hooke's law, the stress is directly proportional to strain, but within elastic limits. So whenever you applied a load to this bar or any material, so it will deform. There will be a deformation in that part or there in that bar. So when you further increasing the load will also increase the deformation in the body. So all deformable body materials deform under the load. So materials under the load deforms, and that deformation depends on the load applied. Clear? So material is said to be elastic if it returns to its original position after the removal of load. Now if you remove this load and the body comes back to its original position, that is L, so this material is known as elastic material, and the behavior is known as elasticity. The phenomena is known as elasticity, or we can say elasticity is the phenomena by virtue of which a material regain its original position. So if this, again I will draw, so if this is the original part and you have subjected it with load, so it will increase, it will deform, and it will come to a new position. So if this was original length L, now the deformation is this much. Clear? So if you remove the load and this body goes back to its original position, that is L, so this material is known as elastic material, and the phenomena by which it comes back to its original position is known as elasticity. Clear? So now what happens if you further increase the load and there is a limit in which the stress is directly proportional to strain, and after that limit if you go further, that there will be also increase in the length, but that length will be that increase will be not linear. So I will also draw over here just for, so if you remember stress strain curve, this is stress and this is strain. So if you applied a load on any material, so it will linearly, by increasing the load, the strain will linearly increase. So it will come to a point P, for example. So this is proportional limit. And if you remove the load, so the material will go back to its original state and there will be no strain. So now further increasing the load will also cause the increase in length. So if this is a point B, I will draw it a bit larger in the next slide. So if you increase the load, there will be increase in length, and a point E, that is known as elastic limit, or elastic limit is achieved. Now again at this point, if you remove the load, it will bring back the object, the object will come back to its original position having no deformation. So that point is known as elastic limit. Now what is the difference between P point and E point? So up till P point, stress is linearly proportional, means if you increase the stress, the strain will linearly increase accordingly. But after point P, if you are increasing the load, the strain will also increase, but that will be not linear. Clear? So we will come back to Hooke's law. The Hooke's law states that within elastic limit, stress is directly proportional to strain. So again, we have studied that if you remove this proportional sign and bring it to equal, so there will be a constant E. So this stress will be equal to E into epsilon. Clear? Now what is E? E is a constant, and that is known as modulus of elasticity. And this E is equal to stress over strain. So now modulus of elasticity is the material property, and by virtue which shows you, actually it shows you the resistance to the deformation, that how much the material resists to deformation and brings it to its original position within elastic region. Clear? So this equation E is equal to sigma over epsilon is the equation of modulus of elasticity, and this equation is only valid in elastic region. Clear? Any question? Okay. Then we will move to stress strain test. This test is a very popular test, and you have performed it in your labs as well. And this test, stress strain test, is basically performed on any material or rod in order to find its yield strength as well as ultimate tensile strength. Now this test is performed on a machine that is known as universal testing machine. You might aware of this machine, universal testing machine. This machine can be used to perform tensile test, compressive stress, bending stress, etc. So now for this universal testing machine or for tensile test, you might need a specimen, and this specimen you have to prepare this specimen according to some standards. There are standards available, for example, ASTM standard, American Society of Testing Material Standards, and according to standard that is available in ASTMs, you have to prepare your workpiece for the testing purpose. Now this part that is according to ASTM is now clamped in universal testing machine, and this machine you can see that it has two jaws, the upper jaw and the lower jaw, in which this workpiece is clamped. Okay, now this workpiece, this jaws can move closer to each other, this can move closer to each other, and this jaw may move opposite to each other. If they move opposite to each other, you can perform tensile test. If it comes closer to each other, so there will be a compressive stress. So you have in that scenario you will be performing compressive strength. Clear? Now there are threads that are created at the end, and the purpose of this thread is that these jaws may able to grip this workpiece in an effective manner such that there is no slippage. Clear? So when this workpiece is loaded or mounted in this jaws, so we will, according to ASTM standards, you have to mark 2 points on this workpiece and note down its length, and this length will be according to ASTM standards. Clear? So after mounting the workpiece on these machines, so based on your requirement of test you perform, you applied the load through this machine. So in tensile test, you applied the load just like shown over here. Let this load is P. Clear? So when you increase the load, the machine automatically records the value of force or stress as well as strain that are produced in the workpiece. Clear? So it will also give you a graph. There are many type of machines available in some machines are connected with computers that give you graphs as well as data point at every instant of load. Clear? So we have to note the loads and the strain as well, and then by using that data we plot the stress strain curve. Otherwise, most of the machines also plots the stress strain curve. So if this is let me draw the stress strain curve also. So if this is on y-axis, we take what? We take the stress. Clear? On y-axis we take stress, and on x-axis we take strain. So when you applied load, so load will be, stress will be directly proportional to strain till elastic proportional limit. Let this point is P. Now what does proportional limit means? That up till this point, if you remove the load, there will be no strain. If you release this load P, so definitely there will be no external force, so there will be no strain, and the object will come back to its original position, and this point is 0. Clear? So up till proportional limit, stress is directly proportional to strain, means that if you are increasing the stress at every point there will be a stress. So at every point there will be a stress. So according to that, there will be strain as well, and this strain is directly proportional to this stress. Now what happens if you further increase the load? So it will further deform. There will be a deformation in the workpiece. But now the deformation is not linear. So up till a certain point, there is point that is known as E. This point is known as E. So let me draw it. This is a point P and this is point E. So again, this point E is in elastic region or elastic limits. What does it mean? It means that if you remove the load, the body will come back to its original position having no deformation. Again, I have told you the difference between proportional point and elastic points. In most of the interviews, they ask you to tell you to define what is the difference between proportional limit and elastic limit. So till proportional limit, the stress is directly or linearly proportional. Clear? But in elastic, if you cross the proportional limit and move toward elastic limit, clear? Sir, or elastic region. So here the stress is producing strain, but it is no more linear. So this point is known as elastic region. Now if you further increase the load, so it will further causing the strain in the body, and a point will come where a permanent deformation will be occurred in this workpiece, and this point is known as yield point. Why? This is elastic point, this is proportional point, and this is yield point. Now till yield point, the workpiece is safe, and if you remove, the workpiece will come or the workpiece can come to its original state with having no strain in that. Clear? So if you cross this limit, this yield point, so then there will be a permanent deformation. What does permanent deformation means? That if you cross this point or stress beyond this, if you apply stress beyond this point, so now the deformation is permanent, and if you remove the stress, so there will be strain in that object, and the object will not go back to its original position. So that is known as permanent deformation. Any question till now?
No, sir.
If you have difficulty in English, I can switch as well. ठीक है ना? अगर आपको कोई मसला है तो बताएं फिर. So up till point E, this region, अगर मैं यहाँ से ये जो इस पॉइंट से इस पॉइंट तक का ये स्ट्रेट होगा, this region is known as elastic region. Elastic region. What does elastic region means? That in this region, if you remove the stress, so there will be, the body will come back to its original state and there will be no strain. But if you cross this yield point, यहाँ तक, again I am, let me correct it, यहाँ तक, yield तक, यहाँ तक, that is elastic limit. ठीक है ना? Clear? But if you cross the yield point, so now this region will be plastic region. Yeah, because there will be a plastic deformation. And if you remove the load, so the object will not come back to its original position and there will be a strain in the object. Now, this point where yielding start or where the permanent deformation start, so at this point the stress will be known as sigma y. नजर आ रहा है आप लोगों को? इस पॉइंट पे जो है, मैं इधर लिख देता हूं, इस पॉइंट पे जो स्ट्रेस होगा दैट विल बी यील्ड स्ट्रेंथ. ठीक है ना? सो नाउ देयर आर टू टाइप ऑफ यील्ड stress. The one is upper limit and the one is lower yield strength. The one is upper limit yield strength, upper yield stress, and the another one is lower yield stress. I will discuss it now. So what is upper yield stress and what is lower yield stress? So if you go to the microstructure of any material. So atoms are arranged in a definite order and they are bounded with each other as well. So now if you applied a load on that, it will cause the length of the material to increase, or the bonding between the atoms will tend to deform. Clear? So it will deform if the load is P. So further applying the load, the length will increase, and this bond or this strength or the bonding between these two atoms will resist this against this applied load. So a point will come that this bond will not able to resist further the load. So in that point, at that point, the slippage will occur between the planes. Clear? So अगर आप देखें, so this point is known as upper yield strength. Clear? So why it is upper yield strength? Because you can see that applying load on these atoms will cause the elongation in their bonding length. Clear? So when you apply the load, the resistance will increase. So this resistance, that is known as yield strength. Now what happened when you further increase the load? So there will be further elongation in this bond, and at certain point it will not be able to resist. So definitely there will be resistance, there will be slips in the planes, and it will be not in equilibrium condition. जो मैं कहना चाह रहा हूं उसका मतलब ये है कि इनिशियली अगर आप स्ट्रक्चर देखें, सेल स्ट्रक्चर देखें किसी भी मटेरियल का, so in that case they are in equilibrium condition, but when you applied load, so it will resist against this load. Clear? That is known as upper yield strength. But when you keep on increasing the load, so definitely a point will come where this bonding will not be able to resist the external load, so there will be slippage in their planes. आपने ये मेटलर्जी या मटेरियल में पढ़ा होगा, slippage of planes. So it becomes unstable, or it will be not in equilibrium condition. So in that case, during the slippage of planes, the stress will be reduced. आपके पास जो strength है या जो stress है वो reduce हो जाती है, and that is known as lower limit of strength. So this is upper limit of yield strength and this is lower limit of yield strength. फिर again मैं बता देता हूँ कि strength क्यों decrease हो जाती, yield strength क्यों decrease हो जाती है, इसलिए क्योंकि slippage of planes होती हैं और वो plane effectively वो load नहीं gain कर पाती, ठीक है ना. तो इसीलिए जो है वहां पे ये yield strength जो है वो नीचे की तरफ जाती है. But जब once it comes to another equilibrium state, जब slippage of plane हो जाती है, तो उसके बाद जो atoms हैं उनमें आपस में bonds जो है वो या उनकी position जो है वो rearrange होती है और उनमें फिर एक equilibrium establish हो जाती है. So after that, when you further increasing its load, it will resist. So this graph will go upward, just like that. Clear? So एक point आता है where the material can be able to take the maximum load, and that point is known as ultimate. At this point, the stress will be known as ultimate tensile stress, and this is the maximum stress that a material can bear. ठीक है. अच्छा, अगर मैं इसको, ये कौन सी स्लाइड है, ये वाली स्लाइड है, अगर मैं इसमें न्यू स्लाइड ऐड कर दूं नीचे और इसको मैं थोड़ा साफ करके बनाऊं तो थोड़ा बेहतर होगा. सो दिस इज स्ट्रेस एंड दिस इज स्ट्रेन. ठीक. सो अगर आप देखें तो ये इनिशियल पॉइंट है 0, ये लाइन आपकी वर्टिकल होनी चाहिए. So in elastic region, stress is directly proportional to strain, or this is point P, this is proportional limit, again this is point E, that is elastic limit, and then at yield point, this is known as upper limit of yield, U upper limit of yield strength. And after that point, the strength goes down. Why it goes down? Because due to the slippage of plane, the material is not able to take the further load, and you can see that load is not there. There is decrease in the load, but there will be a significant deformation in the material. So आपको yield, आप जब टेस्टिंग करते हैं UTM पे, तो आपको yield पॉइंट का तब पता चलता है कि जब आप रीडिंग्स देख रहे हो, उसमें आपके पास उस पॉइंट पे जहां पे लोड कम हो रहा है एकदम, या इंक्रीज नहीं हो रहा और आपके पास स्ट्रेन की वैल्यू बढ़ रही है, तो वो लोड आपका yield स्ट्रेस होगा या yield स्ट्रेंथ होगी, ठीक है ना. सो दिस इज द लोअर लिमिट of yield strength, and after that lower limit of yield strength, the slippage of the planes, the atom rearrange to a new equilibrium state, and then further increasing the load will also now the atom will further resist the external load, and it will keep on resisting. Now there will be a point, मैं ये चीजें थोड़ा इस लाइन को डिलीट कर देता हूँ, ठीक है ना. So at further increasing the load, there will be a point where a material can bear the maximum load, and this point is known as ultimate point, and stress at this point is known as ultimate stress. So ये point है आपका, that is ultimate stress. और इस point पे जहाँ पे yielding होती है, at this point is known as yield stress. So yield stress is less than ultimate stress. Ultimate stress is the maximum stress that a material can bear. Now what happened that if you further increase the load, now ये वो stress थी जो material maximum material जो है वो उठा सकता है. After that point, आपने अगर वो टेस्ट देखा हो तो the load keep on decreasing and a point comes where it rupture, ठीक है ना. So that is known as रप्चर लोड. उस पे मटेरियल टूट जाता है. क्यों? अच्छा, अगर आप देखें तो इस पॉइंट पे मैक्सिमम लोड है और ये एकदम जो है वो कम हो जाता है लोड, लेकिन स्ट्रेस तो बढ़ना चाहिए ना, क्योंकि आप तो मटेरियल पे लोड अप्लाई कर रहे हैं. स्ट्रेस किस चीज के बराबर है? फोर्स पर यूनिट एरिया. सो इफ यू आर गोइंग टू इंक्रीज द लोड, सो डेफिनेटली स्ट्रेस शुड बी इंक्रीज. सो इसको इस तरह होना चाहिए था, ठीक है ना. मैथमेटिकली इस ग्राफ को इस तरह जाना चाहिए था, लेकिन आप जब टेस्ट करते हैं तो आप देखते हैं जो ग्राफ बनता है वो अल्टीमेट टेंसाइल स्ट्रेंथ के बाद इट गोज डाउनवर्ड. सो जो आपको मैंने कहा था कि मैथमेटिकली इट शुड गो अपवर्ड, दिस स्ट्रेस इज नोन एज ट्रू स्ट्रेस. अगर आप इस जो है क्या नाम है, इस पॉइंट से शुरू हो के और ये ग्राफ इस तरह जाता है और ये ग्राफ ड्रा करते हैं, दैट इज नोन एज ट्रू स्ट्रेस स्ट्रेन कर्व, या इसे हम ट्रू स्ट्रेस भी कहते हैं, ठीक है ना. बट एक्चुअली इट गोज डाउनवर्ड एंड सडनली इट ब्रेक्स. नाउ ये क्यों डाउनवर्ड जाता है? क्योंकि जो उसके पास जो मैक्सिमम उसकी कैपेसिटी थी लोड उठाने की, वो तो उसने उठा दी. इसके बाद जो है वो इसमें इस मटेरियल में नेकिंग शुरू हो जाती है, जिसकी वजह से वो लोड बेयर नहीं कर पाता, और जब बेयर नहीं कर पाता तो वो लोड जो है वो डिक्रीज हो जाता है और वो मटेरियल टूट जाता है, ठीक है ना. सो अगेन दिस अप टिल दिस पॉइंट दिस इज नोन एज इलास्टिक रीजन, and this portion is known as plastic region, because there will be a permanent deformation in the material. Clear? So अब हम आते हैं जी
सर, अपर यील्ड पॉइंट पर जब पहुंच जाए सर, तो उससे वापस मटेरियल अपनी हालत में आ सकता है.
अच्छा, टिल दिस पॉइंट यील्ड अगर क्रॉस हो जाए तो फिर मटेरियल जो है वो वापस अपनी ओरिजिनल फॉर्म में नहीं आ सकता. देयर विल बी स्ट्रेन इन दैट, ठीक है ना. लेकिन अगर यील्ड पॉइंट तक है उससे मतलब वो क्रॉस नहीं हुआ, वो पॉइंट अभी वो पहुंचा नहीं, आप कह सकते हो कि इस यील्ड पॉइंट से पीछे जो है अगर आप उससे स्ट्रेस रिमूव करें या लोड रिमूव करें, सो इट विल बी go back to its original position having no strain. But if you cross this yield point, so there will be a permanent deformation.
Okay, sir.
Okay, so we were talking about true stress, and this stress is known as engineering stress. Engineering stress. अच्छा, बहुत सी जगहों पे टेस्ट इंटरव्यूज में ये भी पूछते हैं व्हाट इज डिफरेंस बिटवीन true stress and engineering stress. So difference is that true stress is actually the validation of mathematical equation that is sigma is equal to P over A, and if you increase load, so definitely according to this equation the stress should increase, but the stress is decreasing here. Clear? And the reason is that the material is not able to take the further load because it weakens inside due to the necking. ठीक है ना, जब उसमें नेकिंग हो जाती है तो वो मटेरियल उसको सस्टेन नहीं कर पाता और जो है वो उसमें लोड कम हो जाता है, मतलब वो लोड सस्टेन नहीं कर पाता, ठीक है ना, तो जिसकी वजह से वो एक पॉइंट आ जाता है कि वो मटेरियल ब्रेक हो जाता है, एंड दैट स्ट्रेस इज नोन एज इंजीनियरिंग स्ट्रेस. हम ये नेक्स्ट स्लाइड में इसको देखते हैं, फर्दर इसको डिफाइन करते हैं. एंड वन मोर थिंग दैट रिमेंबर दैट इन मोस्ट ऑफ द मटेरियल this point P, E and Y, they are so much close to each other that you cannot identify at micro level. ठीक है ना, क्लियर? सो यहाँ पे तो हमने ये पॉइंट के दरमियान इतना डिफरेंस शो किया हुआ है, ये तो हम खुद हाथ से बना रहे हैं, बट इफ यू परफॉर्म द रियल टेस्ट, सो इन मोस्ट ऑफ द मटेरियल्स यू कैन नॉट आइडेंटिफाई P, E and Y. Instead you can just identify the elastic या यील्ड पॉइंट. ठीक है ना, तो आपको पता होगा कि उसमें आप ये कहते हैं कि यील्ड पॉइंट से पीछे जितना भी है उसमें अगर आप लोड रिमूव करें, सो इट विल go back to its original position, and that will be the elastic region. But if you cross the yield point, so now the deformation will be permanent and that will be in elastic region. Any question till now?
No, sir.
Okay. So now you will see the stress strain. In this coming two slides we will discuss about the stress strain diagram for ductile material as well as for brittle material. Now what is ductile material? Ductile materials are those materials that can be drawn into wires or in which the permanent deformation in which a deformation occurs. ठीक है ना, वो मटेरियल जो कि जिसमें परमानेंट डिफॉर्मेशन हो सकती हो और दैट कैन बी ड्रॉन इनटू वायर. बाय परमानेंट डिफॉर्मेशन मींस दैट देयर मे चेंज इन लेंथ और देयर मे बी अ सिग्निफिकेंट इलोंगेशन आफ्टर द अप्लाइंग लोड्स. सो वो टूटे ना, मतलब एक सर्टेन लिमिट तक वो टूटे ना, बट दैट कैन बी चेंज इनटू that can be deformed. And why we deform? In order to get to our desired shape. सही है, तो हम फोर्स किसी भी मटेरियल पे इसलिए अप्लाई करते हैं अगर हमने उसकी शेप चेंज करनी हो तो उसमें हम लोड अप्लाई करते हैं ताकि ये डिफॉर्म हो और अकॉर्डिंग टू आवर रिक्वायर्ड शेप दैट कैन बी चेंज. सो these are the we will in this slide we will talk about the stress strain diagram of ductile material. Here you can see that there are two stress strain curves. One is for low carbon steel and another one is for aluminum alloy. So you can see that if you keep on increasing the load, so there is a point, yield point. So up till this, from 0 to this point, this region is known as elastic region. Clear? And the stress at this yield point is known as yield stress. Now after that you can see there is a drop in stress. And why this drop? Because I have told you that due to slippage of plane and inequilibrium condition, the stress will goes down. Now stress is not increasing, but you can see that on x-axis the strain is increasing. at after some time when the atoms or cell or atoms comes to another new equilibrium condition, so now it will resist the external force and the stress will go on increasing, and a maximum point will reach that a material can bear the load, and that load is known as ultimate tensile stress, and then it rupture after some time. Clear? And that load is known as rupture load. Now this is the elastic region R, and this is the yielding. Yielding means that there is a permanent deformation. So all after this elastic region, all these regions are known as plastic region. अच्छा, जब आपके पास yielding हो जाती है and then further increasing load also cause strain hardening. What is strain hardening? अगर आप देखें तो if cold working और hot working का आपने सुना होगा, cold working and hot working, ठीक है ना. अब hot working में क्या होता है? hot working में ये होता है कि आप इसको hot करते हो, गर्म करते हो, and then you deform without applying stress, ठीक है ना. So that is known as hot working. cold working में ये होता है कि आप उसको उस पे stress apply करते हो, but you do not change the temperature. So यहाँ पे भी यही हो रहा होता है कि without applying heat, so with the help of load, you are going to permanently deform the object, and this phenomena is known as strain hardening. Now, when it reached to ultimate strength, so you can see that, अगर मैं इसको थोड़ा zoom करूं, so you can see this figure. This was a tensile test specimen. So if you keep on increasing the load after ultimate strength, so the area is going to decrease somewhere in the mid portion. It is not necessary to mid portion, but it will be, the area will keep on reducing at some portion. So you can see that area is reducing, and this area, this phenomena is known as necking. अब यहाँ पे एरिया कम हो रहा है. अगर आपको मैं थोड़ा और अगर zoom होता है, ठीक है ना, so you can see that there is a necking. There is a reduction in area. So when you further increase, it will break at this point. So there will be a cup, cone and cup. If the material is ductile material, so there will be a cup and cone. So अगर आप देखें तो यहाँ पे हमारे पास cone बनेगा इस तरह, ये position है, ये वाली. This is a cone shape, and there will be a dent, cup shape. Or you can also say that there will be a concave portion, convex, sorry, this is convex, ठीक है ना, and there will be a concave portion. So ये आपको concave, this shows you the behavior of ductile material. तो अगर आपको कोई एक वर्कपीस भी दे जिसमें ये फेलियर हुई हो, तो आप इन रीजन्स को देख के बता सकते हैं कि these materials are ductile or brittle. So if the pattern is like cup and cone or convex and concave shape, so you can say that this is a ductile material. Clear?
Okay, sir.
Acha. Another example is for aluminum alloy. So now in this example, you can see that there is no elastic or proportional limit, because the why it is not given, I have already told you that in most of the material it is impossible for us to locate the elastic point or proportional limit. So the ultimately point is the yield point, and we can say that below this yield point the stress is in elastic region, and after this point there will be a permanent deformation. So you can see there is a ultimate strength and then it rupture. So this load is known as breaking load or rupture load. So remember that this stress strain curve is very interesting and very easy, but it will require your a little bit interest as well. ठीक है ना. तो अगर आपका इंटरेस्ट हो और एक दफा आपको इन चीजों की समझ आ जाए, तो आप इसको इजीली सारी उम्र आपको याद रहेगा। अच्छा, अब हम आते हैं, यहाँ पे हमने कहा था कि देयर इज अ ट्रू स्ट्रेस, ठीक है ना, एंड दिस इज इंजीनियरिंग स्ट्रेस, कहा था ये ट्रू स्ट्रेस, ठीक है ना, मैं टी स्ट्रेस लिखता हूं, और दिस इज ई स्ट्रेस, इंजीनियरिंग स्ट्रेस। सो अगर आप देखें तो हमने कहा था स्ट्रेस इज इक्वल टू लोड पर यूनिट एरिया। सो एट दिस पॉइंट, अब ये अल्टीमेट टेंसाइल के बाद अगर आप देखें तो एरिया रिड्यूस हो रहा है रिड्यूस यहाँ पे, और लोड इंक्रीज हो रहा है। तो इसके मुताबिक ये वैल्यू डिक्रीज हो रही है, लोड इंक्रीज हो रही है, तो स्ट्रेस को तो इंक्रीज होना चाहिए ना, ठीक है ना। और मैथमेटिकली अगर हम देखें तो एक पॉइंट आएगा कि जहां पे ये दोनों एक दूसरे से अलग होने लगेंगे, एक किस्म का कांटेक्ट पॉइंट होगा, सिर्फ कांटेक्ट पॉइंट, जहां पे वी कैन से दैट एरिया अप्रोचेस टू जीरो। सो इन केस इफ एरिया अप्रोचेस टू जीरो, सो स्ट्रेस क्या होगा, दैट विल बी इनफाइनाइट। सो ये इसीलिए ऊपर की तरफ जाता है, इनफाइनाइट। सो अब हम कहते हैं कि यहाँ पे ये फिर टूटता क्यों है, क्योंकि लोड इनफाइनाइट हो जाता है और उस मटेरियल की बर्दाश्त खत्म हो जाती है, इसीलिए जो है वो उसको नहीं सह पाता और टूट जाता है और ये कर्व नीचे आती है। दैट इज व्हाई दिस इज नोन एज इंजीनियरिंग स्ट्रेस एंड दिस इज नोन एज ट्रू स्ट्रेस। आई थिंक इट्स क्लियर टू यू नाउ। अच्छा, लेट मी चेक दैट how many people are present there. So 18 people are there. Good. Okay. Then these two curves are stress strain curve for ductile material. Now we will talk about brittle material. Now brittle material are those material which do not deform permanently, which do not perform permanently, but it suddenly rupture or break, ठीक है ना। आप अगर इसमें देखें तो इसमें तो ये आपको कहता है कि ये जितना भी आप इस रीजन से जितना भी आप उसको शेप चेंज करना चाहते हो, डिफॉर्मेशन चेंज करना, डिफॉर्मेशन उसमें क्रिएट करना चाहते हो जी, अभी भी नहीं आ रही
सर, इंटरनेट के मसले की।
ओके, यस, अभी आ रही है आपको?
यस सर, यस सर।
ओके, ठीक है, हाँ, दैट देयर वाज अ इंटरनेट कनेक्शन प्रॉब्लम। ओके, सो अगर आप देखें तो डक्टाइल मटेरियल्स के लिए जो है यू कैन क्रिएट सिग्निफिकेंट डिफॉर्मेशन। और क्यों हम डिफॉर्मेशन क्रिएट करना चाहते हैं? इन ऑर्डर टू चेंज द शेप और ज्योमेट्री, ठीक है ना। सो यू कैन प्ले इन दिस एरियाज, ठीक है ना, इन ऑर्डर टू गिव यू द शेप ऑफ द मटेरियल, बट आप यहाँ फिर नहीं जा सकते क्योंकि वो मटेरियल उसको बेयर नहीं कर पाता, ठीक है ना। अच्छा, नॉर्मल अमूमन हम करते भी हैं कि अगर हम ऑब्जेक्ट पे लोड अप्लाई करते हैं इन ऑर्डर टू चेंज द शेप, सो हम यील्ड स्ट्रेंथ से ज्यादा ऊपर नहीं जाते, क्योंकि उसके अगर जाते भी हैं तो हम फिर कहते हैं कि ये टेंसाइल लोड से ज्यादा नहीं जाना चाहिए, क्योंकि अगर वो ज्यादा लोड आप अप्लाई करेंगे सो द मटेरियल विल फेल, ठीक है ना। बट इन केस ऑफ ब्रिटल मटेरियल, इफ यू आर गोइंग टू प्रोड्यूस permanent deformation, there will be a deformation, but at certain point it might rupture, it might break. There is no yielding in that brittle material. So in this case you can see the stress strain curve. If you keep on increasing the load, there will be deformation, but suddenly it may rupture. So there is no yielding. ये आप मटेरियल ब्रिटल मटेरियल की प्रॉपर्टी ये है कि देयर यू कैन नॉट जज देयर यील्डिंग पॉइंट, ठीक है ना, उसमें यील्डिंग नहीं होती और वो डायरेक्ट आपको रप्चर लोड दे देता है। जिस तरह अगर हम प्रीवियस देखें तो यहाँ पे हमें पता चलता है, अगर टेस्ट परफॉर्म भी हो रहा हो और हम रीडिंग देखें तो हमें पता चलता है कि इस रीजन में अब यील्डिंग हो रही है और ये यील्ड स्ट्रेंथ है और स्टिल अभी भी सेफ है। लेकिन in this case we cannot judge the material and it suddenly rupture at some load, so the जिस पॉइंट पे ये रप्चर करता है या टूट जाता है उसे हम कहते हैं रप्चर लोड ऑन अल्टीमेट स्ट्रेंथ ऑफ और अल्टीमेट स्ट्रेस ऑफ फॉर ब्रिटल मटेरियल. सो दिस इज ये आपको एक टिपिकल ग्राफ बता रहा है. अगर आपसे कोई ये भी पूछे कि व्हाट विल बी द स्ट्रेस स्ट्रेन कर्व फॉर brittle material, so you can simply say that there will be no elastic or yield point, so you can say that this might be rupture at this point u. So this is stress and this is strain. ठीक है ना? So this is the behavior of brittle material under the loading condition. Now we will talk about modulus of elasticity for different material, for different steel grades. So you can see that this is the graph, stress strain graph. This is stress and this is strain. So this is stress strain graph for different materials. So first one is for pure iron, the second one is for carbon steel A36, the third one is for high strength low alloy steel A992, and the fourth one is quench tempered alloy steel. Now what does it shows? It shows that in all these stress strain graph you can see. So अगर मैं आपको दिखाऊं तो ये पहला जो ग्राफ में इस तरह आपको बता रहा हूं, ये वाला, ये एक सेपरेट स्ट्रेस स्ट्रेन कर्व है, एंड दिस इज फॉर प्योर आयरन. अगेन दिस इज another stress strain curve, but it is for carbon steel A36, and the third one is for high strength steel, and the fourth one is for quench tempered steel. So in this figure there are four stress strain curves given for four different materials of steel or different grades of steel. So अगर आप देखें तो stress strain diagram for iron and different grades of steel. So अगर आप यहाँ पे देखें तो ये पहली अगर stress strain curve को देखें, so this will be yield strength of iron, ठीक है ना? This will be the yield strength of carbon steel, ठीक है ना? For high strength alloy steel, this will be the yield strength, and for quench it will be the yield strength. Similarly, ultimate tensile strength for pure iron will be somewhat this. For carbon it will be here, for high steel it will be here, and for quench steel it will be somewhat here. तो अगर आप इस स्ट्रेस स्ट्रेन कर्व को देखें, ठीक है ना, सो इन सब स्ट्रेस स्ट्रेन इन सब आयरन और डिफरेंट स्केल ऑफ ग्रेड्स में एक कॉमन चीज ये है कि दिस लाइन इज कॉमन, ठीक है ना, जिसे हम कहते हैं इलास्टिक प्रोपोर्शनल या यील्ड पॉइंट तक, ठीक है ना. एंड दिस लाइन, द स्लोप ऑफ दिस लाइन, ये जो आपके पास ये लाइन आ रही है, ये स्ट्रेट लाइन जो एक किस्म की आ रही है, द स्लोप ऑफ दिस लाइन डिफाइन यू द मॉडुलस ऑफ इलास्टिसिटी. जिस तरह हुक्स लॉ कहता है स्ट्रेस इज डायरेक्टली प्रोपोर्शनल टू स्ट्रेन एंड स्ट्रेस इज इक्वल टू स्ट्रेन इनटू ई, एंड दिस ई इज इक्वल टू stress over strain, and this E is modulus of elasticity. And what is this E? This E is actually the slope of this line. Clear? क्यों slope of this line? कि let's say अगर हमारे पास यहाँ पे थीटा है, यहाँ पे स्ट्रेस है और यहाँ पे स्ट्रेन है, तो टेंजेंट ऑफ थीटा हमारे पास क्या है? स्लोप आता है, and that is equal to stress over strain. ठीक है ना? This stress value और strain, ठीक है ना, perpendicular over base, ठीक है ना. So again this tan theta will be equal to E, which is modulus of elasticity. So this linear line shows you the modulus of elasticity. So below yield stress, we know that stress is equal to E into epsilon, where E is modulus of elasticity or Young modulus. So now in this case you have seen that strength is affected by alloying, heat treating and manufacturing process, but stiffness, elasticity is not. So अगर आप देखें तो ये सारे के सारे डिफरेंट मटेरियल हैं, मतलब ग्रेड्स हैं, डिफरेंट ग्रेड्स हैं स्टील के. ये प्योर आयरन है, ये भी alloy है, ये भी alloy है, या grades are different steel के. So in all these you can see that their modulus of elasticity is same. Clear? So modulus of elasticity same है, means के resistance to deformation same है, but they have different strength. अगर आप देखें तो यहाँ पे इसकी yield strength change है, इसकी change है, इसकी change है, इसकी. Similarly tensile strength इसकी भी change है, ultimate tensile strength इसकी भी change है, इसकी change है. ठीक है ना? तो उसकी रीजन क्या है कि strength is affected by alloying. कि ये प्योर आयरन है तो इसकी स्ट्रेंथ कम है, लेकिन आपने इसको एलॉय कर दिया तो इस एलॉय की अपनी स्ट्रेंथ है, इसकी अपनी. तो ये जो स्ट्रेंथ इंक्रीज हो जाती है, दैट इज ड्यू टू एलाइंग और हीट ट्रीटिंग और बाय एनी अदर मैन्युफैक्चरिंग प्रोसेस, बट देयर मॉडुलस ऑफ इलास्टिसिटी और ई विल नॉट चेंज, इट विल बी द सेम. ठीक है, क्लियर? सो कहने इसको शॉर्ट समराइज इस तरह करते हैं कि फॉर डिफरेंट ग्रेड्स ऑफ स्टील वी हैव सेम मॉडुलस ऑफ इलास्टिसिटी, बट द स्ट्रेंथ इज डिफरेंट एंड दैट इज ड्यू टू द allying of the different grades, or this strength may be due to the heat treatment or due to the different manufacturing process through which they are made. Any question till now?
No, sir.
Okay. Then we will see what is the difference between elastic and plastic behavior. So up till now we have discussed that during elastic limit, stress is directly proportional to strain. So let this point B is elastic limit or yield point. You can say this is the yield point, and after yield point there will be a permanent deformation. But below this point B, if you remove the load, it will go back to original position having no strain. So if this is strain, on x-axis it is strain, and on y-axis it is stress. So you can see that at point A the strain is 0 as well as load will be 0, because if there is no load on any object, so there will be no deformation in that object. Clear? So if within elastic limit or below the yield point, so stress, if you remove the stress, it will come back to the original position having no stress. But and this region is known as, क्या है ये बताएं?
Elastic region, sir.
This region is known as elastic region. Clear? But if you cross the yield point, so there will be a permanent deformation. So now you can see you are increasing the load beyond the yield point. So let's say at point C. Clear? So there will be a permanent deformation. Now if you remove the stress, so it will go to the point D. Clear? So you can see at point D there will be some strain. At point A there is zero strain, but at point D there is a strain, and that is epsilon R, and this epsilon R is known as residual strain. What does it mean? It means that there is no load applied, but the object is permanently deformed. There is strain in the material that has been created. So if strain disappear when the stress is removed, the material is said to behave elastically. And that is known as, and the region is known as elastic region. So the largest stress for which this occur is called elastic limit. Clear? When the strain does not return to zero after the stress is removed, the material is said to behave plastic. So now this is the plastic behavior, and by plastic behavior we means that if we remove the load from the workpiece and the deformation is still there, so the material is said to be in plastic behavior, means the material have been permanently deformed. But if you remove the load and there is no strain or no deformation in the object, so you can see that object is in elastic behavior. So I hope you have now clear about elastic behavior as well as plastic behavior. Clear?
Yes, sir. Yes, sir.
Okay. Now we will move toward fatigue. We will talk about fatigue. What is fatigue? up till now we have seen that in ductile material as well as in brittle material. So in ductile material you have seen, let me show this. For ductile material, this is stress strain curve for ductile material. ठीक है ना? अच्छा, up till now we have seen that by using by stress strain curve for ductile material, that the material behave elastically till elastic region, but if it cross the elastic region, it behave as plastic behavior, and there will be a significant deformation in the object. But up till this point where the material can take the maximum load, and this point is known as ultimate load. After that, the material breaks. So you can see that the permanent deformation will occur in any material if we applied load that exceed the yield strength. Clear? If applied load is below the yield strength, so there will be no deformation. And again, if you applied load that exceed the ultimate strength or the maximum load that a material can bear, so if you apply the load above the yield ultimate strength, so you know that material fails. Similarly, for brittle material, you can see that if you know the ultimate strength of brittle material, so you can see that if you applied the load below the ultimate strength, so the material will not fail. But now we are talking about fatigue. So there may be chances, in few cases you can see that you will see or you have seen that in most of the cases people have noted that often material fails below the yield strength as well. हम कहते हैं ना कि yield strength के बाद उसमें deformation होती है, और ऑब्जेक्ट कब टूटेगा? जब maximum yield से maximum टेंसाइल स्ट्रेंथ, अल्टीमेट टेंसाइल स्ट्रेंथ से जब आपका स्ट्रेस बढ़ जाए तब ऑब्जेक्ट टूटेगा. हम यही सोचते हैं ना, अभी तक तो हम यही पढ़ते आ रहे हैं ना.
Yes, sir.
अच्छा,
Yes, sir.
बट देयर अब यील्ड स्ट्रेंथ सबसे ज्यादा है. यील्ड स्ट्रेंथ इज अल्टीमेट स्ट्रेंथ इज ग्रेटर देन यील्ड स्ट्रेंथ. ठीक है ना? तो अब देयर माइट बी सर्टेन केसेस दैट ऑब्जेक्ट कैन फेल बिलो द यील्ड पॉइंट. अल्टीमेट पे तो जाना दूर की बात, वो यील्ड से भी कम स्ट्रेंथ पे जो है या स्ट्रेस पे टूट सकता है. और वो कंडीशन कब होगी? वो कंडीशन होगी फैटीग लोडिंग में. ये किसका माइक ऑन है बच्चे? ये माइक जरा ऑफ कर दें. सो फैटीग लोडिंग इज द केस इन विच द ऑब्जेक्ट माइट फेल बिलो द यील्ड स्ट्रेंथ. अब फैटीग लोडिंग है क्या चीज? फैटीग लोडिंग वो लोडिंग है that is cyclic load. Cyclic load means that with the passage of time, the load is changing its direction as well as magnitude. ठीक है ना? And constantly repeating. जिस तरह वाइब्रेशन है, तो वाइब्रेशन को देखें तो वो आपके पास repeated load है. ठीक है ना? और magnitude of force is changing continuously. So due to fatigue loading, the material can break below the yield strength. See, ठीक है? So we will not go in detail about fatigue. Fatigue आपने मशीन डिजाइन में भी पढ़ा होगा थोड़ा बहुत, या आप पढ़ेंगे जिन्होंने नहीं पढ़ा. ठीक है ना? तो वहां पे आपको चीजें और क्लियर हो जाएंगी. तो हम अब तक कहते आ रहे हैं कि ऑब्जेक्ट को जो है वो डिजाइन करते हैं बेस्ड ऑन यील्ड स्ट्रेंथ एंड ultimate strength, but now there is a new factor that is known as fatigue strength. ठीक है ना? तो fatigue strength को भी आपने डिजाइनिंग के वक्त इनकॉर्पोरेट करना है. If you do not incorporate the fatigue stress or fatigue strength of material, so due to the cyclic load, your part or your product may fail below the yield strength. अब fatigue फेलियर, या अगर आप देखें ना, आपके पास एक वायर है, ठीक है ना, एक पतली सी वायर है कॉपर की, और उसको आप टेंसाइल लोड अप्लाई करें। नॉर्मली आप लें ये वायर और इसको आप खींचें, कैन यू ब्रेक दिस? आप इसको हाथ से तोड़ सकते हैं अगर ये काफी बारीक हो। कॉपर, जिस तरह ये बिजली की तार है, इसमें से आप एक बारीक कॉपर वायर निकालें एंड यू अप्लाइड लोड, टेंसाइल लोड, कैन यू ब्रेक दैट? नो, ठीक है ना। बट अगर आपके पास यही वायर है और इस वायर को आप मतलब बेंड करें, इस तरफ आप दोनों इस तरफ बेंड करें, ठीक है ना, और फिर इस तरह ऊपर की तरफ बेंड करें एंड फिर नीचे की तरफ बेंड करें, तो एक पॉइंट आएगा कि यहाँ पे वो मटेरियल जो है वो वायर ब्रेक हो जाएगी। ये आपने कभी एक्सपीरियंस किया ये?
Yes, sir.
ओके,
Yes, sir.
सो नाउ व्हाट हैपेंड, आपने लोड अप्लाई किया, वो नहीं टूट रहा, लेकिन यहाँ पे आप उसको दो पीसेस में आसानी से कर देते हो। नाउ दिस इज ड्यू टू फैटीग लोडिंग, कि आप अल्टरनेटिंग चेंजिंग द लोड, आप कभी लोड को इस तरफ कर रहे हो, फिर ऊपर कर रहे हो, फिर नीचे, फिर साइक्लिक लोड। तो जब आप उस पे साइक्लिक लोड अप्लाई करते हो, ठीक है ना, सो एट डिफरेंट स्ट्रेस एंड डिफरेंट नंबर ऑफ रिवर्सिबल साइकिल, so material fail below the yield strength. Now this is the SN curve for steel grade 1020 HR and aluminium 2024. Now SN curve अगर किसी को नहीं पता, जो कि न्यू कमर्स हैं, मोस्टली आप इस क्लास में जो है वो सारे सेकंड सेमेस्टर से अबव के हैं, ठीक है ना। तो आप लोगों ने फैटीग थोड़ा बहुत पढ़ा होगा। फैटीग में हम SN कर्व हमारे पास होते हैं या हम बनाते हैं। SN कर्व मींस स्ट्रेस ऑन y एक्सिस एंड नंबर ऑफ रिवर्सिबल साइकिल, ठीक है ना, ऑन x एक्सिस। सो दिस इज द ग्राफ बिटवीन नंबर ऑफ साइकिल्स एंड स्ट्रेस। सो अगर आप देखें यहाँ पे हमें ये एक SN कर्व दिया हुआ है स्टील के लिए और एल्यूमिनियम के लिए। सो आप ये देखें तो अगर हम ये पॉइंट लें, इफ वी कंसीडर दिस पॉइंट, so at this point the strength will be this. अच्छा, before going to that, यहाँ पे अगर आप देखें, if I clear it, ठीक है ना, यहाँ पे now you can see कि ये हमारे पास स्टील है और ये एल्यूमिनियम एलॉय है। तो इसका यहाँ पे सिग्मा यू क्या है? अप्रोक्सीमेटली 60 है, 60 KSI, ठीक है ना। और यील्ड स्ट्रेंथ की क्या वैल्यू है? 40 से थोड़ा नीचे है, मतलब 35 समथिंग होगा, ठीक। ये आप नोट करें, ज़हन में रखें, ठीक है, 60 और 35। हम वापस जाते हैं फैटीग की तरफ। अच्छा, नाउ इफ यू लुक एट दिस पॉइंट, सो यू कैन सी दैट व्हाट विल बी द लोड, इट माइट बी 45, क्लियर, KSI। एंड इफ यू गो डाउनवर्ड, अगर मैं इस पॉइंट को प्रोजेक्ट करूं, इफ आई प्रोजेक्ट दिस पॉइंट टू दिस पोजीशन, सो इट द नंबर ऑफ साइकिल विल बी इन बिटवीन 10⁴ एंड 10⁵ सो यहाँ पे जो भी नंबर ऑफ साइकिल आता है, इट शोज दैट एट दिस नंबर ऑफ साइकिल द स्ट्रेस इज 45 KSI। मतलब इतने नंबर ऑफ साइकिल्स हो और आपका लोड 45 KSI हो, तो ये ऑब्जेक्ट, ये स्टील टूटेगा, ठीक है। मींस कि अगर आप किसी भी ऑब्जेक्ट पे 45 KSI लोड अप्लाई कर रहे हो और वो लोड जो है वो कितनी स्पीड से 10⁴ की उससे रिवर्सिबल साइकिल से उस पे आप अप्लाई कर रहे हैं, तो ये स्टील आसानी से टूट जाएगा, ठीक है ना। सिमिलरली इफ यू टेक दिस पॉइंट, ये पॉइंट जिसपे 40 वाला है, तो 40 अगर हम नंबर ऑफ साइकिल्स को 10⁵ कर दें, तो फिर जो है वो ये स्टील जो है वो 40 KSI पे टूट जाएगा, ठीक है ना। क्या इसका मतलब हुआ? इसका मतलब ये है कि नंबर ऑफ रिवर्सिबल साइकिल इंक्रीज कर दिए तो उसकी स्ट्रेंथ कम लोड पे भी अब वो ब्रेक हो जाएगा। एंड कीप गोइंग ऑन। नाउ इफ यू नोटिस एट दिस पॉइंट, इस पॉइंट पे देखें, इस पॉइंट पे आपके पास जो है वो स्ट्रेस क्या है? ये है, या अगर आप इस पॉइंट पे देखें, इस पॉइंट पे आपके पास जो है स्ट्रेस 30 है और उसके नंबर ऑफ साइकिल 10⁻⁷ है, तो मींस 10⁻⁷ साइकिल। अब आपने number of reversible cycle, you have increased the number of reversible cycle, so now less load will be required to break the material and it will fail due to fatigue loading, so fatigue loading will be 30 ksi। अब अगर आप देखें तो इसके बाद, इस पॉइंट के बाद आप जहां पे भी लें, जितने भी नंबर ऑफ, लेट से आपने ये पॉइंट लिया, ये वाला, इस पॉइंट पे देखें, अगर आप नंबर ऑफ साइकिल को 10⁻⁹ पे भी ले जाएं, सो इट विल बी स्टिल एट ब्रेक एट 30 ksi। मींस के इस पॉइंट के बाद आप जितने भी नंबर ऑफ साइकिल इंक्रीज करें उसका कोई इफेक्ट नहीं होगा। फॉर एग्जांपल मैं कहता हूं ये लोड 30 से नीचे, ये मैं इसको दूसरा कलर देता हूं, ये मैं इस पॉइंट पे लेना चाहता हूं, इस पॉइंट पे। Now you can see I have drawn these three lines. This will be 25, let's say, या this will be 20 or this will be 15। तो यहाँ पे अगर आप देखें इस स्ट्रेंथ पे, ये लाइन जो है वो इस एल्यूमिनियम वाली लाइन को, ये जो स्टील वाली लाइन को क्रॉस नहीं करती। नजर आ रहा है ये जो स्टील वाली है ना, ये कर्व, SN कर्व फॉर स्टील, और ये जो लोड है ये इसको क्रॉस नहीं करती। अब इसका मतलब क्या है क्रॉस नहीं करती? इसका मतलब ये है कि आप जितने नंबर ऑफ साइकिल्स 30 के SI से आप नीचे जितना भी लोड अप्लाई करो, ठीक है ना, 30 के SI से जितना भी नीचे लोड अप्लाई करो और जितने भी नंबर ऑफ साइकिल बढ़ाओ, ये ऑब्जेक्ट नहीं टूटेगा ड्यू टू फैटीग। क्लियर? सो ये जो 30 है ना, 30, दिस 30 के SI इज endurance strength or fatigue strength, endurance strength or fatigue strength, fatigue strength। अब endurance strength और fatigue strength का मतलब ये है कि ये इतना लोड आप, मतलब इससे अगर आप कम लोड अप्लाई करेंगे तो वो उसको बर्दाश्त कर पाएगा, ठीक है ना। लेकिन once you cross the endurance limit or endurance strength, so object will fail due to fatigue loading and this fail may be less than the yield strength। मेरी बातों की समझ आई है आपको जो मैं कहना चाह रहा हूँ? हाँ, ठीक है ना। एंड द सेम इज केस फॉर एल्यूमिनियम। सो थोड़ा मैं इसको वो कर देता हूँ, फिर हम नेक्स्ट टॉपिक की तरफ मूव करते हैं। तो अगर आप देखें यहाँ पे, तो एल्यूमिनियम इतने नंबर ऑफ साइकिल पे इस स्ट्रेंथ पे ब्रेक होगा। लेकिन अगर आप ये पॉइंट लेते हैं तो इस पॉइंट पे जो लोड होता है, इससे अगर आप नीचे लोड अप्लाई करेंगे, सो अगर आपके नंबर ऑफ साइकिल काफी तादाद में भी हो, रिपीटेड साइकिल, सो द एल्यूमिनियम एलॉय विल नॉट फेल अंडर द फैटीग loading। So this is the fatigue property as shown in SN diagram। So a member may fail due to fatigue at stress level significantly below the ultimate strength if subjected to many cycling load। So this is the new phenomena। और अगर आप देखें तो कई चीजें जो है वो आप हैरान हो जाते हैं कि यार इसकी यील्ड स्ट्रेंथ अल्टीमेट स्ट्रेंथ तो ज्यादा थी और लोड भी हमने कम अप्लाई किया था। सो क्या रीजन हो सकती है? सो one of the reason is that if there is a cyclic load, so maybe due to that load your object might fail। ठीक है? So when stress is reduced below the endurance limit, so इसके लिए इस केस में हमारे पास endurance limit क्या थी? स्टील के लिए 30 थी और इसके लिए हमारे पास endurance limit ये है, इस पॉइंट पे जो भी। तो अगर हम endurance limit से नीचे लोड अप्लाई करते हैं, so हमारा पार्ट जो है वो सेव होता है। क्लियर? ओके। I think we should take a 5-minute break and then we will start again। Okay, the next topic is deformation under the axial loading। Now what is axial loading? We have discussed in our previous classes that axial loading are those loading that is centric loading. What does centric loading mean? That if you have this part and you have central axis is those axis which is passing through the centroid of this member. So if the load is centric load, if centric load is applied, so this load is known as axial loading. Clear? ये हमने पहली क्लास में जो फिजिकल क्लास थी उसमें हमने डिटेल से इस पे बात की थी. So now you can see that there is a circular rod of length L that is represented as BC having area A. Now this is round bar. The cross section. If you draw the cross section, so this will be the area A. Clear? Now, according to that, if you applied the load, so definitely after applying the load, a deformation will be in that may cause an increase in the length or decrease in the length, but depend on again load. If the load is like this, so definitely there will be a tensile load. So there will be a increase in the length, and that increase is represented as delta. So there will be this length. So according to Hooke's law, stress is directly proportional to strain. So stress is equal to E into epsilon, where E is modulus of elasticity, epsilon is strain, and sigma is stress. So strain is equal to E over strain is equal to sigma over E. Clear? So अगर आप देखें तो हमारे पास जो है वो strain is equal to sigma over E है, ठीक है ना. अब ये स्ट्रेस किस चीज के बराबर है? दिस स्ट्रेस इज इक्वल टू P by A and E is also there. ठीक. सो स्ट्रेन क्या हो जाएगा? स्ट्रेन विल बिकम इक्वल टू P over AE. Clear? Now this अगर मैं let me select another new page or a new slide ताकि मैं आपको clearly समझा सकूं. So if you have, let's say this was the rod having area A, length, original length is L, and it is subjected to tensile load or axial load. Axial loads are those loads passing through centroidal axis or central axis. Okay, so if after applying load, the length may increase, and this is the change in length. So according to Hooke's law, stress is equal to E into strain, and this strain is equal to stress over strain. Clear? Now stress is equal to stress. We define stress. Stress is equal to P by A. So we will put the value of stress over here. So it will become P by A, and this epsilon. This is actually E, not E. This is strain. This is E, modulus of elasticity. Clear? So E into epsilon. नहीं यार गलत कर दिया ना. Stress is equal to E into epsilon, where E is equal to stress over epsilon. Clear? And if you want to write it A into epsilon. Clear? So if you want to have epsilon over here, so आप क्या करते हैं? ये इक्वेशन हमारे पास इस तरह हो गई ना कि मॉडुलस ऑफ इलास्टिसिटी इज इक्वल टू P डिवाइड बाय A एप्सिलॉन. तो अगर एप्सिलॉन इधर चाहिए तो ये इधर आ जाएगा. सो वी विल गेट एप्सिलॉन इज इक्वल टू P डिवाइड बाय A इनटू E. क्लियर? या अगर हम शॉर्टली इसको कहें कि हमें यहाँ पे एप्सिलॉन चाहिए, तो एप्सिलॉन किस चीज के बराबर है? सिग्मा ओवर E, और सिग्मा जो है वो P ओवर A के बराबर है और E यही, तो वही चीज आती है. ठीक है ना? So epsilon is equal to P divided by AE. Now we have, what is this epsilon? It is strain, and this strain is equal to change in length divided by original length. Clear? So if this is equation 1 and this is equation 2. Now equation 1 tells us that strain is equal to P over AE, and equation 2 that strain is equal to change in length divided by original length. So if we equate equation 1 with equation 2, because epsilon इसके भी बराबर है और epsilon इसके भी बराबर है, so these two may be same. So change in length divided by original length will be equal to P divided by AE. Clear? And if you find this change in length will be equal to PL divided by AE. So this is how we can find the change in length that is subjected to axial loading. जी, किसी का कोई क्वेश्चन है? ओके, सो नाउ अगर आप देखें तो थोड़ा इसको फर्दर एलिब्रेट करते हैं. हमारे पास क्या आया? दिस चेंज इन लेंथ इज इक्वल टू PL डिवाइड बाय AE. सो अगर मैं इसको लिख दूं P मल्टीप्लाई बाय L ओवर A मल्टीप्लाई बाय 1 ओवर E, ठीक रहेगा? तो ये क्या है? P क्या है? दिस इज लोड. L बाय A क्या डिफाइन करती है? L बाय A ज्योमेट्री को डिफाइन करती है, ज्योमेट्री. एंड दिस E इज मटेरियल प्रॉपर्टी. So this change in length depends on load, geometry as well as material. Now in previous example, this is the very simplest and basic example. So if you have step rods, मैं step rods की बात कर रहा हूँ. Step rods means you have rods of having different diameter. Clear? So you can see that this is the rod, step rods. So this is having dia D1, it's having dia D2, and it's having dia D3. And there might be loading. Let's say P is the loading. And if the material are same, so E will be same. But if the materials of these three rods are different, so its modulus of elasticity will be E1, it will having E2, and it will having E3. Now in this case, if you have been given a step rod with the loading condition and all the other necessary parameter, and you have been asked to find the elongation, change in length in total rod, so what will you do? You will have to find the elongation in this, you have to find the elongation in this, and you have to find the elongation in this. So that will be elongation in 1 plus elongation in 2 plus elongation in 3. Or generally we can see that elongation is equal to PL divided by AE. So for 3, we write the elongation formula in a general way, that sum of elongation from I start with PI, LI, AI, EI. So I start from 1 to how much? 3. For example, in this case it is 3. So what does this equation tell you? It will tell you if I is equal to 1, so we will have P1 L1 over A1 E1. Plus if I is equal to I will 2, summation means sum of. So for I is equal to, it will be P2 L2 over A2 E2. And similarly for I is equal to 3, it will be P3 L3 over A3 E3. So that will give you total elongation. And again simply this is sigma 1, this is not sigma, change delta 1, delta 2 plus delta 3. The same thing which I have written above. Clear? Now this equation is valid when you have different material. But if the material is same, so you can take the E. If material is same, then E1 is equal to E2 is equal to E3 is equal to E. But for same material. So in that case, you can take out this E as common. So it will be, the equation will become P1 L1 over A1 plus P2 L2 over A2 plus P3 L3 into A3 multiplied by 1 over E. Clear? Is it clear to you? Hello?
Yes, sir.
I think there was a disconnection.
Yes, yes, sir.
So, अच्छा मुझे तो नहीं पता था कि पीछे वो डिस्कनेक्ट हो गया है. कहाँ तक आप लोग इंगेज थे मुझे ये बताएं तो फिर मैं उसको करता हूँ.
जब जहाँ तक सेम हो सर.
अच्छा फॉर सेम यहाँ तक.
यस सर.
अच्छा ये माइक थोड़ा बंद कर दें जो शोर है. अच्छा अगर E सेम मटेरियल इज सेम देन E1 is equal to E2 is equal to E3 and that will be equal to E. So in that case all will be E. So आप you can take out E as common. So आप इसको कर सकते हैं total is equal to 1 over E. ठीक है और ये हो जाएगा P1 L1 over A1 plus P2 L2 over A2 plus P3 L3 over A3. तो ये इक्वेशन कुछ इस तरह हो जाएगी. क्लियर?
Yes, sir.
Okay, now we will solve a problem, but before solving problem for these type of examples, you must know that. Let me delete something like this. So if you have been given the problem like that, so you have to take the sections in order to finding the load as well as the strain. So in this example, there are three portions, D1, D2 and D3. So you have to section the load, section the material based on these three, load, geometry and material. So if there is change in load, so you can take the section over there. If there is a change in geometry, means now the diameter is increased, so you can take the section over here. Again, in this scenario, if there is the again change in geometry because the diameter is increasing, so you can take the load. So we will see this in next example. So let's move toward that example. So this is example 2.01 and it is given in figure that these are the step rods and the diameter of this rod is obviously the bigger rod having diameter 1.07 inch and the smallest diameter is 0.61 inch. It is given an E value is given. Now there is one E value, it means that material is same for both the rods. And you have been asked to determine the deformation of steel rod shown under the given condition. So this is a steel rod, step rods, and the loads are shown. At this point there is a 30 kips load, and at this point there is 45 kips load, and at this point there is 75 kips load. And the length are also mentioned in this figure. So you have to ask the total deformation. Clear? So what will you do? You have to section the load. How you will able to section the load? So you have to move from freely end to the fixed end. So this is a fixed end. So now if you move toward this, you can see that there is a load. So if you cut it, it will be your first section. Or if you move from this to this end, so you can take this as one, but it depends on you. ठीक है ना? Let's say मैं आपको यहाँ पे समझा रहा हूँ, फिर जो बुक्स में जिस तरह आप जो फॉलो करते हैं, you can follow that. Now, if at this point, you can see at this point, the diameter increase. Clear? So you can take the second section over here. Clear? And if at this point you can see the load is there, ठीक है ना? So you can also take the section at this point. So depend on load, geometry and material. क्योंकि इस प्रॉब्लम में मटेरियल सेम है तो हम मटेरियल की इसलिए मैंने बात नहीं की. So only where the load is changing or geometry is changing, I have taken the section. So we will find the first reaction forces and then we will move toward finding the deformation. So this was the example. यहाँ पे इन्होंने क्या किया, यहाँ पे they are moving from this point. So if they are moving from this point, so you can see at this point there is a section. Clear? So sorry, यहाँ start इन्होंने इस point से लिया है, लेकिन इसको इन्होंने नाम दिया हुआ है 1 2 3. You can give name as 1 2 3 as well. That depends on you, no matter. ठीक है ना. तो फ्रीली एंड से हम मूव करते हैं फिक्स एंड की तरफ. तो अब यहाँ पे ये पहला रॉड है तो इस जगह पे इसने सेक्शन लिया है और उसको ड्रॉ किया है. अब जब सेक्शन लिया है तो आपके पास यहाँ पे लोड क्या अप्लाई हो रहा है, 30 किप्स तो ऑलरेडी अप्लाई हो रहा है. ठीक है ना. और यहाँ पे रिएक्शन फोर्स दैट इज P3, दैट इज अननोन. सो बाय यूजिंग इक्विलिब्रियम कंडीशन ये फोर्स इस फोर्स के बराबर होना चाहिए. सो P3 विल बी इक्वल टू 30 किप्स. 30 किप्स से मतलब 30,000 पाउंड. क्लियर? So P3 will be equal to 30 into 10 raised to power 3 lb. Now when we move toward this point, so at this point, now you can see that geometry is changing because the diameter is increasing. So you can take section at any point. आप इस point से B से पहले आप कहीं पे भी section ले सकते हैं. That will be your this section. Clear? B और C के दरमियान आप कहीं पे भी सेक्शन ले सकते हैं. ठीक है ना. सो जब आप इसको सेक्शन करते हैं, नाउ यू कैन सी, आप फिर इसको ड्रॉ करते हैं, यू कैन सी कि यहाँ पे तो वही 30 अप्लाई है. ठीक है ना. और इस C पॉइंट पे वही 45 अप्लाई है. सो देयर विल बी अ रिएक्शन फोर्स P2. अब होता क्या है कि इन दोनों का सम जो है इक्विलिब्रियम कंडीशन में इसके बराबर होना चाहिए. या सम ऑफ ऑल द फोर्सेस along this direction must be 0. So अगर आप देखें तो ये 30 किप्स है और ये 45 है, तो इन दोनों का डिफरेंस कितना आता है? 15 आता है ना.
yes, sir.
ठीक है ना. तो हमारे पास 15 किप्स जो आता है, लेकिन अगर हम 15 किप्स अप्लाई करते हैं इस डायरेक्शन में तो वो क्या आता है? 15 और 45 कितना हो जाएगा? 60 हो जाएगा ना.
yes, sir.
तो ये तो इक्विलिब्रियम में रहेगा नहीं. तो हम क्या करते हैं, हम कहते हैं कि यहाँ पे जो इन दोनों का सम जो आपको दे, दैट इज अगर आप 30 से 45 माइनस करो तो -15 आता है. सो यूर P2 विल बी -15 lb. क्योंकि जब P2 -15 किप्स होगा, ठीक है, और ये 45 किप्स है, तो इससे इन दोनों के सम से क्या आता है? 30 आता है ना. यहाँ पे जो नेट फोर्स लगेगा 30, वो इसको बैलेंस करना चाहिए. क्लियर? अच्छा मैं दोबारा समझा देता हूँ. अच्छा यहाँ पे यू कैन सी दैट वी हैव सेक्शन दिस पार्ट ओवर हियर. यहाँ तक तो समझ है ना. ये 30 किप्स तो वही है और ये 45 किप्स एट C पॉइंट पे लग रहा है, लेकिन चूंकि हमने इसको इधर काटा है, सो देयर विल बी अ रिएक्शन फोर्स लाइक दैट. नाउ देयर सम शुड बी इक्वल टू 0 इन ऑर्डर टू ब्रिंग दिस इन इक्विलिब्रियम कंडीशन. ठीक है ना. यहाँ तक क्लियर?
सर ये रिएक्शन फोर्स B पॉइंट का है या C पॉइंट?
ये रिएक्शन फोर्स जब आपने अगर पहली क्लास ली हो तो हमने कहा भी था कि जब आप कहीं पे कोई सेक्शन करते हैं, बी, ये जो फोर्स लग रही है ना, ये तो बी पॉइंट है, लेकिन ये जो मैंने सेक्शन ड्रॉ किया है ये बी पॉइंट वाला नहीं है. यहाँ पे लोड नहीं अप्लाई हुआ, लेकिन चूंकि जब हम यहाँ पे इसको काट रहे हैं तो इन ऑर्डर टू कीप द इक्विलिब्रियम हम यहाँ पे एक रिएक्शन फोर्स कहते हैं कि यहाँ पे एक रिएक्शन फोर्स लग रही है, दैट इज P2, बिकॉज इट इज एट we have section it at section 2. Clear? ओके, नाउ जिस तरह हमने कहा था कि इक्विलिब्रियम कंडीशन के लिए सम ऑफ ऑल फोर्सिंग मस्ट बी इक्वल टू 0, सो ये 30 किप्स है, ये इस डायरेक्शन में लग रहा है। इन ऑर्डर टू कीप द इक्विलिब्रियम कंडीशन आपके पास 30 फोर्स इस डायरेक्शन में भी लगनी चाहिए। क्लियर?
Yes, sir.
ओके, सो यहाँ पे अब आप देखें तो यहाँ पे 30 किप्स लग रहा है, यहाँ पे 45, तो इन दोनों का ये 30 इस तरफ लग रहा है, 45 इस तरफ लग रहा है, तो इसका नेट कितना होगा? आप 30 से 45 माइनस करें तो क्या आता है? -15। तो P2 जो होगा वो -15 होगा। क्यों? क्योंकि अब अगर यहाँ पे 15 अप्लाई करेंगे प्लस 15, तो ये 45 और 15 कितना हो जाएगा? 60 हो जाएगा, जो कि 30 से ज्यादा है, तो ये तो इक्विलिब्रियम कंडीशन में नहीं रहेगा। But if you have -15 and that is 45, so it will give you net force of 30, जो कि इस 30 को बैलेंस करता है।
Right.
Now it is clear?
Yes, sir.
Okay, so P2 is equal to -15 kips। अगर आप किप्स नहीं लिखना चाहते तो आप लिख सकते हैं किलो पाउंड, और किलो की जगह 10⁻³ आ जाएगा और पाउंड LB, ठीक है ना। एंड नाउ वी आर, जब आप इधर मूव करते हैं एक पॉइंट बी पे आ जाते हैं, तो जब पॉइंट बी पे आ जाते हैं सो देयर इज अ लोड। अगेन हमने कहा था कि आप सेक्शन वहां पे करेंगे जहां पे सडन लोड आ जाए या मटेरियल चेंज हो। तो नाउ एट फ्रॉम दिस पॉइंट बी यू कैन टेक सेक्शन, ठीक है ना। और जब आप इसको ड्रॉ करेंगे सो आप देखें बेसिक एम ये है कि आपने अपने आप को कंफ्यूज ना करें। ये देखेंगे 30 किप्स वही लिखा हुआ है, ये सी पॉइंट पे 45 लिखा हुआ है, ये बी पॉइंट पे 75 लिखा हुआ है, और ये रिएक्शन फोर्स है। आपने देखना है कि ये 30 और ये 45 -15 हो गया और ये 75, तो 60 हो गया। तो आपके पास इधर फोर्स कितना होना चाहिए? 60 होना चाहिए। क्लियर? ठीक है ना? कुछ समझ आई है इसकी? ये काफी आसान है। आप देखें ना, आप
Yes, sir.
30 और 75 ये दोनों सेम डायरेक्शन में, कितना हो गया? 105, ठीक है। और 45 और 60 ये दोनों एक डायरेक्शन में, तो ये भी 105 हो गया। सो इट इज इन इक्विलिब्रियम कंडीशन, ठीक है ना। So you have find out the P1, P2 and P3 and these are the reaction forces at section 1, section 2 and section 3, ठीक है ना। Now हमने कहा था हम चूंकि टोटल डिफॉर्मेशन फाइंड कर रहे हैं, we have seen that this change in length is equal to sum of P in Pi Li over Ai into Ei, where I start from 1 and it can be to any number of sections. So we have 3 sections, so we will put first 1, so P1 L1 over A1 E1. Similarly for 2, P2 L2 over A2 and similarly P3 L3 over A3, ठीक है ना। अच्छा, जब अब चूंकि हमारे पास मटेरियल सेम है, तो हमने E1 is equal to E2 is equal to E3, जो कि मैंने यहाँ पे लिखा है, ये वाली इक्वेशन, ठीक है ना। ये वाली इक्वेशन यूज, अगर आप तो E1 और E1 को बाहर कर दिया तो P1 L1 और A1, P2 L2 और A2, P3 L3 और A3. So in this scenario you can see that you have the value of E that is given. ये value of E की वैल्यू दी हुई है यहाँ पे। आपके पास यहाँ पे एरिया क्या होगा? A1 होगा, और A1 किस चीज के बराबर है? π/4 d², और d क्या है? ये है, ठीक है। A2 और A3 का एरिया सेम होगा ना, दैट इज π/4 कैपिटल D²। तो इसकी वैल्यू आप d की वैल्यू यहाँ पे डाले और यहाँ पे डाले, आप कैलकुलेट करें, जो कि यहाँ पे कैलकुलेट हुई है, ठीक है ना। ये A1 A2 बराबर है, दैट इज 0.9 इंच स्क्वायर इंच। 0.9 किस तरह आया है? π/4 इंटू डायमीटर ऑफ दिस लार्जर शाफ्ट और रॉड, ठीक है ना। और A3 0.9 आया है, ठीक है ना। नाउ L1 क्या है? लेंथ ऑफ रॉड 1 यहां से यहां तक, दैट इज L1। L2 क्या है, इस पॉइंट से इस पॉइंट तक का ये L2 है, और L3 क्या है, इस पॉइंट से इस पॉइंट तक का. दैट इज आल्सो गिवन इन द क्वेश्चन. अगर आपको मैं इधर ये रिमूव करूं, so you can see this distance from this point to this point, this is L1. From this point to this point, this is L2, and from this point to this point, this is L3. Now you have all the values you have to put in this equation. तो P1 क्या था, P1 60 है, ठीक है. होल्ड करें, कॉल है. Okay, so now you have all the value. P1 that is 60, L1 is given, that was 12 inch, and area A1 is 0.9. So आप जब ये सारी वैल्यूज पुट करेंगे और इसको कैलकुलेट करेंगे तो आपके पास टोटल डिफॉर्मेशन आएगी 75.9 into 10⁻³ इंच. क्लियर. सो इस तरह के प्रॉब्लम्स आपकी इस चैप्टर नंबर 2 के एंड्स पे हैं, डिफरेंट स्टेप रॉड्स के. सो नाउ यू हैव टू ट्राई दैट प्रॉब्लम्स इन ऑर्डर टू लर्न मोर इफेक्टिवली. क्लियर. Okay, I will stop here.
Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Okay, sample problem 2.1. In this problem, it is given that this is a bar and that is linked with bar A, B and C, D. So the rigid bar, the rigid bar means the bar does not undergo to the deformation under the load because it is rigid. So the rigid bar BDE, so this is BD, this bar is a rigid bar, is supported by two link AB and CD. So there are two link that is attached with this bar BDE. So link AB is made of aluminum, that its modulus of elasticity is given, that is 70 gigapascal, and cross sectional area of 500 square millimeter. So area and modulus of elasticity is given for AB. Similarly for link CD, modulus of elasticity as well as cross sectional area is given, and the load of 30 kilonewton is applied at this end. So you are asked to find out the deflection of A of B. The B part is deflection of D and deflection of C. So you have to find the deflection at this B in link AB. So that is deflection of B. Deflection of B is actually is equal to deflection in AB link. Similarly, deflection in D is equal to deflection in CD, and deflection at this end, which is deflection of E. So you have to find this. For that, we must know about the forces that are available in these links, because delta B will be equal to PAB into L length of AB divided by area of AB into E of AB. So you can see that you have been given EAB, AAB length is also given over here, but you do not have force. So how you will find the force? So definitely for that you have to draw the free body diagram in order to find the unknown forces. So let's move toward that. So if you draw free body diagram of this rigid bar BDE, so it will be like that, and you can see that at point E there will be a load, at point D there is a force, and at point B there is also a reaction force, and the distance is same as given above. So what do you think if this load is applied? So definitely this will tend to stretch DE, and again this force will be upward, but this is the force that will be in this bodies. Clear? And if you want to show them on this rigid bar, so it will be like this will be this will tend to exert on this body, and similarly this will also tend toward it. So if you assume any direction, but when you do calculations you will get the value, and based on that value you can see that whether it is tensile or compressive. So let's start with this. So now here it is given that that is 30 at point B. Point D, the reaction force is FD, because we have removed the link CD. So this reaction force is represented as FCD. Similarly, at point B, the reaction force is FAB. Now, how can we find the unknown forces? So we know the equilibrium condition that sum of all the forces along x direction is equal to 0, or sum of all forces along y direction is equal to 0, or we can use sum of all the moment at any chosen point that is taken as 0. So if there is no horizontal force, so definitely we cannot apply this equation. So we will start with sum of all the forces along y direction is equal to 0. So we can see that this is minus 30 plus FCD plus FAB is equal, their sum should be equal to 0. So we have one equation like this. Again, we can also use the moment equation. So sum of all the moment we are taking at point B. So if you are taking the moment about point B, so one force that is 30 kilonewton that will produce movement in clockwise direction. Clear? So in clockwise direction, so this moment will be 30 into this distance, this whole distance, and this is 0.6, and it is clockwise direction, so that is negative. So minus 30 kilonewton into 0.6. Now the second force that is creating movement about point B is FCD. So FCD into perpendicular distance is 0.2. So it is producing counterclockwise, so that will be positive. So plus FCD into 0.2. So that will be equal to 0, and when you simplify it, you will get FCD will be equal to 90 kilonewton. So plus sign means that you have assumed direction in this upward, that is correct one. Clear? Now, if you put this FCD over here, it will be also okay. So if you put the value over here and then you move it, so you will get FAB is equal to minus 30. Wait a minute. I have a call from chairman. You can see that you can use this equation, and if you do not use this equation, clear? So you will, okay, let's use this equation as well. So FAB will be equal to plus 30, it will go toward this, and FCD is 90 and it will go there, and that will be minus 90. So it will be minus 60 kilonewtons. So now you have FAB as well as FCD. One more thing, if you do not want to use this equation, so second method is that if you want to take the moment about D, so you can also use that. So in that case, one movement that is produced by this 30 into 0.4, that will be clockwise, and the second one is movement about point D is FAB into perpendicular distance, and it is also in clockwise direction. So both will be negative, and by using this equation you can also find FAB, which is negative. So it means that FAB is in compression. So we have assumed here the force upward, so it means that our desired or our given or assumption that we have taken this force upward is wrong, so it should be toward downward. Clear?
Yes, sir.
Okay, then we will move to find the strain in each bar. So you can see here that this was the link AB, which was over here. So now the force that is, we assume that this was upward and was, but actually the reaction force on this bar is toward downward, and similarly the same force on link will be in opposite direction, because here you are showing the reaction forces, but the actual force acting on this link AB is upward. Clear? So this is 60 kilonewton. 60 kilonewton. Okay, and there is also a reaction force at the top as well here. So it will this link AB will be in compression. Clear? So we know that deflection in AB or deformation in link AB is equal to PL divided by AE. So you know here the force is compressive, so P in this area is minus 60, which you have calculated earlier. Clear? So this is minus 60 into 10 raised to power 3. Length is given as length of link was given above, that is 0.3. And area is also given for AB, which is 500. So all values are present, are available. Clear? So you have to put the value and you will find the deflection in or deformation in link AB, which is equal to B, and that is minus. So it means that there will be contraction in AB. Now displacement at point D. So at point D we will draw the link of CD. So as this force is reaction force is upward, so it means the force acting on link CD is downward. So now this force is creating tensile stress and tensile force. Now due to tensile force there will be elongation, and that elongation in link CD can be found by using this formula, PL over AE. P is the load, that is here tensile load 90. L is the length of this link, which is 0.4, that is given. Area was also given 600 square millimeter, and G for this material is also given. So you have calculated the deflection or deformation at point D. So in this problem you have up till now calculated the part A, which is deflection at B, part B deflection at D. Now we will find the deflection at this point E. So for that we have to draw a simple line or diagram like that. So this was the initial problem. You can see that this BE is total length of this rigid bar, and this is point B. Now you have noticed in previous solution of deflection at in link AB, so you found that the deflection there was a negative one. So you means that there is compression, upward compression, and that compression was 0.514. Similarly at point D you have noticed that there is a deflection, and that is positive, which is 0.3. Again, if you want to find deflection over point D, so that will be deflection at point E, delta E. Now you can, if you draw this figure, you will find that this, if you join this point with this, so you will find that there is a point at which there will be no deflection. But we do not know where the position of this point lies. So initially it is given 0.2 meter or equal to 200 millimeter. So let this point H is at a distance of X from D. So this distance will be equal to 200 minus X. Clear? So you have a height BB dash, DD dash and DE dash. BB dash is the deflection at point B, which is compressive. DD dash is deflection, or deflection means elongation. So elongation at point D, which is positive, means there is elongation which is 0.3, and you do not know the elongation or deflection in point E. So for that, if you see this figure, so we have three equal triangles. Clear? So this triangle B dash H, we have another triangle HD D dash, and similar triangle, not equal, similar triangle. So we have another triangle E dash. By similar triangle, we means that if two triangles are similar, then the ratio between their corresponding length will be same. So what does it mean? It means, for example, if you are going to take triangle B dash H, that is similar to triangle H D dash. So it means that if you are taking the ratio of B dash with respect to D dash, it will be same for BH over HD. Clear? Is clear to you?
Yes, sir.
Okay. So BB dash is what? BB dash is 0.514 and DD dash is 0.30. BH is actually 200 minus X and HD is equal to X. Clear? So you have this equation. If you solve it, you have to multiply this X over here, and then you further solve it, so you will get X is equal to 73.3 millimeter. It means that from point D, when we move till 73.7 millimeter, so we will get a point where deflection will be 0. Now the same methodology will be applied between these two triangles, HE dash and HD dash. So we will take the ratio between their corresponding sides. So EE dash ratio is taken with DD dash. So EE dash over DD dash is equal to EH or HE over HD. Clear? Now EE dash is generally represented as delta E, and you know that DD dash is 0.3. HE is total length, which is what? Which is the length of X plus this length 0.4. Now it is in meter and here it is 400, that is in millimeter. So 400 plus this distance X, which is 73.3. So that is HE. Divide by HD. HD is 73.3. So when you calculate it, you will get the deflection at point E. So by this you have calculated the deflection or deformation at point B, D and E. So this was all about sample problem 2.1. Any question? If you have any question, you can ask.
सर क्वेश्चन में जो हमें ये बार दिया गया है सर, ये तो इसने कहा कि रिजिड है.
हाँ, रिजिड है. तो इस अच्छा इसमें इस बार में एट पॉइंट ई वो डिफॉर्मेशन इसमें नहीं आ रही, मींस ये डिफ्लेक्शन है जो इसमें, मतलब ये इनिशियल पोजीशन से नीचे, तो ये डिफॉर्मेशन नहीं है, ये एक किस्म का डिफ्लेक्शन है. जबकि ये सी डी और ए डी हमने उस फार्मूला से यूज किया, पी एल डिवाइड बाई ए ई. ठीक है ना? सो ये डिफॉर्मेशन है और ये डिफ्लेक्शन है. समझ आई?
सही सर, सही.
क्लियर?
यस.
एनी अदर क्वेश्चन? Okay, now we will move towards static indeterminacy. So what do you mean by static indeterminacy? So whenever you have been given a problems and you have, for example, if you have any problem and there are four unknowns, and you have by using equation of equilibriums, you have three equations: sum of all forces along x, sum of all forces along y is equal to 0, and sum of all moments is equal to 0. Now in this case you have four forces or four unknowns, but you have three equations. So you cannot find the four unknown by using three equations. ये तो clear है ना आपको? So we cannot solve this problem by using these available three equations. So such type of problems or such type of condition comes under the category of static indeterminacy. So structure for which internal forces and reaction cannot be determined from statics alone are said to be statically indeterminate. Clear?
Yes, sir.
Okay, it will be clear to you further when we move ahead. So yeah, so this is the example. You can see that this is a member having cross-sectional area A 400 square millimeter and length is 300 mm. Clear? And this is there is another member of area 250 millimeter square and there is a load acting at point D and K. So if this in this condition, if you take this condition, so there will be a reaction force from the bottom that is represented as RB, and if you remove this reaction at point A, so there will be reaction at RA. So if you apply the equation these by using three equations, so as sum of all forces along x direction is equal to 0 cannot be applied on this because there is no horizontal force in this condition. Sum of all the force along y direction can be applied. So in that equation we will get RA minus RA plus RB minus D minus K is equal to 0. So there will be two unknown. But we cannot also use moment equation in this problem because if you want to take the moment at point B, K or D or any, so all the forces are passing through the same point, so there will be no moment. See? So we can only use one equation. Sum of all forces along y direction is equal to 0. Clear? Now if you use this equation, so in that equation you will have two unknowns and the equation is 1. So you cannot solve this problem by using equilibrium condition. So this type of problem is known as this is known as this phenomena, or this is known as statics indeterminacy. So we will solve it by using a method that will be explained now. Clear? So if you want to solve that type of problems you may encounter, so for that you have to take one of the reaction force as redundant force. Now redundant forces are those forces if we want to neglect or remove it, so it will no effect on this on the statics of this body. How? अगर आप ये रिएक्शन फोर्स इधर से हटा दे तो ये फोर्स इस पे लग रही हैं, ठीक है ना, तो ये इस बॉडी को मूव नहीं कर पाएंगी क्योंकि इट इज आल्सो सपोर्टेड एट ए. सिमिलरली अगर आप ये सपोर्ट ऊपर से हटा दें और ये पड़ी हो यहाँ पे, तो इस कंडीशन में तब भी ये ऑब्जेक्ट या ये बॉडी मूव नहीं करेगी. क्लियर? सो वी विल यूज दिस टेक्निक टू फाइंड आउट द सॉल्यूशन. तो अगर आप देखें तो ये पहली जो इसको मेथड अगेन इसको देखें, इस पहली वाली को, इसको जो मैंने टिक लगाई है. सो इफ यू लुक एट दिस इज द सेम थिंग and the reaction is given below. Clear? So there is no deflection or no deformation. Now this is statically indeterminate. So what is the solution? So first we will neglect this redundant force at or reaction force at point B. So if you neglect this force, so definitely you see that due to these forces there will be elongation in this member, and this elongation will be, let's say this was its original length, so there will be elongation that is delta L. Clear? Why? Because we have neglected this reaction force at point B. Now this deflection can be found by using the technique that we discussed earlier in our previous lectures. So you have the equation sigma is equal to PL over AE, but it is not easier as you think. So here you will have to take one section over here, then there is a sudden load change, so another section over here, then there is another area change, so you have to take one cross section here and here. So totally four sections you have to find the deflection and then you have to add that. ठीक है ना, आगे सॉल्व है उसको देखते हैं, बट आपको सिर्फ समझाना है. Once you get the deflection, that will be elongation due to these stresses. Plus, if you have to neglect these forces, so it will be like that, this reaction forces and this upper forces. So in this case, we have neglect these forces, so we say that this is compression, and due to this compressive forces, it will compress to this amount, delta R, due to compression. This is reducing. But if you look at the problem, initially it is given that total deflection or total deformation is equal to 0. So we have changed our problem from this to combination of two combinations, in which one elongation is increasing and in other the same elongation is now as the load is in compressive, so same decrease in length is seen. Now as total elongation must be equal to 0, so sigma L plus sigma R should be equal to 0. Now this is the second equation with the help of which we can find the two unknown forces. How? So let's see this example. So again, this is the same thing. I will go toward this thing. So first you have to take from free end to the fixed end, we will move. So you have to take the first first section over here. Now at this point there is a load change, so here you have to take in second area, or at this point you can take, now there is a change in area over here, so that will be third section, and there will be a change in load, fourth section. So we will see, if you cut this at point 1, let's see, this is the 1. If you cut at this point 1, so there will be no load. So here in this condition, P1 will be equal to 0. At point 2, there is a load. Clear? That is how much? 600. So P2 is equal to 600. And at point 3, the same load. If you cut it and draw the reaction forces, so P2 and P3 are same. That is 600 kilonewton. Now at point 4, so if you cut it at point 4, so there definitely all the forces, this force, this is 600, this is 300, 900. So reaction force will be also 900. So P4 is 900. Again, you have the diameter, you have the area that is given of this section. So area A1 will be same. This A is equal to A1 and A2. And this area is same for A3 and A4. Any confusion? Is there any confusion?
No, sir.
So A1 and A2 is equal to 400 into 10 raised to power minus 6 square meter, and A3 and 4 have same value. Now L1 is, this is given, this was, let's say, the length of first section, this is the length of second, third and fourth. So all are equal in this case, that is 150 millimeter, and if you convert it, it will be 0.150 meter. Now change in length can be found by using this equation, summation of Pi Li over Ai into Ei, and when you put all the values P1, P2 and all this value, and you solve that, so you will get this change in length is equal to 1.125 into 10 raised to power 9 divided by E. Clear?
Yes, sir.
Now the material is same. There is nothing is mentioned that this is different material. So we consider that E is same. Clear? Now this is sigma L. Also, this is elongation. Also, we note that if you consider that, neglect these forces and choose the second scenario in which reaction forces are available. So you can see now here, if you take one section, so So that will be here, the force will be equal to RB. And if you take the second section, so load will be same, P1 and P2 will be same, equal to minus RB. Clear? Because the forces will be compressive. And you have A1 and A2 as well as L1 and L2 as well. And so again you use the equation change in length. So you will, when you solve it, so sigma R will comes out to be 1.95 into 10 raised to power 3 into RB divided by E. Now it is given that total strain is equal to 0. So you have to, the sum of these two must be equal to 0. So when these two are added, so the value of sigma L is inserted and R is inserted, and that should be equal to 0. So now there is one unknown RB. So if you put the value of RB and you have E, so you can calculate the reaction force at point B, 577, sorry. Clear? Now you have the equation which I have talked about earlier, sum of all forces along y direction. So RA minus 300 minus 600 plus 577 is equal to 0. And so you can calculate the reaction force at RA. So initially we have seen that this problem is statically indeterminate. Clear? But for handling such type of problem, we have divided this into two scenarios. One with removing the redundant reaction, and other in which the forces are neglected. And then we solved that and we calculated the two equation, change in length of increase in length or deformation and decrease in length, and their sum must be equal to 0. And then we solve this problem to understand this all the phenomena that is mentioned above. So we calculated RA and RB value. So this is how static indeterminate problems can be solved. I think it is clear. Clear?
Yes, sir.
Okay, now we will move toward another topic, that is thermal stresses. Now, thermal stresses, from its name it is mentioned that these are the stresses which are due to the heat or change in temperature. So these are the stresses that are generated in the body due to the change in temperature. Now this change in temperature may be increase in temperature or decrease in temperature. So you know that if there is an increase in temperature, so there will be elongation in the length of the body, and if there is decrease in temperature, so it will shrink, there will be a contraction in this body. So we have a bar EB that is fixed in between 2 points A and B. The length of this bar is L. So this beam is fixed. Now due to change in temperature, it will tend to elongate. Clear? But we have restricted it from elongation. We have support over here. So in this scenario, change in length will be equal to 0. Because why change in length is equal to 0? Because we have restricted them. We have restrained them. So a temperature change result in change in length or thermal strain. Whenever there is a thermal temperature difference, so there will be a change in length. That change in length is known as thermal strain. Usually that change in length is thermal strain. Clear? That is due to heat. But in that case, there is no restriction. For example, if this is the same bar and one end is fixed and other is not fixed, and it is subjected to thermal loads, due to temperature change, it will elongate. So initially it was of length L. Now there is elongation, that is T. Why? Because there is no restriction at this end, so it will tend to elongate. So in that cases there will be no thermal stresses in the body. But if you restrain them or if you restrict them at both the ends, so there will be no elongation or no deformation in that. So in that case there will be stresses generated in this body, and these stresses are known as thermal stresses. Clear? So again, if you look into this problem, this beam is attached or supported at both the ends. So there will be, if we remove this reaction, so there will be a reaction RA, and at this point there will be a reaction RB. So you have two unknowns, and you can apply this equation only. Sum of all forces along x direction is equal to 0. So by using this equation you cannot find both of the unknowns because there is one equation. So this problem is statically indeterminate. So how we will solve this problem? So let's start that. So assume that if this beam is fixed at one end but at the second end it is not supported. So due to heat thermal change or due to temperature change, it will tend to elongate and it will come to a new position, that is, or the change in length is delta t. Now you have studied this in your metric or FEC, that due to change in temperature, the deflection or deformation that is equal to delta t is equal to alpha delta t into L. Clear? So this alpha is known as coefficient of thermal expansion, L is original length and change in temperature. ये याद है आपको?
Yes sir, 9th में था.
हाँ ठीक है. So this elongation due to thermal heating is this much, and we can, if you have alpha, you have change in temperature difference and original length, so you can find the elongation. So one elongation can be found by using this. Now in first scenario we have considered that there is no reaction. We have removed this redundant reaction at this point, which is RB, and considered that there is no reaction at this. So due to temperature difference it elongates. But now we assume that there is a reaction force due to this support B. So we represent this reaction force as compressive force. Clear? So now due to this compressive force, we say that due to this compressive force there will be a contraction in the length. And how much will be the contraction? This will be the same as that elongation, but it will be in opposite direction. So again we say that sum of all deflection, if you use this problem initially, so here total deflection is 0. Now if this total deflection is 0, it means that change in length due to thermal plus change in length due to the redundant or reaction force, that must be equal to 0. Clear? आपके पास ये value है sigma t, which is given over here, and due to these reaction forces the deflection can be found by using PL over AE. Now P is this reaction force, L is total length, A is the area, E is the modulus of elasticity. So again we will use the same this equation. Total deflection is equal to 0, so that is equal to delta T plus delta P is equal to 0. Delta T is alpha delta T into L. इस डेल्टा टी की जगह हमने ये पुट कर दिया, वी हैव पुट दिस, एंड डेल्टा पी की जगह हमने पी एल ओवर ए पुट किया. एंड व्हेन यू सॉल्व दैट, so you do not have actually P, which is reaction force at B. So you will get P is equal to minus AE alpha into delta T. So you can find this reaction force. जब आपके पास एक reaction force आ गई, आप उसी equation में put करें sum of all forces along x direction. So you can also find this reaction force at A. Now one more thing is that if you divide this A on both sides, so that will be P by A, and it will be, this A will be cancelled, so P by A is equal to sigma, and this sigma is equal to minus E alpha into delta T. Now this is known as thermal stress, because due to this reaction or strain, there is no elongation in this rod. But if no elongation is there, so definitely thermal stresses will be generated in this body, and this thermal, the value of this thermal stresses can be found by using equation sigma is equal to minus E alpha into delta T, and this is known as thermal stresses. Clear?
Yes, sir.
Any question? Okay, now we will move. जी किसी का कोई क्वेश्चन है?
No, sir.
Okay, we will move toward Poisson ratio. So उसके लिए आपको थोड़ी चीजें मैं समझानी पड़ेंगी, और उसके बाद जो है फिर मैं पॉइजन रेशो की तरफ आता हूं. सो फॉर दैट मैं आपको, मुझे थोड़ी स्पेस चाहिए. सो आई विल स्टार्ट फ्रॉम दैट. ओके, सो लेट चूज एनी. ओके, फ्रॉम दिस पॉइंट, इससे ऊपर में या कोई भी कह देते. Okay. So, for example, if you have a bar, that for example, this is the bar. There, having original length L naught, yeah, L, and that is subjected to normal load P. Clear? So after applying load, you have noticed that the length will increase. Clear? So this is, that change in length is represented as delta. Now the strain will be equal to change in length over original length, and normal stress will be equal to P by A. Let A is the area of this bar. Clear? So this strain that is produced in the direction of force or along this direction, that is known as linear strain. And let if this is X, this direction is Y, and this direction is Z. So the strain that is given in X direction is epsilon X, and it will be equal to change in length divided by original length. So due to this tensile load, there will be elongation in horizontal axis. Clear? But at the same time, the height will decrease. There will be contraction in height as well as in width. Clear? So length increases positive की तरफ, but width and height that decreases, mean there is a contraction. So how you will find it? So you will find it by using Poisson ratio. Now what is Poisson ratio? Poisson ratio is actually represented as nu, and it is equal to lateral strain over longitudinal strain. Longitudinal strain. अब lateral strain क्या है? Means के this is the longitudinal strain, longitudinal direction, and this is other than longitudinal, that are lateral. This direction, this is lateral, and this is lateral. That is perpendicular to this longitudinal strain. So nu is equal to lateral strain over longitudinal strain, and it is written in these two brackets. What does it mean? It means that nu is a positive value. So how you will find it? So this nu will be equal to, so if the load condition is like this, only there is a horizontal force, so there will be strain in the x direction and there will be a strain in y as well as in z direction. ये जरूरी नहीं है कि आपके पास सिर्फ लोड x डायरेक्शन में है, y और z में नहीं है, तो उस डायरेक्शन में स्ट्रेन नहीं होगा. नहीं, ड्यू टू दिस हॉरिजॉन्टल or normal load in x direction, strain will produce in x direction as well as in y and z direction, but there will that will be negative, means there will be contraction in x and y and z direction. Clear? So nu is equal to minus, what will be the lateral strain? इस डायरेक्शन में लेटरल स्ट्रेन क्या होगी? इट इज y, एप्सिलॉन y. सो माइनस एप्सिलॉन y ओवर लेटरल स्ट्रेन क्या है? एप्सिलॉन x. क्लियर? सिमिलरली अगर आप z के लिए फाइंड करना चाहते हैं, सो माइनस एप्सिलॉन, सॉरी ये y डायरेक्शन नहीं है, ये z है, z है, तो आई हैव टू चेंज इट z बिकॉज इट इज मेंशन ओवर हियर दैट दिस इज z डायरेक्शन. क्लियर? Now in y direction there is a contraction, so that is epsilon y over epsilon x. Clear? So if you want to find this, so that this will be equal to minus nu into epsilon x. Similarly, the strain in z direction will be equal to minus nu into epsilon x. So इस फोर्स लोड P की वजह से हमारे पास तीन किस्म के स्ट्रेन प्रोड्यूस हो गए. वन इज स्ट्रेन इन x डायरेक्शन, one is strain in y direction, and one is z. But one is positive, means that it is going to elongate in this direction, and the other two are negative, so it means there is a contraction in y and z direction. And how you can find the contraction? So you can use this formula, epsilon y is equal to minus nu time epsilon x. Similarly, epsilon z is equal to nu time epsilon x. Clear? So we'll move to upward again. So Poisson ratio, so this is the same thing which I have explained over here, यहाँ पे, ठीक है ना. So इसको भी देख लेते हैं. So this is the bar, ठीक है, subjected to load P, and this is x direction, the upward is y and this is z. So now due to this force, you can see this was the original area. Clear? And due to the load, applied load, the length is increased. Clear? So this is the increase in length in x direction, but there will be a contraction, the diameter, the area is reduced. There will be a contraction in thickness as well as in weight. Clear? So this is the scenario. If you simplify it, that load in x direction is given, there is no load in y direction and z, means no normal load in y and z direction. So in this scenario, there will be three strain, epsilon x, epsilon y, and epsilon z. So epsilon x can be found by using the stress strain equation. So that is epsilon x over epsilon y. Now epsilon, as the stress sigma y or load along y and z direction is equal to 0, so it does not mean that epsilon y will be equal to 0 and epsilon z will be equal to 0. No, the case is that due to this single load along x direction, I have discussed it here, that due to this load there will be contraction in x direction as well as in y direction, and that is the strain. So you have to, so according to that, sigma epsilon y is equal to epsilon z, that is not equal to 0. And how you will calculate that? For that we know the Poisson ratio. So Poisson ratio is lateral axis divided by axial strain. Lateral strain over axial strain. So lateral strain is along z direction is minus epsilon z, and normal axial strain is epsilon x, and lateral strain in y direction is minus epsilon y over normal or axial strain, that is this. So if you use that, so nu is equal to minus epsilon y over epsilon x. So you want to find epsilon y. So epsilon y will be equal to minus nu time epsilon x. Similarly, nu z is equal to minus nu time epsilon x. So you have find out the epsilon x, which is here, and epsilon y and epsilon z in term of Poisson ratio and axial strain. Clear? Any question?
No, sir.
Okay.
No, sir.
Okay. So also I will need another slide. So for example, up till now I have shown you that if you have the state of stress, for example, this is object, this is x direction, for example, is this direction is x, this is y, and this is z. इसको भी थोड़ा remove कर दूं. If this is, for example, if this direction is x, and you applied a load that is sigma x, clear? So in this condition, sigma x is there, but sigma y and sigma z is not equal, is not there. So they are zero. But due to this normal stress, strain will produce in x direction as well as in y direction as well as in z direction. And it will be minus nu into epsilon xx, and it is equal to minus nu into epsilon y. And this will be equal to sigma x over E. ये अभी तक हमने ये किया. So this is for unidirectional stress. This condition is known as unidirectional stress. But what if we apply the stress in y direction as well? Now this y is not equal to, sigma x is not equal to 0, and sigma y is not equal to 0, but sigma z will be equal to 0. So in that case, these strain will be produced. Also we will have epsilon y, epsilon x, and epsilon z due to this vertical strain, vertical loading, vertical stress, normal stress. Now what will be its value? Its value will be epsilon y, sigma y over E, and this epsilon x will be equal to minus nu time epsilon y, and this z will be equal to minus nu time epsilon y. समझ आई?
Yes, sir.
अच्छा, अब हमारे पास टोटल स्ट्रेन, अगर मैं इसकी कंडीशन लूं तो टोटल स्ट्रेन इन अलोंग एक्स डायरेक्शन क्या होगी? सिग्मा एक्स ओवर ई. ठीक है? और ये क्या है? इधर भी है ना, y फोर्स की वजह से, y लोड की वजह से, लोडिंग अलोंग y डायरेक्शन, सो दैट विल बी माइनस nu इनटू epsilon y. क्लियर? सो ये टोटल डिफॉर्मेशन होगी in x डायरेक्शन. Similarly, for y direction, epsilon y will be there. So one y direction में जो x डायरेक्शन में जो लोडिंग थी, सिग्मा x की वजह से जो लोडिंग थी, उसकी वजह से y डायरेक्शन में कितनी स्ट्रेन आ रही थी? माइनस nu इंटू एप्सिलॉन x. अब y की वजह से y में भी पॉजिटिव आ रही है, दैट इज प्लस सिग्मा y ओवर e. क्लियर? एंड व्हाट इज टोटल? इसको मैं t लिख देता हूं, और ये भी t. और z डायरेक्शन में क्या होगी? तो z डायरेक्शन में होगा माइनस nu इंटू एप्सिलॉन y माइनस nu इंटू एप्सिलॉन, सॉरी ये मैं गलत लिख दिया था, इधर ये x है, nu इंटू एप्सिलॉन x. क्लियर? सो दिस विल बी योर टोटल strain. So these three are the strain that is produced due to the 1, 2 and 3. ठीक है ना? This is the total strain due to bidirectional loading. Bidirectional means normal stress in x direction as well as in y direction. Clear?
Yes, sir.
Okay. So now we will move toward three-dimensional when a bar or object is subjected to three-dimensional loading. So in that case we see what will happen. So ये डायरेक्शन में x हो गया, x डायरेक्शन में, ठीक है, सॉरी x, ये y डायरेक्शन में भी इस पे लोड आ रहा है एंड z डायरेक्शन में भी आ रहा है. Now this is in three-dimensional loading. The body is under the action of three-dimensional loading. Three-dimensional stresses हैं. ठीक? Clear? मैं अगेन कह रहा हूं कि अगर आपको कहीं पे इशू आता है आप पूछें, क्योंकि अगर पूछेंगे तो चीजें क्लियर होंगी. अच्छा, अब हम आते हैं, पहले इसको सिंपल करते हैं. फॉर x मीन फॉर x डायरेक्शन. तो x डायरेक्शन में लोड क्या है? सिग्मा एक्स एक्स. तो इसकी वजह से कौन सा स्ट्रेन प्रोड्यूस होगा? सिग्मा एक्स एप्सिलॉन एक्स होगा. सिमिलरली y डायरेक्शन में कंट्रैक्शन होगी और z डायरेक्शन में भी कंट्रैक्शन होगी. और ये कंट्रैक्शन कितनी होगी? माइनस नू टाइम एप्सिलॉन एक्स एंड दिस विल बी माइनस नू टाइम एप्सिलॉन एक्स. और ये इलांगेशन होगी जो कि सिग्मा एक्स ओवर ई के बराबर है. मैं किसी जगह अगर मैंने एक्स एक्स लिख दिया तो उसका मतलब सिग्मा एक्स ही है. ठीक है?
Yes, sir.
सो ये केस 1 के लिए जब सिर्फ और सिर्फ x डायरेक्शन में लोडिंग हो. नाउ अब x के साथ साथ y में भी है, तो y फॉर y डायरेक्शन. तो y डायरेक्शन में सबसे पहले तो y पे लोडिंग है, तो y में तो लेंथ इंक्रीज होगी लेकिन x और z में कम होगी. तो एप्सिलॉन y क्या होगा? एप्सिलॉन y होगा सिग्मा y ओवर e. अब एप्सिलॉन x क्या होगा? उसमें कमी आ रही है x में, तो दैट इज माइनस नू टाइम एप्सिलॉन y. एंड सिमिलरली z डायरेक्शन में भी माइनस नू टाइम एप्सिलॉन y. ये दूसरी कंडीशन. अब तीसरी कंडीशन ये है कि अब तीसरी z की वजह से जो z डायरेक्शन में जो ये मैंने इधर ये z है, सॉरी ये z है. कोई आप लोग भी सोए हुए हैं, आप लोग ये नहीं कहते कि ये z है. तो ये z है. फॉर z डायरेक्शन, so if there is a tensile stress or tensile force in z direction, so definitely change in length occur and there will be elongation in z direction. So that z will be equal to sigma z over e. जबकि एप्सिलॉन there will be a contraction in x direction and that is minus nu into epsilon z, and similarly in y direction that is minus nu into epsilon z. ठीक है ना? तो जब अगर ये था पहली कंडीशन कि जब x फोर्स हो, ये थी दूसरी कंडीशन, ये थी तीसरी कंडीशन. अब जब बॉडी अंडर थ्री डायमेंशनल लोडिंग है तो टोटल डिफॉर्मेशन कितनी होगी x डायरेक्शन में? x डायरेक्शन में टोटल डिफॉर्मेशन कितनी होगी? तो इस x को लें, इस x को लें, सॉरी स्ट्रेन इन x डायरेक्शन और इस x को. सो इट विल बी इक्वल टू सिग्मा x ओवर e माइनस नू टाइम एप्सिलॉन y, ये वाली, और फिर माइनस नू टाइम एप्सिलॉन z. क्लियर? फिर टोटल स्ट्रेन इन y डायरेक्शन वो कितनी होगी? अच्छा, अब y में देखते जाएं. एक y ये है सिग्मा y ओवर e, दूसरा y क्या है? ये है विच इज माइनस नू इंटू एप्सिलॉन x, एंड तीसरा y ये है माइनस नू इंटू एप्सिलॉन z. एंड सिमिलरली टोटल स्ट्रेन इन z डायरेक्शन वो क्या है? अब z डायरेक्शन में ये है सिग्मा z ओवर e माइनस ये क्या है? माइनस नू इंटू एप्सलॉन, अगर x तरतीब में लिख लें तो बेहतर है, माइनस नू इंटू एप्सलॉन x एंड माइनस नू इंटू एप्सलॉन y. Now this is the total strain in x direction due to three-dimensional loading. This is the total strain in y direction due to three-dimensional loading, and this is strain in z direction due to three-dimensional loading. Clear? Any question?
यस सर क्लियर.
अच्छा, तो ये यही चीज यहीं पे एक्सप्लेन है. ये देखें, ये जो इधर ये है, ठीक. सो अगर आपके पास लोड है x डायरेक्शन में भी, y डायरेक्शन में भी और z डायरेक्शन में भी, तो टोटल स्ट्रेन जो होगा वो इसके बराबर होगा, जो कि मैंने इधर डिराइव किया हुआ है. ये अगर आप दोनों अपने पास लिख लें और दोनों को मैच करें, दे विल बी द सेम. ठीक है. तो फिर अगर आप जब ये स्लाइड्स देखें तो आपको पता होना चाहिए कि ये लिखा हुआ है और ये कहां से आया है. ठीक है ना. सो टोटल स्ट्रेन इन x डायरेक्शन इज दिस, टोटल स्ट्रेन इन y डायरेक्शन इज दिस, एंड टोटल स्ट्रेन इन z डायरेक्शन इज दिस. वन मोर थिंग, दैट पॉइजन रेशियो का हमने कहा था लेटरल स्ट्रेन डिवाइड बाय एक्सियल स्ट्रेन. ठीक है ना. और इसके साथ हमने इधर मॉड भी लगाया था, इसकी वैल्यू पॉजिटिव आनी चाहिए. बट जब हम कहते हैं इधर यहां पे कि जब हम ये फाइंड करते हैं, ये पॉइजन रेशियो इज इक्वल टू माइनस एप्सिलॉन y ओवर एप्सिलॉन x. Why we have taken this y? Because we know that in y direction there is a contraction, so ये वैल्यू नेगेटिव होगी. So negative will give you a positive value, and that's why epsilon, the value of epsilon is a positive value. You will see next in next few slides as well. Clear? यहाँ तक clear?
यस सर.
Okay. Now we will see that let we have a cube. Let we have a cube and having each dimension as unit. In x, in y direction it is unit, and in z direction is it's in unit. When this is applied to three-dimensional loading as shown over here, sigma x, sigma y and sigma z, so definitely there will be change in length in x direction, in y direction as well as in z direction. Clear? So let this change will be 1 plus, in x direction it is 1 plus epsilon x, in y direction it is 1 plus epsilon y, and in z direction, in this direction, it is 1 plus epsilon z. So where value of epsilon x, epsilon y and epsilon z is given over here. ठीक है ना. अच्छा, तो फिर क्या होता है, हम इसको इसलिए एक्सप्लेन कर रहे हैं कि वी आर मूविंग टुवर्ड अ न्यू टॉपिक, दैट इज डायलेटेशन और बल्क मॉडुलस. नाउ व्हाट इज डायलेटेशन और बल्क मॉडुलस? Up till now we talk about strain, that is change in length over original length, that give you linear strain. This is known as linear strain. So what about if volume change? So change in volume per unit volume or original volume, change in volume per unit volume, that will give you dilatation. Dilatation. It is the ratio of dilatation is basically the ratio of change in volume to the original volume. So again, if this is the cube having unit dimension in each, and after applying three-dimensional loading, now there is an increase in length in every direction, in x direction, in y direction as well as in z direction. Clear? So initially the volume is what? 1 multiplied by 1 multiplied by 1. So it will be 1. So initial volume is 1. Now new volume is what? New volume. Volume new. वो किस चीज के बराबर होगा? 1 प्लस एप्सिलॉन x, इसको मल्टीप्लाई करें इस लेंथ को, इस लेंथ को और इस लेंथ को, मल्टीप्लाई बाय 1 माइनस 1 प्लस एप्सिलॉन y मल्टीप्लाई बाय 1 प्लस एप्सिलॉन z. जब इन तीनों को मल्टीप्लाई करेंगे न्यू वॉल्यूम आएगा.
यस सर।
अच्छा, फिर आपने क्या करना है, फिर आपने इन सबको मल्टीप्लाई करना है, तो आपके पास कुछ इस तरह इक्वेशन आएगी। मैं पूरी की पूरी इक्वेशन नहीं लिखता, लेकिन मैं यहाँ पे नीचे थोड़ा लिखता हूँ। वी न्यू इज इक्वल टू 1 को 1 से मल्टीप्लाई किया 1 आया, 1 को एप्सिलॉन वाई से मल्टीप्लाई किया तो एप्सिलॉन वाई आया। सिमिलरली एप्सिलॉन को इससे मल्टीप्लाई किया तो एप्सिलॉन एक्स आया, और इसको इससे मल्टीप्लाई किया तो ये एप्सिलॉन एक्स इंटू एप्सिलॉन वाई आया, एंड सो ऑन। जब ये कंप्लीट हो जाए फिर इनमें इनके जो टर्म्स हैं उसको आपने मल्टीप्लाई करना है इससे, एंड सो ऑन। अब कहने का मकसद ये है कि एप्सिलॉन काफी छोटी वैल्यू है, ठीक है ना। तो अगर 2 छोटी वैल्यू या 3 छोटी वैल्यू लेट्स से 0.1 है, तो ये 0.1 के 0.2 के साथ मल्टीप्लाई हो जाए तो क्या आता है 0.02, विच इज अप्रोक्सीमेटली इक्वल टू 0। सो वी विल नेग्लेक्ट दिस टर्म। सो आखिर में हमारे पास वी न्यू जो निकल आएगा, दैट विल बी, जो आखिर में आप जब ये सॉल्व करेंगे सो आपके पास आ जाएगा एप्सिलॉन एक्स प्लस एप्सिलॉन वाई प्लस एप्सिलॉन जी, तो ये वी न्यू आ जाएगा। नाउ व्हाट विल बी चेंज इन वॉल्यूम? नाउ चेंज इन वॉल्यूम इज इक्वल टू ओरिजिनल वॉल्यूम माइनस न्यू वॉल्यूम। ओरिजिनल क्या था 1 और न्यू क्या है -1 इंटू -1 प्लस एप्सिलॉन एक्स प्लस एप्सिलॉन वाई प्लस एप्सिलॉन जी, ठीक है ना। तो ये 1 1 के साथ कट जाएगा और हमारे पास चेंज इन लेंथ जो होगा वो ये आ जाएगा, ठीक है। यहाँ पे मेरे ख्याल से थोड़ी सी मुझसे कोई मिस्टेक हुई है। ये सारी की सारी जो है वो चेंज इन लेंथ इज एक्चुअली कम्स आउट टू बी एप्सिलॉन एक्स एप्सिलॉन एप्सिलॉन वाई प्लस एप्सिलॉन जी, ठीक है ना। अच्छा, हम कहते हैं, सॉरी मैंने गलती क्या की है, चेंज इन वॉल्यूम इज इक्वल टू न्यू वॉल्यूम माइनस इनिशियल वॉल्यूम। अगर आप इसको उल्टा कर दें तो ये हो जाएगा न्यू और ये ओरिजिनल हो जाएगा, तो -1 इधर आ जाएगा। तो आपके पास चेंज इन वॉल्यूम जो होगा वो होगा एप्सिलॉन एक्स प्लस एप्सिलॉन वाई प्लस एप्सिलॉन जी। So this is change in length. Now, so we have defined dilatation as the ratio of what? Change in volume per unit original volume. Clear? So change in volume क्या है? Epsilon x plus epsilon y plus epsilon z. Original volume क्या था? y 1 था, ठीक है ना। So this is known as dilatation, ठीक है ना। अब बल्क मॉडुलस क्या है? बल्क मॉडुलस जिस तरह आपने यंग मॉडुलस पढ़ा था इसी तरह बल्क मॉडुलस भी है। बल्क मॉडुलस इज एक्चुअली द मटेरियल प्रॉपर्टी एंड इट इज रेजिस्टेंस टू द वॉल्यूमेट्रिक डिफॉर्मेशन। बल्क डिफॉर्मेशन आपको शो करता है रेजिस्टेंस टू द वॉल्यूमेट्रिक डिफॉर्मेशन। क्लियर?
यस सर।
सो डायलेटेशन इज comes out to be epsilon x epsilon y plus epsilon z। अच्छा, ये हो गया यहां तक, ठीक है ना। नाउ अगर मैं अगेन इसका डुप्लीकेट क्रिएट करता हूं और मैं आपको एक चीज शो करना चाहता हूं, इसमें है कि नहीं, लेट मी चेक 1 मिनट। ओके, नहीं है। ओके, दैट इज नॉट मेंशन। सो उसे भी मैंने आपको दिखाना चाहिए। 1 मिनट, डुप्लीकेट स्लाइड, से द सेम थिंग इज, आ गया डुप्लीकेट स्लाइड। अच्छा, ये यहाँ पे भी आ गया, यही चीज है। सो अगर मैं इसको यहां से रिमूव करूं, ये जो मैंने लिखा है, लेट मी डिलीट ऑल दीज थिंग्स। ओहो, सो नाउ ये जितना भी केस अभी तक हमने डिस्कस किया था, ये सारा का सारा जिसमें ये 3 डायमेंशनल स्ट्रेसेस थी, दे आर इन टेंसाइल स्ट्रेसेस, ठीक है ना। दे मे बी कंप्रेसिव स्ट्रेसेस एज वेल। So let's talk about that. इसको इससे मिटा देते हैं. So up till now we discussed the volumetric change and original volume, and we discussed what is dilatation, that is the ratio of change in volume divided by original volume, and then we discussed the bulk modulus, that is resistance to a volumetric change. Now you have seen that this problem is solved by using the stresses that are normal, but these are tensile stresses. What if all the stresses in y direction, in z direction, x direction, as well as z direction will be in compressive? ये भी हो सकता है case. So in this condition the object is said to be in hydrostatic pressure because the pressure exerted from every edge is same. So this, in this case, sigma x is equal to sigma y is equal to sigma z is equal to p. Clear? Minus p because they are compressive. So अगर आप इस इक्वेशन में, अच्छा ये इक्वेशन अब यहां तक तो हमने कर दिया था, डायलिटेशन ई से रिप्रेजेंट होता है, और हमने कहा था आखिर में कि डायलिटेशन बराबर है एप्सिलॉन एक्स एप्सिलॉन वाई प्लस एप्सिलॉन जी. नाउ in this condition we can say that further अगर आपके पास ये जो इक्वेशन है E is equal to एप्सिलॉन x प्लस एप्सिलॉन y प्लस एप्सिलॉन z, इसमें आप एप्सिलॉन x की जगह ये वैल्यू पुट करें, ये वाली वैल्यू कहाँ गई जो हमने फाइंड की थी यहाँ पे, ये वैल्यू पुट करें इस एप्सिलॉन x की जगह टोटल, इस एप्सिलॉन y की जगह ये पुट करें और इस g की जगह ये पुट करें इस इक्वेशन में, ये जो अभी मैंने आपको दिखाई है इस इक्वेशन में, और इसको सॉल्व करें. दैट इज अवेलेबल इन बुक. ठीक है, अगर कोई इसको सॉल्व करना चाहता है, देखना चाहता है, दैट इज अवेलेबल इन बुक. सो जो आखिर में इक्वेशन आपके पास डायलिटेशन की आती है वो आती है 1 माइनस 2 नू ओवर ई इंटू एप्सिलॉन एक्स प्लस एप्सिलॉन वाई प्लस एप्सिलॉन जी. ठीक है, यहां तक क्लियर?
Yes, sir.
Acha, now if the stresses are compressive one, if all the stresses are compressive one, this sigma y, sigma x and sigma z, they are compressive. So that will be in state of hydrostatic pressure, and let this, all the stresses are same, so that will be minus P, internal pressure P. ठीक है ना? So replace, I will put the value of, मैं इधर वैल्यू पुट करता हूं. सो E will be equal to 1 minus 2 times nu over E into सिग्मा x की जगह माइनस p, सिग्मा y की जगह माइनस p और सिग्मा z की जगह माइनस p. सो ये हो जाएगा माइनस 3p. सो E will become equal to minus 3p into 1 minus 2 nu over E, जो कि यहां पे देखें ये लिखा हुआ है. क्लियर?
Yes, sir.
अच्छा, now if I leave p over here, ठीक है ना, अगर मैं इस e की, ये इसको मैं मिटाता हूं दरमियान में से एक मिनट, तभी अभी क्लियर हो जाएगा स्टेप वाइज. अच्छा, if I leave this p over here, clear, minus p, and this e is there, जब अगर मैं इसको डिवाइड करूं दोनों ऊपर और नीचे, तो दैट विल बी 1 माइनस 2 नू इंटू 3 हो जाएगा ना?
Yes, sir.
जो कि यहाँ पे दिया हुआ है. ठीक है ना, यहाँ पे. अब इस टर्म को ये दिस e ओवर 3 इंटू 1 माइनस 2 नू, दिस इज अ कांस्टेंट एंड इट इज रिप्रेजेंटेड एज k, and this constant is known as bulk modulus. जिस तरह E था हमारे पास यंग मॉडुलस था, तो K जो है वो बल्क मॉडुलस है. और बल्क मॉडुलस किस लिए फाइंड करते हैं? वॉल्यूमेट्रिक रेजिस्टेंस टू, इट शोज यू द रेजिस्टेंस टू वॉल्यूमेट्रिक चेंज. ठीक है ना, और इस K की वैल्यू है E ओवर 3 इंटू 1 माइनस 2 नू. So this equation will become E is equal to minus P, and instead of writing this whole term, we can just write K, where K is bulk modulus. So dilatation will become equal to E is equal to minus P by K. Clear?
Yes, sir.
अच्छा, the last thing is that कि आप देखें तो इसमें इस टर्म में जो K is equal to E over 3 into 1 minus nu, इसमें ये E की वैल्यू पॉजिटिव है और K की वैल्यू भी पॉजिटिव आती है, ठीक है ना. सो ये टर्म पूरा का पूरा पॉजिटिव होना चाहिए. सो फॉर दैट if E is positive and K is also positive, so definitely 1 minus 2 nu should be greater than 0. क्योंकि ये टर्म अगर greater than 0 होगा तो ये K की वैल्यू पॉजिटिव आएगी ना.
Yes, sir.
So 1 minus 2 nu should be greater than 0, or implies that 1 is greater or 2 nu is less than 1, ठीक है ना, and nu is less than 1 by 2, means कि nu की वैल्यू जो है वो 0.5 से नीचे कम होनी चाहिए, means nu ranges greater than 0 and less than 0.5. so nu जो है पॉइजन रेशो, उसकी वैल्यू हमेशा greater than 0 होती है, less than 0.5, and nu is a positive value. That's why अगर आपको याद हो तो यहाँ पे मैंने आपको कहा है कि हम nu के साथ यहाँ पे मॉड लेते हैं. क्यों? क्योंकि nu की वैल्यू पॉजिटिव है. और फिर मैंने आपको ये भी बताया था कि यहाँ पे हमने nu इज इक्वल टू माइनस लिखा हुआ है, तो माइनस इसलिए लिखा हुआ है क्योंकि वाई डायरेक्शन में भी कंट्रैक्शन हो रही है, सो ये वैल्यू भी माइनस होगी. सो माइनस माइनस द वैल्यू ऑफ nu विल बी प्लस. क्लियर?
Yes, sir.
अच्छा, एंड आई थिंक यस, शेयरिंग स्ट्रेन. अब जिस तरह just like normal stress produces normal strain, in the same way this shearing stress. Now what is shearing stress? When the stress applied over a surface is parallel to the area on which it is acting, so that type of stress is known as shear stress. Now due to shear stress, shear strain produce, and shear strain is represented as gamma. Clear? So you can see that this is a cube and the shear stress is applied top of xy, top of yx, and the angle between these two edges is 90 or pi. Clear? Initially it is pi. Now due to shear stress, shear strain will be produced. And what is shear strain? Shear strain is actually deformation, the angular deformation between the two surfaces. ठीक है ना? So this, after applying the shear stresses, it will slide like this. Clear? अगर आप देखें इधर आपको नजर आ रहा हो तो, let me zoom. So you can see now the angle is now reduced, but here the angle is increased. Similarly, यहाँ पे angle increase हो रहा है और यहाँ पे decrease हो रहा है. So initially it was pi by 2, now it is pi by 2 minus gamma into xy. Shear stress, shear strain. Similarly, it is here it is increasing. So this gamma into xy is shear strain in that plane, and this is measured in radian. So जिस तरह आपको याद हो, stress is equal to E into epsilon x. अगर x डायरेक्शन में, अगर y में है तो ये y हो जाएगा. So this is Hooke law for linear stress or linear strain के लिए. So here shear stress is represented as tau into g into gamma. Now tau is, you can see this is stress, but this is normal stress. This is stress, this is shear stress. This is strain, that is linear strain, and this is strain but shear strain. This is E, which is modulus of elasticity, but here this G is known as modulus of rigidity. So it basically, this is for linear system and this is for rotational system or tend to rotate. ठीक है ना? So it is analogous of force analogous of rotational system. So हमारे पास जो है वो shear stress बराबर है G into gamma simply. ठीक है ना? Clear?
यस सर।
अच्छा, अगर आप मुझे एक 2 या 4 मिनट और 5 मिनट और देते हैं तो लेट मी क्लियर वन इंपॉर्टेंट कंसेप्ट एंड देन वी विल क्विट द लेक्चर। ठीक है ना? सो अगर बोर है तो वी कैन टेक 4-5 मिनट ब्रेक। Let take 3 or 4 minute break. I will also drink water. Let's start with that. For example, if you have a body like that, सुन रहे हैं आप मुझे?
यस सर।
इसको थोड़ी तवज्जो दें, ये आपके लिए फायदेमंद साबित होगी। आपको कहीं पे भी मसला आएगा तो आपको क्लियर होगा। लेट्स से दिस इज डायरेक्शन x, दिस इज डायरेक्शन y एंड दिस इज डायरेक्शन z। क्लियर? सो आपको ये पता होना चाहिए कि एक्स वाई डायरेक्शन में जो प्लेन आता है, एक्स वाई डायरेक्शन में जो प्लेन आता है, ठीक है ना, वो जेड प्लेन आता है। ठीक है, ये एक्स है, ये एक्स है, सॉरी ये एक्स, ये जो फ्रंट को अगर आप देखें तो ये वाई डायरेक्शन है और ये जेड है, सॉरी वाई डायरेक्शन है एंड दिस इज एक्स। सो दिस फ्रंटल, दिस प्लेन इज नोन एज जेड प्लेन। सिमिलरली वाई जेड जो प्लेन है दैट विल बी एक्स प्लेन। अब वाई जेड प्लेन, वाई जेड क्या है? y is this direction and z is this direction. So ये वाला जो प्लेन है, ये वाला that is known as x plane. Clear? And similarly zx. So zx क्या है? z ये है, ये डायरेक्शन है और x ये है। So ये वाला जो प्लेन है, ये टॉप वाला, ये होगा y प्लेन। इस तक समझ आ गई आपको?
यस सर।
अच्छा, अब हम आते हैं स्ट्रेस मैट्रिक्स की तरफ। आपने ये नाम शायद पहली दफा सुना हो या हो सकता है सुना भी हो। सो हम स्ट्रेस प्लेन हमारे पास फॉर 3 डायमेंशनल प्लेन हम इस तरह रिप्रेजेंट करते हैं, सिग्मा एक्स एक्स टॉ ऑफ एक्स वाई। मैं समझाता हूँ आपको इसके बारे में। टॉ ऑफ एक्स जेड, सिमिलरली सिग्मा वाई वाई, सॉरी गलती हो गई, टॉ ऑफ वाई एक्स sigma yy and tau of yz. Similarly, tau of zx, tau of zy and sigma zz. This is known as stress matrix for 3-dimensional stress. ठीक है ना? Clear? And as well as all the shear stresses are also available it. So now we will simplify it. सबसे पहले तो आप ये देखें कि लेट से यही आपके पास बॉडी है और आपके पास सिर्फ x डायरेक्शन में स्ट्रेस है। ठीक है ना? तो आपके पास स्ट्रेस मैट्रिक्स इसका क्या, किस तरह बनेगा? इस बॉडी पे कौन कौन सी स्ट्रेसेस लग रही हैं? जी, सिग्मा एक्स लग रही हैं। तो ये सिग्मा एक्स होगा, ये सारी की सारी वैल्यूज जो हैं वो 0 होंगी। ठीक है ना? सिमिलरली अगर आपके पास इस तरह ये वाई डायरेक्शन में है तो ये आपके पास ये स्ट्रेस मैट्रिक्स जो हो जाएगा वो ये हो जाएगा, सिग्मा एक्स एक्स 0 0 0, सिग्मा वाई वाई 0 0 0 0। तो फॉर दिस स्टेट ऑफ स्ट्रेस, ये वाली your stress matrix will be like that. But if there is stress in z direction as well, so now this will not be 0. So this will be equal to what? Sigma z। ठीक है ना? अब आते हैं इनके बारे में देखते हैं। So इसको किस तरह टैकल करेंगे, अगेन इसको इस तरह टैकल करेंगे या इसको इस तरह समझेंगे कि मैं फिर से दोबारा ये बनाऊंगा। अच्छा, जब आपके पास इफ यू हैव द सेम अगेन सेम block, sorry, this is x direction, this is y and this is z. Now सबसे पहले before discussing that we will see हमने लिखा हुआ है tau of x y, tau of x z, इसी तरह हमने लिखा है tau of y x, tau of y z या tau of z x और tau of z y, ये है क्या चीज, इसको हम रिप्रेजेंट किस तरह करेंगे। सो इसमें इन जो नीचे ये जो वैल्यूज हैं x y है, इनमें x का क्या मतलब और y का क्या मतलब, या ये पहले वाला जो है 1 और ये है 2, तो 1 का क्या मतलब है, ये सबस्क्रिप्ट है कि मैन्युस्क्रिप्ट है, क्या कहते हैं जो सबस्क्रिप्ट होता है, क्या कहते हैं जो छोटा, हाँ
यस सर
मतलब आपको समझ आ गई कि मैं कहना क्या चाह रहा हूँ। अच्छा, मैं आपको इधर थोड़ा जूम करके आपको समझाता हूँ। tau of x y, this is first value and this is second value. Now this first value shows you plane, क्या चीज, plane, and the second one show you direction. Now how we will plot it and you will be able to understand that. Tau of x y, so x plane, by x plane means x plane means y z direction, so this is y and this is z, so this plane is x plane, so this shear stress will be in this x plane, clear, but in the direction of y. So this direction can be upward or downward, depend upon the situation. So this stress is known as this is represented as tau of x y. Clear? अब हम आते हैं tau of x z. Now what does tau of x z mean? X plane, but in the direction of z. So ये x plane है और ये direction of z जो है वो इस direction में z is. So that is tau of xz. Similarly, tau of yx. So y plane कौन सा होगा, ये वाला, ये x और z डायरेक्शन में जो है ये प्लेन जो फ्रंटल है, ये वाला, एक मिनट मैं आपको ये मार्कर से हाईलाइट करता हूं।
टॉप वाला नहीं होगा,
नहीं, ये क्या है, ये x, हाँ सॉरी टॉप वाला होगा, एग्जैक्टली, गुड। x डायरेक्शन में ठीक है ना, और नहीं tau ऑफ वाई एक्स, तो y प्लेन की बात करें तो y z, हाँ ये टॉप वाला, सो ये टॉप वाला जो होगा ये होगा y प्लेन, क्लियर। अब हम tau ऑफ yz को yx को रिप्रेजेंट करते हैं, tau ये y प्लेन है और इन द डायरेक्शन ऑफ x, सो ये देखें tau ऑफ yx। अब एक सिचुएशन यहां पे भी देखें, tau ऑफ xy ऊपर है, tau ऑफ yx अपोजिट है, ये दोनों एक दूसरे के साथ मिल रहे हैं, और हम आप शायद बुक में भी अगर किसी टाइम मिला सो हम कर लेंगे, अदरवाइज ये बुक में एक छोटा सा टॉपिक है विच शो दैट tau ऑफ xy इज इक्वल टू tau ऑफ yx। सिमिलरली tau ऑफ zx इज इक्वल टू tau ऑफ xz, ठीक है ना। तो ये अलग एक टॉपिक है, उसमें हम ये प्रूव है कि ये बराबर है। अब हम आते हैं, ये भी हो गया, ये भी हो गया, ये भी हो गया। अब tau ऑफ yz, तो y प्लेन यही है और z डायरेक्शन कौन सी है, ये वाली है, सो ये क्या होगा tau ऑफ yz, क्लियर। अच्छा, tau ऑफ zx, अब z प्लेन कौन सा है, ये वाला, ठीक है ना। tau ऑफ z इन द डायरेक्शन ऑफ x, तो x की डायरेक्शन कौन सी है, ये क्या है tau ऑफ zx। अब tau ऑफ xz इस डायरेक्शन में है, tau ऑफ xz इस डायरेक्शन में है, और tau ऑफ z एक्स इस डायरेक्शन में। दोनों आपस में मिल रहे हैं ना? सिमिलरली टॉप ऑफ जेड वाई, तो ये जेड प्लेन है और वाई डायरेक्शन में ऊपर ये वाला टॉप ऑफ जेड वाई, तो ये देखें टॉप ऑफ जेड वाई और टॉप ऑफ वाई जेड आपस में मिल रहे हैं। तो आप अगर आपको सिंपल में, अब कहने का मकसद मेरा ये है कि अगर आपको एक बॉडी दी गई हो, इस तरह एक बॉडी दी गई हो और उस पे आपको स्ट्रेसेस दी गई हो, एक्स डायरेक्शन में हो या शेयर भी दी गई हो और एक्स वाई और जी डायरेक्शन भी डिफाइन हो, और आपको कहा जाए कि आप उसका स्ट्रेस मैट्रिक्स लिखो, तो आप लिख सकते हो?
यस सर।
तो जो स्ट्रेसेस होंगी, नॉर्मल स्ट्रेसेस होंगी, वो आप डालें, जो नहीं है तो वो जीरो हो जाएंगी, और जो शेयर स्ट्रेसेस हैं वो आप डालें, जो नहीं है वो जीरो हो जाएंगी। सिमिलरली आपके पास स्ट्रेन मैट्रिक्स भी है और वो भी इसी तरह है, एप्सिलॉन एक्स एक्स गेमा ऑफ एक्स वाई, गेमा ऑफ एक्स जी, गेमा ऑफ वाई एक्स, एप्सिलॉन वाई वाई, गेमा ऑफ वाई जी, गेमा ऑफ जी एक्स, गेमा ऑफ जी वाई एंड एप्सिलॉन जी जी। ठीक है ना? तो इंशाल्लाह किसी दिन टाइम मिला तो हम इसको और भी डिटेल से देखेंगे। बट जो मैंने आपको जो सिखाना था, बेसिक जो बताना था, अगर मोस्टली आप लोगों को पता होगा बहुत को, लेकिन अगर किसी को नहीं समझ तो उनकी रिवीजन हो गई कि अगर आप मैं कहूं कि टॉप ऑफ एक्स जेड को प्लॉट करो, तो आप यू मस्ट बी एबल टू नो और यू मस्ट बी एबल टू प्लॉट टॉप ऑफ वाई एक्स जेड, टॉप ऑफ जेड एक्स, टॉप ऑफ वाई जेड एंड सो ऑन। क्लियर? अच्छा, अब जो मैंने इधर देखें लिखा हुआ है सिग्मा एक्स एक्स, तो इसका क्या मतलब? एक्स प्लेन है और इन द डायरेक्शन ऑफ एक्स, सिग्मा वाई 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 प्लेन है इन द डायरेक्शन ऑफ वाई, और सिग्मा जी जी लिखा, अगर जी जी लिखा है तो इसका मतलब ये जेड प्लेन है और इन द डायरेक्शन ऑफ जेड। क्लियर? So this was all about second lecture, or you can say the part B of second lecture. If you have any question, you can ask. Thank you.
Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Okay, let's start with chapter number 3, that is about torsion. In this chapter we will study about introduction, torsional load on circular shaft, net torque due to internal stresses. We will then talk about axial shears component, shaft deformation, shearing strain, stresses in elastic range, then normal stresses arises due to torsion failure moods, then there is a sample problem, and then last two topics are about angle of twist in elastic range, and then finally statically indeterminate shaft. So let's start with introduction. The first topic is about torsional load on circular shaft. As you know that whenever you have a shaft that is fixed at one end, where this end is fixed, and you applied a torque, or you applied a torque on one end of the shaft, it tend to deform the shaft, or it tend to twist the shaft. Now this effect of twisting due to this torque is known as torsion. Clear? So in this figure you can see that there is a turbine that is attached with a generator through shaft. Whenever turbine rotates, it tend to rotate the shaft, and you can see that it tend to rotate the shaft in this direction by applying torque on this shaft. Clear? So when this shaft rotates, it tends to rotate the generator as well. Clear? But due to the inertia of this generator, or because it's having some mass, so due to its inertia, this generator resists this applied torque. Clear? And this resistance is offered in opposite direction. So turbine is actually applying a torque on the generator, while in response generator apply a reaction torque on this shaft. So we can see here below, in below example, you can see if these shafts are coupled, if we remove or we section them, so you can see that these shaft having applied torque in this direction, while due to generator there is a reaction torque that is represented as T dash in this direction. Now due to this opposing torques, a twisting effects or deformation will be created in this shaft. Now this twisting effect due to this applied torques or couples is known as torsion. Clear? Because we can see that if we remove the if we remove the support from this end as well, so there will be a reaction torque as well. So again, in short, whenever a torque is subjected to torsional load or couple load, so it will create twisting moment or it will create angular deformation in the shaft, and this is known as torsion. Clear? So interested in due to torsion loads or due to torque, the twisting effects will be created in the shaft, as well as this twisting effect there will be strain and stresses also generated in that shaft. So we are interested to find out the stresses and strain of circular shaft that are subjected to twisting or couple loads, and you have seen the example of this turbine which exert a torque on this shaft, and this shaft transmit power to the generator. Clear? In response, generator creates equal and opposite torque T on the shaft. So now this shaft is purely under twisting effects, and this phenomena is known as torsion. Now we will find the net torque due to internal stresses. So this is the same shaft. If you take this shaft as the previous one, so this is shaft AB, and that is subjected to the two opposite torques that are acting at point A and point B. Now due to these two torques, twisting effect will be created in this shaft. So this phenomena is known as torsion, or this is the this shaft is under pure torsion. Clear? So if you take out the section at point C, in order to find the internal stresses created in this shaft due to this torsion. Clear? So we take a section at point C. When you section this shaft at point C, so it will be like this. Point B will be having same torque T dash, while point C will be also having a reaction torque, but we want to show that this torque is due to the internal forces that are created in the shaft. So if you take this circular section, that this is the circular section, and you divide it into small area which is dA, that is also represented over here. So if you divide this circular cross section into small area, this is dA, all are dA, same differential area. Clear? So there will be a shear force acting on that area, which is also represented as dF. Clear? And this area is at a distance of rho from this center point. So if I draw it like in a zoomer mode, this is a center, for example, this is a differential area dA. Clear? And a shear force dF is applied on that small incremental area. Similarly, this is area and this is another area. All are a distance of rho. Now what is rho? Rho in this exercise or in this chapter, rho is used for the radius, and it is a variable radius. What does variable radius means? That rho is greater or equal to 0 and less or equal to C. Now what is C? C is the maximum distance from center to the outermost surface, and which means that C is the radius of the shaft. So rho varies when at center rho will be equal to 0, and at outermost point of the shaft rho will be equal to C. So let all these differential area are at a distance of rho from the center. So in order to find the net torque due to these internal shear forces, we assume this we divide this circular cross sectional into small incremental area, that is each area is represented as dA, and the force acting on this differential area is dF. Now you can see that torque is the product of force into displacement, clear, or distance, clear. So now you can see this is the shear force dF, and that is acting at this point, and from the center this distance is rho. So we can see that due to this differential force F and multiply by rho, it will create a torque. Similarly, in order to find the net torque applied due to these small areas under the load, under the differential shear force, so we can write this equation that net torque is equal to integral means sum of all the torques applied on this surface, clear. So this integral into dF into rho is the torque, which is torque for this only. But if you integrate it, it means that you are taking the net torque on this area. So torque will be equal to integral of rho. Now dF, as you know that dF will be equal to, this is the force, not stress. We know that force is equal to stress into area, clear. Now due to this force, shear stress is generated. So shear stress, this dF will be equal to shear stress into area. So instead of this dF, if we put shear stress into dA, will it be okay or not? So it will be okay, because this dF is equal to tau into dA. Now remember that, let me clear some things also. Okay, so again, if you see this shaft, so it's the axis of shaft, clear, and this axis of shaft is perpendicular to this face. For example, if this is the axis of shaft, this is the axis of shaft. Now this axis of shaft is perpendicular to this surface, this area, clear. So whenever any surface that is perpendicular to the axis of the shaft, so that shaft is under torsional load, clear. So definitely in that area shear stress will be, or shear force will be generated. I will repeat again, whenever any surface that is perpendicular to the axis, this is the axis and this surface is perpendicular, clear. So this and this is applied with the torques, okay? No, that so that this surface will be acted upon by shear forces, and this shear force will be equal to shear stress into shear area. And if you want to find the net torque on this surface, so that will be equal to integral of rho into dF, and similarly this dF is equal to tau into dA. So if you integrate it, you will get the net shear, which is also represented here as T. So this T is equal to, actually this is equal to integral of rho tau into dA. Now distribution of shear stresses is statically indeterminate, and we must consider shaft deformation. So only by using these external torques we cannot solve this problem. You will see at the end of this lecture there is a slide about statically indeterminate shafts. So you will see that we have to then take the we have to consider the deformation as well. And in unlike the normal stresses due to axial loading, the distribution of shearing stress due to torsional load cannot be assumed uniform. And similarly, we have seen in our previous lecture that whenever you have any shaft that is subjected to normal or axial loading, by axial loading we means that load passing through the axis. So whenever there is axial loading P, so we assume that stress is in the material is distributing, but this distribution is this distribution will be maximum in the vicinity of this load and it will be minimum at the end, but it will be like that. But as the load is an axial load, so we take the average stress, average normal stress, that is we simply write is as P over A. But in torsions, the shearing stress distribution due to torsional load, it cannot be assumed uniform. There is a proper distribution of shearing stress of the shaft that is under torsion. We will also derive that equation or relation which shows you the shear stress distribution along the shaft in next few slides. So, but you should remember that distribution of shear stresses due to torsional load cannot be assumed uniform in the rod, and we will see the distributions again in next few slides. Now, axial shear component. Now you can see that there is a shaft and these shafts are made up of axial slits. These are the slits. If I zoom it, these are the slits. And there are red marks that is available on this shaft. When this shaft is subjected to torque loading, when this is applied to external torques on both the end, and these torques are opposite torques, so it will create twist in this shaft, or you can say it will create shear strain, because there is an angular deformation of initially all the slits are parallel to each other. Now parallel to each other and also parallel to the axis of rotation of shaft. But now these slits are at certain angle to the axis. Clear? They are no more parallel to this axis. So they have been deformed, and this deformation is known as shear strain. Clear? So let's take any section of this axial shaft. Clear? So for example, a portion of this shaft is shown over here. This is the axis. This is some portion of the shaft. Now we have already told you that any face, for example, this portion of the shaft has this face. Clear? Similarly, it has this face. This is, for example, phase 1. This back face is 2. This is 3. And this is 4. All are the faces of this portion of the shaft. So we have already discussed that any face that is perpendicular to this axis, shaft axis. So you can see this face is perpendicular. This is perpendicular to this axis. So there will be shear force on this face, and this shear force is represented as tau. This shear force will be in this direction. Again, there is another face that is opposite to this. I will represent it as dotted line. So this face is also perpendicular to the axis of shaft. So there will be a shear force also on that face, and this shear force will be in this direction. Now you can see that there are two shear stresses. Two shear stresses are acting on the two faces, and they are at a distance from each other. So due to this couple will produce, and it will tend to rotate in counterclockwise direction. Clear?
Yes, sir. Yes, sir.
Okay. Similarly, I will remove the thing so that it should not mess up. Similarly, these faces, this face. Now this face is parallel to the axis of shaft. So it will also be applied, it will also be experiencing the shear force. Why? The reason is that we have seen that those faces which are perpendicular to this axis will experience a shear stress. Similarly, on this faces it will experience a shear stress. So due to this, a torque or couple is produced. Clear? A couple is produced, and that will be in counterclockwise direction. For this piece of the shaft to be in balance, there should be anti-clockwise torque or a couple that is also applied in order to make this piece of the shaft in equilibrium condition. So we say that those faces which are parallel to the axis of shaft under the torsion will also experience a shear stress as well, and this shear stress will be like this. Similarly, the opposite face will also experience a shear force in opposite direction. Now you can see that these two shear stresses also produce a movement that will be in clockwise direction. Clear?
Yes, sir.
So torque applied to shaft producing shearing stress on the face perpendicular to the axis of shaft as well as parallel to the axis of shaft that are under pure torsion. From this slide we conclude that torque applied to the shaft produces shearing stress on the face perpendicular to the axis, and due to this is for the body to be in equilibrium, the faces that are parallel to the axis of shaft also experience the shearing stresses. So condition of equilibrium require the existence of equal stresses on the faces of two planes containing the axis of shaft. So this is the same thing which I am talking about. The existence of axial shear component is demonstrated by considering a shaft made up of axial slats. These slats slide with respect to each other when equal and opposite torques are applied to the end. So basically this is a continuation of finding the shear strength or stresses in the shaft under pure tension. Now we will talk about shaft deformation, that whenever a shaft is subjected to torque, it will produce deformation in the shaft, and that shaft and this deformation of the shaft is known as shear strain. Clear? And there will be a twisting effect in this shaft as well. So we will also find the angle of twist for that. So how? So let's consider this is a beam, cantilever beam, or a circular rod that is fixed at end B having length L, and there is a line AB mark on this shaft. So you can see this is point B and this is point A. So when you applied torque, point B is fixed. When you applied a torque on this shaft, clear? So point A will tend to move to another position. So point A will tend to move to another position from A to A dash, and a new line A dash B is formed. So now you can see initial line is represented as dotted line, while the new line is represented as solid line, that is line B A dash. And if this is the center, so if you connect the center with original point of A, so that will be A. Now the point A has been shifted to A dash due to this applied torque. So if you join the center with A dash, so you will get OA dash. Clear? Now there is a change of angle between point A to A dash, and this angle is known as phi, and this phi is known as angle of twist. Clear?
Yes, sir.
Now this angle of twist is directly proportional to the applied torque. So if there is more torque, there will be more twisting angle. So from observation, the angle of twist of the shaft is proportional to the applied torque, and this angle of twist is also proportional to the length of the shaft. Higher the length of the shaft, higher will be the twisting effect due to the torsion. Clear? Now, when a shaft is subjected to torsion, every cross section of circular shaft remains plain and undistorted. So if we assume this is the same shaft and that is applied with the torsion at our torque at the both ends, and these torques are opposite torques. So you can see for a circular shaft, if you applied the torque, there will be a distortion, there will be a shear strain. But at every section, if you take any section, you have seen these circular arcs or circular shapes, these. You can see that at every section, the circular shaft remains plain and undistorted. It means that it will be remain circular when you take the cross section at any point. Clear? Clear? So shaft that is subjected to torsion, it will remain the same. It will remain plain and undistorted. So cross section of our hollow and circular shaft remains plain and undistorted because the circular shaft is axisymmetric. While in case of non-circular shaft, you can see that if this is a square or rectangular shaft that is subjected to torsion, so now you can see twisting effect has been created in this shaft, and whenever you take the cross section at any points, so every cross section will be totally different from the previous one because they are no more plain and they are distorted. Is it clear?
Yes, sir.
Okay. So we will continue further for finding the shear strain and angle of twist as well. So this is the same thing. This is the shaft that is supported at this fixed point and having length L, and when it is subjected to torque, it will move, this line will move to another point. This is point O. This is the angle of twist and O. From O to this point, for this was taken as A dash, so from O A dash is equal to OA, and that is equal to C. What is C? C is radius of shaft. Clear?
Yes, sir.
Okay. So if you want to find the internal effects of the torque on this shaft, so we will take internal portion of the shaft. So consider an interior section of the shaft. As torsional load is applied, an element on the interior cylinder deforms into a rhombus. So this was initially a shaft. Now we have taken the interior portion of the shaft. So you can see this dotted line is actually the original shaft. Clear? And this smaller portion, the inside, this one is actually the interior portion of the shaft. Now this interior portion of the shaft is taken and a square portion is marked on that, and this is the same line AB. This is the same center O, and this. Now if this was the initial diameter, so from center to outermost distance is C. Clear? But if you want to take any hollow, any internal portion, so now from this to this portion, this distance is represented as rho, because rho I have already told you rho is greater or equal to 0 and less or equal to C. So rho is for radius, but it is a variable term. It can be 0, it can be any value at any point, but minimum value is 0 and maximum value is the radius. So if you have taken the internal portion of the shaft and a square or rectangular red marks is marked on that, but after applying the torque, clear, so it will create deformation, angular deformation in the shaft. Now the point A is now shifted to point B. You can see here that this point A has been shifted to this point A dash, and similarly rho will remain same because OA and OA dash is same, that is rho. Clear? Acha, one more thing that I have written about OA is equal to OA dash is equal to C, but this is for the original shaft. If you take the original shaft, clear? So I will remove this OA dash and OA for removing the confusion. Okay, so you can see that this, after applying the torque, this shaft will deform and there will be a shear strain as well as angle of twist. Now this, due to the movement of this initial line AB to new line A dash B, this circular or rectangular mark has been converted into a rhombus. Now it is no more square or rectangular, it is deformed into a rhombus shape. And you can see that the angle which line AB makes with a new line A dash B dash is known as gamma, and this gamma is known as shear strain because we have defined shear strain as change in angle. Do not confuse this shear strain with this angle of twist. This is angle of twist, clear? And shear strain is the strain or deformation that is produced in the shaft. Now further we will explain this. Again, if you see that this arc AA dash, is common in triangle. If you consider it as a triangle AB A dash, in triangle AB A dash, AA dash, and in triangle OAA dash, this AA dash in both triangle AA dash is same. Is it same? Is it? So this AA dash is same. So if you take triangle OA dash A, so this AA dash will be equal to rho into A, because whenever, for example, you have this center and this is point A dash, this is point A, and this is the center point, and this is angle of twist. So this, by using S is equal to R theta, and for example this is rho, so by using S is equal to R theta, so here S is AA dash, length of this R, clear? R is rho and theta is a phi, so that is equal, AA dash will be equal to rho into phi, not A. Clear? Similarly, in triangle BAA dash, this AA dash is equal to length into gamma, L into gamma. So we will get this equation, L into gamma is equal to rho into phi, where L is the length of the shaft, gamma is the shear strain, rho is the variable value of the radius, it can be changed, and pi is the angle of twist. So this is the same equation. You can see this is written over here. L into gamma is equal to rho into phi. From this equation we can get phi. Phi will be equal to L into gamma over rho. So this is the angle of twist. Angle of twist is equal to length into gamma over rho. Now, we can also find out gamma as well from the same equation as we get the angle of twist. So, if you use this equation, so gamma is equal to rho into phi over L, which is the same written over here. So this equation is the important equation, that is shear strain is equal to variable radius into angle of twist over total length. Now you can see, I will write this equation. Okay. So L into gamma is equal to what? Phi into rho. This was the equation. From that we write that angle of twist is equal to L into gamma over rho. Also we can write from this equation that this gamma is equal to phi into rho over L. So this is the formula for angular deformation or shear strain, and this is the formula for finding the angle of twist. So I will further use this formula. Now in this formula you can see, if I rewrite, we can say this is equal to rho over L into phi. Now rho is what? Rho is a variable radius. So if you are talking about whole shaft, so this rho starts from 0 and less or equal to radius C. So for when rho is equal to 0, it means the center of the shaft. You are talking about the center of shaft. So shear strain will be equal to what?
0.
Shear strain will be 0. It means there is no deformation in the center. So on center line will remain the same. But if rho is not equal to 0, so there will be a shear strain. And when rho is equal to C, so then this shear strain will be known as maximum shear strain, and that will be equal to C over L into phi. Clear? So shear strain is 0 at the center and it is maximum at outer radius, at a distance of radius from the center. So this is another formula for finding the maximum shear strain. This is the same. Instead of rho, you have placed rho with C, and we know that shear strain will be maximum at a distance of C from the center, because C is the radius. Now you can also get a relationship between the gamma max and gamma. How? You simply just put the value of phi in this equation. So I will write it over here. Gamma max is equal to C over L, and phi is what? Phi is this, L into gamma over rho. So LL will cross. So shear strain maximum will be equal to C over rho into gamma. This is the relationship between the maximum strain and the maximum shear strain and the strain. So now from this formula we can also conclude that if rho is equal to 0, clear? So shear strain will be 0. And if rho is equal to C, so this C will be cut with C, so gamma will be equal to gamma maximum at rho is equal to C. Means at outer radius maximum shear strain will be equal to this gamma. Clear? And at rho is equal to 0, there will be no shear strain. Clear?
Yes, sir.
Okay. Now we will discuss about the distribution of shear stresses in the circular shaft. As we have already discussed that distribution of shear stresses in circular shaft subjected to a torsion is not uniform. So you can see from previous equation, that is gamma, that was the relationship between gamma and gamma max. One more thing, one thing should be clear. This gamma max will be equal to C over L into phi, and this phi. So we can also write this equation in term of gamma. Gamma is equal to rho over C into gamma max. So if you remember this equation, so you can create the equation for gamma max in term of gamma or any other. ठीक है ना? So you must know this equation. Okay, as we know that gamma is equal to rho over C into gamma max, that is written in previous slide, that this gamma is equal to rho over C into gamma max. Clear? So now if we multiply G on both sides, modulus of rigidity. Clear? Now we have studied that shear stress is equal to modulus of rigidity into shear strain for elastic region. ठीक है ना? So for elastic region, when there is a shear stress, so there will be a shear strain in that, and within elastic limit, this shear strain is directly proportional to shear stress, and this shear stress is equal to G into gamma, where G is modulus of rigidity, gamma is shear strain, and tau is equal to shear stress. Clear? So I have applied G on both sides of the equation, that was a relationship among shear strain and maximum shear strain. So this term will be equal to what? This will be equal to tau. Clear? And this G into gamma max will be equal to, this rho over C will be the same, and this will be equal to tau max. So we also derived a relationship between shear stress and maximum shear stress. So by using this equation, we will find out the variation of shear stresses in a circular shaft. Clear? So if rho is equal to 0, then shear stress will be equal to 0. So you can see at center point, shear stress is 0. But when rho is equal to C, so tau will be equal to C by C into tau max. So tau will be equal to tau max. So at outermost or at the radius, shear stress will be maximum. So the variation of stress from 0, if you join this point with 0, so this triangle shows you the variation, that shear stress is increasing from the center to the outermost and 0 at center. Clear? And this is only for the solid circular shaft. So if you have a hollow circular shaft, the thing will remain same, but we will consider, because in hollow shaft we have two inner radius and outer radius as well. So I hope it's clear the stresses in elastic range and distribution of stresses in the shaft. So in shaft, at the center, shear stress will be 0 and shear stress will be maximum at the outermost or at a radius. So the shear stress linearly varies with the radial position in the selection. So it means that shear stress is totally dependent on this rho, linearly vary with the radial position. If radius is equal to 0, shear stress will be equal to 0. If radius is increasing, so shear stress will be increasing. Similarly, for hollow cylindrical shaft, so you can see now from point O to inner radius, this is represented as C1. From O to the outer, this is C2. So C1 is the smallest radius and C2 is the largest radius. Clear? And if you want to find the stresses at this point C1 and C2. So at point O there is no material, so there will be no shear stress, and the shear stress will be minimum at point C1. So we can find this as well. So tau minimum will be equal to C1 over C is the maximum, which will be equal to C2 into tau max. And tau max is what? Tau max is equal to C2 over C2 into tau. Tau max will be equal to that tau. Clear? So minimum shear stress will be at point C1 while maximum shear stress will be at point C2. But this C1 shear stress at C1 is not 0. It will have some value, and this value is determined. This minimum shear stress is found by using this tau minimum. This the same formula is used. यही formula use हुआ है. Instead of rho we put C1 and instead of C we put C2, and tau max is the same. So you will get a certain value of shear stress at point C1, and at C2 tau max will be the maximum. So again the distribution of stress in hollow shaft will be like that. There will be no shear stress in the hollow portion. It will start from C point and from C1 to C2, and the stress is linearly increasing from C1 to C2. Clear?
Yes, sir.
Okay, so now we are recalling from our previous equation that was about net torque on the surface of shaft. That was this equation. This torque is equal to rho into integral of rho into TA into dA. So let me write it again over here so that it does not confuse you. So that torque was equal to integral of rho tau into dA. Rho tau into dA. Clear? Now we will replace this tau with this equation. Tau is equal to rho over C into tau max. Rho over C into tau max. Instead of this tau, we write rho over C into tau max, and this rho will be the same and this dA will be the same, and this is the integral sign. Clear? So this torque will be, net torque will be equal to integral of rho square over C into tau max into dA. Clear? Now tau max is the maximum value, means it's a fixed value, it is a constant, and C is also a fixed value, radius. So we will take these two terms out. That will be equal to tau max over C into integral of rho square into dA. This is the torque, this is the maximum shear stress. Now you might have studied that this rho into integral of rho square into d is the polar moment of inertia, and this is represented as J. So J will be equal to rho square into dA. Clear? And this J is the same. This is a polar moment of inertia. What does polar moment of inertia means? It resists the angular deformation, just like I double X or I double Y, second moment of inertia. It resists the bending moment. Clear? So J is the polar moment of inertia. It resists the twisting effects. So when you, instead of writing this whole term, you can easily put tau max into C over into J. This J is polar moment of inertia, and the value of J for different shapes are different. For circular shaft, for circular solid shaft, it is pi by 2 pi by 2 C4. This is written over here. Or pi by 32 D4 if you have diameter. Clear? And for hollow shaft, this will be the same 1 over 2 pi, but it will be C24 minus C1. That is written over here. So the value of J for different shapes will be different. So you can calculate the J value by using that formula. Okay, so now we will find out the maximum shear stress. A very important or basic formula, maximum shear stress due to the torsion. If you leave this at here and multiply C with this, so that will be T into C and you will divide by J. So this is the famous formula, tau is equal to T into C over J. This is the tau max. Maximum shear stress is equal to the product of torque into radius divided by polar moment of inertia. So if you have given a shaft that is subjected to the value of torque, clear, the diameter of the shaft is given, so you can easily find the maximum shear stress. What will you do? You will have a torque, you have a diameter, so you can calculate J, and if C is equal to D by 2. So if you put all the values, so you will easily calculate the maximum shear stress in this shaft due to torsion loading. Clear?
Yes, sir.
Now again, this tau max is equal to T into C divided by J. This is for the maximum. So if you know that shaft having center and it's having rho, and this rho start greater or equal to 0 and less or equal to C. So for finding the stresses for variable radius, so this tau will be equal to T into rho over J. Clear? So rho start from 0 and it is less than less or equal to C. So if you put rho is equal to 0, shear stress will be equal to 0. If you put rho is equal to C in this formula, so tau will be the maximum and that tau will be equal to T into C divided by G. So similarly, shear stress at center point is 0 and shear stress at the radius is maximum, for example. So if you join this, so this will be this shear stress distribution in the shaft. I hope it's clear to you now.
Yes, sir.
Okay. Now we will move toward another topic, that is normal stresses. So up till now we have seen that whenever a shaft that is subjected to torsion or torque, clear, and if the surface or faces that is parallel or perpendicular to this axis, the shaft axis. So if you take the A face, this face, now the A portion having the face that is either parallel to this axis or perpendicular, so their faces will experience maximum shear stress, because their faces will experience shear stress. But why this is maximum? Because it is taken at the outer surface, so their faces will share maximum shear stress. Clear? But when this portion, or you can say this portion of the shaft, or any patch or any incremental part of this shaft is now not, their faces is not neither parallel nor perpendicular, and it is subjected to torque. So in this condition, this will experience normal stress as well. Clear? So if the faces are parallel or perpendicular, then this problem is under pure shear. This problem is under pure shear. There will be no normal stresses due to the torque or torsion. But if you can say if there is the change in orientation of the patch or any portion of the shaft, clear, where the surface where its faces are neither parallel nor perpendicular to this axis. So in that condition, along with the shear stresses, there will be normal stresses as well. So how we will find that normal stresses? So again, if you look at this portion, okay. So if you look at this portion and if you cut it like this or this, in any way, for example, if you cut it like this, so this will be the portion BEC, and if you cut like this portion, this one, so this will be the same, clear? So when you cut it, so there will be a normal force that will be acting perpendicular to this surface, and on this face there is a maximum shear stress and maximum shear stress, and that is this area is A naught. So maximum shear stress into this area will equal to the force in this direction, clear? Shear force in this direction. Similarly, below here, the maximum shear stress into area will give you the shear force. Fs, shear force. Now, as this is a square and you have cut it, so there is a 45-degree angle, clear? And there is a normal reaction force that is acting perpendicular to this surface. Now, element with faces parallel and perpendicular to shaft axis are subjected to shear stresses only. Normal stresses, shearing stresses, or combination of both may be found for other orientation, and this was the orientation. Now you can see their faces are perpendicular and parallel, but this face is neither perpendicular nor parallel, so it is experience a normal force. So how you will find this normal force? So you can see that this is the shear stress maximum and this. So we will divide these shear stresses into components. One component will be in this direction and one component will be in this direction. Similarly, one component of this shear force will be in this direction and other one will be in this direction. Now, as the angle is 45 degrees, so here the angle is also 45 degree and this angle will be also 45. This angle between this line and this line will be 45. So this portion that is opposite, this component of the shear stress which is opposite to this normal force, this will be equal to tau max in A naught cos of 45 degree. And similarly, this component, ये वाला component, this component will be also equal to tau max A naught cos of 45 degree. Clear? Now, for finding this force, this F dash will be equal to this force and this force, means 2 times tau max A naught cos of 45 degree. Clear?
Yes.
Now we know that cos of 45 degree is equal to what? It is equal to 1 over under root 2 or under root 2. किस चीज के बराबर है? That is equal to 1 over under root 2. Clear? So if you put 2 into tau max A naught cos of 45 की जगह if you put 1 over under root 2, so now we can write these two as product of under root 2 multiplied by under root 2 because they will multiply and it will give you again 2 Tom x into a naught into 1 over under root 2. So this will cut with this. So we will get f dash is equal to under root 2 Tom x into a naught. Clear?
Yes, sir.
Tom
Yes,
x
sir.
a naught into under root 2. Now what is a naught? So if this is a naught and this is a naught, so this area will be what? This area will be equal to a naught square plus a naught square under the root. Pythagoras theorem है ना? This BA, area of BA. So that will be equal to under root 2 a naught. Clear? So if you put this under a naught area, that will be under root 2 a naught. So again, you have area this. Okay, so you have find out the force. Now due to this is the normal force, so you want to find the normal stresses, and this as this is cut it at a 45-degree angle, so normal stress is at 45 degree. We know that this is equal to F over A. Since it is F dash, so you can write F or F dash, anything. So you know that normal stress is equal to force per unit area, and this force is equal to under root 2 Tom x into a naught. And this area, which is the area of this portion, this portion, this area, this is area, while this area was a naught and this area was also a naught. So this area A is now equal to 2 into under root 2 into a naught. So a naught will cancel, under root 2 will be cancelled. So normal stress at 45 degree will be equal to the maximum shear stress. It means that when the orientation is 45 degree, so normal stress will be there, but the value of normal stress will be the maximum shear stress. Clear?
Yes, sir. Yes, sir.
So element A is in pure shear. So if this was the element A, so it was under pure shear. But element B is now under shear stress as well as normal stress. Element C is subjected to tensile stress on the two faces and compressive stress on the two. So note that all the stresses of element A and C have the same magnitude. Now we have divided this element A into two portions. So, and we have taken the force either in this direction or in this direction. You can take the force in any direction. If you take the force below, so it means this is compressive. So the value will change to the negative. And if you take it away, so the value will be positive. So normal stresses at 45 degree will be equal to plus minus Tom x. Plus means tensile stress or tensile force, and minus means compressive stress. Clear?
Yes, sir.
Okay, torsion failure mode. So whenever a shaft that is ductile, clear? So ductile material generally fails in shears because they are weaker in shear force, and ductile materials are stronger against the tensile force, while brittle materials are weaker in tensile than shears. So brittle material have higher strength in shear than in tensile. Clear? While ductile materials are usually weaker in shear and stronger in tensile. So if you look at this shaft, so maximum shear is equal to TC over J, and if you take this, so sigma 45 degree is equal to maximum shear. Now this is a shaft that is of ductile material, and when it is applied with the torque or torsion, so it will shear at this face, and this face is perpendicular to the shaft axis. And we have already seen that any face that is perpendicular to the shaft axis will experience a shear force. So this deformation of ductile material is due to the torsion, while we have a brittle material that is subjected to opposing torque, and it fails at this angle is 45 degree. Clear? So this is maximum shear stress. Sigma 45 will be plus minus tau max, which is equal to plus minus TC over J. Clear? So you can see that brittle material shear are deformed at angle of 45 degree. So this is also one of the way that you can predict that this type of failure, this is a brittle material as the failure is at 45 degree. So you can see this is a brittle material. As this here in this example, as the failure moved, this surface is perpendicular to this axis. So you can see this failure is due to shear force, and this is the shear failure of the ductile material. Clear?
Yes, sir.
Okay. Then we have sample problem 3.1, sample problem, and then angle of twist in elastic range and statically indeterminate shaft. So we will cover in this. We will cover this in lecture number 2. Thank you. Now problem 3.1 states that shaft BC is a hollow with inner and outer diameter of 90 mm and 120 mm respectively, while shaft AB and CD are solid of diameter D. So you can see that there is a shaft. There are shafts, different shafts, on which this you can say pulley or this mass that is rotating on this shaft. So this shaft is AB. This shaft is AB, while the mid shaft is BC, and there is another shaft third, that is CD. The diameter of this shaft is not known, that is represented as D, and diameter of shaft AB is D, while diameter of shaft CD is also D. The diameter of shaft BC is given, that is 120 millimeters, and the torque on this portion is given as 6 kilonewton. Similarly, torque at point B is given as 14 kilonewton, and C 26 and TD. So you have been asked to find the minimum and maximum shearing stress in shaft BC. So this is the BC, that is hollow shaft. So tau max in BC shaft and tau minimum in BC shaft. You have to find this. This is the part A of question. Second, you have been asked to find the required diameter of shaft AB and CD if allowable shearing stress in this shaft is 65 megapascal. So B point is to find diameter D. As diameter of AB and CD is same, so you have to find diameter D of the shaft for allowable shearing stress. Tau allowable is 65 megapascal. This is a very simple question. There are steps. When you follow these steps, it will be easily solved. So the first step is cut this section through shaft AB and BC and perform static equilibrium analysis to find the torque loading. So basically the first step is that you have to take the section at different location of the shaft, and you will apply the equilibrium equation in order to find the torque in these shafts, or torque in this shaft AB, BC and CD. After finding the torque in this shaft, then you will have to apply the elastic torsion formula to find minimum and maximum stress on the shaft. Then you will apply this formula, that this torque is equal to rho over C into tau max, or simply the formula of shear stress, that is TL over C. TL over C, clear? And then for second part, you will be given allowable, so that will be allowable and all the value will be available and you will be able to solve this question. So let's start. But remember, you have to find maximum shear stress and minimum shear stress in shaft BC and the diameter of shaft AB and CD for allowable shearing stress 65 megapascal. So let's start with step number 1, that is cut through section of shaft AB. So we will start from the shaft AB. So if you look, if you cut this shaft at this point, if you cut the shaft at this point, so this portion will be there, clear? And the same torque at point A is 6 kilonewton. So if you have cut it at this point, so there will be a reaction torque, which is tau AB, which will be the torque in this shaft. And this torque in shaft can be found by using the moment equation. So moment about this x should be equal to 0 for equilibrium condition. So 6 kilonewton is TA, so that will be equal to TA, that is counterclockwise, so this will be positive, minus TAB, which is clockwise rotation, that their sum must be equal to 0. It means that TAB is equal to TA, and TA is 6 kilonewton. So you have find out the torque in shaft AB. Now we will move toward the second section, that is, now you have to section it in this. So all these things will be the same. You will see in the picture. So you can see this is the point, same point A, this is the same point B, and here we cut the shaft. So if you cut the shaft, so there will be a reaction torque that will be in shaft BC. Clear? Shaft BC. Okay. So you know that this is torque A, torque at point A, which is given as 6 kilonewton, torque at point B is also 14 kilonewton, and this is the reaction torque, that is a resisting torque that is generated in this shaft. So this can be also found by taking the same equation, sum of all moment about this axis must be equal to 0. So you can see TA is positive because it is counterclockwise. Similarly, TB will be also positive, minus TBC, which is clockwise, and their sum must be equal to 0. It means that TBC is equal to TA plus TB. TA is 6 kilonewton into meter, while TB is 14 kilonewton into meter, and their sum is equal to 20 kilonewton into meter. TAB. Clear? So now you have find out. Similarly, as in you do not need the third section. Why? Because let me clear it also. So because if you take the section in third portion, so this is TC26, this is 14, and this is 6. So 2046. Clear? If you also find this, so that will be T is equal to 40, and that will be opposite to that. But here, if you remember, if you want to find the torque in CD, it is also given at the end. TD is equal to 6 kilonewton, because you will have to take the whole body, that will be in balance. So here also the torque will be torque of in this AB is 6 kilonewton. So again in third portion it will be 6 kilonewton because TAB is equal to TCD, that is 6 kilonewton. So now we have find out the torque in each shaft. Then we will move toward the second step, that is about equilibrium analysis or apply elastic torsion formula for minimum and maximum stresses on the shaft. So the first part was to find out tau max in BC and tau minimum in BC. And BC is a hollow shaft whose outer and inner dia was given. So you can see that inner radius is given as 45 millimeter and outer is given as 60 millimeter. Let me show you in the question as well. The inner and outer diameter of 90 and 120. So inner radius will be 95 and outer radius will be 60. Because we are dealing with radius, so we have to convert into radius. Okay. So you can see that C1 is 45 and C2 is 60 millimeter. Now you know that tau is equal to TL divided by GJ. Clear? That we derived earlier. So now you have torque in, if you are interested in BC shaft, so you must have torque in BC, length of BC, modulus of rigidity and polar moment of inertia. And polar moment of inertia for this hollow circular shaft is pi by 2 into C2 power 4 minus C1 power 4, where C2 is the outer radius and C1 is the inner or smallest radius. So you have value, you will just have to put this in the formula. So pi by 2, C2 is 60 millimeter as the calculation has been done in meter. So you have to convert 60 millimeter into meter, that will be 0.060 meter. Similarly, C1 is also converted into meter, so that is 0.045 meter. So put the value when you calculate this, the J value comes out, or polar moment of inertia comes out to be 13.92 into 10 raised to power minus 6. Now this has been calculated, the J value has been calculated. The G value will be given in the question. G value is given or not? The G value should be given. The minimum and minimum stress in the shaft is 65. Okay, there is a missing data about G. So let assume that it is steel shaft or any other material. The G is given over here as, okay, sorry, I have made a mistake. I have to see what is the mistake. This tau max is actually TC over J. Okay, not TL. Torque is equal to TC over J. You people are also sleeping. TC over J. So now we have calculated J. We have torque, that is in AB or BC. Sorry, BC. Again, this is also BC, not AB. Here, this tau BC is 20 kilonewton meter. Okay, so this is available, and C is depend on outer radius or inner radius. So we have to find tau max and tau minimum, and you know that tau is equal to rho over C into tau max. That was derived earlier. Clear? So we will use this formula. So as we know that tau max is equal to TC2 over J. This will be tau max because C2 is the maximum radius. So when you can see here that tau max is equal to T2, which is equal to torque in BC into C2. C2 is the outer, divided by J. So you have TBC, which is 20 kilonewton. Mention over here. C2 is 0.060 meter and J is. When you calculate it, the maximum shear stress, tau maximum, comes out to be 86.2 megapascal. So tau max has been calculated. Now we will calculate tau minimum. As you know that tau is equal to rho over C into tau max. So if you divide it, we will get tau over tau max will be equal to rho over C. So if this tau is minimum tau, for minimum you will have to find tau minimum. So this rho will be equal to C1 and the below one will be equal to C2. So we will get a equation tau minimum over tau maximum is equal to C1 over C2. Now you have C1, you have C2, and you have tau max. So put it in this formula, or this is also solved over here. Tau minimum over tau max is equal to C1 over C2. So tau minimum C1 is given, C2 is given. Whether you want to convert into meter or not, it depends on you, because the unit will cancel each other. So it will give you the same value. So tau minimum will be equal to 86.2 into the product of this value, 45 over 60. So tau minimum comes out to be 64.7 megapascal. Clear?
Yes, sir.
Okay. Then we will move to the second portion. The first part of this problem has been calculated. The second part was to find D for AB and another shaft BC, for which shearing stress should be 65 megapascal, allowable. So you know that shearing stress is equal to TC over J. Now this shearing stress is 65. So 65. Torque in AB was also calculated. That was 6 kilonewton. Diameter, you want to calculate this C, which is not known. And J is, for this you have to calculate J as well. Pi by 2 into C4 or D4, which is not known. When you calculate this, C will cut with this, and we will have 65. 65 is equal to 6. This is 6 kilonewton, so 6 into 10 raised to power 3 divided by pi by 2 into C cube. So when you calculate this, this C will come out to be 38.9 into 10 raised to power minus 3 meter. Clear? So now you have C. C means radius. Clear? C means radius. So D will be equal to 2 times C. So you will multiply 2 with 38.9 and D will comes out to be 77.8 millimeter. So this is the diameter of the shaft AB and BC, for which the shearing stress is 65 megapascal. Clear? And this is 65 megapascal, so you will also have to give 65 into 10 raised to power 3. Clear? Okay, wait. So this was all about sample problem 3.1. If you have any question, you can ask now. Any question?
No, sir.
Okay, let's move to another topic, that is angle of twist in elastic range. How you will find the angle of twist in elastic range? For that we have a formula, that is phi is equal to TL divided by JG. So I will show you how this formula comes out. Clear? Where T is the torque, L is the length of the shaft, J is the polar moment of inertia, and G is modulus of rigidity. Clear? So from our previous lecture, or in previous, we discussed that gamma max means the maximum shear strain. is equal to C over L into phi. Clear? So we have this formula, and also you know that tau is equal to G into gamma. So tau max will be equal to G into gamma max. And again from this formula, we can say that gamma max is equal to tau max over G. Clear? So now gamma max is equal to tau max over G, and gamma max is equal to C pi over L. So if this is equation 1 and if this is equation 2, so both equations are same. So if you equate equation 1 with equation 2, so we will have C pi over L is equal to tau max over G. So we are interested in finding the angle of twist, which is phi. So phi will be equal to tau max. Phi will be equal to tau max into L over tau max into L, G into C. So this is the angle of twist for maximum. No, there is a mistake. Again, this gamma is equal to tau max over G. Okay, we will see what is the difference. Okay, ये correct था, ठीक है. So this phi will be equal to tau max into L over G into C. Now this tau max is actually T C over J. Remember? So if you remove this tau max and you put this, that will become equal to T into C divided by J, and similarly L over G into C. So C will cut, so we will have angle of twist that is equal to T into L over J. So this is the formula for finding the angle of twist. So if you have T torque in the shaft, you know the length of the shaft, you know the material or modulus of rigidity, and if you have diameter, you can also calculate the polar moment of inertia. So you can easily find the angle of twist. Clear?
Yes, sir.
Now, if you have shaft having step rods having different diameter, clear, or different material, you can have the shafts. For example, if this is smaller diameter, this is larger, and again this is smaller. So again, if you have different materials or different diameter of shaft, so then angle of twist will be different in each shaft. So for that purpose, you will have to calculate the angle of twist in every shaft. You have to find the angle of twist in AC. You have to find the angle of twist in EC. You have to find the angle of twist in BE. And for total angle of twist, that will be equal to sum of twist in AC, sum of twist in EC, and sum of angle of twist in BE. So for that, what we do, we can write this angle of twist formula in generalized form. That angle of twist is equal to sum of TI LI over JI into GI, where I start from 1 and it depends upon the number of sections. So if this is for let's say this is 1, this is 2, and this is 3. So that will be equal to, total phi will be equal to T1 L1 over J1 G1 plus T2 L2 over J2 G2 plus T3 L3 over J3 into G3. So in this way you will be able to find the total angle of twist in this shaft. So there are problems also available at the end of exercise. Kindly try that problems. If you have any difficulty, then you can ask. Clear? Okay. Another topic is that statically indeterminate shaft. So in previous lectures we discussed that what is indeterminate what is mean by statically indeterminate. So if you have more than one unknowns and you have one equation, or if you have two equations and three unknowns, so this type of problems you cannot solve by available two equations. So they are known as statically indeterminate problems. Clear? So we will now discuss statically indeterminate shaft. So you can see this example that this is a hollow shaft, or this is a shaft that is fixed at both ends, and there is torque applied at the mid, which is 90 pound into foot. So if you remove the reaction forces, so definitely at point A there will be reaction torque, and at point B there will be a reaction torque. So you now in this scenario you can see that there is one torque known and two are unknown. So if you want to take the moment about this axis, for example, let this axis is x. So moment about x will be equal to 0. So TAB plus TA plus TB will be equal to 90 pound. सही? Okay. Okay. Then how you will find or how you will solve this, because you have one equation and there are two unknowns. Clear? So it is impossible to find two unknown by using this one equation. So what will you do? You will then take the section at this point. So when you section it, then T1 TA will become equal to T1, and at point B T2 will be equal to TB, and sum of total twist will be equal to theta pi 1 plus pi 2. Pi 1 is with TA L1 over J1 G minus TB into L2 J2 G2. Why there is minus sign? Because if you see it, it is twisting like that, and it is again it is opposite to that. So phi will be equal to, actually total twisting will be the sum of two, but one is in one direction, another is in second direction. So that why this is minus. So when their sum should be equal to 0, total deflection should be 0, because it should cancel, or it should be total angle of twist should be 0, because it is cancelling the effect. So when this equation become equal to 0, so you can move this whole term to this side. So it will become equal to TA L1 over J1 G is equal to TB L2 over J2 G. So from that you can calculate, you can write it in term of equation A. Clear? Or in term of equation B, that depends on you. Here it is converted into TB. So TB is equal to, इसको इधर छोड़ दें TB को. So TB is equal to TA L1 over J1 G, since the material is same, multiply by J2 into G over L2. Clear? So you can see this is the same TA L1 J2. This is for L1 J2 over L2 over J1. So GG will be cancelled. So now this is TB. So you have to put this value of TB over here, that this TB in term of TA. So you will find TA, if you put this, so you will get the value of TA, because all the values are in TA. So when you find TA, again you will put the TA value over here and you will subtract TA from 90, so you will get TB. Clear? This is how you can solve statically indeterminate shaft. Clear?
Yes, sir.
Okay, thank you for your time.
Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you. Okay, let's start with chapter number 4, that is about pure bending. So in this chapter we will discuss about what is pure bending, other type of loading that are applied on the beam, then symmetric members in pure bending, then we will discuss about bending deformation, strain due to bending, and then we will a little bit discuss about beam section properties, property of American standard shapes, deformation in transverse section. Then at the end we will have a simple problem 4.2, and in part 2 of this lecture we will discuss the bending of member that is made up of several material, for example composite beams, and then their example. So let's start with what is pure bending. So whenever a beam is applied, for example I will show you over here that, for example, this is the beam and this is applied, this is for example supported at the end, and there is a force applied in the mid of the beam, or stress is applied, or force that is applied. So due to this force there will be reaction forces at the end. For example, this is reaction RA and this is reaction RB. Clear? So RA will be equal to half of F and this will be also half of F. How we will find this? We will find it by using the equation sum of all force along y direction is equal to 0 and sum of the moment that is equal to 0, and let the length, total length is L, and the beam is symmetrical because half the force is applied on the mid of the beam, that is half of L. So the beam is symmetrical because the loading on this side is same as that of this. So in short I just write RA is half of F and RA is half of F. Now you can see that if we cut the beam at this point, or at if we cut the beam at this point, so definitely you can see this is the force and this is the reaction force. Clear? So let me zoom it. This is the force and this is also force, and it produce couple. For example, if we take this section, so there is a force and this reaction force, and this reaction force produce movement or couple in a rotation. Clear? So due to this loads or due to the couple, there will be a bending in this beam. Just like in below example, you can see that there is a weightlifter and she has left some weight. So you can see that the weight of this will act downward, while the second end the weight will act downward, and this force is acting in upward direction. So if I assume this beam over here, for example these are the load 80 pound loads that is acting downward, 80 pound, and similarly this 80 pound is acting downward. Now these are the reaction force, that is RC for example, and this is RD, and these are, for example, these are not known, and this is the total distance, that is 12 inch from this support to this support, it is 26 inch, and again this is 12 inch. So you have to find this reaction forces RC and RB. So by using this equation, sum of all forces along y direction is equal to 0. So minus 80 plus RC plus RD, this is RD, minus 80, their sum must be equal to 0. So we can see that RC plus RD, that will be equal to 160 pound. Clear? So this is the one equation. By using this equation we cannot find two unknowns. So we will apply moment equation as well. So let this is point A, this is point B. So you can take the moment at any point B, A or B. So when you applied the moment, let apply this as well. The moment about point A must be equal to 0 and counterclockwise is taken as positive. So the first force that is producing movement is RC multiplied by 12 inch and it is producing a counterclockwise. So RC into 12 inch. This second force is RD. It is also producing counterclockwise. RD into, now the perpendicular distance is 26, 27, 28 into 38. And this force 80 into perpendicular distance. This is producing a clockwise rotation. So minus 80 into perpendicular distance is 24, 6, 30, 50. So their sum must be equal to 0. So 12 RC plus 38 RD minus 400 is equal to 0. So 12 RC is equal to minus 38 RD plus 400 is the equation. In term of R, we can see RC is equal to minus 38 over 12 into RD plus 400 over 12. So this is the equation. When you put this equation in this equation, this one equation, this one, so you will get RC or RD is equal to 80 pound. And again, if you put RD 80 pounds, so you will get RC the same 80 pound. So this is how we find the reaction. Now we will talk about the bending. So you can see that this was the scenario. The weightlifter is going to lift this weight and it is represented here in diagram. So if you see that due to this 80 pound force and this RC, there will be a movement or a couple that tend to rotate. Similarly here, if we remove these forces, so these forces are also produce couple in this direction. So this one is in this direction and this one is in direction. So if we take the section CD that is shown over here. So this is the section CD. So instead of these forces, I have shown the couple. This one couple is shown over here. Similarly, due to this, equal and opposite forces are also producing couple in this direction. So this is shown in this direction. So due to this couple, this beam will tend to bend like this. Clear? So this is the axis. So this beam will tend toward to like this. The upper surface will be in tension and the concave surface will be in compression. Why? Because you can see that if it tends to bend like this, so the upper surface is going to be stretched, elongation, and elongation means that there is a tension, while the lower portion, the length of lower portion is, our concave portion is decreasing, so it means there is a compression. Clear? So we will see this is, now we will define the bending, that what is bending. So whenever a beam is loaded or subject to load or couple, and these couples are in same lateral plane, this movement is acting in the same plane. So due to this movement, there will be a deformation or there will be a bending, and this is known as pure bending. Now in this scenario, the beam is in pure bending. So we will define that prismatic members subjected to equal and opposite couple acting in the same longitudinal plane. So these are the movements that are applied on the same longitudinal plane, and due to this couple, this beam bends. Clear? So this effect is known as bending. Are this phenomena, now this beam is in under pure bending. Any question? Okay. Now we will discuss some other type of loadings. So we have already discussed this in our first or second lecture, the different type of loading. The first one is eccentric loading. The second one is transverse loading. And the third one is principle of superposition. Now one load is centric load, not eccentric. Centric load is that load which is passing through the center of any member. For example, this is the rod and this is the center. Clear? And if you apply the load that is passing through the center of this beam, so this type of load is known as centric load. Centric. The load that passing through the center, that is known as centric load. The second one is eccentric load. Now, eccentric loads are those load, axial loading, which does not pass through the section centroid, and it produces internal through section centroid producing internal forces equivalent to axial forces and a couple. Now you can see this is the object or member, and there are two forces are applied, P dash and P, 150 pound, and this is the centroid of this part, and this C dash is the centroidal axis that is passing through the centroid. Now you can see that these are the forces that are not passing through this centroid. So if you want to move this force to be passed through the centroid, so you have moved this force to this much distance, 5 inch. Clear? So whenever you section this and you want to show the force, you want to move this force to this point. So this force will be moved toward this. Now there will be a couple. There will be a movement, and this movement is P times or 150 times multiplied by 5 inch. So there will be a movement at this point. M dash is equal to 750 pound into LB. Now 750 pound is when you multiply 150 pound with 5 inch. So you will get 750 pound into inch movement. Clear? So this type of loading is known as eccentric loaded. Again, those loading are axial loading which do not pass through the centroidal section, which do not pass to the section centroid. These are known as eccentric loading. In order to convert it into centric loading, we have to move that force to the centroid along with a couple, and this couple will be equal to the force multiplied by the distance it moves to the centroidal section. So this type of loading is known as eccentric loading. The second one is transverse loading. So you have seen that concentrated or distributed transverse load produces internal forces equal to shear or couple. Now this is the cantilever beam, and it is acted upon by a force of P at point A. The length of the beam is given as L. So if due to this force there will be internal forces generated in this beam. So if you want to cut out the section at any point, for example between A and C or at any point, so when you cut the beam, so this was the initial force P. Clear? So whenever you cut it at any, there will be a shear force V, and there will be a reaction movement at the end. So let this distance where you have cut this section is X. X can be any distance. So this P will be equal to V. P will be equal to V. Clear? But it will be, it will be in opposite direction to P. Clear? In order to equilibrium, to make an equilibrium condition, because when you apply force, sum of all force along y direction is equal to 0. So in this scenario you can see the P is acting downward, that will be minus P, and V is upward, that is equal to 0. So V will be equal to P. Now what will be about the moment? So we can also find the moment. Their sum must be equal to 0. So if you take at this point, let this point is 1. So moment about point 1 is equal to 0. So what you have to do, this moment, the force into perpendicular distance x is producing counterclockwise, that will be equal to P into x, and this moment is m, that is also counterclockwise, mx or m is equal to 0. So means that m is equal to minus P into x. So we have assumed that this is the direction, but according to our equation m is equal to minus px, it means that movement is counterclockwise direction. So our assumed direction, you can see we have assumed the direction like this. So it is wrong. It means that it is producing movement lie in this direction. So this was all about transverse loading, that whenever you have a loading on beam and if you want to find the force at any section, and so whenever you will cut it, the beam, so there will be a shear force along the movement. So it's saying about the set that it produces internal forces equivalent to shear force and a couple. Clear? Any question?
No, sir.
Okay. So
No, sir.
the third thing is principle of superposition. Now what does principle of superposition means? That the normal stresses due to pure bending may be combined with the normal stresses due to axial loading and the shear stress due to shear loading to find the complete state of stress. So you can see here that this is the force that is applied on the beam. Now in the same scenario, just like in previous examples, so we have seen that whenever a body is applied, okay, let me delete some things. So principle of superposition tell us that you can add normal loading with the stresses that is generated due to pure bending and shear stresses to the shear loading. Just like in our previous example or in previous lectures, we draw the stress matrix, and that stress matrix was sigma xx, tau of xy, tau of xz. Similarly, tau of yx, sigma yy, and tau of yz. Similarly, tau of zx, tau of zy, and sigma zz. Let me erase this. Sigma zz. Now whenever you will have a scenario in which stresses are produced, and that stresses are due to normal stresses, so you can combine them. You can combine the normal stresses, just like you cannot add these normal stresses with the shear stress. So you can only add the normal stresses that is due to pure bending may be combined with normal stresses only. And whenever you have shear stresses, you can add them, but you cannot combine them with the normal stresses. So that is known as principle of superposition. We will see in the examples that how this principle of superposition exists. Okay, now we will move toward the symmetric member that are in pure bending. We will see this. We will derive the equation of bending moment for the beam that is under pure bending. So you can see here that this is the symmetric, this is a member or prismatic member. Now prismatic members are those members having same cross section throughout all the length, whether you cut it at this point or this point or this point. It will be the same cross section. Clear? So these are known as prismatic members. Now, symmetric members in pure bending. Symmetric members are those members that are similar or image shape with respect to a certain plane. So if you see that if we cut this beam AB at point or at plane C, so this is a plane C. So if we cut the beam with respect to plane C and that is subjected to couple MM dash that is acting on the same plane, you can see that this movement is the same in a same plane. This plane is a longitudinal plane. This plane is a longitudinal plane and this couple is acting on this longitudinal plane. So this is the beam that is acting upon a couple that is in the same longitudinal plane. So, and if we cut the beam at this with respect to this plane CC, so you can see this plane is this beam will be in symmetrical because the loading or the shape or the distance is same from this plane to this plane is same as that of this. That is why these are known as symmetric members. So internal forces in any cross sections are equivalent to the couple. The moment of couple is section bending moment. So if you cut the beam at this plane C, so if I again draw it, so the figure will be like that. So if you cut the beam, so there will be internal forces that will be generated and that at the end their resultant will be the couple. So you can see that this beam is cut over this plane and shown that there is an internal couple. Now, from statics, a couple M consists of two equal and opposite forces. Now, this couple that is shown over here is due to two equal and opposite forces. How we will show, I will show you below. But remember that this couple consists of two equal and opposite forces. And from static, we also note that sum of component of forces in any direction must be equal to 0. So we will use this condition of equilibrium in order to find the equations. So if you see this figure, just like, let me choose the another color. So if this is the same face of the beam, that is this face, this is this face. So when you cut it, there will be a internal forces, reaction forces due to this which result in this couple. Clear? Now if again I recall you, let this is the x-axis, this is x-axis, this is your y-axis and this is your z-axis. And you have already studied that, for example, this is the member. I will just recall you. This is x, this is y, and this is z. So this face is this z direction and y. So this is x face or x plane. So on this x plane there will be one normal stress, that is sigma xx. Clear? One is tau of x in the direction of y and the second force will be like this. Agar main isko, I will draw it over here like this, the face. So this, there will be a normal force sigma xx, there will be a shear force on this surface that will be equal to tau of xy and there will be another shear force that is tau of xz. Clear? So this was just for recalling purpose. Now we will apply the same thing on this surface of the beam, that is section at point C or at plane C. So you can see this was the plane. Let's divide this face into small areas. That is shown over here also. So this is the small area having area dA. So let's concentrate on any one. For example, this one. So this is the small area having area is dA. Its area is dA. Now at this small area, there will be a perpendicular or normal force that will be in x direction, and this force will be equal to normal stress into the smaller area, because force is equal to stress into area. Stress is equal to force per unit area, and force is equal to stress into area. So this normal stress that is acting on this differential area dA is equal to sigma x into dA. Just like I did that on this face, there is a stress, normal stress xx or sigma x. Clear? So another force that is on this face, there will be two shear forces. One will be tau of x z. Tau of x in the direction of z. This is z direction. This is x direction. This is y direction. And there will be another shear force, that is tau of x in the direction of y. So you can see this is the force. This in the direction of z. There is a force, shear force, tau of xz in this direction. You can see this is tau of xy, and this was tau of xz. So there is a tau of xz that is acting on this small area. So this shear force is converted. This shear force is equal to tau of xz into differential area A. Similarly, on this differential area, there is also a shear force. I will zoom it so that you can easily understand. So you can see there, this is the shear force that is acting. Now this shear force is equal to, this is xz plane, this plane is xz plane or x plane. Sorry, xz plane, not xz plane. This is x, this is z, and this is y. So this plane is x. So tau of x, y. X mean on x plane and in the direction of y, and tau is shear force. So shear force that is acting on x plane but in direction of y. So when you multiply shear force with the differential area, so you will get a shear force. So basically on this small differential area, there is a one normal stress and there are two shear forces. Clear? Clear? Okay, now the same thing is shown over here, but now the stress is like this. In order to show that the sum of all the forces acting on this surface is equal to 0. Clear? So these are the same thing. Means if you take the integral of our whole area, you can find the total stresses. So let's move forward. We will apply the equation of equilibrium. We have stated that sum of all forces along any direction must be equal to 0. So in this scenario, you can see along the x-axis there is the force that is represented as Fx. Fx means force along x direction. And we have stated that sum of all forces along x direction must be equal to 0. So how we will find the sum of all forces? That is integral of all the forces over the entire area. So this is the force, sigma x into dA is the normal force. Clear? When you integrate it, so sum of all the forces along the x direction, that must be equal to 0. We state that. The second thing that is very important and you must be able to understand that is the moment is the same about any axis perpendicular to the plane of couple and 0 about any axis contained in the plane. So you can see that this x, this is the plane, longitudinal plane mm dash, and you can see this longitudinal plane contain axis x and y, not z. Z is perpendicular to this longitudinal plane. So it is saying that movement is same about any axis perpendicular to the plane of couple. Now this z axis is perpendicular to this longitudinal plane. So this movement will be actually mz. This will be the movement about z axis. Or we can say that this movement is actually about z axis, because this z axis is perpendicular to this plane movement, to this plane containing movement. Now the movement is same about any axis perpendicular to plane of couple and 0 about any axis contained in a plane. Now you can see this x-axis is contained in this plane. So movement about x will be equal to 0. Similarly, movement about y must be equal to 0. Why? Because we have been told that movement, that is movement about any axis contained in plane will be 0. That's why this y-axis and x-axis that is contained in this plane, that is having movement. So movement about these axes will be 0. Only the movement that is only the movement exists on axis that is perpendicular to the plane containing the movement. So only the movement mz is not equal to 0. I hope it's clear to you. Okay. So you can, I will again I will erase some things so that you can fully understand the concept. So if I zoom it again, if I zoom it like that, so you can see here that this was the differential area dA and it is at a distance of z from this origin z, and similarly this differential area is also at a distance of y from this base. It is y much times above this axis. Clear? So now the stress or this stress, the movement about this stress, this normal stress, this is the normal stress sigma x, and this sigma x into dA is the normal force. Now this normal force is producing a movement about y-axis, because this is the force and this is the perpendicular distance. So it tend to rotate it along y-axis. So we say that this movement about y, which is equal to integral of sum of x into dA, and perpendicular distance is z. Clear? The movement. But according to the above mentioned rule, that axis containing in a plane that is having movement will be equal to 0. So this my is equal to integral of sigma x into dA into perpendicular distance z. Their product must be equal to 0. Clear? Now the second is that movement about z. We want to find the movement about z. So this normal stress is also producing a movement about z-axis, because this is the normal force and the perpendicular distance is this y. It will tend to rotate about z axis, and this movement will be the same as it is rotating in clockwise direction. So that will be equal to minus normal force, which is sigma x into dA, clear, into perpendicular distance, and this perpendicular distance is y. So this mz is equal to integral of minus y sigma x into dA, and it is equal to the same as the moment applied in the longitudinal plane. This mz is equal to m. Any question? I think it's clear. Okay, let me move further. Okay, so basically you must understand how this equation comes out and what is the meaning of these equations. We will use further these equation in our coming slides. So you must be clear about these things. So now we will move toward the bending deformation, that what will be the deformation or what will be the shape of deformation when a beam is subjected to couple or movement. So you can see that beam with a plane of symmetry in pure bending. So let's say you have a symmetrical beam. This beam, this was the initial, let me write it over here. So this is the initial beam, clear, and it is subjected to m dash, two equal and opposite couple. This is point A dash, this is B dash. The upper point is A and B. So due to this loading, I think we should use some, let me select portion so that I can also write it clearly. Notebook. A, B, C, any name. We will have to wait. Okay, so where are the shapes? This is the beam, for example, and that is subjected to couple m dash. This is the couple, two equal and opposite. This is A dash, this is B dash. Similarly, this is A or B. So we will go with the book. So A, it's okay, clear. So this is due to this type of loading, this beam will tend to bend. It will just like this shape. Clear? So this is A dash, B dash. The length below this surface will be increased, and there will be a decrease in length above, because this concave surface is in compression and this convex surface will be in tension. Clear? So there will be increase in the length below because this surface is in tension while this surface is in compression. We can also have this type of scenario that, for example, you have the beam like this and the loading is opposite like this. So in this type, the deformation will be like this. So this now the upper portion is in tension while the lower portion is in compression. But this scenario depends upon the moment that is applied on the beam. So you can see here that this was the beam, this is the frontal view of the beam, and this is the top view of the beam, and this beam is applied moment m dash. Due to this type of movement, the shape will be like this, it will bend like, the beam will bend like this. So you can see that there will be a deformation in the upper and lower boundary. The upper boundary, the length on the upper portion is decreased. So it means that there will be a compressive stress on this surface, or the surface is being compressed, while there is elongation below this surface, or elongation in A dash B dash. So it means that this surface A dash B dash is under tensile load. Clear? So member remains symmetric, bends uniformly to form a circular arc. So if the beam is applied with this pure couple force, so it will deform and it will tend to form a circular arc. So if you join the end, if you join this A dash, and if you also extend B dash, they will join at a point, and let this point is point C. Clear? So length of top decreases and length of bottom, length of top decreases and length of bottom increases. So in between top and bottom, there will be a plane or a line in which there will be no deformation, which will have the same length as above, as original length of the beam. So that will also lie in between the upper and lower beam. Let this is the line, for example. So where the deformation is equal to 0. In upper portion, deformation exists, but that is negative. Negative mean compression. In below portion or convex portion, elongation exists and it is positive, means tension. In between upper and lower portion, there is a plane or there is axis which remains the same length as that of initial beam. So this is known as neutral surface or neutral axis. So a neutral surface must exist that is parallel to the upper and lower surface and for which length does not change. Clear? So we will also see that this in our this topic. A neutral stress and strain are negative compressive above the neutral plane and positive below the neutral axis. So you can see here this is the neutral axis. So strain above the neutral axis is negative. So it means the stress will also negative. That will be compressive. And the strain below the neutral axis is positive. So the stress will be positive. But this is true for this type of loading. So if you reverse the loading just like this, so it will be now vice versa. The upper portion will be in tension and lower portion will be in compression. I hope you have got this point. Clear? Now we will find what are the strain that are produced in the upper and lower surface. What will be the behavior of strain that is applied? What is the behavior of strain for a beam that is applied under the couple loading? Clear? So again, this is the same thing. So you have seen that the beam was applied with the moment, and due to that moment, the beam bends. Initially, the beam is of length L. This is A dash, B dash, A and B. This is before loading. When you apply moment, it tend to bend like this. The length A dash B dash increase, clear, and length A B decrease. A dash B dash increases and AB decreases. So we have already explained that there is a plane in between upper and lower portion whose length did not change, and that axis is known as neutral axis. Clear? So let this DE is the neutral axis and this point O is the center. Clear? So if you extend this line A dash B dash, A dash A, and you also extend line B dash B, so they will meet at point C. Clear? As shown in this figure. So distance from neutral axis to the C is represented as rho. Clear? This rho is radius of curvature. We will discuss it in a while. So let the distance between this neutral surface to the center of this curve is rho, and these two lines AC are BC. They are making an angle theta. Clear? So we know that initial length, this length DE, this DE is equal to what? DE is actually the length of the beam. D is the neutral axis, and we have explained that neutral axis does not change. Length of neutral axis does not change. So DE is equal to L. So by using, as this DE is arc, so we can see that DE is equal to L and it will be equal to rho into theta. Clear? This is the original length of the beam. The original length of beam is rho theta. Now after deformation, or you can say that the length is decreased on the top side. Clear? So this length is decreased on the top side, and if you take any axis about the neutral axis, so the length will be decreased. On this axis the length will be decreasing, on this axis the length will be decreasing, and go on. So maximum decrease in the length will be on the top portion, that is AB. So let this JK is a imaginary axis where you want to find the strain. You want to find the decrease on this JA. So the new length will be L dash. This length JK, that will be new length because it is changed from L to L dash. Let this length is L dash. Now this L dash will be equal to what? And this L dash or this JK is at a distance of Y from the neutral axis, or L. Clear? It is at a distance of Y from this. So now from CK, the distance CK will be equal to distance of CD is rho. CD was rho. Clear? This CD was rho. Now CJ or CK. This CJ or this CK is same. This is equal to rho minus Y. This total, this from this point till this point, this is rho. Clear? So you want to find distance from this point till this point. So you have to subtract this Y from rho. So this distance rho minus Y. So new length JK, the length of new axis JK, or deformation in the JK is L dash, which is equal to rho minus Y into what? Rho minus Y into theta. Clear? So this was the original length. This is the change or new length. New length. Now you have to find. You know that change in length is equal to. Change will be equal to new length minus original length. So new length is new length is rho minus y into theta, and new is rho theta. So you multiply it. So rho theta minus y into theta minus rho theta. So rho theta will cancel with rho theta. We will left change in length or deformation is equal to minus y into theta. That is given over here. This L dash is equal to rho minus y into theta. So change will be equal to new length minus original length, which is equal to minus y into theta. And you know that strain in x-axis, because this was x, this direction is x, clear, and upper is y. So strain in x direction is equal to change in length divided by original length. Now this change is equal to minus y into theta divided by original length, which is L. So V comes out to be strain is equal to minus y theta over L. So it means that strain varies with y. So as you move above, the strain will increase. Clear? So this was the neutral axis. As you move away from neutral axis, so strain will increase. So at this plane there will be strain, this plane, this plane, this plane, but maximum strain will be on the top. Clear? So as the top is the strain will be maximum, but it will be negative, means that there will be a contraction. Similarly, the y is also varies below the neutral axis, but there is a tension. So we can say that this is maximum strain will be here and here. I will write epsilon m. Epsilon m will be maximum, but here the value will be negative and here the value will be positive. Clear? And again you can see that if you put y below the neutral axis, so the value of y will be negative. So negative will be positive. So the strain below the neutral axis will be positive, means the lower portion is in tension. Clear? Okay, so we see that strain is equal to change in length divided by original length, and change in length is minus y into theta, and original length is L, and this original length is already rho into theta. Clear? This is shown over here. So in short, strain in x direction is equal to minus y over rho. Strain is equal to minus y over rho. Clear? So what does it mean? It means that strain varies linearly with y. If y increases, strain increases. If y decreases, strain decreases. So from this equation you can also find the maximum strain as well. So let me erase again something from this. So I will write another marker. Okay, so we have shown that the y is distance from neutral axis to above. Now this y will be maximum at this point. So let distance from neutral axis to the topmost layer or to the bottommost layer. This distance is C. Clear? So C is maximum if I replace y with C. So epsilon x will be equal to epsilon m, means maximum strain. So maximum strain is equal to, इस y को replace कर दें c से, so that will be equal to c over rho. This is for upper portion. For lower portion, that will be equal to C over rho. Clear? So you have understand that this is maximum strain, epsilon m, that is equal to C over rho. Or if you want to find the rho, radius of curvature, so we can have formula C over maximum strain. Clear? Now, again, if you put the value of, okay, let me write it again over here. मुझे ये आप बताते जाएं. ये क्या था? Epsilon x is equal to minus y over rho. ठीक है ना? So maximum strain was C over rho. Okay, why C over rho? Because from neutral axis to the uppermost layer, this y is positive, and from C to the lower portion, this y will be the negative. So maximum strain will be, if you put this y as minus C, because the maximum strain will be in tension. There will be strain in compression, but that will be contraction. So maximum strain will be equal to C over rho. And again, this rho is equal to maximum strain over C. We have, let me write, this is equation 1, this is equation 2, and this is equation 3. So this is strain in x direction, this is maximum strain, and this is radius of curvature. So if you put this strain, the value of the value of radius of curvature in equation 1, so this will be epsilon x will be equal to minus y over epsilon m into epsilon m over c. So that will be equal to minus y y into c over, I think there is a confusion over here. Let me check it. We did mistake in equations. Minus y over rho. Y is equal to minus y over rho. This is clear. So C over rho. C over rho. This is also clear. And this rho is equal to C over m. This rho is equal to C over, this rho is equal to C over m. So epsilon x is equal to, rho is equal to C over epsilon m. Rho is equal to C over epsilon m. We did mistake over here. So if rho over here, that will be equal to, so you people are also sleeping. So this rho is equal to C over epsilon m. And when you put over here in this equation, so that will be C over rho m, and that will be equal to minus y over C into epsilon m. So epsilon x is equal to minus y over C into epsilon m. So if you have maximum strain, you want to find the strain at any point above the neutral axis. So you can find the strain by using this equation. So again, you can see that there are 4 variables: epsilon x, y, c, epsilon m. If you know any 3, you can find the 4th one. Clear? So remember this equation as well. So this is epsilon x is equal to minus y over c into epsilon m. Clear? So again, this is the cross-sectional area that is shown, that this is the neutral axis, and this is from neutral axis to the topmost, the distance is c, and it is maximum distance. And if you move from the neutral axis to above, let this distance is y. Clear? Now this slide was all about strain that is due to couple or moment loading in a beam, and that moment is in a same plane. Now as there is strain in the upper and lower portion, there will be strain in this portion, concave, as well as in convex. So in concave portion, the strain is negative, so means there will be a compressive stress. And in convex portion, it is positive, strain is positive, so there means there is a tensile stress or tensile stress. So how you will find these stresses? So again, in short, as we know that stress in x direction or stress in x direction is equal to modulus of elasticity into strain in x direction. So from previous slide, this strain in term of maximum stress, maximum strain, this if I write E same, and this epsilon was minus y over c into epsilon m. So this stress will be equal to sigma x. Clear? Sigma x. Again, you have write this strain in term of this sigma x is equal to E into epsilon x, but you have written your epsilon x in term of maximum strain. So this strain will be also maximum. Clear? So again, this strain is linearly varying with the stress. Sorry. Okay, this is the same x, not m. This is the same x is equal to minus y over c. Now this E into epsilon m. Again, if let me write this, sigma x is equal to minus y over c into E into epsilon m. Clear? So E into epsilon m is sigma m. So stress is equal to minus y over c. Just like you have written that epsilon x is equal to minus y over c into epsilon m. So you can also write epsilon x is equal to minus y over c into sigma m, where sigma m is the maximum stress. Clear? So this stress also linearly vary with y. So again, if this is the neutral axis, so from this equation, sigma x is equal to minus y over c into sigma m. If y is equal to 0, so if you put y is equal to 0 over here, so 0 divided by anything is equal to 0, so stress at neutral surface will be 0. If you increase y any value, so that there will be stress, negative stress. So this negative stress will be maximum when this y will become equal to c. So this sigma x will be equal to sigma m. Clear? So if y is equal to c, y is actually distance from neutral axis to anywhere you want to find the stress or strain. So if y becomes c, so then this stress is sigma x will be minus sigma m, and this minus mean negative sign, compression. So you can see that stress linearly varies, increases, and it is maximum at the top. So this sigma m is the maximum stress, and the direction will be over here, means that it is in compression. Similarly, if sigma x, if y is increasing downward below the neutral axis, so it will be increasing, but if y is equal to c below, So if you put y is equal to minus c over here, so sigma x will be equal to sigma m, not minus, positive. So means that stress linearly varying, and it will be the maximum. It will be the maximum at the outer layer. So this was all about the stress distribution in beam that is under bending or couple. Clear? Did you understand about the stress distribution in the beam? Okay, so till now we have explained that stress linearly vary with y. Clear? So if y is increasing, stress will increase. So above the neutral surface, if y is increasing, so c is the maximum distance from the neutral axis to the outer surface. So stress will be the maximum, and that is sigma m. And this sigma m will be equal to sigma x. This will be the maximum stress. Similarly, below the neutral surface, the stress will be the maximum, but it will be positive. So means there is tensile stress. So this here sigma. So okay. So again, I will repeat that stress linearly varies with respect to y. If y is increasing, stress will increase. So at neutral surface, the stress will be 0. Clear? So maximum stress will occur on the both upper and lower surfaces, but on the upper surface it will be negative and compressive, while the lower surface it will be positive and tensile stress. Now from our previous equation, static equilibrium condition, that we discussed that f of sum of all forces along x direction must be 0, and we wrote that this is equal to integral of sigma x into that small differential area that must be equal to 0. Now this stress is actually sum of all forces is equal to 0. Now we can see that this stress is actually minus y over c into sigma m into dA. That must be equal to 0. So y and c is sigma maximum is a constant value, c is also a constant value. So I will bring them out. So sigma m over c minus, and that will be equal to integral of y into dA. That must be equal to 0. Now you can see sigma m is maximum value, that cannot be 0. Y is also c is also a constant and maximum value, that cannot be 0. It means that integral of y into dA is equal to 0. So integral of y into dA is the first moment of inertia. So first moment of inertia that is passing through the first moment of inertia about the neutral axis is equal to 0. So this is also proof. This if someone asks you to define how first moment of inertia about the neutral axis comes out to be 0. So this here is a proof that sum of all forces along x direction must be equal to 0. So then you have to put the stress or force in x direction, and you have to put all the values. So from that, at the end you comes out with the equation that integral of y into dA is equal to 0. So integral of y into dA is the first moment of inertia, and that is equal to 0. So first, this shows you that whenever a beam is given with a neutral axis, so its first moment of inertia about the neutral axis must be 0. Clear? So here it is also given that first moment with respect to neutral plane or neutral axis must be equal to 0. Therefore, neutral plane must pass through section centroid, and that neutral section must pass through centroid. If it is not passing through centroid, then first moment of inertia will be not 0. For example, if this is the beam and this is center, cross section of the beam, and this is center, and if this neutral axis is passing through centroid, so in this scenario, the first moment of inertia about this neutral axis will be equal to 0. But if this is the center, for example, and this is your neutral axis, for example, so in this case, first moment of inertia about this neutral axis will not be equal to 0. Clear? Okay.
Yes, sir.
So again, I will erase some things from screen. And from our static equilibrium condition that sum of all forces along x direction must be equal to 0, we came with a conclusion that first moment of inertia about neutral axis that passing through the centroid of the section must be equal to 0. Now we already discussed that moment that is about z axis is equal to m, and that was equal to integral of minus y x into dA in our earlier slides. That moment about z that is equal to m, which is equal to integral of minus y into sigma x into dA, that is equal to m, not equal to 0. That is equal to m. So again, this integral of minus y and sigma is equal to minus y over c into sigma m into dA. So again, sigma and c is constant value that will be outside, so sigma m over c integral of minus y that will be plus y square into dA, and that is equal to m. Now this term integral of y square into dA is the second moment of inertia about the neutral axis. Clear? And we represent this integral of y square into dA is equal to I. So I will just write m is equal to sigma m over c into I. Clear?
Yes, sir. Sir, recording on की है, sir?
Yes, the recording is on. Okay, so let's check. Okay. So moment is equal to sigma m into I divided by c, where sigma m is the maximum stress, I is the second moment of inertia about neutral axis, c is the distance from neutral axis to the topmost or bottommost layer, depends upon. Clear? So if I divide I above and below, or if I divide the numerator and denominator with I, so I will get sigma m is equal to c over sorry, there is a mistake, I was confused. Okay, so this was the equation. This m is equal to moment is equal to sigma m into I over c. So I want to find the sigma m. So sigma implies that sigma m maximum stress will be equal to m into c divided by I. This is the equation of bending stress for the beam that is applied with the couple or moment m, and this stress is the maximum stress. Clear? Which is given over here as well. This sigma m is equal to mc over I. So again, this sigma m is equal to mc over I. So if I divide the above term by C and below term by C. There will be no effect. So this sigma m will become equal to m over I by C. Now this I by C is represented as S. S is equal to I by C, and this is very important term. This S is known as section modulus. Section modulus. How it is important, that is explained in a slide that is in slide number 9 or 10. So we will explain this, the importance of section modulus. So now maximum stress is equal to M over S, where S is equal to I over C. Clear? Any question till now?
No, sir.
Okay. Now you know that sigma x is equal to minus y over c into sigma m. So if you put the value of sigma m, which is m over s, or just you mc over I will show over here. Okay. Sigma m is equal to mc over I. Clear? And sigma x is equal to minus y over c into sigma m. So you have to put the value of sigma m over here. So that minus y over c into mc over I. So CC will cancel. So sigma x comes out to be minus m into y divided by I. This equation and the above equation, both are same. You can see that this is C. C is the maximum distance from the neutral axis to the top. So definitely it will yield you the maximum stress. Now this sigma x varies with this y. Y is the distance from neutral axis to the top or below. And this minus sign exists when you move above, that will be, this y will be positive, and when you move below, this y distance will be negative. So the same thing, same equation, but the difference is that this is for maximum stress and this is for the stress at any point from the neutral axis, either above or below. I think it's clear. And this is the equation, bending equation. This is the equation for finding the bending stresses in the beam when it is subjected to a couple load or moment load in the same longitudinal plane. This was all about the stress in the beam under pure bending. Clear?
Yes, sir.
Okay, now we will move toward to define section modulus. So we discussed that sigma m is equal to mc divided by I, and then we discussed that maximum stress is equal to m over I by c, and then we said that this I by c is equal to S, which is known as section modulus. So stress, maximum stress is equal to m over S. Now you want to have minimum stresses in the beam. Clear? So for that you must have higher section modulus. If section modulus is high, then the stresses generated in the beam will be the lower one. So you have to, section modulus is the modulus of the beam. If its value is high, then the stresses generated in that beam will be low. Clear? So the maximum normal stress due to bending is equal to sigma m, which is equal to m over s. If s is higher, so sigma m will be lower. So a beam with larger section modulus will have lower maximum stress. Now, for example, consider if you have a rectangular beam. cross section is rectangular. This is its breadth and this is its height. Clear? So, and this is the center. As this is rectangular, so center will be at a distance of h by 2. Clear? This will be h by 2 and this portion is also h by 2. Now, we know that section modulus is equal to I over C. So, for beam having breadth B and height h, the second moment of inertia is equal to BH cube over 12. Clear? So, this I for rectangular beam is equal to 1 over 12 BH cube. While C is what? C is the distance from neutral axis to the topmost and that is h by 2. So when you put h by 2, section modulus comes out to be 1 over 6 BH cube. Now area of this rectangular cross section is equal to B into H. Clear? So if I write 1 over 6 BH cube as B into H square, I can write it as well. So this 1 over 6 will be 1 over 6. Sorry, this is H square. And this BH is area and no. This is 1 over 6 BH cube. Clear? And we want to have. Acha, ye H is case 1 H will be cancelled. This is 1 over 2 BH square. Clear? So again I have to erase this thing. There is an error. So this is 1 over 6 BH. No, so BH is area and H is height. So section modulus for rectangular cross section is 1 over 6 into AH. Now the question is that section modulus for rectangular beam is equal to 1 over 6 into H. Now if you have been given as example that these are the two beams having height, one having height is equal to 6 inch and breadth is 4 inch and the second is height 8 and breadth 3 inch, both having area 24 inch square. Now both the beams have same area. So what will you prefer to choose? Which beams you will prefer to choose? Because both have the same area. So you will prefer to the beam having higher height. Because in this both scenarios, area is the same. But you know that section modulus is equal to 1 over 6 A into H. Now the beam having higher height will be selected and will be the safer than that of the same area beam with lower height. Clear? So it means that if you have two beams that are of same area, but you have to select that beam having high height. Clear? So if height is higher, so definitely the value of section modulus for this beam will be higher than this. Clear? So S section modular, let this is 1 and this is 2. So section modulus of 1 will be less than section modulus of 2. So definitely sigma M2 will be greater than sigma M1. Clear? So sorry. Sigma M1. Again, you people are sleeping. This S2 is higher. So sigma M2 will be less than sigma M1. Stresses in M1 or this beam 1 will be higher because it's having lower section modulus, not area. Section modulus of 1 is lower than section modulus. I have written section 1 modulus is lower than section 2. So stress in section 2 will be minimum as compared to the stress in section 1. So sigma M1 will be greater than sigma M2. Clear? Any question? So again, in short, if you conclude that, so a beam with higher section, a beam having higher height, or a beam with higher height will be having higher section modulus. So less stresses will be generated in that beam. There is another example of short beam and wide flange beam. So you can see that this is S beam. S beam means short flange beam and wide beam means wide flange beam. So if I draw the beam over here, I will draw it roughly. So if this is the beam, let's say for example, if this is the beam, so this upper portion, this portion and this portion, this is known as flange. If I draw it, let me erase this line and also erase this. So if I draw it in 3-dimensional, so this plate will be the top plate, this is the bottom plate, and so on. So in 3-dimensional, so this about this portion, this top one is known as flange, and this below portion is also known as flange. Clear? And the middle portion, or this middle plate, or this portion, thin portion, this is known as web. Clear? This is the breadth or width of the beam. This is from flange to flange, from top of the flange to the bottom of the flange. This is known as height of the beam. Again, if I draw it like this shortly, so the thickness, this thickness of the flange is known as TF, which is thickness of flange. This thickness of web is known as TW and known as thickness of web. Clear? So this is short beam, this is wide beam, short flange beam and wide flange beam. You can see its flange is short and you can see its flange is wide. Clear? They are shown both having the same neutral axis. Clear? So now between two beams with same cross-sectional area, the beam with greater depth will more effective in resisting bending. Structural steel beams are designed to have large section modulus. Clear? So now this is the short flange beam, this is wide flange beam. Clear? So in between these two beams, which will you prefer to select? Any answer?
this case, both.
Which?
So stress,
Which one?
wider one.
Wider one. But you can see both will have same, as the height is same. Wider one will be the safer one, but actually due to its higher weight of the beam, the weight of the beam will also increase. So you have to consider, being an engineer, you will have to design a beam or any system that should be of lesser weight. Again, by putting the material into your design does not mean that it will be safer. It will also again increase the weight. So you have to design, both the beam have same height, but this will having less weight. Although this will be more safer, but it will increase the weight of the structure. So you will have to choose you will have to keep in mind that the weight of the structure should not increase as well. Clear? So conclusion is that section modulus is important in design parameters. So a beam with higher section modulus will have lesser stress, or it will resist more to the stress. Clear? We will also see in design problems, when we design a problem, we will see that you can also calculate section modulus. For example, I will describe in a short that stress is equal to M over S. Clear? So if the stress is given and moment is given, you can calculate S. When you have the value of S, you have table properties of American Standard Shape that is at the end of the book as appendix C. So you will have any value from here, the S value. Then you have to simply look at the value of S in this table. If any value that matches with this, any one, for example, if your value that you have calculated above comes out to be this or closer to this, so you can select this short flange beam 510 by 120. So this is how you design the beam. Now this is property of American Standard Shapes, and this is available at the end of the book. So the shape is short flange beam. Sorry. You can see this is the beam. This is BF. BF means width of the flange. D is the height of the beam. TF is the thickness of flange. TW is the thickness of beam. This is x-axis. This is y-axis. So for example, S610 by 180. Short flange beam 610 by 180 means that it's having area 22900 square millimeter. Total height is 622 millimeter. This height will be 622 millimeter. Width is 204. This width will be 204. Thickness of flange TF will be 27.7. Thickness of web will be 20.7. Moment of inertia about, second moment of inertia about x-axis will be this one. Section modulus will be this one. Radius of gyration that we will discuss later on. Okay. Similarly, about y-axis, second moment of inertia is this one. Section modulus is this one, and radius of gyration is this one. So this table show you the properties of standard shapes that are produced by American industries, steel industries. So by using this table, you can select the required beam of your required design. Clear? Any question till now?
Sir, section modulus x direction, y direction.
This varies. Okay. Again, I have solved some problems related to this chapter number 4 that are available. So you can observe in that I-XX is different and I-Y is different. How? So if you watch that video of that problem in which I-XX is also explained and I-Y is also explained, so you will be able to understand that why these are different. So based on that, section modulus about y-axis, because section modulus is equal to I over C. So if you are going to take I-XX means second moment of, or Ix means second moment of inertia about x-axis. So it will be SXX or SX. So if you are going to find SY, so it will be I-Y over C. Again, this can be cleared if you watch that problem carefully, that how this differs. Because in that problem, you have been asked to find the movement about x-axis or movement about y-axis or stress at about x-axis or stress about y-axis. Clear?
Okay.
Okay. Next topic is deformation in transverse section. So as discussed previously that this was the beam and that is bent due to the movement as shown over here, that is m and m dash, and this movement was about z-axis. Clear? So due to this movement there will be a contraction in the upper portion and there is expansion in the lower portion, or above the neutral axis the upper surface contracts, or there is a shortage in length, or you can say the length is decreasing, while below the neutral, this is the neutral plane or neutral axis, so below the neutral plane the length is going to increase. So due to that we discussed that there is a radius, this is the radius of curvature, and we discussed this thing in the above slide. I will show you here. So we here obtain radius of curvature equation, we here obtain the strain in the x direction, which is sigma epsilon x is equal to minus y over c into epsilon m. Epsilon m is the maximum strain. Clear? So again we will use this equation. I will write down again. So from that we discussed that radius of curvature was equal to epsilon m over c. Let me check it. Epsilon m over c. Epsilon, sorry, c over epsilon m. Let me correct it as well. So you have to memorize it as well. So epsilon m is epsilon is equal to c over epsilon m. So now if 1 over, if I take inverse, so 1 over rho is equal to epsilon m over c. Now this 1 over rho is known as curvature. So if you want, if anyone asks you what is curvature, so 1 over rho is equal to 1 over rho is actually a curvature, and you can also define that curvature is the reciprocal of radius of curvature. So 1 over rho is equal to epsilon m over c. Now from this formula of curvature, 1 over rho is equal to epsilon m over c, and if this c remains the same, you know that epsilon m is equal to sigma m over E, as maximum stress is equal to E into epsilon m. So epsilon m will be equal to sigma m over E. So that will give you maximum strain. So if you put the value of this maximum strain, that is sigma m over E over here, so 1 over rho will become equal to sigma m over EC. Clear? Now also you know that this sigma m is equal to mc over I. So again when you put the value of sigma m over here, so that will be equal to 1 over EC, and instead of sigma m that will become mc over I. So cc will cancel out, so 1 over rho, which is curvature will be equal to m over EI. So if you know the movement, you know the material modulus of elasticity, and if you know the second moment of inertia, so you can easily calculate the curvature. Now this was something about the curvature. We will now discuss that what is an elastic curvature. So if you see that there is a contraction in the length and above the neutral axis, and expansion in length in the below the neutral axis. Again, if you see that the length is decreasing longitudinally above, along x-axis in upper portion, but in cross section you can see that this length is increasing. Similarly, length increasing in longitudinal axis below the neutral surface, but again in transverse direction the length is decreasing. So it is increasing and it is decreasing in cross or transverse portion. Clear? So due to expansion in the upper portion above the neutral axis in transverse direction and contraction in below transverse section, this creates an effect that is known as anti-elastic curvature. So expansion above the neutral surface and contraction below it cause as in plane curvature. So you can see previously for curvature we just take this and we extended this, but now due to transverse expansion and contraction, if you join them, they will meet at point C dash. So from neutral axis to dash this C dash, because these planes are this transverse direction, expansion and contraction also produce an in plane curvature, and that is represented as rho dash, and this rho dash is equal to rho over nu. Now I will explain it how. So actually whenever in Poisson ratio we have told that strain in lateral plane, if for example, again I will explain just by using example. So if this is a body that is subject to stress in x direction or force in x direction, so it will produce strain in x direction as well as it will produce strain in y direction, which is contraction, and we discussed that this is equal to minus nu time epsilon xx. Similarly in z direction there will be a contraction, and that is also equal to minus nu time epsilon xx. So due to this anti-elastic curvature, so this will be equal to radius of curvature divided by nu. So similarly, as 1 over rho is curvature, so 1 over rho dash will be anti-elastic curvature, and it will be equal to nu times 1 over curvature. Clear? So I think this is clear to you now. And this expansion above the neutral surface, that is in transverse direction, and this contraction below the neutral surface in transverse direction, it causes an in-plane curvature, and this is known as anti-elastic curvature. So this anti-elastic curvature is 1 over rho dash, and that is equal to nu times 1 over rho. So this was deformation in transverse section. Next we will move to sample problem, and this problem is already solved by me in my problem videos, but I will also go here again. So you can see this is a member that is fixed at one end, and the moment is given over here, that is 3 kilonewton. So due to this moment, this will tend to bend. So there will be tension or increase in length in upper portion, and in below portion there will be a contraction, so means compression. The cross section of this member is given as it is T shape, so width is 90, the lower portion is 30, total height is 60. Clear? So in question it is given that a cast iron machine part is acted upon by 3 kilonewton into meter couple, knowing that E is 165 gigapascal and neglecting the effect of fillet. So you have to neglect this effect, this and this effect, this fillet effect. You have to determine the maximum tensile and compressive stresses. So maximum tensile stress will be in top portion, and maximum compressive force will be in below portion. So in both cases we will use MC over I formula, because C is the maximum distance from center to the outermost. Clear? So for this problem we have to find the centroid of these members. So we cannot identify how to find the centroid. So there is a method which is used to find the centroid, and this is the formula: y dash is equal to sum of y dash into a divided by sum of area. So what we will do is we will have to divide it into two portions. This will be the portion 1 and this will be the portion 2. Now if I expand this formula, y dash is equal to y for member 1, this will be y1 dash into a1 plus y2 dash into a2. Now what is y1 dash and y2 dash? So y1 is this member, so the center of this member 1. So this is 20, so it will be at the center will be this. But this y1 will be from this baseline to the middle of first member. And this is the y1 dash. And if you see this is 40, so this y1 dash will be 50. Clear? Similarly for y2 it will be the half of, so half of 40 will be 20 mm. So this y2 dash is 20 mm. The area A1 will be 90 into 20. So this is width is 90 and thickness is 20. Similarly, area A2 will be equal to 40 multiplied by 30. So when you will put all the value, so this will be the given and divide by total area. So total area is equal to A1 plus A2. So when you solve this, you will get y dash, and this y dash will be the distance from this base to the required value of y. We will see below. So let's start with its solution. So now you can see you have divided it into two portions. This is portion 1 and this is portion 2. So y1 dash is 50 because the area, half of this 20 member 1 will be 10 this and 10 this. So 10 plus from the base it is 40. So y1 dash is 50. Clear? And y2 dash is 20 as discussed above. Clear? Now we have area A1 which is 20 into 90. This is A1. Y1 dash for one member it is 50. Similarly for area for 2 which is 40 multiplied by 30 and 1200 square millimeter, and y2 dash is 20. So if you multiply this 1800 with 50, so you will get y1 dash A1 which is 90 into 10 raised to power 3. Similarly for second member you have to multiply area A2 which is 1200 with y2 dash. So when you multiply it you will get this. Now the sum of area A1 and A2 which is equal to 3000. You can add them, you will get this. And sum of y dash A, if you sum both this you will get 114 into 10 raised to power 3. Now the distance of centroid from this base is given by formula y dash, and if you put the value 114 into 10 raised to power 3 divided by sum of area, so you will get 38. It means that the centroid of this member is 38 millimeter away from this base line. So center will lie this. You can see this is y dash. Means centroid of this member lies at a distance of 38 millimeter from this base line. So we have find out this centroid. Now you can see that there are two members 1 and 2. So again sigma is equal to m into c divided by I. Now you have centroid, you can find out the distance from center to the topmost for finding the maximum tensile stress, and distance from centroid to the lower, that will give you the compressive strength. So we have moment, we can also find this C, but we do not have I. So we will find the I. Whenever, and the formula for this I is equal to I sum of all, because there are two members. So I dash plus AD square. Now what is I? I is the second moment of inertia of any member So there are two members, so the moment of inertia of this one plus area of this member 1 into d square. Now d square, what is d? D is the distance of the first member centroid, first member center with respect to centroidal axis. So this distance is d. Similarly, you have to find the moment of inertia of this two member plus area into d. So let's solve it. It will be more clear to you in a while. So up till now we have calculated out the distance of centroidal axis from the base, that comes out to be 38. Now we will find the moment of inertia I. So there are two members. So if you look at this I is equal to moment of inertia plus AD square. So for any members in which the centroidal axis, if the centroidal axis, this formula, actually this formula I dash plus AD square is only valid when your centroidal axis is not, or your neutral axis is not passing through centroid. So for that we will use this. If your, for example, if this is the member and its neutral axis and it is center, so if your neutral axis is passing through centroid, so in this case d will become 0, so this term will be 0 just in rectangular section. But if your centroidal, let's say for example, if your centroid is this and your neutral axis is not passing through centroid, so in this case there will be a distance d. So for finding the moment of inertia in such case, so you will use this formula I dash plus A into d square. So let's solve this. Again, the moment of inertia is equal to, for rectangular shape, this first part is rectangular and the second portion is also rectangular. So we have the sum of these. So we will start from the first part. So you can see the first part is I dash. So I is the moment of inertia for rectangle. It is equal to 1 over 12 BH cube. So its B is 90, that is given above. Let me show also. So B is 90, height is 20. So 1 over 12 B into H cube plus area of A1. Area of A1 is 1800. So it is also given as 1800. Now D square. So the center of this portion lies this, from this point till this point. This is 20 because this is 20. So sorry, not 20. This from this point is, it is 20 and half of this will be 10. So 10, and from the center to this point is 2 mm. How? Because the total distance over here given as 40, clear, and y dash is at a distance of 38. So there is a gap of 2 mm. This gap is 2 mm. So 10 plus 2 is 12. So D square. D is in this case is 12. So 12 square. Similarly for the lower portion, 1 over 12, breadth is 30 and height is 40. So that is 1 over 12 BH cube plus area of A2. Area of A2 is 1200. And D, what is D? So its center is 20 distance and this y dash is 38. So when you subtract 38, when you subtract 20 minus 38 minus 20, so this is 38, and when you subtract this 20, so the remaining distance from this point till this point, this is D2 for member 2, and this comes out to be 18 mm. So when you put 18 and you take square, and when you calculate this, you will get I is equal to 868 into 10 raised to power 3 mm4. This is mm4, and when you convert into meter, it will be this. Now we have M value, we can also find C, and we have I value as well. So we will first find the maximum stress which is at the outer surface at point A. Clear? So as we know that maximum stress is equal to MC over I, we have M, we have I, we will now check what is the value of C. So you can see that this C is at a distance of 38 mm. This distance was Y dash, and that is 38 mm. 38 mm. So this distance was 2, this gap, plus this distance was 20. So total from this point to this point, this centroidal, this C is equal to 22 mm. And when you convert into meters, so that will be 0.022. So sigma A is equal to M. M is given as 3 kilonewton into meter. CA is the distance from neutral axis to the topmost layer, that is 0.022, and I is also calculated above here. So when you solve this, you will get the value of stress, maximum stress at point A is 76 megapascal. Similarly for point B, again this formula sigma is equal to C MC over I. Now C is this distance from neutral axis. This is already 38, but if you are taking downward, so that will be minus 38 mm, and it will be minus 0.038. So this formula will be sigma B is equal to MCB over I. So this is the CB distance. Clear? So 3 kilonewton minus 3 kilonewton into CB distance over I. So when you solve this, this comes out to be minus 131.3 megapascal. Now this minus show that lower portion is in compression or under compressive stress, while the the value of sigma A is positive. This means that upper portion is in tensile stress. So we have solved the first portion, in which we have been asked to find the maximum stresses in the upper and lower portion. Now the second portion is to calculate the radius of curvature. So as we know that 1 over rho, which is curvature, is equal to M over EI. Now we have M value, we have E that is given in the question, we have I. If you put it, the curvatures come out to be 20.95 into 10 to the power 3. And if you take reciprocal, so radius of curvatures come out to be 47.7 meter. So this was all about today's lecture. I hope you have enjoyed. In next video, we will discuss the bending of member that is made up of several material. We will see this theory and how to tackle with this such type of problems. Then we will discuss reinforced concrete beam and how to solve this problem, how to tackle with these problems. So all will be discussed in the coming lecture. If you like the video, kindly subscribe, like and share. Thank you. Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Bismillahirrahmanirrahim. Today we will start with the topic that is bending moment of member made up of several materials. So in this case we can see that we have a beam that is made up of two material. So this is the beam and having made up of material 1, clear, and this is the material 2. So those beams that are made up of several materials are known as composite material. So this is composite beam that is made up of material 1 and material 2. So this material 1 will have modulus of elasticity E1 and this material 2 having modulus of elasticity E2. As we know that stress is equal to modulus of elasticity into strain. So we can see that stress is a material property. So stress in material 1 will be different and stress in material 2 will be different. So consider a composite beam formed from two material E1 and E2 as shown in the figure. So in this type of problems or in this composite beams, it is very difficult to find the centroid of this beam. So there is a method to solve such type of problem. So before going that, I will explain some basic things. As we know that stress is equal to E into epsilon, and we also know that stress in beam is equal to MC over I. This is for maximum stress, and for stress at any point is minus My over I. So in such type of beam, composite beams that is subjected to movement, so definitely there will be a bending. If there is a there is a decrease in length in the upper layer above the neutral axis, so it will be under compression, and if the surface below the neutral axis is in elongation, then there will be a tensile stress, but that depend on the direction of movements. Clear? So as from this general formula, the stress distribution in this such composite beam is given over here. I will explain it as well over here. So for example, we have two beams, the beams that is made up of two material, composite material. For example, this is one and there is another material that is two. So this is one, this is two. And in such type of composite material, it is very difficult to find the centroid or the neutral axis in this beams. So this neutral axis may comes in material 1 or it may comes in material 2. For example, if the neutral axis is in material 2, in such type of cases we are going to find the stress distribution. For example, this is a neutral axis and this is the vertical line. So you can see by using the formula sigma is equal to My over I. There is a negative sign. Clear? So for material 1, you can see that if Y is equal to 0, so stress will be 0 at this point and stress will be maximum at this point, but this will be the maximum and compressive one. Similarly, if you go to this point, there will be some stress, and this point there will be stress, and so on. So this is the stress distribution in the first portion. Clear? Now this is minus sigma, which means that the upper portion is in compression. Now for point material 2, you can see there are some portion of the second material is above the neutral axis and rest is below. So this portion above will be negative. So let this is the neutral axis. So at this point it will be like this and it will come to 0 like this. And for further portion it will be toward this positive, because now it is going toward toward tension side. So this is the stress distribution that is shown over here. So you can see that for first portion that is under compression, sigma 1 is equal to E1 over Y over rho. As we know that sigma is equal to E into epsilon, and this epsilon in x direction is equal to Y over rho. Clear? That is epsilon in x direction is equal to minus Y over rho. So sigma is equal to minus EY over rho. For material 1, this sigma is equal to minus E1 Y over rho 1, and the distribution is shown over here. So it's starting from 0, because neutral axis is this one, for example. So from Y is equal to 0, stress will be 0 and Y will be maximum at outer surface. So this is the distribution. If I zoom it over here, so this is the maximum. So this is distribution for first material. Now for second material, you can see that some material is above the neutral axis. So y will be definitely above value, that will be positive value. So if you put in this, so that will give you negative value. So it means that some portion of the material 2 above the neutral axis is also in compression. When the neutral axis reaches, so definitely the stress will be 0, because if y is equal to 0, so stress will be 0. Now, if you move downward further below the neutral axis, so you can see y will become negative. So if you put the y negative, the stress will be positive, and the stress will be maximum at the outermost surface. So stress in this portion is positive, means that sigma 2 is in tension. So this is the formula for finding the stress at in material 1, that is minus E1 y over rho, and this is for stress in the material 2, that is also minus E2 y over rho. So if you put the value of y in this equation, you will get the stress in material 1 and material 2. Clear? So this is generally a stress distribution in composite material. Now let's start how to tackle a beam that is made up of more than one material. So consider a composite beam formed from two material E1 and E2, and we also know that normal strain Ex epsilon x is equal to minus y over rho. So you can see from first material we have stress is equal to sigma 1, that is equal to E1 over epsilon x, and if you put the value of epsilon x from here, so sigma 1 will be equal to minus E1 y over rho 2. Similarly, sigma 2 is equal to E2 into epsilon x, and if you put the value of epsilon x, then stress in material 2 is equal to minus E y over rho. Now in this case, the neutral axis does not pass through section centroid of composite material, and it is very difficult to find the neutral axis of the composite material. So what we will do is that we will divide, or we will convert this beam into transform section. Now what is transform section? In transform section, what we do is we convert the material of 2 into 1. We will replace material 2 with material 1, or material 1 with material 2, so that it becomes a beam that is made up of single material, and then we will solve it by using our technique that we discussed in earlier problem. So let's start with conversion of composite beam into a single material beam. So this is the beam that is having width B. Clear? B. This is material 1, this is material 2. Now you have taken a small differential area A. This. Similarly, you can also take a small differential area A in the upper material. So this is dA. So force in this element, this is for example first element dA1, and this is 2 element. So the force on this smaller area will be equal to dF1. Similarly, the force in this smaller differential area of second material will be equal to dF2. So now elemental force on this section dF1 is equal to, dF1 is the force acting on small differential area of material 1, and this is differential area will be equal to stress into area, stress into differential area dA. There, let me zoom it also. So this will be in first material, so dF1 will be equal to sigma 1 into dA1. Similarly, for this smaller differential force in the second material, this area, this dF2 will be equal to sigma 2 into dA2, which is also mentioned over here. So elemental force in the section are dF1, which is equal to sigma 1 into dA1, and elemental force dF2 in material 2 is sigma 2 into dA. Also, we know that stress is equal to E over minus E over Y over rho, which is mentioned above here. Clear? So putting the value of sigma 1 will be equal to E1 Y over rho, and the remaining thing will be the same, minus E1 y over rho into dA, and dF2 will become equal to E2 y over rho into dA minus. So these are the forces in material 1 and material 2. Now we have to transform this beam, composite beam, into a single material beam. For that we will describe a term that is N, and this N is the ratio of two material modulus, for example E2 over E1. Now N is the ratio of modulus of elasticity of second material over modulus of elasticity of first material. So it's a number having no unit. So from this equation we can see that E2 is equal to N E1. We can also take E1 over E2. You can take it as well, but till now it is recommended that to use higher modulus in numerator and lower modulus in denominator. So a material having higher modulus should be taken in upper numerator, and lower value is taken as denominator. We can also take the lower in upper and higher in the lower, but this effect will be clear to you in a while. So let's N is equal to E2 over E1, where E2 is the modulus of elasticity of material 2 and E1 is the modulus of elasticity of material 1. So E2 is equal to N times E1. Clear? So up till now we discussed dF1 is this and dF2 is this. Now to convert this composite material into a single material, what we will do, we will replace E2, this E2 by this equation. So if you put E2 is equal to N E1, so dF2 will become equal to minus, in place of E2 that is N E1, and the rest thing will be the same, y over rho into dA. So if you take this E1 y over rho minus over here, and that will be equal to N into dA. So what does it mean? It means that if you change the material E2 with E1, so what will happen? You have to, the area of the second portion should increase n times. So this is how we have shown, they have shown over here that this is the material 1 that is of the same B and height. Clear? And now this material 2 is replaced with this area. Clear? So you can see that the area is N dA. Okay, let me explain one more thing, that N into dA means that area is increased. Now area of rectangle, as you know that area of rectangle A is equal to B into H. Clear? So if area increases n time A is equal to n time B into H. So here you have provision to increase the B, but you cannot change H, because if you change H, so height will increase and our centroidal axis or neutral axis may disturb. We do not want to change the neutral axis, the location of neutral axis. So the solution is that only you can change B. So breadth will increase n time. So height is the same, and this area has been changed by increasing breadth to n time. So this portion is converted into this portion. Height remains same, only breadth change. So this material 2 is transformed into material 1. This section, this area, or this is equivalent to this. Now this complete composite beam is transformed into a beam that is of single material. Now this is also material 1 and this is also a material 1, but shape change, only shape changes. So now we will solve this further by using our concept that we discussed in previous section. Rest the same thing is same as we studied earlier. Now you can see you have changed this beam into a beam that is made up of single material. So it's easy to find the centroid of single beam by using same formula. Y dash is equal to sum of y dash into a plus divided by sum of area. So you can find I by using this formula, y dash by using this formula, and then you can also find moment of inertia. Once you find the moment of inertia and y dash, you can calculate the maximum stress, that is equal to mc over I. So moment will be given in the problem. C is the distance of from centroid to the outermost. You can also find that, and I you can also calculate for this beam. This is how we will solve a composite beam under the moment load. Again I will repeat. So in composite materials or in composite beam, you have to convert you have to convert it into transform beam of having one material. So you will have N is equal to E2 over E1. So E will be equal to NE1. And if you replace the material 2 with material 1, so area of material 2 will enhance by N times of dA. Clear? And then you will convert it into a beam of single material. Now this is transform beam. So we will see how to solve such problem. We will have a sample problem. So let's start with that problem and then we will move toward. Again, you can see this is an example 4.0 regarding a composite beam. So you can see that this is the beam bar that is made up of bonded pieces of steel and brass. Modulus of elasticity of steel is given and modulus of elasticity of bar is also given. So you have to determine the maximum stress in steel and brass when a moment of 40 kips is applied. Clear? So again you can see this is steel, this is brass. So first you have to transform the bar into equivalent cross section that is made up of entire brass. So for that, what will you do? You have to find N. And N is equal to larger E, which is E of steel, divided by E of brass. So you will get any value. So from that value, so what will you do? That value will increase the transform will cause this beam to transform into a single material, so the area will increase. Clear? Then equivalent cross-sectional properties of transform section we will see in a while, and then we will calculate the stress in transform beam. This is the correct maximum stress of brass pieces, and then you have to determine the stress in steel as well as in brass. One thing that I have missed in the above topic is that when you find the stress in this maximum stress in this, so that will be the stress in this material 1. So for material 2, that will be equal to N times sigma M1. So this is how you will able to find the maximum stress in material 2. Now we will solve this problem, and after solving this problem you will definitely understand how to solve problem that is related to composite material. So now in this figure you can see this was our given beam that is made up of composite material. The total height of this beam is 3 inch. Now you can see that this is a rectangular beam, so definitely half of 3 will be 1.5, which is the center of this beam. So first step is to transform the bar into equal cross section made up of entirely brass. So what will you do? You use N is equal to E of steel over EB, modulus of elasticity of bar. So E of steel is 29 into 10 to the power 6 psi, and E of brass is 15 into 10 to the power 6. When you divide it, it will be 1.99. So N is equal to 1.933. Now, if you replace this steel
with a material of brass, so area will be increased with n time. So area will increase, area of this will increase n time. So Na of steel will increase. So N into 1.933. So if you replace the steel with brass, so you can see that the area, we do not want to change the height, so only breadth of the steel will increase, the height will remain the same. So BT, now the BT is total width of the transform beams. So this 0.4 mm width of brass and this 0.4 mm width of brass will remain same. So total transform breadth of the transform beam will be equal to 0.4, which is over here. Now the only breadth of steel will change, which is equal to 1.933 into breadth of this steel beam, which is 0.75, and rest this 0.4. So now you can see that total breadth of the transform beam has been changed to 2.25. Initially for composite material it was 0.4 plus 0.4 plus 0.5, 0.075. But now you have transformed this composite beam into a beam of that is purely made up of brass. So the total breadth is changed to this one. So you can see this is 0.4 is the same, 0.4 is the same. Only the breadth of steel is changed into 1.45, and total height is also remains the same because we cannot change the height for given problem. If we change the height, so it will disturb the neutral axis, and the neutral axis is at a distance of 1.5 inch from the base or from the base. Clear? Total breadth of the transform beam is 2.25 inch. Now you have to find the moment of inertia of this beam. As we know that moment of inertia is equal to B1/12 BH cube plus AD square So in this case, the neutral axis is passing through centroid, so D will be equal to 0. So moment of inertia for this rectangular beam will be equal to, transform beam will be equal to 1/12 BT H cube. So you can see this is 1/12 BT is the breadth of transform beam, which is 2.25 inch, and total height is 3 inch, so 3 cube. So this will give you the second moment of inertia of this transform beam about this neutral axis. Now you will have to find the maximum stresses, and you know that maximum stress is equal to MC over I. You have moment that is given in the problem. So let's check that moment. So in this statement of the problem, it was given that a moment of 14 kips is into inch is applied. So moment is also given. Moment is 40 kips into inch. C is distance from neutral axis to the topmost or bottommost. So C is also given, and moment of inertia that you have calculated for transform beam is this. So if you calculate it, maximum stress will comes out to be 11.85 KSI. So this maximum moment, this maximum stress is for brass, because this transform beam is converted into purely one material that is made of brass. But actually we have a composite beam that is made of brass and steel. So in order, the stress in brass will remain the same, but maximum stress in steel will be equal to N times maximum stress in the brass. So N was 1.933 and maximum stress in brass is 11.85 KSI. So you will multiply it, so you will get maximum stress in the steel is 22.9 KSI. So in this way we have find out the stress in brass as well as in steel. So this was all about how to solve the stresses in composite beam. Now I will mention that if n is equal to, let's say it is equal to E1 over E2. So E2 is smaller, E1 is smaller and E2 is greater. So its value will be less than 1. Clear? So again in this scenario, if you want to remove, if you want to replace, so in that case n time a will also reduce the area. So again, so you have to, in this case, you have to reduce the area. Rest the area will reduce. So it means that you have to reduce the breadth of the replaced material, and the rest of the steps are same. So this is the reason you can also take n is equal to E1 over 2 E2 or E2 over E1, but it is recommended that you should use higher E in the numerator and lower in the denominator. Rest the steps are same. I hope you have now a clear understanding of how to solve or how to find the stresses in composite beams. Now we will move toward another example of composite beam, that is reinforced concrete beam. So you might have heard about this concrete beams that are used in construction industries or for building homes. So in such type of beams there are two materials used. One is concrete that is acting as a mattress, and other one is steel rods. You can see these small steel rods, and that is acting as a fiber or reinforcing component. So let we have a reinforced concrete beam that is having breadth B and height D. Now this height D is from the topmost to the center of these rods, that is given as D. Now we know that the concrete that is very it show resist to the compression very well. Clear? Concrete is good in compressive stresses, but it does not bear the tensile stresses. Under tensile loading it breaks, but under compression it offer good resistance. On other hand, these steel rods that are very good under the tensile load. Clear? And it is not good in compression. So in concrete beam we use the concrete in that portion where there is compressive stress, and in the beam where the tensile load is maximum, so we use the steel rods. Clear? So concrete beams subjected to bendings are reinforced by steel. So actually if it bends like that, so usually the steel rods are placed in that area where there is a tension, and where there is a compression only concrete is available. So while designing the reinforced concrete beam, we always place the steel rods in such a place that is under the tension. So if we can also place the steel rod over above place, but we will see to the condition that if whether the above portion above the neutral axis is in tensile or below. If above is in tension, so you have to place this steel rod above the neutral axis. But generally they are placed below the neutral axis, because the beam when bent like this will have a tension in the lower portion below the neutral axis. So we will see in this topic that how to solve or how to find the stresses in reinforced concrete beam. The steel rods carry the entire tensile load below the neutral surface, while concrete takes the compressive load. The upper part of the concrete beam carries the compressive load. So this is the composite beam or reinforced concrete beam. So we will see how to transform this beam into how we will transform this beam into a transformed section. Clear? So in transformed section, the cross-sectional area of the steel is AS and is replaced by equivalent area NA, where E is equal to E of steel over EC. Now you can see that what we will do, the same thing is that we have to find out E, and E is equal to, as modulus of elasticity of steel is greater than concrete, so N is equal to ES over EC. So this is the value of N. Clear? Now the diameter of this steel rod or area of this steel rod is, let me zoom it also. If A is the area of steel, AS is the area of steel, and we know that is equal to pi by 4 d square. Clear? So now you can see there are 3 steel rods are available, so that total area of this steel rod will be equal to N times. N is the number of steel. Clear? So it is replaced by equivalent area AS. So total NS is the total steel rod. Clear? This is total cross-sectional area of the rod. Total area of the steel will be equal to N times. N is the number of steel rods that are used. So you will get ATS. Now, what will you do in, as N is equal, N will be some value that will be greater than 1. So the total area of the steel rod, if you want to replace the steel, so total area of the steel rod will be N time of A steel. So it is NAS. Now let this beam is transformed into 2 sections. The first one, this is the first portion that is about the neutral axis, that must be concrete. This is the portion in concrete about the neutral axis. Again, this steps is used in order to find the centroidal axis or neutral axis, because in such type of composite material it is difficult to find the neutral axis. So we have to find the neutral axis. So we are going to convert this reinforced concrete beam into transform section. So for that we say that this is the rectangular section that is above the neutral axis, and let this distance of neutral axis from the top place is x. Actually we are interested in to find out x, that where is this centroidal axis actually locates from the top. So let this upper portion is made up of concrete, that is B, and width of this beam, this section is B, and total height is x. Now you can see this is a rectangular portion, so its half will be 1/2 into x, and the total height from the top till the mid of this rod is D. So if this is the total, and the lower portion of the steel rod, its area has increased to NS. So the area of the steel rod is increased into NS. Clear? So from top till the mid of this rod, that is total D. So if this is X, so remaining portion will be equal to D minus X, and this is the neutral axis. Clear? So this is how we will find the value of X, and then if X is found, we will find the moment of inertia and then stresses. Remember that in transform section, the cross-sectional area of steel is AS, and that is replaced equivalent to the equivalent area NAS, where N is equal to ES over EC. So up till now it is clear. Now we will move further. As we know in our previous lecture that first moment of inertia, that is passing through centroid, is equal to 0. If you recall the previous lecture of pure bending and its derivation, we have found out that first moment of inertia passing through centroid is equal to 0. So we will use this equation in order to find this location of centroidal axis from the top. So first moment of inertia of this rectangular section is equal to B into its total height is X. So this area multiplied by the distance of centroid from the centroid till the mid of first section. So this is the centroidal axis. So it's and this is the centroid of this section of concrete beam. So its location from centroidal axis is 1 over 2x. So that is equal to area into centroidal distance, which is x by 2. And you have to minus it from the centroidal first moment of inertia of this steel rod. Now we know that the area of this steel rod is total area of this steel rod is ns. So this is ns, and its distance from neutral axis is at a distance of d minus x, and their sum must be equal to 0. This equation is first moment of inertia about neutral axis that must be equal to 0. So this is the first moment of inertia of concrete with respect to neutral axis, and this is the first moment of inertia of steel with respect to neutral axis, and their sum must be equal to 0. So when you solve this, you will get 1 over 2 bx square plus n into ax into d minus n as into d, and this minus will be plus, this will be equal to n as into x. Now this is a quadratic equation. So you know the breadth of the beam, clear? You know the area of the steel rod, clear? That the diameter of the steel rod will be given, and you know total depth. Depth is the location of this steel rod from the top of the surface. If you know all these values, so you can easily find the value of x. Now if you find the value of x, you can say that the neutral axis lies x distance from the top of the beam, and rest you can also find d minus x. If you have total depth, so you can also find d. Once you find this x is the location of centroidal axis, so you can find the stress in the same manner, that is m c over I. So if you know this x will be actually c, clear? You will have m, but you do not have I. So how you will find the moment of inertia of this transform beam? So let me derive it also. As you know that moment of inertia is equal to 1 over 12 bh cube for this portion 1, this concrete. So 1 over 2 bh cube plus ad square. This is for steel. Let if I write steel plus moment of inertia, concrete. This is not steel. This is concrete. Let me erase. This is for concrete. So for steel, that will be also equal to 1 over 12 bh cube plus ad square. So we will see for the both. So I will be equal to, now 1 over 12, what is the breadth of this concrete portion, that is b. What is its height? Height is x. So 1 over 12 bx cube plus area is b into x, because the area of concrete will be b into x. So b into x, and what is its d? So distance from centroid to the section centroid, that is 1 over 2. That is 1 over 2, which will be equal to 1 over 4x cube. 1 over 4x cube. Plus, we will come towards steel. Now steel, its height is this height. This is the height of steel rod. Clear? So that will be equal to 1 over 12 bh cube plus area of steel rod as, and d is d minus x, distance from neutral axis to the center, which is d minus x whole square. If I zoom it over here so that you can better understand. So you can see that this is equal to 1 over 12 bx cube plus 1 over 4 bx cube plus 1 over 12 bh cube plus area of steel into d minus x whole square. Now this two term 1 over 12 bh cube plus 1 over 4 h cube x cube, they will give you 1 over 3. This I, if I write over here, let me write the whole equation again. This I of transform beam is equal to bx cube over 12 plus bx cube over 4 plus b of steel, height of steel over 12 into n plus n time area of steel into d minus x whole square. This is the area moment of inertia of transform beam. Let me check over here. One more thing is that for steel you have right to S as well, and for area, as steel area is equal to ns, so you have to multiply n as well. Clear? So this is the same equation that I have written over here. So let's see is also the breadth. One more thing is that also the breadth of steel bar is increased because area increases due to breadth. So n of b as height of steel. So this equation is now clear. Now we will further solve this equation. So as the steel rod is of having height h, this is small height. Clear? So if you take the cube of the height, it will be further very less value. So this term will, if we neglect this term, is equal to 0. So these two terms will give you bx cube over 3 plus n into as into d minus x whole square. So this is the second moment of inertia of transform beam for concrete beam. Clear? So we will use in this formula. This is how we can find out the second moment of inertia of this transform beam. Once you find out the moment of inertia, so you can have this value, you have this value, you can find this, you can take the y at any distance, so you can find the stress. Similarly, once you find the stress, this will be the for concrete, and for steel it will be equal to n times sigma x, because the area is increased, so n will also increase for the steel. So this is how we transform a reinforced composite beam into a transform section, and then we can solve the problem in order to find the maximum stresses in the composite beam. So the idea will be further clear if we solve if we look into the sample problem 4.4. So you can see that a concrete floor slab is reinforced with 5 by 8 inch diameter steel rod. So diameter of steel rod is given, that is 5 by 8 inch. Clear? The modulus of elasticity is 29 for steel. So E of steel is given, that is 29 into 10 raised to power 6 psi. Similarly, and 3.6 for concrete. So E for concrete is also given 3.6 into 10 raised to power 6 psi. Clear? With an applied bending moment of 40 kips into inch for 1 feet width of slab. So you can see this movement is given as 40 kips into inch, but it is for 1 feet slab. So you can see that these are the steel rods that are at a distance of 6 inch from each other. So as you know that 1 feet is equal to 12 inch. So if you take the center of this rod, from center of this rod to center of this is equal to 12 inch and which is equal to 1 foot or 1 feet. So moment is given for 1 feet. So you have to determine the maximum stresses in steel and concrete. Also, the distance from top to the center of this rod is given 4. So actually this 4 is actually D. Again, if you have clear understanding of how to tackle with concrete beams, you know these formulas, so you can easily put the values in this in order to find the stresses. But if you do not memorize this formula, it's also okay, because if you have clear concept, you can derive this formula during your problems. So let's start with the problem. First, what we will do, we will transform this concrete beam into transform beam in order to find the X. So what we will do, we will have a concrete portion. This is, let's say, B breadth, and this breadth will be equal to 12 inch because we are going to analyze for 1 feet, from the center of this to the center of this rod. So this breadth is 12 inch, and let this height is X. We are interested in to find out the X. Let's say this X is, this is neutral axis, and the area of the steel rod is increased to N into AS, and this, from this point till the center of this distance is D. So definitely from this to this center it will be equal to D minus X. Clear? So if you know this figure, you will be definitely able to solve this problem. So you can see that for finding the X value, so what we will do, we will have to find the X, and that is also given in this equation. You can directly use this equation. 1 over 2 bx square plus n into as into x plus n into as into d is equal to 0. So you have b in that, which is 12 inch. You can have area of steel, you can find, because diameter of steel is given. You can also find n, which is equal to E2 or E1. So you have to just put all the values in this equation so you can find the X. Clear? So let's move toward this problem. So this was a transformed section. Now this is the total B, this is X. So this is total 4 inch. So this will be equal to 4 minus X. Now N is equal to E of steel over E of concrete. So if you put the value, so N will be equal to 8.06. Now the area of the steel, which is equal to pi by 4 D square. D of the steel is given, which is 5 by 8. So when you put pi by 4 into D, so that will be area of one rod. So from this figure, if we can see that this distance is taken from the center of one rod to the center of another rod. So in between these two, there are two total steel rods. One is this one, half is this one, and half is this one. So total area of steel rod will be equal to 2 times pi by 4 d square, which will give you total area of the steel. So this is the total area of the steel, and when you multiply it with n, so area will increase n times, so that will give you 4.95. So this ns is equal to 4.95 inch square. So the second step is to find out the distance of neutral axis from the top of this, and this is x. And we also note that the formula was 1 over 12 bx cube, or if you do not, if you are not able to memorize it, so let's see. So the first moment of inertia about x-axis is equal to 0. This is first moment of inertia about neutral axis must be equal to 0. So you can see the area of the first section, which is 12 into x. So this is given 12 into x. Now the distance of its center from the centroidal axis. So this central axis is from this distance is x by 2. Clear? So this distance is x by 2, which is given over here, minus area of the total area of the steel rod, which is n into s transformed. Clear? And its distance from the neutral axis, which is 4 minus x. So when you solve this, so x will comes out to be 1.450 inch. So it means that the neutral axis of this concrete beam lies at a distance of 1 point. This x is equal to 1.450. It means that this neutral axis lies 1.450 from the top surface. If you have this x value, now you can find the next step is to find the moment of inertia of this transform beam. So you can see that the moment of inertia of the formula for moment of inertia, you can take the formula directly from here, which I have derived here. B 1 over 3 bx cube plus n into as into d minus x. So you can take this value formula from here, or if you want to simply derive it, you can also derive it over here. So let's put the formula, let's put the value in that formula. We have 1 over 3 bx, first term is this one, 1 over 3 bx cube, or 1 over 3 bx cube. So you can see 1 over 3 b is breadth, which is 12, and x is now known, which is 1.45 whole cube. So this is the first term. The second term is n into as into d minus x. So n is also known, area of steel is known, d is known, and x is known. So you have to put the value over here. So this is the area NAS, which is given over here, into d minus x. So this is x. So d minus x is equal to 4 minus 1.450, which will be 2.55. So this is 44.4 inch. 4 is the second moment of inertia for this transform beam. Now, what is formula for finding the maximum stresses? So for maximum stresses in concrete beam, we know that sigma c is equal to mci over mc1 over I. So moment is given 40 kips into inch. C1 is distance from neutral axis to the top, which is 1.450, and I is the moment of inertia, which you have calculated over here. So you have to find out the compressive or maximum stress in concrete. Now for steel, it is equal to we have in our previous lecture or previous slide, we have seen that this steel is equal to n times sigma, that is calculated above or in concrete. But now you can see that this equation is only valid when this centroidal or neutral axis is in the half of the total depth. But here you can see the C value for concrete is 1.450 and C value for steel, which is 2.5. There are two different values. So we can see that steel is equal to n time mc2 over I, where n is equal to E2 over E1, which is ES over EC, and that is 8.06. And m is the moment, C2 is the distance from neutral axis to the mid of this steel, and I is the moment of inertia. So when you put it, you will get the stress in steel, which is 18.52. Now you can see, if you want to show them on the beam or stress distribution in the beam. So this is your portion of the beam that has been transformed. Clear? So let's say this is your neutral surface. So from neutral surface you can see there is a compressive stresses. Clear? And there are two rods. They are taking the tensile stresses. Clear? And below the portion of neutral axis, this concrete portion is not having no importance, because they are just holding these steel rods, and only the tensile loads are taken by these steel rods. So the stress in these steel rods is shown over as sigma S, and that is 18.52. So this is the stress in concrete portion, and this is stress in the steel. So this was all about how to play with the problems like composite beams or concrete beams. I hope you have enjoyed the video. If you have any question, you can ask in comment section. Thank you. Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you. Bismillahirrahmanirrahim. Today we will discuss chapter number 5, that is about analysis and design of beam for bending. So in this chapter we will first have some introduction or some previous thing that we discussed in chapter number 4. Then we will discuss shear and bending moment diagram. Then we will have sample problem 5.1 and 5.2. Then we will discuss the relation among load, shear and bending moment and their problems. And then at the end, design of prismatic beam for bending and its related sample problem. So in our previous lecture, that is about pure bending. So we discussed that if a beam is given, if let's say you have a cross section of the beam that is given and its neutral axis and the moment, the value of moment is given. Clear? So we find out that bending stress is equal to mc over I. Now this bending stress is the maximum bending stress. Now what is C? C is distance from neutral axis to the outermost surface. This is C. This is the moment, that is moment that is applied to the beam. And I is the second moment of inertia of this beam with respect to this centroidal axis or neutral axis. We have also an equation that sigma x is equal to minus my divided by I. Clear? So in this case, this y is variable distance. It starts from neutral axis to the anywhere. This can be a y distance, or you want to find the stress at this point. So this can be a y, and y start from y is greater than 0 or equal to 0 and less than or equal to C. So that was maximum bending stress, and that was a stress at any point above or below the neutral axis. So in our previous chapter, we discussed the topics and problems in which you were given the bending moment, clear, and section of the beam, either that is rectangular beam or I-beam or wide flange beam, any beam that is given. And you were asked to find the maximum stress, that is either tension if it is above the neutral axis or its compressive strength. That was given. Now in this chapter we are going to analyze the whole beam. We will find out what will be the behavior of beam under the applied load. So we have a beam that is shown in this figure. That this is the beam, and there is a support at the end. That is supported at the end. One of, let's say there is a load apply at this point, and there is a distributed load that is given at this end. So this is P1, this is P2 applied force, P1 and P2, and this is the uniformly distributed load, that is W. Clear? That this point is A point and this point is B point, and this is the length of the beam. This is the neutral axis, or this direction is known as x direction. So we will see that the bending moment will vary along the length. Here if you take this section 1, here the value of bending moment will be different. If you section it at point 2, the value of bending moment at this section will be different, and if you take it at point 3, the value will be different, and if you take it over here section 4, the value of bending moment will be different. So we will see in this lecture that bending moment M is actually a function of length of the beam, or x. Clear? Similarly, due to this load, these loads are actually transverse loads. Now what do you mean by transverse load? Transverse load are that load in which the force is perpendicular to the axis of the beam. For example, this P is the transverse load and this P is perpendicular to the axis. Similarly, P2 is also perpendicular to the axis, and this W uniformly distributed load is also perpendicular to the axis. And we have already discussed that due to the transverse load, if you want to section the beam at any point, so let I section it over here. So there will be a shear force and a reaction moment. So that is V and M. Clear? So due to transverse loading, if you cut the section at any point, there will be a shear force and a moment. So due to this load, we can have shear force and moment, and this shear force and moment will be different at different section. For example, at section 3, the value of shear force will also change and the moment will also change. And similarly, at section 4, the value of shear force and moment will also change. So both shear force and bending moment, this is bending moment and this shear force, they are a function of length of the beam. That depends on the length of beam. So in this lecture, we are going to show you what is the behavior of beam under the loading condition, and that behavior can be obtained from its shear force and bending moment diagram. So for shear force, we will derive shear force equation, and for bending moment, we will derive bending moment equation, and then we will draw their shear force diagram as well as bending moment diagram. So always remember that draw the shear force and bending moment below the beam. So first we will draw the shear force and then we will draw the bending moment, because they are related with each other, and you will see in next few slides. So this was the initial beam. This is P1, this is P2, and similarly this is W or W naught. So this was reaction point. If you remove the support, so there will be a reaction force RB, and again at this point there will be a reaction force RA. So for that you have to draw the shear force, and this is the length of the beam, and this direction is represented as X. Over this X direction we will take the length of the beam, and we will also draw the bending moment diagram along the length of the beam. So we will see that what we will draw the shear force and bending moment diagram, and from that we will see the behavior of beam under the applied load. So from these maximum shear stresses and bending moment, we will design the beam. For shear stresses, we will derive the shear stress, and from bending moment, that will give you the normal stress. This is shear stress, and this from shear force we will derive shear stress, or we will get the shear stress. That will be discussed in the coming lecture. And from bending moment we will derive the bending stress, that is again mentioned in these formulas. So this movement, bending moment, will yield you the normal stresses, and we will find the maximum bending moment from the bending moment diagram, and then we will put this in the formula in order to get our desired required value, either section modulus or the maximum bending stress. So these things are coming in a while. So these are the normal stresses. In this chapter, our focus is totally on finding the maximum bending moment of the beam. We will find the maximum bending moment, because bending moment throughout the length is changing. So we have to identify the maximum bending moment, and then maximum bending moment we will use to find out the maximum normal stresses in the beam. So this was initially introduction about design and analysis of beam, or you can say why shear force diagram and bending moment diagrams are necessary. They are necessary because we want to find the behavior of a beam under the applied load. From shear force we can calculate the shear stress, and from bending moment we can calculate the normal stresses, and then these normal stresses are further used to design a beam. So you can see the objective of this lecture is analysis and design of beam. By analysis we means we want to check that beam under a given loading condition is behaving like we want to check the behavior of beam under the loading condition, that what is its behavior, and from behavior we means we want to calculate its shear force as well as bending moment. We will have the shear force and bending moment, but at each section of the beam the shear force and bending moment will be changed, and we are focusing to find out the maximum bending moments. So this was all the objective of these lectures. So now beams are defined as they are structural members supporting transverse loading at various points along the member. So this is a beam and they are supporting this transverse loading. And again I have discussed that transverse loading are those loading in which the load is perpendicular to the axis of beam. So whether this is concentrated load, so P2 is concentrated and P1 is concentrated, or it may be distributed load. Distributed load may be uniformly distributed load, it may be linearly varying load, it may be parabolic load, or it may be any load. Clear? So beam are the structural members supporting transverse load at various points along the members. Transverse loading of beams are classified as concentrated load or distributed load. So this P1 and P2 are concentrated load while this is distributed load. Now here the distributed load is uniformly distributed. You can see that load is uniformly distributed over the length of A. We can have linear varying load, means that it is linearly varying. Here, so this is linear varying load. We can also have parabolic load, so that will be our random distributed load. So you can see this, there is a random variation. So whenever beam is applied to the external forces, so there will be internal forces generated in the beam, and that forces are shear forces. Clear? And we know that along with the shear forces there are bending couple or bending moment also generated. So
in transverse loading, we define transverse loading that if a transverse load is applied on a beam and if you want to cut the beam at any section, for example at section C, so you can see if you cut the section, so there will be a shear force, internal shear force that is represented as V, and there will be a reaction moment at this point C. So applied load result in internal forces consisting of shear from the shear stress distribution and a bending couple from the normal stress distribution. So there will be a bending couple and shear force that will be generated. So normal stress is often, again let me clear something. Okay, so you can see that normal stress is often critical design criteria because the beam is designed on the basis of normal stress, and you know that normal stress is equal to minus my divided by I. M is the bending moment, y is distance from neutral axis to the any point above or below the neutral axis where you want to find the normal stresses. Similarly, this sigma m is the maximum bending stress and it is represented as modulus of m into c divided by I. Because why modulus of m? Because we want to find the maximum value. It can be negative or positive. Negative or positive show you the sense of counterclockwise rotation and clockwise rotation. So if you take the mod of bending moment, so it will give you the maximum bending moment, clear, and c is the distance from neutral axis to the outermost surface, that it can be above or below the neutral axis, and I is the second moment of inertia. Again, if you divide c in numerator and denominator, so you will get sigma m is equal to m over I over c. And this I over c, in our previous lecture we discussed that this is known as S, and S is section modulus. So normal stress is often critical design criteria, and for this normal stress you need the maximum bending moment. So as we discussed that the behavior of bending moment will be throughout the length will be different. It will be the bending moment will be here is different from this section and it will be totally different from this section. So we want to find out the maximum bending moment. So when you get the maximum bending moment, so obviously you will be able to find the maximum stress, and that is often used in design criteria for the beam, and it requires the determination of location and magnitude of largest bending moment. So this is basically same thing. We need the largest bending moment that is occurring, or the location of the largest bending moment in this beam under the given load. Again, one more thing is that if you cut this section, so one portion will remain the same. Again, let me explain this, that this is the beam under given load condition. So this is uniformly distributed load that is acting at a distance of A from this point A, and there is a load P1 that is acting, and there is P2. So if you want to solve this equation or this problem, so the first step will be to find out the reaction forces at point A. So at point A and at point B. So at point A there is a pin reaction, so there will be a F1 force, F1y, that will be upward, and there will be a reaction force in x direction. If you remove the pin force, there will be two reaction forces, one along x direction and one along y direction. At point B there is a roller support. So if you remove the roller support, so you have to provide a reaction force, that is, let's say this is F2, or you can also use FB and FA. So let's use FA, that will ease you, FAX and FAY. Similarly FBY. So first of all you have to find the reaction force, and this reaction force can be found by using the equilibrium equation. So sum of all force along y direction is equal to 0, and sum of all movement about any point either A or B, it will be equal to 0. So by using this equation, you can find out the reaction force at point A and B. Now you want to find the value of shear force at point C. So basically you will cut the beam at this point C. So obviously there are transverse loading that will be on the left side of the beam, that will remain the same. Now this uniformly distributed load will be converted into concentrated load for calculation of shear force in order to determine the shear force and bending moment. So this uniformly distributed load W will be multiplied by total length A. So that will be converted into concentrated load. Now the question is that where this concentrated load will act. So if you have uniformly distributed load that is acting on a beam of certain length or entire length, so you want to convert it into concentrated force, so you have to multiply this W with the length where this distributed load is applied. So here length is A, so W into A. Now this uniformly distributed load is converted into concentrated load, but location will be at the mid of this length. So if this is A, so this will lie at a distance of A by 2. Similarly, it will be also A by 2. Clear? Now you can use this section for finding out the shear force and bending moment. So let's assume, I will just explain it in problem, but let me solve it over here. So we will use sum of all force along y direction must be equal to 0. So you can see there is a reaction force that is acting upward. So upward is taken, let's say we assume upward is positive. So RA, there is another force which is minus because it is in downward direction, RA minus W into A, and again there is a force P which is acting downward, so minus P, and there is a shear force that is acting downward, so their sum must be equal to 0. So from here we will get V is equal to P1 plus WA minus RA. So this is the shear force equation. Now for finding the bending moment, sum of all moment at point C must be equal to 0. So you can see there is a force RA and assume that counterclockwise rotation is positive. So you can see RA is producing a clockwise rotation, so that will be negative. So RA, let this distance where you have cut this beam is at a distance of x. So you can also see that this distance will be x, and this uniformly distributed load is acting at a distance of A from this point A. So RA into x, this is the moment and it is clockwise. Clear? So that will be negative. There is a force, concentrated force WA that is acting, and it is also producing a counterclockwise rotation. So that will be plus WA into, now perpendicular distance from this load to this load is this. So this distance is A by 2. So this remaining distance will be equal to x minus A by 2. That will also x minus A by 2. Again, this force is producing movement in counterclockwise, so that will be also positive, and that will be P1 into, now perpendicular distance from is this one. Total is x, so you have to find this. So x minus, if you have this distance, so you can also place that distance, and plus this reaction moment, their sum must be equal to 0. So in this way you can find the equation of moment till, or you can find the moment at point C. This is a general problem, but for understanding purpose I discuss these things. Now the
Bending moment equation and shear force equation can be obtained by using another method. So this is the left portion of the beam. If you cut the beam, this is left side and this is the right side. You can also find out the same bending or shear stress at point E by taking the right side of the beam. So if I take this right side of the beam, so this is point B, this is reaction at B, this is point 2 P2, and there was a reaction. So if you have cut the beam, let this was the length X. So if you cut this point at C, there is a shear force downward and bending moment in counterclockwise direction. So this point C is the same. So here the shear force will be upward, that is V dash, and there will be a bending reaction bending moment M dash, and that will be opposite to this M. Similarly, the shear force will be opposite to this one. Now what will be this length? So if total length of the beam is, let's say, L, clear, and this is X, so definitely this portion will be, if total is L, if this is L and this is X, so this distance will be equal to L minus X. Rest you can apply the shear force, some of equilibrium condition and bending moment equation. So it will yield you the shear force equation and bending moment equation. But when you put the value of this section from this point or from this point, so it will give you the same value of shear force and bending moment. I have solved a problem that is available on my channel as well, in which both the sections were taken left and right, and it was shown that from using either left or right, both will yield you the same bending moment and shear force at any section. So you can check that as well. But in this problem, in this book of Beer and Jhonston, they are usually taking the left section. By convention, they are taking the left section. But you must know to handle this situation by taking the left side as well as the right side of the section. So let's move towards solving a problem, and all your idea will be clear in a while. Now, classification of beam. We can have different type of beams that is based on the beam supports. So you can see this is a simply supported beam. The beams is supported simply. We can have overhanging beam. So you can see some of the portion of beam is at this end is hanging. So this is overhanging beam. We can have a cantilever beam which is supported, fixed supported at its one end is fixed supported. We can have continuous beam which have more than two supports. So this is a continuous beam. This is a support, pin support. This is a roller support. This is a roller support. We have beam fixed at one end and simply supported at one end. So this beam is fixed at one end and simply supported at another end. We can also have a fixed beam, that is both ends of the beams are fixed. So if you see that in this first type simply supported beam, there is a pin support. So in order to remove this support, so there will be a reaction force. Let's say this is RA. So this will be RAY, and there will be a horizontal force RAX. If you do not know, now learn that if you have pin support and you want to remove it, so definitely you will have to give there will be two reaction forces, one in vertical direction and one in horizontal direction. Similarly, this is the roller support, clear? And if you want to remove this support, so there will be only a vertical force. Let this is a point B. So if you remove this support, so there will be a reaction force in the vertical direction, and that will be RBY. Similarly, you can see in overhanging beam there will be total. So in this case there are total three unknown forces acting. Now in overhanging beam you can see there is a reaction force RAY and RAX if you remove this pin support. And similarly, if
if you remove this rolling support, so there will be, let's say this point is B, so there will be a vertical force. So again in this case there are three unknown reaction force which you have to find. Now similarly in cantilever beam, the one end of the beam is fixed. So if you want to remove this fixed supports, so there will be a vertical force F. Let this vertical force is F, and there will be a bending moment either in this direction or this direction. Beam is acting downward, so it will produce clockwise, so it will be, this should be counterclockwise. This should be like this. So the main thing is that if you have a cantilever beam and you want to remove the fixed end, so there will be a vertical force followed by a reaction movement. So again in this case you can see that these are the two unknown. One is the vertical force and the movement which you need to find out for finding this reaction force and movement at the end. Now in below continuous beam you can see there will be a vertical force and horizontal force. Similarly there will be a vertical force and there will be a vertical force or reaction. So in this case we have four unknowns. Here 3, here we have also 3, here 2. One is force and one is movement. In this condition you can see one is horizontal force and rest are 3 vertical force. So total 4 unknown force. Now beam fixed at one end and simply supported at other end. So at this point there will be a vertical reaction force, and at this, if you want to remove the fixed end, so there will be a vertical reaction force along with the movement. So 2 forces and 1 movement, so 3 unknown. Now at fixed end, so if you remove this fixed support, so there will be a force and movement, and again at this end there will be a force and the movement. So in this case 4 unknown. Now we will now discuss statically determinant beams and statically indeterminate beams. Now what is statically determinant beams? That if you have the beam and that is under support, so if you check that number of supports or the number of unknown forces, if before this we can have equilibrium equation. By equilibrium equation we can have sum of all the forces along y direction is equal to 0, sum of movement about any point is equal to 0, and sum of all the forces along x direction is equal to 0. So in two-dimensional problems we have these 3 equilibrium condition. We are generally discussing the two-dimensional problem. So for two-dimensional problem we have sum of fx is equal to 0, sum of vertical forces is equal to 0, and sum of movement about 0. Now you can see that in this beam, that is simply supported beam, there are 3 unknown forces and we have 3 equation of equilibrium. So by using these 3 equation of equilibrium we can find out these 3 reaction forces. Similarly overhanging beam, you can see there are 3 reaction forces and we have 3 equation of equilibrium. So by using these 3 equations we can find out this Rax, Ray and Rby. Similarly for cantilever beam there is a force along y direction, reaction force, and there is a movement. So we have 3 equations and 2 unknowns. So this problem can also be solved by this equilibrium equation. So these are known as statically determinant beams because the reaction forces, unknown reaction forces can be solved by using the equilibrium condition. But in below these 3 examples, you can see that there are 4 unknown reactions. There are 3 unknown reactions and there are 4 unknown reactions. So you can see the there are 4 unknowns and we have 3 equations. So it cannot be solved easily by using this equation of equilibrium. Now in this case you can see there are 3 unknowns. One is 2 are in vertical direction and one is movement, no x direction. So basically now we cannot use these 2 equations in order to find out these 3 unknown reactions. Similarly here 4 unknowns. So again by using these two equation, as there is no x force in x direction, so we cannot use this equation. So we have remaining two equations. So by using these remaining two equation of equilibrium, we cannot find out the statically indeterminate beam. So statically indeterminate beams are those beams in which the reaction forces are greater than the number of equilibrium condition, and we cannot easily find out these reaction forces by using this equilibrium condition. So such type of beams are known as statically indeterminate beams. Now this is the same thing. You can see that there is a beam. I have explained this as well in previous slide. So this is the same beam. This is a beam that is supported at point A and point B. There is a pin support, there is a rolling support, there is a load P1 that is acting at this point, there is a load P2 that is acting at this point. Clear? So there is a uniformly distributed load, that is W, acting from point 1 to this point. There is a load P2, that transverse load at point P2. So we are interested to find out the maximum normal and shearing stress, or we can get the maximum normal stress by finding the maximum bending moment. So for that we need to draw the shear force and bending moment diagram. So determination of maximum normal stress and shearing stress requires the identification of maximum internal shear force and bending stress. So we can cut the beam at any point. You can take the section at this point, you can take the section at this point, or you can take the section at this point. So if you remove this reaction, so there will be a vertical force RAY, and as well as there are reaction force in a x direction, that is RAX. Similarly at point B there will be a reaction force, that is RBY. Clear? So that is shown over here. Clear? Now if you see that at point A there is a load, but if you move from point A there is no load, so you can take the section at this point. Again if you move from this to this, there is a load. You can also find the shear stress in this area and bending moment. So we will see in a while how to calculate the equation for how to find the equation of shear force and bending moment for any given region or for any section of the beam. So you can find out the section at this. Similarly, if you move from this to forward, so there is a load, so definitely the behavior of load at this section will be different. There will be a different shear force and bending moment. So again this beam is sectioned at point C, which I have discussed earlier one or two slides ago. So you can see there is a reaction force. RAX is taken as 0 because there is no reaction force, so sum of all forces along x direction is equal to 0, and there is only force acting along x direction, RAX, and that must be equal to 0. So RA is shown, P point is also shown, omega is the uniformly distributed load, and this beam is cut at C. So you can see these are the transverse loading, this is concentrated load, this is uniformly distributed load, and if you cut the beam at point C, so there will be a shear force in below direction, and there will be a normal reaction. These are the internal shear forces and the moment that is generated at this point or this surface C. So this is the left side of the beam. So now you can also analyze the same thing by using the right side, this portion of the beam. So this portion of the beam is also shown. Said this was RB, this is point B, and if you cut and show the shear force below, so here the shear force will be in upward direction, and that is V dash, and again moment will be M dash. I will not solve it further because I have explained it earlier. So whether you use left side or right side of the beam, both will yield you the same value of shear force and bending moment at section C. Clear? I have also solved the problem. You can also watch that in order to have a clear picture of this type of scenario. Okay. Shear force and bending couple at points are determined by passing the section through beam and applying an equilibrium analysis on the beam portion on either side of the equation. So whether you take left side of the beam or right side of the beam, the only thing is that you will use the equilibrium equations and then you can find out the shear force and as well as bending moment of the beam. Now what are the conventions that are used for shear force and beam? So if you cut the beam at point C, so if this force is taken, is usually in this book it is taken as left side shear force is taken as below and the moment is taken as counterclockwise. But if you want to show the forces on right side of the section, so shear force here, reaction shear force will be upward and this moment will be in clockwise direction. Both value will be the same, only the direction will be changed in order to show the equilibrium condition. Now let's move toward sample problem 5.1 and we will discuss all the things that we discussed earlier in this lecture. So you can see this is a timber beam and loading is also shown. Here you have been asked to draw the shear force and bending moment diagram and determine the maximum normal stress due to bending. So you can see this is the beam, timber beam, and this is cross section of the beam is given, height is 250 and width is 80 mm. There is a point A and the loading on point A is a concentrated load of 20 kilonewton. At point B it is a simply supported or pin supported. At point C there is a concentrated load of 40 kilonewton and at point D there is a rolling force, rolling support. So if I draw the beam like that, so this is a point A. At point A there is a 20 kilonewton force. Clear? At point, this is a point B. So at point B there will be a normal force as well as horizontal force. So we ignore the horizontal force because there is no other horizontal force acting along x direction or in this axis. So it will be 0. So only the reaction force will at point B is RB. At point C, this is a point C, and at point C there is a force of 40 kilonewton. And at point D there is a rolling force, and that if you remove the rolling support, so there will be a reaction at point D which is RD. All the distance are given from point A till point D. It is 2.5 kilometer. From point B to point C this is 3 meter, and from point C to point D is 2 meter. So this problem can be solved by using two methods. First, I will use a simple method in order to show you a clear understanding that how you will able to determine the shear force and bending moment in this case. Similarly, in next problem, we will solve the same type of problem by using another method that will depend on the in that problem we will show you that shear force and bending moment varies along the length of beam. Here it also varies, but I will not consider this in this problem. So let's start its solution. So first of all, the first step is to find out the reaction force RB and RD. So how you will find? So you will have equation sum of all forces along y direction is equal to 0 and upward is taken as positive. So you can see one force is 20 kilonewton that is acting downward, so it is minus. There is a reaction force at point B that is taken upward, that is RB, plus there is a force, minus, there will be a minus force because this 40 kilonewton is acting downward. So minus 40 plus RD which is acting upward. So their sum must be equal to 0. So from this equation we get RB plus RD is equal to 60. So this is the first equation because minus 40, minus 20, minus 60, and when it moves toward the right side it will be 60. Now the second equation that we will use is sum of all moment you can take at either point B or point D. So let take at point D is equal to 0. So one force that is producing moment is 20 and it is perpendicular distance is 2, 2.5, 4.5 and this 3, 7.5. So 20 into 7.5. Now we assume that counterclockwise movement is taken as positive. So you can see this 20 kilonewton is producing a counterclockwise rotation, that is why it is positive. Now this RB force, this RB is unknown and perpendicular distance is 5 meter from point D. Clear? So RB is producing clockwise rotation. So that is minus RB into 5. And the third force that is producing movement in counterclockwise is 40 kilonewton. So plus 40 into 2 perpendicular distance. Their sum must be equal to 0. So if you calculate that, you will find out the reaction force will be, so let me calculate as 5 RB is equal to 4 into, it is 80, this term is 80 and this 5 RB is moved toward the right side of the beam. Let me open the calculator, that is 20 into 7.5 will give you 150. So this is 150. So 150 plus 80 will give you 230. So 230. So 5 RB is equal to 230. So RB will be equal to 230 over 5. And that is equal to 166. Okay. So let me check it again. This minus 20 plus RB minus 40 plus RD is equal to 0. So their sum must be equal to 0. Now moment at point D. So 20 into perpendicular distance is 7.5 minus RB into 5 plus 40 into this perpendicular distance 2 is equal to 0. So let me check it also. So reaction force is 20. Let me calculate it. Okay, so let me erase something from here. This pen use. If you divide 230 by 50, sorry, it gives you 46. This is 46 kilonewton. Now you know RB, so you will put over here. So RD will be equal to 60 minus 46. That will be equal to minus 60 minus 46, that will be 40 kilonewton. So this is how you find out the reaction forces at point D and point B. So let me clean these things. I will show you. Erase all. It's not easy. Okay. This was a let me check it why it's not working. So basically that was 46 kilonewton and RD was 14 kilonewton. These are the steps. So treating entire beam as a rigid body, determine the reaction forces, and we did the same. We first find out the reaction forces, then the second step is section the beam at a point near support and load application point. So this point is very important. important to understand. So first of all, you can see there is a point load, so you have to section near this point load, and this distance must be taken very small, negligible distance. So again, section the beam at a point near the support and load application point. So this is a load application point, so you can section it over here. There is support, so you can section closer to the load, just before this support. You can take the let this is 2. You can take the section just after this support, so that will be 3. Again, you can take the reaction force at you can take the section before the load 4, and you can take the section at just after the load, and again before this support 6. So you can see that you can take 6 different sections of the beam in order to find out the shear force and bending moment diagram. So when you find out the shear force and bending moment in this section, you will plot them on shear force and bending moment diagram distribution, and from that diagrams you will identify the maximum shear as well as the maximum bending moment. So let's solve this problem. And how you will, when you get the maximum bending moment, so definitely you will apply the sigma m is equal to mc divided by I, maximum bending stress, and this is known as flexure formula that is used to determine out the maximum bending stress. So this is the solution of the sample problem 1. So you have seen that this is point A, this is point B, reaction force is 46 kilonewton, this is point C 40 kilonewton, and this is point D 14 kilonewton. Here reaction force is 46, not 40 kilonewton, and RD is 14 kilonewton. So again, treating the entire beam as a rigid body, and we want to find the reaction forces, and we did in the previous slide, and we calculated RB is equal to 46 kilonewton and RD is 14 kilonewton by using the equilibrium equation. After that, now we will have this beam. The total length is 7.5 mm, and the length distance between A and B is given 2.5, from B to C 3, and from C to D it is 2 meter, that is given. Now you have to take the section just after the application of point load. So at point A you can see there is a point load, so you can take section just after the application of load. So this is section 1. Now the distance between point A and section 1 is assumed to be very small. This x or this distance is assumed to be very small, such that point 1 A is point 1 approaches to A. So we take the section of beam, so we this is point A. On point A 20 kilonewton is applied. So if you section it, so there will be a shear force that is acting downward, and there will be a reaction movement. Clear? So this is point A. In order to find out this shear force, so we will use sum of all forces along y direction is 0 and upward is positive. So now you can see that only one force that is acting downward, so that is minus 20, and there is a reaction shears minus V, their sum must be equal to 0. So V will be equal to minus 20 kilonewton. So it means that at this point 1, the shear force is same as at point A. And bending moment, this M, this is point 1, so moment about point 1 must be equal to 0. So at point 1 there is external moment acting as M1, clear, and plus the moment produced due to this load or this couple
this load, sorry, 20. So as this distance is taken as very small, so it means this distance is approximately equal to 0. So it means there will be no movement. So M1 will be, or this reaction movement, let me erase this. This reaction movement must be equal to 0. So movement at point 1 or section 1 will be equal to 0 because only reaction force is M and M2, and this reaction force will be, this reaction movement will be equal to this movement. But since the distance is taken as very small, so we can say that this movement is 0. Now you can also take section before the application of this point load, just before, and you can take it, let's say this is at section 2. Now distance of this section 2 from point A is assumed to be 2.5 meter, which is exactly the same point, but we assume that point 2 or section 2 is just before the point B, or you can say it will be on the left side of the point B, just before point B. So we will find out the shear force and bending moment for point B. So you can see this, at point A the 20 kilonewton load is given. So before point B, so if you cut it, so there will be reaction at point 2 which is V2 and reaction force M2. So again, if you apply the sum of all force along y direction is equal to 0, so you can see only force 20 kilonewton, that is minus 20, and this is minus V2 is equal to 0. So V2 is equal to minus 20 kilonewton, which is same as V1. Means that after point A and before point B, the shear force is constant. Clear? Now at point 2, you can see that at point 2, just before point 2, so movement, sum of all movement about point 2 is equal to 0 and counterclockwise is positive. So you can see now that this is the diagram, and this M2 will be equal to, there is a movement M2, and there is a movement produced due to this load, this 20 kilonewton into perpendicular distance, and that is taken as 2.5. So 20 into 2.5, and it is also counterclockwise, so 20 into 2.5, that is equal to movement. So movement will be equal to M2 will be equal to 20 into 2.5 will yield you 50. 50 kilonewton into meter, but it's minus 20, that is 50. Okay, so movement at point 2 is now minus 50 kilonewton and meter. So you can see that the shear stress is constant, but now the movement is not constant. At point 1 the movement was 0, and at point 2 now the movement is minus 50 kilonewton. Similarly, you can also find out at point just after, let me solve it as well at point C. So at point 3, so point 3 is just after the point B on the right side, and this distance after the point B where you have taken the section 3 is very small, mean it approaches to point B. Clear? So we will find the shear force. This is the equation. So this is 20, this is 46 kilonewton, this distance is 2.5, and this distance is approximately from this point to this is approximately 0. So you can find out the reaction forces are sum of all forces along y direction must be equal to 0. So now you can see there is one force minus 20 kilonewton, other one is plus 46, and other one is
minus V3. Their sum must be equal to 0. So V3 will be equal to 26 kilo Newton. So from this we conclude that this actually point 2, section 2 and section 3 are very closer to point 3, and we assume that this distance is very small, that it is assumed that it lies at point B. So now there are two shear forces. One is 2, which is minus 20 kilonewton, and one is V3, which is 26 kilonewton. So it means that at this point B on the left side, the shear force was minus 20 kilonewton. But now after slightly moving from point B, the shear force is 26 kilonewton. And you can also find out the moment 3, and this moment 3 will be what? This will be the same as M2, which is minus 50 kilonewton. Because why? Because this distance is very small. Clear? That is approximately. So this force is not producing any shear. Only 20 into 46, 2.5 force is acting, 20 into 25. So M3 here will be also minus 50 kilonewton into meter. So you can again, now you have to solve at point C by assuming that C at point 4, and this point 4 is before the application of this point load, which is at point C. So you have to assume that this distance is very small. It means the distance of distance of section 4 from point A is now 5.5, but it will be to the left. And similarly, you can take the section at point 5 and you can solve it point 6. I will remove all this working and we'll see. Okay. So now you can see that this was the V1, which is minus 20 kilonewton, and M1 was 0, because this distance is very small and equal to or approximately equal to 0. So 20 into perpendicular distance, which is 0, is equal to 0. So V1 is equal to 0, M1 is equal to 0. Now at point 2, we have find out that V2 is actually this minus 20 that I have done a little bit earlier, and M2 is minus 50 kilonewton. And at V3, now the shear force is changing to 26, and I have also done that. And at point 3, M3 is again the same as M2, minus 50 kilonewton. And we similarly you can find out V4, M4, V5, M5, and V6 and M6. So now if you take this at point 6, so sum of all the force must be equal to 0. So 20 plus minus 20 plus 46 is 26, and again this is minus 14. So that will be minus 14. So V6 will be minus 14, and shear force is 0. Now we will plot it in order to get the shear force and bending moment diagram. So let's move toward that. Again, this is the beam and these are the sections shown and these are the reaction forces are shown. So you have to draw the two vertical lines from the end of the beam in order to draw the shear force and bending moment diagram. So first we will draw the shear force. So between these two lines you have to draw a horizontal line which show you the length across the beam. So at this point, from point A to this is point A, this is point B, this is point C, and this is point D. And distance between A and B is 2.5. From B to C it is 3, and from C to D it is 2 meter. So we have to draw the shear force and bending moment diagram. So from our previous slide, we can see that at point 1 or at point A, there is only shear force minus 20. So you have to take the minus 20 in
below this line axis, below, because below force is taken as negative and above force is positive. One more thing is that while you draw the shear force and bending moment diagram, always draw it on the graph paper. And if you do not have the graph paper at the moment, so you can draw the shear force and bending moment diagram by taking the appropriate scale. So on y-axis you can divide it into equal number of parts, and you can say that this one division is equal to, let's say, 1 kilonewton. So definitely you have to draw the divisions on vertical axis, and on the basis of scale you have to take the shear force. So at point A we have a shear force of, or at point 1 we have a shear force of minus 20 kilonewton. So again from point A, and according to your scale, so you will have to plot minus 20 kilonewton. For example, let this point is minus 20 kilonewton. So this is your first point. Now at point 2, so point 2 is approximately at point B, but it is on the left side. So at point 2, we know that at point 2 the shear force is again minus 20. So this is the point 2. Let's say this is point 2, but before this support. So again the shear force is minus 20. So it will be a, if we join it, it will be a straight line. But if you notice that at point B we have this left side and right side. So just before the point B and just after the point B. So before the point B we have 20 kilonewton, and just after the point B we have shear force 20 kilonewton. So now you have to draw, this is minus 20 and this is plus 26. So again you have to move it from plus 26. So this is minus 20 kilonewton, and if you draw it plus 26, so let's say this is minus 20, again this is again on the basis of scale you have mark out plus 26. So on that point you will go to the plus 26. So if you join the line, so what does it show you? It is a straight line. It show you, this portion show you that this is just before this point B, and this portion, this from this axis to the upper portion, this shows that just after point B the shear force is changed. Now at point similar, this was a point 3, at point 3 we shear force was plus 26. I will show you. At point 4 it is again same as 26. When you calculate it, you will see that V4 will be 26. So again at point 4, so this is the point 4 or section 4, which is approximately at point C. So this point will be the same, plus 26. So again if you join them, this will be a straight line or constant line. Now at point C you can see on the left side as well as the right side. So and on the left side it was 26, and we will see the shear force at point 5. So shear force at point 5 is now minus 14 kilonewton. Clear? So minus 14 kilonewton. So you will have from this point you have to go to minus 14. So this is minus 20. So minus 14 will be somewhere. So if you plot it, so this will be the point or section 5. So you have to join them straight. So this upper portion shows that this is the shear force before this point C, and this is the shear force which is going toward the negative, and that is after point 5. Again, if you are confused how to find this V5 or V4, so definitely you can check that if you section it, so 20 is negative, 46 is positive, so we have 26. Again 26 is upward and 40 is downward, so we will have minus 14. So that y is minus 14. And at similarly at this point section 6, it is also minus 14. So at this is point. So if you join it, so this will give you the shear force. So this is how we draw the shear force diagram. So now we will move toward plotting the bending moment. So for bending moment, again you have to draw a horizontal line between the two ends of the beam, and this axis is show you that the beam length is varies in x direction. So let's start from point 1. So if you look at this, this is the point A is the application of concentrated load. So there is no movement because this force is passing through point A. Or you can see that movement at point 1 is equal to 0. So again you have to take the appropriate scale and mark this vertical line as above this axis and below as well, so that you can accurately plot the points at various sections. So this is point 1. So you can see the movement at point 1 was 0. Now at section 2, so you can see that at section 2 movement was minus 50 kilonewton. So when you draw or when you locate minus 50 kilonewton, so you will have division and according to your scale, and if this point is minus 50, let's say this is minus 50 kilonewton. So at point kilonewton into meter. So at point 2, so point 2 is at this point B. It lies at point B because we have told you that this point B is so much closer that it is just before the point B. So it is at a distance of 2.5. So at a distance of 2.5 and at point B, so you have to draw the minus 50 kilonewton into meter. Now the question is that we have point 1 and we have point 2. How to join them? You can join them straight, you can join them like this way, you can join like this way. So how you will know that how we will join these two lines? So let me explain it also. So now you will judge it from using the shear force diagram. So from point A, this was a point A and this is a point B. So from shear force from point A and B, you can see this is a constant value, or is a line with zero slope. So always remember that bending moment equation is 1 degree higher than shear force equation. I will repeat that bending moment equation will be 1 degree higher than shear force. So if shear force is a constant, means it is a 0 degree equation. So the bending moment will be the first degree equation, and first degree equation gives you a straight line. As this is a constant, so from point A to point B, you can join them in a straight line. Why? Because the shear force is a constant value or 0 degree line having zero slope. So the bending moment is 1 degree higher than shear force. So you can see this is 1 degree equation or linear equation. So if you the linear equation will be, if you plot using linear equation, it will be a straight line. So you can quickly join point A with point B using a straight line. Now at point B, you can see that before point A, which is 2, and after point 2, these movements are same. Clear? So basically this point, this is M2 and it is also equal to M3, and this is minus 40 Newton. Now we will check the moment at point 4. So moment at point 4 is now 28 kilonewton into meter. So definitely you will go toward, you will locate 24 kilonewton. So let this point is 28 kilonewton. So this point is 28 kilonewton into meter. Again, you have to join this point with this point. So you will see the shear force line. So this shear force is a 0 degree line, and again the bending moment line will be a linear. So you can easily join B with point C with a straight line. Now at point C, we have moment at point 4 and 5. We will check moment at 4 and 5. So moment at 4 and 5 are same. So this will be the moment at point C is equal to moment 4 and moment 5, that is equal to 28 kilonewton into meter. Now at point 6, so at point 6 you can see that moment is 0. So if you plot 0, so it will be point this. Again, this is the shear force line or shear force diagram between C and D is a constant line, so it will be up, and it is negative, so definitely it will go toward downward. There will be a downward, so this will come to 0. Again, if it is going from, shear force is going from negative to shear force from negative to positive, and again from positive to negative. So that's why it is, this linear equation is going to upward, and here it is going from positive to negative, so shear force will be downward. So this is how you can find the shear force diagram and bending moment diagram. So now if you look at this shear force diagram and bending moment diagram, you can see that one bending moment is minus 50, one is 28. So maximum bending moment is, if you take the mod, so maximum bending moment is actually minus 50 mod, which is equal to 50 kilonewton into meter. Here we are only interested in order to find the maximum bending moment. We are not interested in shear force, and that will be discussed in coming lectures. So from this we get the maximum bending moment. Now we will use, you can see that maximum shear force is 26 kilonewton into meter, and maximum bending moment is 50 kilonewton into meter. So then you have to apply the formula sigma m is equal to maximum divided by S. So what is S? For rectangular beam, we can see that S is equal to, let's say this is B and this is height. So section modulus for rectangular beam is 1/6 into BH square. So you can, if you look at the start of this problem, so B is 80 mm and height is 250 mm. So you have to convert them into meter, because this length is in meter. So for consistent units, you have to convert it into meter. So 1/6 B into H square. So B is 0.080 meter and height is 0.250 whole square, and S section modulus comes out to be 833 into 10 raised to power minus 6 meter cube. Now you have M, maximum bending moment, that will be at point B, and you can have, you have calculated the section modulus, you will put it and you will have a maximum bending stress, that is sigma m is 60 megapascal or 60 into 10 raised to power 6 pascal. So this is how you will find out the maximum stress in the beam. So in this problem you have seen that shear stress at any section or shear stress is changing along the length of beam. Similarly, the bending moment is also changing along the beam. So we have to find out the maximum bending moment. Once you get the maximum bending moment, you can find out the maximum bending stresses, and further these maximum bending stresses will use to design the beam, that is in next few slides, or that will be discussed in the next few slides. One more thing is that area under the shear force will give you the bending moment. So if you look at from point A to B, so this is the area of shear force. So this distance is this vertical distance. This is a rectangular, so you know that rectangular area is B into H. So let's say this is H and this H is minus 20 and this is B. So minus 20 is just value, so its height is 20 and this width is 2.5. So if you multiply 20 with 2.5, it will give you 50. So the area under the shear force will give you the bending moment. So this is minus 50. Now you can see area under this shear force between B and C. So this height is 26, clear, and this length is 3. So if you multiply it, this is 20 and this is 26, clear. So again this is 26, clear, this is 26. So 26 multiplied by 3 will yield you what? It will yield you the bending moment in this region, clear. And see, if you take this region, so you can see this is minus 14 and 2 minus 28. So this is the same as 28. So again the area under the shear force diagram for any section will give you the bending moment. So if you do not know the bending moment at start, so you can also find out for quick finding the value of bending moment. So you can also check that the bending moment in this section AB will be this, bending moment between B and C will be this, and bending moment C and D will be this, and this can be calculated by using the area under the bending moment, shear force diagram. Sample problem 5.2. The statement of problem is that the structure shown is constructed of W10 by 112 rolled steel beam. Draw the shear force and bending moment diagram from the beam and given loading, and the part B is determine the normal stress in section just to the right and left of the portion. So W is the wide flange beam, that is 10 by 112. You can take the properties of W10 by 112 from the appendix C that is given at the end of the book. So from that appendix C, you can take the value of IX. You can also check the height, width and breadth of the beam, thickness of flange, etc., etc. So as we know that sigma M is equal to MC over I. So I value can be taken from that table, and if you know the cross section of the beam, so you can also calculate the C, distance from neutral axis to the topmost. So you can take this value from the table available in appendix C of rolled steel beam. So you can see that this is the beam, and that is fixed support at the end, and there is a load of 10 kips at point E. From point A to C there is a uniformly distributed load, that is 3 kips per feet, and total it is acting on a length of 8 feet. So we will solve this problem by using another method. Now in this method we will section the beam at any point, and we will take that distance as X. X can be any distance from this point A along the length. So let's solve this problem. Now you can see in this problem this 10 kips force is given at point E. So in order to convert, or in order to move this point E to point D, so this force will be 10 kips, and there will be a moment as well, and this moment will be equal to 10 into 2 feet, which is 20 kips into feet. Clear? So if you provide this, if you move this force to point D, and you also provide a reaction couple or a couple, so you can replace this 10 kips with this one.
So if you write this, so then there will be no need to represent this. Okay. So solution, the steps of this solution is that first of all we have to replace this 10 kips force to the point D with a force and a couple system at D. And then we have the second step is then you have to replace this reaction support, so there you will find RB and RB X and RB Y. Clear? And there will be a moment as well at reaction point, that is MB. So you have to find this RBX, RBY and MB at point C by using equilibrium condition. As there is no force in X direction, so we take this RBX is equal to 0. So only force in vertical direction and moment. So you can calculate this RB and MB by using equilibrium condition. So if let me explain a little bit later, you will also solve this by yourself. So if this is point B, so this is the reaction force at point B and there is a moment M. At point D there is a force of 10 kips and there is a moment that is 20 kips into inch, and also a uniformly distributed load at point, this is point A and this is point C, this is point D. So this is W. Now in order to find this reaction force, you have to convert this uniformly distributed load into concentrated load. So you have to multiply this W with total entire length where this uniformly distributed load is acting. So it is 8. So W into 8. W is 3 kips. So it will be, if you want to convert this uniformly distributed load into concentrated load, so you have to multiply with W with its length. So 3 into 8 is 24. So it will be a 24 kips force and it will act at a distance of half of the length, which is 4. Clear? So this distance will be 4 and this distance will be also 4. Also this force, this moment is given, so now you can apply sum of all force along y direction is equal to 0. So you can see you have 24 kips force acting downward, you have 20 kips force acting downward and their reaction force. So by using this equation you can find out the reaction at point B. Now you can take the moment at point B is equal to 0 and you can find out these reaction moments by using this equilibrium condition. So kindly solve it by yourself. I will move forward. It's very easy. I have given you some idea, and one more thing, that it is very basic thing and you must understand how to find out the reaction forces or reaction movement, because it is the first step of the problem. If you have any problem in calculating this reaction forces or movement, then you cannot be able to move on further. So first clear your idea regarding the equilibrium conditions. Then we will take, after finding the reaction forces, we will take the sections at different points. At section the beam at point near the supports and load application points, and then apply equilibrium condition. For example, this is the load point, so you can cut the section over here. After the load application you can take a section over here, and after the support you can also load section here. So basically in this problem we have 3 sections to be analyzed, and in each section we will draw its free body diagram and then apply the equilibrium condition in order to find the shear forces and bending moment. And then when you get the shear force and bending moment at point 1, section 1 shear force and bending moment, at section 2 shear force and bending moment, and section 3, so then you have to draw the shear force and bending moment diagram, and from that diagram we can find out the maximum bending moment. When you get the maximum bending moment, you can calculate the maximum normal stress by using formula sigma m is equal to m over s or mc over I. Clear? So this was the part first. Now in part second it is given, find out the stresses before the point D and after the point D. So we will see from bending moment diagram we will find the stress before the point D and stress after the point D. So let's start with the solution. So first of all, the free body diagram of the beam must be drawn. So here it is drawn, the free body diagram. So you can see this was the reaction force that you have to find, and after calculation it comes out to be 34 kips, and this was the reaction moment that comes out to be 318 kip into feet. Rest all things are same. So this is point D where 10 kips force is applied and a couple or moment of 20 kips into feet. So from point A to C we have 3 kips into feet. So let me write down the distance from A to C. It is 8 feet. This distance is 8 feet. From C to D it is 3 feet. From C to D it is 3 feet. From D to E it is 2 foot. Or from D to E it is 2 foot, feet or foot. And from D to B it is 5 feet. That means this is 5 feet. Okay. So first of all you have to replace that 10 kips with equal force couple system that is shown over here, that is 10 kips force and 20 kips force. Then you have to find the reaction and the moment at point B, which you will calculate, and after calculation you will come to know that reaction force at point B is 34 kips and moment at point B is 300 kips into feet. Now we will cut the beam at any section after the application of load. So you can see at point A there is no concentrated load, but between section A and C there is a uniformly distributed load. So you can take the section at this point 1. Let this is section 1. So if you analyze the beam of the left section of left side, so this was the beam. This is the beam that is shown here. So if you cut the beam, so definitely there is a shear force that will be in downward and the reaction movement M. So, and let this length of the beam where we cut is denoted as X. Clear? Now there is a distributed load. Now this distributed load is 3 kips per feet and the length is here X. So if you want to convert this uniformly distributed load into concentrated load, so you have to multiply this 3 with X. So it will be 3x and it will be acting in the mid of this section. Clear? So total is X, so this distance will be X by 2 and this will be again X by 2. Now you will apply the equation of equilibrium equation. So sum of all forces along y direction is equal to 0 and upward is taken as positive. So you can see there is a force that is minus 3x that is acting downward and minus v which is acting downward. Their sum must be equal to 0. So v will become equal to minus 3x. Now this is for the region when x is greater than or equal to 0 and this x can goes to length 8 feet. You can cut the beam between 0 and 8 feet length. So this is the shear force equation for the section for the length of beam AC, which is 8 feet. So you can cut it over anywhere. Now you have to find the moment. Now this moment at point 1. So sum of all the moment at point 1 must be equal to 0 and counterclockwise is positive. Now you can see there is a force that is acting. This force is 3x and it is producing movement in counterclockwise. So 3x, and what about this distance? this distance is remaining perpendicular distance is x by 2. So 3x into x by 2 plus this moment, their sum must be equal to 0. So moment will be equal to minus 3x square over so minus 3x square over 2, or it is equal to minus 1.5 x square. So this is the bending moment equation. M is equal to minus 1.5 into x square, and this bending moment equation will be valid for x is greater than 0 and less than 8. So for x is greater than or equal to 0 and less than or equal to 8 feet. Now we are going to take the section at this point. This is section 2, and if you represent the free body diagram, so it will be like this. This is the beam. So if you cut the beam, so there will be a shear force and the reaction moment at point 2. So this is point 2. You can see that on the left of the beam of this section, so there is a uniformly distributed load, and this uniformly distributed load from this point to this point, this distance is 8 feet. Clear? So in order to convert this uniformly distributed load into concentrated load, so this load is 3. Clear? And let this distance is cut at a distance of x. Clear? Now this load is acting over the length of 8 feet, so 8 into 3 is 24. 8 is the length and 3 is uniformly kips per foot is the load. So 3 into 8 is 24. Now this 24 kips force will be acting at the mid. So from this point to this point it is 8. So this distance will be equal to 4 feet. And this from this point to this point, this distance is also 4 feet. Also, from the start till the point 2, total distance is taken as x. Clear? So remaining this from the load from this point till this distance will be, this is 4. So this distance will be x minus 4, which is represented over here. So we will again apply the shear force equation at point 2 and bending moment. So now you can see that shear force at point 2 is, there is a downward force that is minus V, and again this force, concentrated force, which is negative, which is 24 kips, and there is no other force. Clear? So that their sum must be equal to 0. It means that V is equal to minus 24 kips. There. Now we have to find this moment at point 2 as well. So sum of all the moment at point 2 is equal to 0, and counterclockwise is taken as positive. So you can see at point 2 there is a moment M that is in counterclockwise direction. So that is plus, and due to this concentrated load, there is a moment that is also in counterclockwise direction. So its magnitude will be 24 times perpendicular distance, and this perpendicular distance is x minus 4. So plus 24 into x minus 4 is equal to 0. It means that M is equal to minus 8 plus 96, minus 8x plus 96. So again this is not 2, this load is not 2, this is 24. So let me clear it. So this is 24, let me write it again. So this M will at point 2 will be minus 24x plus 96. So this is the moment equation for what? For x is greater than or equal to this at point C, this distance is 8. X should be greater or equal to 8 and less than this point is, this is 8 and this is 3 feet. So it is total 11. So x should be greater than 0 and less than 11 feet.
Clear? Similarly, you can let me delete something from the screen. So again, it is also solved. You can see now that if we section at point 3, so the figure is given over here. So let the distance from the starting to the section 3 is x, and the load, uniformly distributed load acting on length of 8 feet is given, and at point D there is a 10 kips force and 20 kips feet moment is given. So by using equilibrium condition you can solve it, and you can also find the equation of shear force and bending moment. It's very easy. So for shear force, the now shear force will be equal to sum of all forces along y will be equal to 0. So it will be minus V minus 24 and minus 10 is equal to 0. So V will be equal to minus 34 kips. And you can also find the bending moment equation at this section by using the equation sum of all the moment about point 3 is equal to 0, and it will yield you a equation for the bending moment through this region. So I clear it, I remove all the writings. So now you can see from A to C, it means x is greater than or equal to 0 and less or equal to 8 feet. So the shear force is 3 into x minus 3x and minus v is equal to 0. So v is minus 3x kips. And this moment m, this is clockwise, so plus m into this force is producing movement again in clockwise. So 3x into perpendicular distance. So if you calculate it, this is the equation of bending moment equation for x is greater than 0 and x is less than 8 feet. Now for section 2, we have, when you apply the equilibrium condition, so you will have v is equal to minus 24 kips. How? And I have explained it earlier. So v, you can see there is a v shear force v that is acting downward, and there is a force minus 24 kips. So this v will be this one, and the moment equation is 96 minus 24 x in kips into feet. I have explained it. Now if you take the third section, so again if you take the third section and you apply the equilibrium conditions, so you will get the shear force is minus 34 kips, and you will get an equation for bending moment, that is 226 minus 34 x kips into meter. Now this is for x is greater or equal to from D to B. So from D to A, this distance is, this is 8 and this is 3. So 11. So x is greater than 11 and less or equal to, total is this 5, so 16. Clear? And similarly from C to D, so x is greater or equal to 8 and less or equal to 11, because D point is at 11 feet distance. So this is the bending, this is the shear force and bending moment equation for x is greater than 0 and less or equal to 8 feet. This is the bending moment of shear force equation and bending moment equation for x is greater than 8 feet and less than 11 feet. And this is the shear force and bending moment equation for x is greater than 11 feet and less than or equal to 16 feet. Now we will plot them, or we will draw the shear force and bending moment diagram for the above beam under the given loading. So now you can see this is the beam under the given loading. So you have to draw the vertical line from the ends, and then you draw the horizontal line in order to show that the length of beam varies along this axis x. Now let me write again. So we have v is equal to minus 3 kips, m is equal to minus 1.5 x square. So this is when x is greater or equal to 0 and less or equal to 8 feet. This was the first one. The second one is v is equal to minus 24 kips and M is equal to 96 minus 24x into kips. And this was for x is greater or equal to 8 and less or equal to 11. For third, we have v is equal to minus 34 kips and m was 226 minus 34x kips into inch, and this is for x is greater than or equal to 11 and less or equal to 16. Now if you have all these equation, you can plot them. So first we will draw the shear force. So we will start from x is equal to 0 and less, x is greater or equal to 0 and less or equal to 8 feet. So at point A you can see there is no concentrated load. So definitely at this point the shear force will be 0. Now by using this equation, this is actually 3x. Again, if you put x is equal to 0, so this force will be at this point will be 0. Now at x is equal to 8, let another point is x, which is 8. Clear? So you have to multiply, you have to place x, you have to place 8 instead of x. So 3 into 8 is minus 24. So if you draw it according to the scale, so and locate minus 24, let this is the minus 24 over the length or at point C or over the distance of 8 feet. So this is 8 feet. Clear? So you have minus 24. Now how you will know to join these 2 points? How? You can see that this uniformly distributed load is a constant load. So again shear force will be 1 degree higher. And you can see that shear force is a 1 degree a linear equation, so bending moment will be a 2 degree. I will discuss it a bit later. So now you can easily join them by joining 2 points. Or if you are confused, you can take the value of x, you can increase the x, you can take x1, it will give you at a distance of 1 feet, it will give you some point. Again at 2 it will give you some point, and again 3. So you can, if you join all them, you will get a straight line. So see, this is the shear force between section A and C. Now we will move at section 2. For section 2 we have shear force is equal to minus 24 kips and x is greater than 8 and less than 11. So it is a constant number, so it means from 8 to 11. This distance from this to this is 8 and this from this to this is 11 feet. So from 8 to 11 only shear force is minus 24. So this again, this point will goes on. This is a constant line, constant value. Clear? Now at point 3 or section 3, you can see that from C to D it is constant, but immediate after point D there will be change in the shear stress. So you can see from point D we have minus 34 when x is greater than 11 and less than 16. So x is greater than 11 and less than 16. This is the region. X is greater than 11 and less than 16. So you can see the shear force is minus 34. So it means that you have, this is minus 24 and you again will go to 10 more downward. So from this point to this point, this total is minus 34. So this will be the point. And again from x is greater or equal to 11 and less or equal to 16. Until 16 it will be the same constant value. There, so this point is again minus 34 kips. One more thing is that the end of the beams having shear force will be the same in the shear force diagram. So you can see at the end of this beam there is no concentrated load, so shear force at this point is 0. Again at the end of this beam
there is a force 34 kips, and in the shear force at the end there is 34 kips. Although the sign is different, but their values will be the same, and this will show you that you are going in a in an accurate track. So you are going well. There is no error in your problem. Clear? So this is the shear force diagram for the given load. Now for bending moment diagram, again we will draw the horizontal line between the end of these two beams. Clear? And we will use these three equations. So let's start with first equation. So now m is equal to minus 1.5 x square. Now x is greater or equal to 0 and less than or equal to 8. So if x is equal to 0, so moment at this point will be 0. Now at x is equal to 8, if you multiply 8 with 1.5, clear? Sorry, if you not with 1.5. Okay, if you if you take the square of 8 square, that is 64, and multiply by minus 1.5, it will give you minus 96. So again you have to plot or locate the minus 96 at point B. So according to your scale, chosen scale, you will identify the minus 96 at point B. So let this point is minus 96. So now these are the 2 points. So how you will join them? So you will see that this shear force is a linear equation. Clear? So definitely the bending moment will be a curve, or it will be a parabolic. But here it is drawn like this one. Why it is not drawn like this? This one is in clockwise direction and this one is in counterclockwise direction. So I will explain this. Remember that if the shear force is a linear equation or a linear curve or a linear line, clear? The shear force is a linear expression or it is a linear line, and it is in going downward, or the slope is going downward. So the moment will be again taken as clockwise. So you can join point 1 and point 2 in clockwise direction. If it is like this, then you have to join them. Sorry, I have just write this line or drawn this line as per understanding, but it's not correct. Depending upon the situation, if this line, linear line, is like in upward direction, or slope is in upward or increasing direction, so then in that scenario this parabolic will be like this one. I hope it's clear. Again I will repeat that you will look to the shear force diagram, and if in the shear force diagram, if this line, linear line, is going toward downward or slope is decreasing, clear? Our slope is in downward direction. So in bending moment, the curve will be in clockwise direction. Clear? Or if you are confused, you can use this formula. You can put the value of x is equal to 1. So at 1 distance or 1 feet length, you will get the value of m. At x is equal to 2, you will get another value. So definitely you will join these points and you will curve like this. So this is the bending moment diagram between section A and B, or x is greater than 0 and less than equal to 8 feet. Now we will move toward from section C to D, which is x is greater than 8 and less or equal to 11. So you have this equation, bending moment equation. So if you put x is equal to 8, so again this will be 24 into 8, and again it will be the same, minus 96 keeps into 4.
And if you put x is equal to 11, so you will get minus 168 keeps into feet. Clear? So you have to locate minus 168. Let this point is minus 168. Now how to join? So you will look the shear force diagram. Now you can see shear force diagram is a constant number or a line with zero slope. So definitely bending moment is line will be 1 degree higher, so it will be a linear line. Now we will move toward from D to B. So our x is greater than 11 unless r equal to 16. So if you put x is equal to 11 in this equation, so you will see that the bending moment will be minus 140. So this will be minus. So it means that bending moment is now shifted toward from minus 168 to minus 148. And if you put x is equal to 16, so it will give you 0 bending moment. So this point will be 0. Again, this is a 0 degree line or a constant number. So the bending moment will be a first degree line, or it's a linear equation. So you can easily join them. So this is the bending moment curve or bending moment diagram. Now you can also see that the area under the shear force, which is AEB, this is a triangle, and the triangle area is equal to half of B into H. B is 8 feet and H is minus 24. So if you put 8 and H is minus 24 and take half, so you will get minus 96 keeps into feet as moment value. Again, this area is a square one, so 11 into this total distance 24, it will give you the moment under the value of moment, which is minus 168. Clear? Okay, and similarly so on, you can check it as well. Now we have solved the first part of the problem, in which we have been asked to find out the shear force diagram and bending moment diagram. In second part, it was given to find out the stress before point D and after point D. So from shear force diagram, you can see that this point, this is point D. At this point, the moment actually this area shows you the left side, and this point show you the right side. So you have to find out the stress before point D and after point D. So we have moment before point D and after point D. So we will put in the flexure formula in order to calculate the stress before point D and stress after point D. So apply elastic flexure formula to determine the maximum normal stress to the left and right of the point B. Now we know that stress is equal to MC over I, or stress is equal to maximum stress is equal to M over S, where M is the bending moment and S is the section modulus. So section modulus for this wide flash 10 into 120 roller beam, if you go to appendix C and you locate this beam, so S is 126 inch cube about x-axis. Clear? So S value is taken from the table. Now to the left of D, this moment is 168. Neglect minus because it is mod. We have to find the stress, maximum stress before point D and after D. So you have to take this value 2016 kips into inch. Now this moment before point D is mod is 168 kips into feet, and you have to convert it into kips into inch. So 168 into 12 will be equal to, because 1 feet is equal to 12 inch, so that will be kip into inch. When you multiply 168 with 12, so you will have 2016 kips into inch. Because why we are converting from foot to inch? Because the S value is in cubic inch. Here, so for consistency in unit, we have to convert this. So when you calculate it, sigma m before the section or before the D point is 16 ksi. Now to the right of D, this is the moment is minus this 148. So if you again multiply 148 with 12, so it will be 1776 kips into inch, and divided with section modulus, so you will have maximum stress at after point D. So this was all about sample problem 5.2. I hope you have learned it. Let's start another topic, that is to find out the relationship among the load, applied load, shear and bending moment. So if you look this beam, there is a random distributed load. So there is a support at point A and support at point B. So let we take a section C dash of the beam, and we will analyze it in order to find the relationship. Let this section is shown here, which is rectangle portion. This is point C and this is point C dash. Now C is at a distance of x and the thickness of this section is delta x. This is a very small section. This delta x. So total length from this point to this point will be x plus delta x. Also, one thing should be clear, that this delta x is very small. So it will be actually a thin section. Clear? So if you cut the beam at this point, so there will be a shear force in upward direction and bending moment in this direction, and there will be a shear force in downward direction and there will be a bending moment at this direction. Let this shear force at point C is M and V at a distance of delta x. Now this shear force is V plus delta V and this moment will be M plus delta M. Also you can see there is a random load over the entire beam. So if this section or if this delta x is very small, so if its thickness is very small, so this will thickness is very small, so it will be, this load will be treated as uniformly distributed load, because the thickness is very small, so it will be approximately a rectangular in area. The load will be rectangular in area. So let this load is W, and if you want to convert this uniformly distributed load into concentrated load, so you have to multiply this W with this delta x. So it is represented over here. So this load is converted into, and this is the magnitude of concentrated load, which is W into x. Now this W into x will be lie in the mid of this section. So this is total is delta x, so it will be at a distance of, this distance will be half of delta x. Now we will apply the summation of force along y direction must be equal to 0. So you can see there are two forces. One is this V, this is an upward direction, so V, and there is another shear force which is in downward direction, that is minus V minus into V plus delta V, and there is a force which is W into delta x, and that is also acting downward, minus W into delta x is equal to 0. So this is will become equal to V minus delta V, clear, minus V minus delta V and minus W into delta x, their sum is equal to 0. So it will be cancelled with this. So delta V becomes equal to minus W into delta x. Clear? Again, if you divide this equation with delta x on both sides, so we will get delta v over delta x is equal to minus omega rw. Clear? Now this delta x is very small, so we will take the limit on both sides. So delta x approaches to 0. Clear? And again we will take limit delta x approaches to 0 into minus w. Clear? This will be in bracket. Now you know that this limit of delta v over delta x when x approaches to 0 is actually, it is dv by dx, and it will be equal to minus w. Okay? And from this we can calculate that dv is equal to minus w into dx. Now this dv is actually vc dash, shear force at point c dash vc dash minus vc, that is equal to minus w into dx. So this is the relationship of the shear force with the load. So w is the load and v is shear force. Our dv is equal to minus w into x. So v is the shear force and w is the load. So we have derived an equation that shows the relationship between load and shear. So again this is also given here, v minus v plus delta, and again same this thing. So if you want to find the shear force and the load relationship at point D, so again dv is equal to minus w into dx. Again this dv is equal to for the entire load we will integrate it on both sides, so this integration from c to d, so that will be equal to vd minus vc is equal to integral of minus w into dx from c to d. Clear? So xc to xd, so vd minus vc. So in this way you can find out the relationship between the shear force and the load at any section, in between any section, from one point to another point. So this is the one basic equation, dv is equal to minus w into r, v is equal to v at one or 2 points, v2 minus v1 is equal to integral of x from 1 to 2 is equal to w into dx minus. Now we will similarly we can also find the moment at point c dash. Their sum will be equal to 0, taking counterclockwise as positive. So you can see at point C there is a reaction moment, that is m plus delta m. There is a movement in clockwise direction in counterclockwise direction. This is counterclockwise and this is clockwise. So that will be minus m. And due to this concentrated load, there will be a movement in counterclockwise direction, that will be positive. Clear? That will be w into x, w into delta x, and the perpendicular distance is delta x by 2. And one more movement due to this shear force, which will produce a clockwise rotation, that is minus v into delta x. So if you solve this equation, you will get delta m will be equal to v into delta x minus 1 over 2 w into delta x whole square. Clear? Again, if you take the limit on both sides, so that is limit delta m is equal to limit
of this equation, V into delta x minus 1 over 2 W into delta x whole square. And this limits from x, delta x approaches to 0. Let me clear some area. So erase these things. Now, this limit of delta m is, if you take the limit, let me write it again over here, limit of delta m and delta x approaches to 0 is equal to limit of delta x approaches to 0 v into delta x minus 1 over 2 omega into delta x 0. If this delta x is approaches to 0, its square will be 0, so its square will be also very small, so we will neglect this and this will take it to 0. So this delta limit over delta m over delta. Okay, one more thing is that if you have limit of if you have you can see this equation, delta m is equal to v into delta x minus 1 over 2. So delta x is common. So if you divide delta x on both sides, so that will be equal to delta m over delta x, and this will be equal to v minus delta x, not x square. So if delta x is very very small, so it's 0. So we have limit of delta m over delta x is equal to limit of v. There, and this limit will be equal to dm over dx, and that is equal to v. Or we can say dm is equal to v into dx. This is another equation, that is relationship between the moment and the shear force, bending moment and shear force. Just like we have dv is equal to minus w into dx, we have dm is equal to v into dx. Now this is the relation that can be used directly in your problems. But there is a limitation, you cannot apply this equation to the concentrated load or point loads. This equation can be only valid if you have distributed load. So now if you want to find the moment at point D, so we will integrate it, so that will be equal to, we will integrate this from point C to D and from point C to D. So MD minus MC will be equal to integral of V into dx, x at C and x at D. So by using this equation, you can solve the problem very easily in order to find the bending moment at any point, at C or at B or C dash, etc. So this was all about relationship among the load, shear and bending moment. Now we will solve another sample problem, and we will use this methodology in order to show you, or in order to clear your concept further. This is also again solved over here. So MD minus MC is equal to this. This is the same thing which I have derived here. So now this is the sample problem. You can see, draw the shear and bending moment diagram for the beam and loading as shown. So this is the beam. So at point A it is simply supported, and at point D there is a roller supports. At point B there is a concentrated load 20 kips. At point C this 12 kips. Now from point D to E there is a uniformly distributed load. The lengths are also given. So first thing is that you have to draw to find out the reaction forces at point D and point C. So you will go through that, and it's your assignment to do
this and to find out RD and RA by using equilibrium condition. So taking the entire beam as a free body diagram, determine the reaction at A and D. After finding the reaction force, then you have to section the beam after the load. So at this you can section it over here, you can section it over here, you can section it over here, and you can section it over here. So you have to apply the relationship between shear and load to develop the shear diagram. So you have to find out the shear force and bending moment. Then this is the same. You have to with the shear force. You have to draw the shear diagram, and after drawing the shear force diagram, you will have to develop the bending moment diagram. Or if you have the equation of bending moment equations for every section, you can draw the bending moment diagram. So at the end, you will achieve your goal, which is to draw the shear force and bending moment diagram for the loading shown. So let's start and solve this problem. So in this problem, we will use the concept dV is equal to minus W into dx, and dm is equal to V into dx. But this formula will be used in the this section DE, not here, because these are the concentrated load. Only the distributed load is available between D and E. So you can solve it is as typically we solved the previous problem, but if you want to use this concept, you can also use. So we will see both of them. So let's start moment at point A. This has been solved. So in order to find the reaction at point D and A, so you have to take the first moment at point. You can use either this first or this first. Both the equation can be used. So at the end you will get the reaction force at point D, which is 26 kips. 26 kips. I will not write the units. And A at AY will be 18 kips. AX will be equal to 0 because there is no other horizontal force. So sum of all force along x direction is equal to 0. It means AX is equal to 0. So let's start with our previous concept, that is as there is a reaction force at point RA which is equal to 18. So let's draw directly their shear force. So from the beam you have to end of the beam you have to draw the vertical line and then join them. This horizontal line shows you that length of the beam varies along this direction. So this is the point. At point A there is a, now we will solve it directly. I will show you how you will directly draw the shear force. So at this point A there is a shear force which is 18. So according to scale you have to look at 18 plus 18 at this point. Now at point B, this 18 shear force will be throughout constant till this length. But at point B now there is 20 kips downward. So 18 is upward and 20 is downward, which is minus 2. So at point B it will be the minus 2. So you have to look at point B minus 2 and you have to join them. So this point 18 is just start at the start of B, and this minus 2 is just after the point B. Now at point C, you can see now at point B this is minus 2. Just after point B it is minus 2. And it will be same till the point C because there is no other load. But when you reach at point C, so total load was minus 2. Now this is why minus 2? Because 18 plus and 20 minus, so minus 2. Now minus 2 and this load is also minus 12, so minus 14. So again you have again go to minus 12 again. So total is basically minus 14 from this point to this point till this point. This is minus 14. Clear? So from this point you have to go to minus 14 point.
Clear? So this C. Now from C to D there is no load. So again from C to D it will be minus 14. But at point D there is a load. There is a point load. So till this is minus 14. And now there is a plus 26. So this will be plus 12. So you have to locate plus 12 above the X line. So this is plus 12. So this shear force line will be like this. Again, at the end, you can see there is no point load. So definitely it will be 0. So you can join them. Also, one more thing, how you will know that this is a straight line. You can see this is uniformly distributed load is a constant load, 1.5 kips per foot. So it will be a linear equation. But at the end there is no load, so it will be a load is a constant, so shear force will be 1 degree higher, so it will be a linear equation. So this is the shear force diagram for this loading. And we have drawn it without any writing the equilibrium equation. You can also write it. I can just show you. Let's say this is point 1. So at point 1 there is only loading, that is A, which is 18 kips. There is a shear force and bending moment at point 1. So let this distance is, for example, X. So by applying the shear force equation, sum of all forces along y direction is equal to 0. So 18 plus minus V is equal to 0. It means that V is equal to 18. Whatever the unit is, kips into foot. Clear? Kips. Now you can find the moment at point 1 is equal to 0. So now you can see that the equation of moment for this will be, this is the moment that is clockwise, and this is the force which is producing moment in this is counterclockwise and this is clockwise. So minus 18 into perpendicular distance is X. So means M is equal to 18x. There. We have not drawn the moment, bending moment diagram, and we will draw it in next slide. But again, if, currently we are focusing on shear force. So let at point 2. So at point 2, there is a load at point A which is 18. At point B, there is a load at 20. And there is a shear force and couple. So this V2 minus plus 18 minus 20 is equal to 0. So V2 will be equal to minus 2. So you can see from this equation this is minus 2. And so on, you can solve it. I have just shown that whether you draw the sections and calculate all these values, you can easily draw the shear force diagram directly. Now, here we have also taken the shear force directly, but we will use dV is equal to minus W into dx. Now we will integrate from d to e. So it will be equal to VE minus VD. VE minus VD is equal to integral of x at d to x at e is equal to minus W into dx. Let me explain this thing. Okay, I will erase all for my ease. So let we have dV is equal to minus W into dx. So from d to we will integrate it, so that will be equal to VE minus VD is equal to integral of W into dx, x from d to x from e. We will solve this and I will show you that it will be the same equation. Okay, so you can see that VD
at the end, VD, VE is this VD. VD is actually 12. At this point, VD is 12. Clear? So we will put VE minus 12 is equal to integral of x at D. So x at D, this distance, is equal to 6 plus 8, 14 plus 10, 24. So x at 24 and E, 24 and 8, 32. So at x at E is 32 minus W into dx. So minus W into 2x. This will be equal to, W is equal to actually, what is the value of W? W is 1.5 gives. So that will be minus 1.5 into integral of dx 24 into 32. And it will give you minus 1.5. Integral of dx is equal to x. So it will be x and 24 to 32. So when you put the value, so VE will become equal to minus 1.5. V is equal to minus, V is equal to minus, not minus 1.5. V is equal to 12 plus 12 plus 12. This 12 will go toward this minus 1.5 times x is 32 minus 24. Clear? So that is equal to 12 minus 1.5 into 8. So if you multiply 8 with 1.5, it is again 12. So V at point E is equal to 12 minus 12, which is equal to 0. So again you can see V at point E is 0. So we have drawn a straight line. This is how you can find the shear force at any point under the distributed load. Now we will move toward finding the bending moment equation. Also we know that bending moment, relationship of bending moment and shear force is written as dm over dx, which is equal to V, and dm is equal to V and dx, that we derived in the slide of relationship between load, shear force and bending moment. So now again, so if you want to draw the shear bending moment directly, so you can see the area under the shear force will be the bending moment. So this y is 18 and this distance is given 6. So 18 into 6 is equal to 108, which is also again here. This is 108. So again, the moment at this point will be equal to 0 because the force is passing through this point. So there will be no moment at point A. And 108. So you want, if you locate 108. So again, this is a straight line, or 0 degree line, or a constant value. So bending moment will be, our line of the bending moment will be 1 degree higher. So this is 0 degree line, this will be a linear line. Here. Now you can see that load at this point is, the area under the section BC, which is this one. So minus 2 into this perpendicular distance, which is minus 16. So again, the total moment will be, this was 108 and this is minus 16. So total moment will be 108 minus 16, which will be 92. So at point C, this will be 92. So you have to locate 92 at point C. And you have this point B and this point C. This is point B and this is point C. And this is a 0 degree line, or constant value, constant number. So bending moment will be 1 degree higher. So that will be a linear line. Again, the area under the shear force diagram between section C and D is this one. So now you can see this is rectangular, so total height is minus 16 or minus 16, and this length between C and D is 10 foot. So minus 16, okay, this length is minus 16, and total height, not minus 16, sorry, I have written wrong. So from this point till this point it is minus 14, so minus 14 and this distance is 10, so minus 140. Now you can see this is 108, this is minus 16, this is minus 40. So at this point we have 92. If you add 92 with minus 148, this will give you minus 48. So at this point minus 48, you have to plot minus 48. Again, this is a 0 degree equation, so you can join them using a linear line, a straight line, or 1 degree, a linear line, simply a linear line having 1 degree. Now this was the shear bending moment till point DE. Now you can see that this shear force is again at this point. The shear force will be the same, minus 48. But at this point, this is a linear line. So shear force, this is the shear force diagram. So you can see this is a linear line. So bending moment will be a parabolic line. So again, the slope of the line is decreasing. So the bending, and at this point there is a 0 shear force, so movement will be also 0. So again, this line is a linear line and its slope is decreasing. So by convention, the bending moment will be a parabolic line and it will be in clockwise direction. So this is how we draw the shear force and bending moment diagram. If you have clear idea, you will not need any equation, or you will not have to section anywhere, so you can draw it easily. Now for understanding purpose, we will also derive, you can also solve it by taking the section at any point, and you can use the equilibrium condition to find out the shear force and bending moment diagram equation at each sections. You can use that method. You can also use the method which is, so in previous equation, that is dV is equal to minus W into dx, that can be used to find out the shear force when there is distributed load. So this equation cannot be used for point loads, while the second equation, that was the relationship between the bending moment and shear force. So dm is equal to V into dx. So it can be applied because you can have the shear force value over here, and over here. So let's use this equation. So dm is equal to V into dx. So this is point A, this is point B, this is point C, and this is point D, and this is point E. So let integrate it from point A to B. dm is equal to integrate from point A to B, V into dx. So it will be equal to mb minus ma, and that will be equal to shear force between point A and B is 18. So integral of 18 into dx from A to B. Clear? As ma is 0 at this point, so this will be mb, and mb is equal to 18 into x from A to B. It means 0 to, from A to B distance is 6 feet. So it will be again 6. So it will be equal to 18 into x, 6 minus 0, which is equal to 18 into 6. 6 8s are 48, 4, 6 108. So you can see that moment at point B is 108, which is over here. Again, you can calculate from between point B and C. Clear? So I will just write forward that moment at point C minus moment at point B is equal to integral of the shear force is now minus 2. So it is minus 2 into dx. You can calculate it as well. Now C start from 6 to this is 6, B is 6 and C is 14. So that is equal to minus 2 into x. So x start from 6 to 14. Again, you will, when you have value of B, MB, which is 108, when you will put it, you will get 92. So moment at point C. So this is how we solve this problem by using the equation or relationship between the bending moment and shear force, and the relationship between shear force and the loading. You can read it as well. These are the same steps. Now sample problem 5.5. So in this problem it is a cantilever beam with uniformly with a linearly varying load. So you can say that the load is going to decrease, and at point B it is 0. So we have to draw the shear force and bending moment diagram for this beam. So first of all, we will find the reaction force at point C and the reaction moment at point C. Also there will be a horizontal force. Clear? So Cy, Cx and moment at point this. So this can be solved by using the equilibrium equation, that sum of all forces along y direction is equal to 0 and sum of all the moment at point C is equal to 0 or at any point is equal to 0, and counterclockwise is taken as positive. So for finding the reaction forces, we have to convert uniformly varying load into concentrated load. So this is W naught. So in order to convert it into concentrated load, so you have to multiply this W naught with A. That will W naught into A, and it will be divided by 2. So this will be this uniformly varying load is converted into concentrated load. Now this concentrated load will act on a point of beam, and it will be at a distance, total distance is A, so it will be at a distance of A by 3 from the larger side, larger magnitude size. And the remaining this distance from this point to this point, this distance will be equal to 2A by 3. Now you will apply the equilibrium conditions in order to find the reaction forces. So take the entire beam as a free body diagram, determine the reaction at C, apply the relationship between shear and load to develop the shear diagram, and also apply the relationship between the shear force and bending moment and draw the bending moment diagram. And this is the solution. You can see when there is a CY or RC reaction at point C, and there is a moment at point, reaction moment at this point C, that is MC. Clear? So in order to find the reaction, there is a horizontal force, but it will be equal to 0 because there is no other horizontal force. So let's start with sum of all force along y direction is equal to 0. So we have stated that in order to convert this linearly varying load into concentrated load, so it will be W naught into A divided by 2, and it will be at a distance of A by 3 because total length for which this uniformly varying load is acting is A, and the remaining distance from this point to this point is 2A by 3. Clear? So the forces acting on this is W naught A over 2, which is given, and it is negative, so negative, plus RC is acting upward. Their sum must be equal to 0. It means RC is equal to 1 over 2 A naught, 1 over 2 W naught into A. Similarly, for movement at point C, we can see there is external movement MC, and there is a movement due to this concentrated load. Actually, it is a uniformly varying load, but we have converted it to concentrated load. So this magnitude of this concentrated load is W naught A over 2, and it is producing a counterclockwise, and perpendicular distance will be this one. So basically this is A by 3, so this distance is equal to L minus A by 3. So you can see 1 over 2 W naught into A is the magnitude of this concentrated load, and the perpendicular distance is L minus A by 3. So when you solve it, so MC is equal to minus 1 over 2 W naught A into L minus A by 3. So this was the reaction forces. Now we will move toward finding out the shear force between point A and point B. So we have dV is equal to minus W into dx. So if you integrate it from point A to B, x at point A and x at point XA to XB, XA to XB. So we will have VB minus VA is equal to integral of x is 0 at point A, it is 0, and at x at point B is A. So 0 to A, and that is, we do not know W. So what we will do, so if you look to the uniformly varying load, so this was a uniformly varying load. So you can see here it is 0. So if this is Y, and that is W naught, the magnitude of this uniformly varying load, linearly varying load is W naught. So if you look at this line, this is a straight linear line. So equation for linear line is equal to Y is equal to mx plus c, where Y is the vertical distance, m is slope, x is the distance on x, and c is the vertical intercept. Clear? So in this case, Y will be equal to W, slope of this line will be, you can see the slope of this line is actually W naught over A, because this is theta, tangent theta is perpendicular by hypotenuse, so M will be equal to W naught over A. X is the distance, clear, which you want, and this C is the vertical intercept, which is again W naught. So the equation of this uniformly varying load will be equal to W naught over A in plus W naught over A into X plus W naught, and it is, if W naught is common, so it will be equal to 1 minus, okay, one more thing, that slope is decreasing. Clear? So this W naught over A will be negative. So if you take W naught as constant, so it will be equal to minus 1 over A plus minus 1 over A. Let me clean it. So it will be minus W naught into 1 by AX plus 1. Clear? So it will yield you, this W will be equal to W naught into 1 minus X by A. So you will put this W with this. Clear? So when you put this W with this, so we will have minus is outside, So W naught into 1 minus x by A into dx. And when you apply limit to that, so we will, as you know that there is no point load at point A, so VA will be equal to 0. So we will have VB is equal to integral of 0 to A into W naught into 1 minus x over A dx. When you take the limit, so you will get VB is equal to minus 1 over 2 W naught into A. Here. So at point, if you want to draw the shear force, so at this point VA is equal to 0, so this will be 0. At point B, the shear force is minus 1 over 2 W naught into A, and it's a negative value. It's a general problem, so assume that this point is this. So at point D, this W naught minus 1 over 2 W naught into A is this. Now, in previous problem, I have stated that if the shear force is a linear equation, if the shear force is a linear equation, then bending moment will be a parabolic equation, and if the slope is decreasing, so bending moment will be like clockwise. But now in this figure, let me clear it as well, clear the screen. Erase all. Now in this you can see that load is a linear line. Load is a linear line, not shear force. Load is a linear line. Clear? And the slope is also decreasing. So in this case, if you want to draw the shear force between these 2 points, so this equation will be a parabolic, but it will be a counterclockwise. So again I will repeat, if the shear force is a linear line, clear? So then in bending moment, you will, if you want to draw the curve between these 2 points, let me draw it. Let's say if the shear force is a linear and slope is decreasing, so in bending moment, the curve will be like this one, clockwise. Clear? But now here you can see that the load or the applied load is linear line. Clear? And the slope is also decreasing. So whenever you want to draw the shear force between these 2 points, so first the shear force will be as quadratic or parabolic, and the direction will be in the counterclockwise. You can also join them this, but the assumption is the convention is that you will move in the counterclockwise direction. I hope it's clear to you now. So this is point A. Again, from B to C there is no force or no shear force, so this will be the constant, and at the end this will be a straight line. At end you can see that this is minus 1 over 2 W naught into A, which is the reaction force at C. Both the value are same, so it means that it is okay, the problem is going in right direction. Okay, now we will find out the bending moment equations, or we will also have to draw the bending moment diagram. So I have told you that the area under the shear force curve will give you the bending moment. So this is a parabolic, so its area will be equal to 2 by 3 into base, which is this, and this base is A, and height. Clear? which is minus which is minus 1 over 2 W naught into A. So this is the area of this parabolic curve under the shear force, or this is the area under the shear force diagram, and this show you the bending moment here. So this comes out to be minus 1 over 3 W naught into A square. Clear? So this will be your area. Again, this is the area and this is a square. So you can see this point, this height is minus 1 over 2 W naught into A, and this length is, if this is total L, so this will be L minus A. Clear? So L minus A into this vertical distance, which is 1 over 2 into W naught and A. So this area under the shear force will give you the value of bending moment. So let's draw it as well. You can also take okay, this thing has been this has been solved. So this is the area this point A. Okay. So now you can see that whenever you applied the relationship between the shear force and the load, that is distributed load, so VB minus VA is equal to integral of 0 to A into W naught. This W naught into 1 minus XA is actually a equation, that is W is equal to W naught into 1 minus XA, which we derived a little bit earlier, into dx. So when you solve it, VB comes out to be this. Clear? And there is no shear change between B and C, so it will be a constant value. Now we will draw the bending moment. So now you can see that this shear force is, at this point the shear force will be 0 because there is no concentrated load, so shear bending moment will be also 0 at this point. At point A we will find the moment, but from area under the shear force diagram we came out with the conclusion that bending moment is minus 1 over 3 W naught into A square. If you use this, you can directly plot this point, so you will get these 2 points. Now question is that this is parabolic second degree equation and its slope is reducing. So again the bending moment will be cubic equation and the direction will be in clockwise. So you can easily join them as well. Now this is constant, so it will be a straight line, and from this area under the bending area under the shear force will give you the moment. And if you plot this point, so let this point is this one. Clear? So now this is a 0 degree equation, so you can easily join them straight. So if you are not aware of this method, so you can just use the relationship between the moment and the shear force. So MB minus MA, so you are basically playing in this area. So MB minus MA will be equal to integral of shear force into dx. So shear force is actually minus W naught into x minus x square over 2a, which is calculated over here. This shear force is in this region is minus 1 over 3 W naught into a square. Clear? So moment at point A is equal to 0, and when you put all the values and take the integral from A start from 0, x start from 0 to A, so you will have the moment value at point B, which is minus 1 over 3 W naught into A square. Similarly, you can also apply it MB minus MC. So now here the shear force V is equal to, you can see, minus 1 over 2 W naught into A. Clear? So again, if you solve it, and now X start from A to L minus L. X start from A to L, and when you integrate all this, you will get moment at point C is L minus A into W naught over 2 into L minus A by 3. So you can see that from whether you calculate it by using equation or whether you use by area under the shear force diagram, both the values are same. Clear? So if you further say welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you. Bismillahirrahmanirrahim. Today we will discuss the part 2 of lecture analysis and design of beam for bending. So in this lecture we are going to teach how to design prismatic beam for bending. In previous lecture we discussed how to draw the shear force and bending moment diagram and how to calculate the maximum bending moment in order to find the maximum bending stresses. So in this lecture we are going to discuss how to design a prismatic beam for bending. Okay, so let's start. As we know that maximum bending stress is equal to M maximum C divided by I, where M maximum is the maximum bending moment, C is the distance from the neutral axis to the outermost surface, and I is the second moment inertia of the beam. Also you know that if we divide both numerator and denominator by C, so it will cancel, and this I by C is known as S, which is known as section modulus. So this sigma max or bending stress comes out to be maximum bending moment divided by section modulus. In previous lecture or the part first of this lecture, we find out how to draw the shear force and bending moment diagram, and the reason of why to draw the bending moment diagram or shear force diagram. So the reason was that we have to find the maximum bending moment in the beam. So in that lecture we discussed that along the length of the beam the bending moment changes. So we have to find the maximum bending moment. So in order to find the maximum bending moment, we draw the bending moment diagram, and from that we find the maximum bending moment, and then that maximum bending moment is used to calculate the maximum bending stress by using the formula maximum bending moment divided by section modulus, which is S. Clear? So here we will also use the same concept and we will find out the maximum bending stress in the beam, and based on that maximum bending stress we can also calculate the section modulus, and this section modulus is the geometrical property of the beam. So this section modulus can also be obtained by using the table that is available at the end of book as annexure C, in which we have W beams and S beams. W is for wide flange beam and S for short flange beam, and in that table we are given the different property of that beams. So we can take section modulus from that table and can also use in our problem. So let's start with a problem or example, and then we will define how you at the end you will be able to design a prismatic beam for bending purpose. Clear? So prismatic beams are those beams which have uniform cross section throughout all the length. So cross section remains constant throughout all the length. So while designing a prismatic beam, a safe design requires the maximum normal stress, that should be less than allowable stress for the material is used. We know that we have one is allowable stress and one is maximum stress. The maximum stress can be obtained by using the bending moment diagram. So in bending moment diagram you will have a maximum bending moment, so from that you can calculate the maximum bending stress. One is the allowable stress. Allowable stress is the stress of the material that is used for beam. Clear? So that indeed the allowable stress for the material depends on the type of material is used. So we will have allowable stress and we have maximum stress. So this maximum stress should not increase the allowable stress. If it increases from the allowable stress, so definitely the beam will fail. So you have to either keep the maximum bending stress is equal to allowable stress, or you have to keep this maximum bending stress less or equal to allowable. But you should not increase the value of maximum bending stress than the allowable stress. So again, maximum bending stress is less or equal to allowable stress. So by using this formula we can also calculate the section modulus, but minimum section modulus should be equal to the maximum bending moment. M is bending and that should be maximum. So maximum mean that is higher value. We will not consider the minus or plus sign, because minus or plus sign will show you the clockwise or anti-clockwise rotation. So that's why we are taking the mod of bending moment, that is the maximum. Clear? So you have to take the maximum bending value moment and divide by allowable stress. That will give you the minimum section modulus of the beam, and it is the same formula that we use here. Sigma m is equal to m max over s. So s will be equal to m max over sigma maximum. So this s is the minimum. So section modulus for the beam that you are going to design, so minimum section modulus must be equal to the maximum bending moment divided by maximum bending stress or allowable bending stress. So this formula is an important formula, and we will use to design a prismatic beam by using this formula. So in this formula you can see we need maximum bending stress and allowable stress or maximum stress. So how we will calculate this minimum section modulus of the beam? So for that we will solve a problem, and at the end you will be able to know how to design a prismatic beam for bending. So this is a sample problem 5.8. You can see this is a simply supported beam that is supported at point A and point B. Clear? So there is a pin support and there is a rolling support, and there is uniformly distributed load of 20 kilonewton that is acting from point A till point B over the length of 3 meter. While at point C there is a concentrated load of 50 kilonewton that is acting downward. In problem it is stated that a simply supported steel beam is to carry the distributed and concentrated load as shown, knowing that the allowable normal stress for the grade of steel to be used is 160 megapascal. So allowable stress is 160 megapascal, and we also stated that this allowable stress is either equal to or greater than the maximum, or we stated that maximum stress or maximum bending stress should less or equal to the allowable. So we are taking maximum allowable stress as 160 megapascal. So again maximum stress is 160 megapascal. Select the wide flange shape that should be used, and we have been asked to design a wide flange beam. So we have to select the wide flange beam by using our design parameter, we will design a beam that will be a wide flange beam. So in this problem you can see, first of all, for the problem to be solved, we have to define the stresses, reaction forces at point A and at point D. At point A there is a horizontal force as well as a vertical force, and at point D there is only reaction force, vertical reaction force. So RAY, RAX. Clear? So how you will solve this to find out the reaction force? So basically you will use the equilibrium condition, that sum of all forces along y direction is equal to 0, and sum of all the moments that must be equal to 0 about any point. So let's start. So as you know, there are the sum of all forces along x direction, there is only one force and there is no other force, therefore sum of all forces along x direction is equal to 0. So RAX will be equal to 0. So we will neglect this force. Only force that is acting in y direction is RAY, or you can also write simply RY, because the vertical force at point RA. Clear? So I will assume this force to be RA. So we will use first this equation. So sum of all forces along y direction must be equal to 0. So RA is the upward force, that will be positive. Now there is a uniformly distributed load that is acting at 3 meters. So 20 into 3 is 60, but it will be negative. So minus 60, and there is again a force of minus 50 plus RD will be equal to 0. So it means RA plus RD is equal to 110 kilonewton. So we will have one equation from this. Now sum of all the moment, let's say about point D, is equal to 0, and counterclockwise is taken as positive. So you can say there is one force RY that is producing a clockwise rotation. Clear? So RY into perpendicular distance is from this point to this point is 5 meter. So into 5, but it will be negative. Now there is a uniformly distributed load that is 60, and it is acting in the mid. This 60 is acting in the mid. So again, perpendicular distance will be 1.5 plus 1 plus 1. So 112 and 3.5. So from this point to this point, this distance is 3.5. So again, this is producing a counterclockwise rotation, so that will be positive. So 60 into 3.5. And there is a force 50 that is also producing counterclockwise. So 50 into perpendicular distance is equal to 1. Their sum must be equal to 0. So that will be 5 RY will be equal to 60 into 3.5. So let me calculate. 60 into 3.5 is 210 and plus 50. Clear? So RY is 5 RY is equal to 260. So 260 divided by 5 is equal to RY is equal to 52 kilonewton. Now you have RY, you can RY, sorry, this is RA, yes, so RA, because it is acting upwards. So RA is 52. Now RA is 52, so RD will be equal to 110 minus 52. So when you will subtract 52 from 110, so RD will become equal to 58 kilonewton. So this is how we calculate the reaction forces at end point. Now these are the solutions. So consider the entire beam as a free body diagram and determine the reaction forces at A and D. Then you have to develop the shear force and bending moment diagram. So for shear diagram, you will use the distributed load and as well as concentrated load and reaction forces to draw the shear force diagram, and then you have to diagram the bending moment diagram, so in order to determine the maximum bending moment. And then you will have a maximum bending moment. Clear? So you will use S minimum is equal to this divided by maximum or allowable bending stress. And once you have minimum section modulus, then you will go toward the table that is available at the appendix C of the book, and you will choose minimum section modulus, and against that you will choose the beam. I will show you in next few slides. So this was the beam, and this is how we calculated. We find out that D is equal to 58 kilonewton, and reaction force at at point A is 50 kilonewton. This is also solved here. Now, how to draw the shear force diagram? So again, you have to draw the two vertical lines from the end of the beam, and then you have to draw a horizontal line, and this horizontal line shows that the length of the beam along the x-axis. Clear? Now at point A, you can see this is point A, and at point A there is only force that is acting is AY, and that is 52 kilonewton. So you have to take appropriate scale. You have to divide this vertical line into your into equal parts or as per your scale, and you have to plot 52 kilonewton. So this is the point where 52 kilonewton lies. So you at point A there is only shear force. On vertical axis we take shear force, and on horizontal axis we locate the length of the beam. So at point A there is only one force, that is 52 kilonewton, that is acting. Now we have to find if you use method of section or the method which we have discussed in earlier. So you have to take sections. Again, it will consume too much time, so we will go toward the shorter we have to calculate it with a less time, with a less consuming time. So better is that this is point A where only 52 kilonewton is applied. Now at point B, you can see that from point A to point B there is a uniformly distributed load, and this is this was 20 kilonewton. Clear? And this 20 kilonewton, if we multiply it with the entire length over which this uniformly distributed load is occurring, so it will give you a concentrated load which is 60 Newton. So this is 20 kilonewton per meter uniformly distributed load. Now you can see this is the uniformly distributed load over the length of 3 meter. So when you multiply 20 into 3, it will be 60 kilonewton. So area under this curve is the shear force. So area under this curve, this is 20 kilonewton per meter, and this is the length. This is the force, on vertical, this is a force that is 20 kilonewton to meter, and this is the total length, this is 60. So at point B, there is 60 kilonewton force will be occurring. But remember that at point A, there was a 50, so at point B, there is a 60. So total, this is plus 52 and this is minus 60. So at point B, there will be a minus 8 kilonewton, because at point B, there is minus 60, and at point A, there is a 52. So again, 52 minus 60 will be minus 8. So at point B, the shear force will be minus 8 kilonewton. Now you can see that the uniformly distributed load is a constant line having 0 degree. So shear force diagram will be the first degree line. So you can join them by using ruler. So when you join them, it will give you the shear force diagram. So at point E, there will be, at point E, it is obvious that at point E there will be no shear force. So shear force will be 0 at point E. So we will have two triangles. So one is this triangle and the second one is this triangle. Clear? So area under these triangles will give you the bending moment. Now from point B to C, you can see there is no force, so the shear stress will be same from point B to C, and that will be -8. So from point B to point C, there will be -8. Now moving from point C to D, we can see at point C there is -8 and -8 to the left of point C. But when we go just just forward from point C, so now there is also a force of 50 kilonewton. So that is -50. So -50 and -8. So it will be total -58. So from 0 you have to locate -58. So let's say this point is -58. So from points, when moving from point C to the forward direction toward point D, so total shear force will be -58. Again from C to D there is no force, so from point C to point D there will be a constant shear force, that is -58 kilonewton. Now you can see at point D there is a -58 kilonewton, and from reaction which we have 58 kilonewton. So it means that your shear force diagram is correctly drawn. Okay, so we have drawn the shear force. Now we will require the maximum bending moment. We have to find the maximum bending moment. So for maximum bending moment, we have to draw the maximum bending. We have to draw the bending moment diagram as well. So one method is either you have to draw the bending moment diagram, or you can use this shear force diagram in order to find out the maximum bending moment. So we will solve both the method. You can see that at point A, the third method is that you have to find out the bending moment equation, and then from bending moment equation you will put the value of x and you will plot, but it will consume too much time. So better is to use a short method. So you can see that at point A there is a shear force that is 52 kilonewton, and it will pass through point A. So there will be Rx is equal to 0, so there will be no shear force. So at point A there is 0 bending moment. Clear? At point A there is a shear force of 50 kilonewton, but at point A there is no bending moment. Now at point, when you draw this shear force diagram between point A and point B, so a point where shear force will be 0. So if you have drawn it as per your scale, so you will measure this length, and this length will be x is equal to 2.6. This is one method. So at a length of 2.6 meter from point A, the shear force will be 0. So at point E, x is equal to 2.6. Also you can see that from point A to E, the area under the shear force diagram is actually the bending moment value. So how you will find the bending value moment is that this is triangle. So area of triangle is equal to half of base into height. Now base is 2.6, so it will be equal to half of 2.6 multiplied by height is 52. So when you multiply it, it will give you 67.6. Again it is written over here. So area under the shear force diagram between A and E is 67.6. So at point E you have to plot the 67.6 as per your scale. So let's say this point is point E, and at this point it is 67.6. Clear? Bending moment is 67.6 kilonewton into meter. Now at point B we have to find also the bending moment. So you can see that area under the line EB is the bending moment value. So how you will find the bending moment value? So you know that this length from E to B is, again this is total from A to B, it is 3 meter. So from A to E is 2.6, so this length will be equal to 3 minus 2.6, which is 0.4. And this is length, let me share. The area of this will be equal to half of base, which is 0.4, into height, which is 8. So again, this will be equal to 1.6. So this is 1.6. Again, this will be downward, minus 1.6, because it is minus. So it will be minus 1.6. So at point E it was 66.7, and at point B it is reducing minus 1.6. So at point B it will be 67.6 minus 1.6, it will be equal to 66. At point C, as the area under the line BC is a rectangle, so its area will be equal to, area of rectangle is equal to B into H. So in this condition, B is length between BC, which is 1, and height is again minus 8, which is this. Clear? So that will be minus 8. So if you subtract minus minus 8 from 66, so it will be minus 58. Let's say this point is minus 58, or sorry, plus 58, because 66 minus 8 is plus 58. And from point C to D, again there is a constant, there is a rectangle, so length is 58 and height is length is minus 58 and height is height is minus 58 and length is 1. So area for this will be equal to 1 into minus 58, so which will be minus 58. So this is plus 58 and minus 58, that will be 0. So this is point E, this is point B, this is point C, and this is point D. Now you will have to join them. You can see that the shear force diagram between a line between point A and E is linear line, but slope is decreasing. So shear force diagram will be the second degree equation, and it will be counterclockwise. Now from point E to B, it is again a first degree line and slope is decreasing, so it will be again a curve. Now from point B to C, it is a constant line with 0 degrees, so shear force equation between D and bending moment line between B and D will be a straight line. And from C to D, again it is a constant line or 0 degree line, so it will be again a linear line. So this is your bending moment diagram. So from this diagram you can see that maximum bending moment is 67.6. Maximum bending moment is not stress. Maximum bending moment is 67.6 kilonewton into meter. This is how we can calculate the maximum bending moment by using bending moment equation. The second method is that you can easily find out that at this point shear force is 0. So maximum bending moment will be at this point. Clear? Which is x is equal to 2.6. And the area under this shear force diagram is bending moment, which is 67.6. Again you have found here it is 66, it is less, and again it is less, and again it is less. So 67.6 is the maximum, and you can find out the maximum bending stress moment from here. If you are confused that how this x is equal to 2.6 comes out, so we have another method. I will also show you. Let me erase something from here. So if you look at these two triangles triangle let's say this point is A dash E, and triangle E B B dash. These are similar triangles. So by similar triangle means if we take the ratio of their corresponding sides, that will be equal. So if we take A dash A dash over B dash, that will be equal to AE over EB. Clear? Let we do not know this distance, and we know that this distance is x. So obviously this distance is x, so this will be, if let's say this total distance is, this is x. So this will be x minus 3, because total distance is 3. So this will be x minus 3. Clear? So you have to put the value A dash is 52, divide by B dash is 8, AE is x, and EB is x minus 3. So when you solve this x comes out to be 2.6. So at x is equal to 2.6, the bending stress, shear force will be 0. So bending stress will be maximum at x is equal to 2.6. So again, if you have the bending moment equation, so you will put x is equal to 2.6, and then it will give you the maximum bending stress. Either you know that at this point x is equal to 0, shear force is 0, so bending moment stress will be maximum at this point. So how you will find? You will find it by taking the area under this shear force diagram. So which is equal to half of this distance, which is 2.6, and this height, which is 52, and that is 67.6. Once you get this maximum bending moment, the value of this maximum bending moment, so you will have to use the formula of minimum section modulus. So let me erase all these things. So you can see that VA is equal to this, and VA minus VB minus VA is equal to area under the load curve, which is minus 60 kN VB. All these things have been discussed, and we came to the point that at x is equal to 2.6, shear force is 0, and maximum bending moment is equal to area under the shear curves from A to E, and this was the area. This is a triangle, and the area is half of 2 into 52, which give you 67.6. Once you know the maximum stress, you know that minimum section modulus is equal to maximum bending moment divided by allowable stress, or maximum stress. So in this case, maximum bending moment is 67.6 kilonewton into meter, and maximum stress or allowable stress is 160 megapascal. So if you solve this and convert this into millimeter, so that will be 422.5 into 10 raised to power 3 cubic millimeter. So this is the section modulus, minimum section modulus required to be chosen. Okay, so from this section modulus, we will see either the table that is available at the end of the book of W or short beam flange properties, and we will choose the beam, or we will have to go to market and we have to choose the beam having minimum section modulus 422.5 or greater than this. Always remember that you have to choose, the minimum value is this one, so you cannot take the beam of section modulus less than this value. So you have to pick either this minimum value, or you can go above this value. It will be the safer beam. But if you select a beam with a section modulus less than this value, so obviously it will be not safe, and the beam can be failed. Clear? So let me show you the section modulus for for the beam. So this is Appendix C that are available at the end of big book. Also, you have to see whether this whether you are selecting a property a table having property in millimeters or in inch. So you can see here the properties are in inches. So you have to go toward the millimeter. So these are in millimeter. So the minimum section modulus was 422. So you have to select the minimum section modulus, that is 422. So you can see there is a value of 475. Let me zoom it. So there is a value of 475, that is W360 by 32.5. That is again maximum than 422. So you can select this value, you can select this, all this. Clear? Again, if you go above let me check again, 442 W10 W2442. So you can see this 416, which is less than, so you cannot select this beam. So you have to check. Also, one more thing is to remember, just like now I have explained that you can use where is it? So you can use this W32.9 W360 multiplied by 39, and you can also use, so you can use all the beams of section modulus above 422 are equal to 422. But remember that in wide flange beam, this W360 multiplied by the second term. So this first value show you the height of the beam. There, this is W360 means it 360 millimeter height, and the second value show you the weight per unit length. So this 551 is kg per meter. Clear? So it is also written over here, a wide flange shape is designated by letter W followed by the nominal depth in millimeter and mass in kilogram per meter. So again, this is 32.9 kg per meter, 39 kg per meter, and 44. So you have to note down all the values of this section modulus. One more thing is, if you look at the table, there is two values, that is Sx and Sy. Section modulus is about x-axis and section modulus above y-axis. So if you look at the orientation of beam, the x-axis will be this one. So let's see, this will be like this. So usually our beams are usually positioned in this manner. So if your beams are not like this, if your beams are like something like in this orientation, so let's say this, if they are lying in this orientation, so again in this sense, this will be your y-axis. So for that you will have to select Sy, but it is not mentioned in our problem, and we consider that beam are usually placed in this orientation, so that's why we are using the value of Sx. Clear? So from that you have to choose the value of section modulus equal to 422 or above. So in our case, I have selected the different values of the beam. So you can see from this figure or from this slide, you can see we have minimum S values, and we have choose different beams that have values equal or greater than 422. So this W410 by 410 multiplied by 38.8 is having section modulus 637 Newton to the power 3 cubic millimeter. So this will have 474, this and this and this. So in all this you can see its values are greater than 422, but we will select the minimum, or we will select the value of S that will have less mass, because as a design engineer you have to also check the cost parameters. So you have to select the beams that will be cheaper as compared to the other beam. So if let's say if you select this, so definitely its weight is 38.8 kg per meter. So if you select this, now it has lesser mass than this. So if you compare these two, so the best choice is this one. Again, you can go to this and this. Also you can check that from all these values, the lesser value of the beam weight per unit length is this one, 32.7. So if you look at this first and this both, this value is section modulus value is the lowest of all. So if this, now we will compare this 1 and 2. So from 1 and 2 we can see that this beam have lowest section modulus and even closer to 422, and this 474 is higher than 422. But if we compare both these two, so we can see that the second value, this is 32.9 kg per meter and this is 46.1 kg per meter. So obviously the weight of this wide flange beam will be very high as compared to this. So we will select this beam. At the end we will select this W360 into 32.9, and this is the best standard beam that you have selected, which meets your design criteria, i.e. the minimum section modulus will be greater than this, which is 474 into 10 to the power 3 cubic millimeter. So this is how we design the beam. Again I will repeat the I will conclude it that we will have a beam that will be under the given loading, and we have to ask to design the beam. So under the beam under the loading, we have to draw the shear force and bending moment diagram, or we have to only draw the shear force, and we by using the shear force we can see where the shear force is minimum or zero. So at that point maximum bending moment will occur. So we have to find out the maximum bending moment, and when you have maximum bending moment, so you will use minimum is equal to bending moment maximum divided by allowable, so it will give you the minimum section modulus. Then you will have to go to the property tables of the beams that is available in book at the end of book as appendix C, and you have to search for the minimum section modulus beam. So from that table you can choose more than beams, but you have to check that it should have lesser mass per unit meter. Clear? So among them you will have to choose a one beam, and that one beam with meeting the criteria of minimum section modulus and minimum weight per meter will be your design beam, and you can use them as per your required loading. So this was all about how to design prismatic beam. If you have any question you can ask in comment section. Thank you for watching. Again, if you like my video, kindly subscribe, like and watch. Thank you. Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you. Bismillahirrahmanirrahim. Welcome back. In today's lecture we will discuss singularity function used to determine the shear and bending moment, and this is the part 3 of lecture or chapter number 5, that is analysis and design of beam for bending. So we will discuss the last part of this chapter number 5. So singularity function used to determine shear and bending moment, the topic is that. In previous lectures we discussed how to find the shear force equation and bending moment equation by using the section methods. We have taken the section between any 2 points or loading, and we find the shear force equation and bending moment equation. There was another method
which is used to find these two equations are shear force diagram and bending moment diagram, and that was the relationship between load and shear force and bending moment. So these two methods were used to find out the shear force equation and bending moment equation, and then by using this equation we draw the shear force and bending moment diagram. While in singularity function, this function is used to represent the shear and bending moment by a single analytical function. So in this method we will have a single shear force equation as well as single bending moment equation, and that will be used to find out the shear force and bending moment, and with the help of this single equation we will be able to draw the shear force and bending moment diagram. So let's recall from the previous section we use the methods, that is for example if you use the section method, so you can see that we have sectioned the beam from A to C and let this distance was x. Clear? So this is represented over here, so this is the point of between this section. Clear? So there is a reaction force that is calculated as 1/4 W naught into A. So you can see this is a beam, simply supported beam, and from point C to B there is a uniformly distributed load. So first of all you have to find the reaction force at A and B. So now after too much discussion about this topic, you will be now able to find out the reaction forces and you will be able how to solve this equation. Here it is solved. The reaction force at point A is RA, which is 1/4 W naught into A, and if we cut the section at this point, so there will be a shear force V1 and a reaction bending moment at this point 1. This is M1 and this was XD. So from this section we can find the shear force and bending moment equation. Now here x is greater than or equal to 0 and less or equal to A, or its x is greater than 0 and less than A. So you can see that there is a reaction force V1 which is acting downward, so minus V1, and there is upward force plus 1/4 W naught into A is equal to 0. So V1 is equal to 1/4 W naught into A, which is written over here. Similarly, for bending moment equation, you can also find the bending moment equation like this. Now if we move at this point and section the beam over here, so it is also represented, and you must be able to understand that how all this comes out. So this is let's say this beam is cut at point A, so this will be your total x. Clear? So at point C this is distance A, which is again here, and this uniformly distributed load which was W naught is now you have to, this distance is total distance is x, this is A, so this will be x minus A. So if you convert this distributed load into a concentrated load, so you have to multiply W naught with this x minus A, and it will be at the center of, so this distance is x minus A, so it will be located at 1/2 into x minus A. Now from this section you can calculate V2x and M2x. So this will be the shear force equation for section 2, and this will be the bending moment equation for section 2, and you must be able to calculate this V2x and M2x if you have a clear understanding of previous lecture. So this is how we calculate the shear force equation and bending moment equation for section 1, and then at section 2 we calculate the shear force equation and bending moment equation. So now if you look for section 1, shear force for section 1 and shear force for section 2, the only difference is the second term, this minus W naught into x minus A. The rest is same. Similarly, if you look at the bending moment equation for section A and section 1 and section 2, so only difference is second term, that is minus 1/2 into x minus A whole square. So if this term is 0, or if this term in bending moment 2 is 0, so it will be equal to m1. So in section method we use to find out the equation of shear force and bending moment at every section, just like in section 1 and in section 2 we have different equation. Now in singularity functions that is used to determine the shear force and bending moment equation, we will see we will have a single equation for whole beam. We do not write V1, V2, or we will section them at 1 and 2. So we will only have one equation for the shear force that is used for the whole length of the beam, and we will have a bending moment equation that will be used for the whole length of the beam. So you can see that the equation of shear force for section 1 and section 2 will have only this term, second term, the difference is only second term. Similarly for bending moment for section 1 and section 2 will have only the difference of second term. Clear? So if we write the shear force and bending moment by using a single function, that is Vx is equal to 1 over 4 W naught into A minus W naught into this bracket x minus A. This is the same equation for V2. Clear? So instead of this I have parenthesis bracket, I have enclosed x minus A in this special bracket, and this is known as Macaulay bracket. Similarly, this bending moment equation is also represented over here, and this term is represented in Macaulay bracket, and this is square. Now if you see that if the second term is equal to 0, if we make this term equal to 0, it will be equal to V1x, which is 1 over 4 W naught into 4. Similarly, if this term is 0, then this moment will be equal to, bending moment will be equal to m1x, which is 1 over 4 W naught into A into x. You can see over here. Similarly, if this term is not 0, so it will be V2, and if this term, second term in this equation is not equal to 0, so this will be m2. So we have represented the shear force, single equation of shear force and bending moment for this beam, that is simply supported beam. So instead of separate equation, we just write a single function for shear force and bending moment, and this equation will be used to calculate the shear force and bending moment. Now you can see that the second term in each function is included in the computation, that is in Macaulay bracket. Clear? So when x is greater or equal to A, when x is greater than A or x is equal to A, so when x is equal to A, so this term will be 0. So, and when x is greater than A, so this term will be a positive number. Clear? Similarly, when this term, in this term, if x is equal to 0, x is equal to A, so this term will be 0, or if x is greater than A, so this term will, the second term will be a positive number. Clear? So it will be moment 2. So the second term in each function is included in computation when x is equal or greater than A. This will be included. This term will be included. But if x is less than A, if x is less than A, so the term in the Macaulay bracket will be negative, and anything inside the Macaulay bracket which is negative, so it will be neglected. We can assume that this is 0. So remember this, anything inside the Macaulay bracket, if it comes out to be negative, so we will have to neglect this or will be taken as 0. Furthermore, the same equation can be used for distributed load. So for example, in this case you can see you have a uniformly distributed load that is function of x. So you can write it also as W is equal to W naught into x minus A ki power 0. So this is W naught and this is x minus A, Macaulay bracket 0. Now this 0 represent the degree of, so you can see this is a uniformly distributed load is a constant value,
are a constant line, so that's why it is w is equal to w naught into x minus a ki power 0. So if x is equal to 0 or if x is equal to a, clear, so then w naught will be equal, this term will be 0. So if x is greater than a, so we will have a positive term and it will be equal to some positive number into w naught. So similarly, shear force and bending moment diagram can be written as can be represented as singularity function, and this w can uniformly distributed load can be written as a function of this term w naught into x minus a power 0. Okay, so we will move further. The expression x minus a Macaulay bracket power 0 or x minus a power 1 or x minus a power 2 are called singularity function for n is equal to or greater than 0. So you can see here n is equal to 0, here n is equal to 1 and n is equal to 2. Now what does this n is equal to 0, n is equal to 1, n is equal to 2 means? So let me explain this also. If n is equal to 0 means it is a 0 degree line. If n is equal to 1, it means it is a linear line. If n is equal to, it means it is a parabolic. You will have a clear understanding in next few slides. So this expression are called singularity function, and this is x minus a power n is equal to x minus a power n when x is equal to a or greater than a. So it will be considered. But if x in this term is less than a, clear, so it will be a negative number, and we have told you that anything inside the Macaulay bracket less than 0 will be considered as 0. Clear? So you will be see whenever quantity between the bracket, Macaulay bracket, is positive or 0, so you have to replace the bracket by ordinary parenthesis. So this anything inside this Macaulay bracket is either 0 or positive, so you can replace Macaulay bracket by using ordinary parenthesis. But whenever the quantity is negative, the bracket itself is equal to 0. So anything inside the Macaulay bracket that is a negative value will be considered as 0. We will now see the three singularity function corresponding to n is equal to 0, n is equal to 1 and n is equal to 2. So for example, if x minus a is inside the Macaulay bracket power 0, so what does it mean? It means that if you draw it on the graph, so this is your x direction and this is your load or n movement or shear force, anything can be on the y-axis. So let me show you. If you see this beam, you can see here is a load, here is a distance a, and then after that it is a. So you will now be able to understand this thing. So if x is, so from 0 to this is distance a, and after that it is, let's say, x. Clear? So if x is less than a, means if x is less than a, so this term will be negative number, and anything inside the Macaulay bracket that is negative will be considered as 0. So from 0 to a, this will be 0. There. Now if you move from further in from point A, now x is greater than a, so it will be a positive number, and if it is a positive number, so means it will be somewhat above, because on y-axis this is positive, so let this will be a positive. So this is, so from a to x this will be a positive. And why this is a constant line? Because the degree is 0, so it will be 0. So again I have explained this. If x is less than a, this region, so here it will be 0. Here it will be 0. If x is greater than a, so means from here it will be a positive number. Similarly, x minus a power 1. So you can again see if x is less than a, so this from 0 to
this distance x is less than a. So you can see anything that will be negative, so it means from 0 to a that will be a 0 because it will be a negative number. But if x is greater than a, so means this there will be a positive value and there is a power of 1, so means linear. So it means it is increasing linearly. This is how you can represent them. So if you understand this thing, so in coming problems you will be definitely it will be easy for you to understand further. Now x minus a to power 2. So again you can see from a region x is less than a, you can see this will be a negative term. So from this to this it will be a 0. So if x is greater than a, clear, so it will be a positive number, and this is there is a square, means that it will be a second degree, so it will be a parabolic. So this is these equations or these graphs will be used in coming problems, and you will see it in a little while. Now you can see there are some basic loading that is given, and their shear force and bending moment diagram is also given. So this is the, let's say this is your first column, that is about loading. The second column show you about the shear force, and the third column show you about the bending moment diagram. So in first case, if you see that this is the beam, and at a distance of length a, and at this point there is a moment m naught is given. So you can see if there is no shear force, so against its shear force equation will be like this, it will be 0. Clear? Now you can see there is a bending moment given over here. So if you use the equation x minus, this will be the x minus a power 0. So you can see the bending moment will be from 0 to a, it will be 0, and if x is greater than a, it will be any number, clear, negative, positive or negative, but that depend on the rotation of bending moment. So let's say this will be negative, clear, and it will be like this. And the bending moment equation, if you have the scenario like that, so you can use singularity function to find out the bending moment equation. So the bending moment equation is mx is equal to minus m naught into x minus a power 0. So if you can see, you can use directly this equation by, if you have the scenario like this. So if x is less than 0, so here the bending moment will be 0. For x is greater than a, so the bending moment will have some negative value, and you can write it over here. Now the second scenario of the beam, in which there is a concentrated load at a distance of a from point O. So you can see that we have the shear force equation. In such scenario, shear force equation Vx will be equal to minus P into x minus a ki power 0. So again, from x is less than a, so you see that this will be a constant line. For x is greater than a, so you can see there will be any positive number which will be multiplied by with p. So this will be your shear force diagram. For bending moment diagram, as you know that bending moment diagram is 1 degree higher than the shear force. So bending moment equation will be m of x is equal to minus p into x minus a power 1. And how we can calculate this bending moment equation? So if you integrate it on both sides, so the integral of this Vx will be equal to m of x, and this term will be equal to positive divided by 1. Clear? Again, if you use for this beam to find out its bending moment, so you can see that for x is less than a, you can see here there will be no bending moment, so it will be 0 till point A. For x is greater than a, you can see there is a bending moment, or this term is positive. So if this term is positive, so it will be power 1. So it means that, and it is negative means downward, so it will be linearly increasing. So if you have scenario like that, you can use singularity function for shear force, and bending moment will be like this, and from this you can draw the shear force and bending moment diagram. The third scenario is that you have the beam in which a uniformly distributed load W0 is given acting at a point, this point, and from distance from origin to the start of distributed load is given as A. Now you can see that this uniformly distributed load is a constant load, so its equation for load will be equal to Wx is equal to W0 into x minus a की power 0. That is given in this over here. Let me show you. This was the equation. Clear? So again this equation is used. Now for drawing the shear force will be 1 degree higher. So if you are confused, so you can integrate. So if you integrate this will be the shear force, and this will be, as it is acting downward, so minus W into this will be the power 1. Now for region x is less than a. Clear? So this term will be 0. For region x is greater than a, this will be a positive number, and if the load is power 0, so shear force will be 1 degree higher, so it will be like a linear line. Similarly, the bending moment equation for this loading is mx is equal to minus 1 over 2 W0 into x minus a की power 2. Now the shear force equation is the first degree equation, so bending moment will be again 1 degree higher, and it will be second degree equation. And how you can find it? You have to integrate it on both sides, so it will be again minus W into x minus a 1 plus 1 divided by 2, so it will be minus 1 over 2 W0 into x minus a की power 2. Again for x is less than a, so this term will be negative, so from 0 to a it will be 0. And from x is greater than a, so this will be a positive number, and it is 2 degrees, so it will be a parabolic, and it will be like this. So this table is used to find out the shear force and bending moment equation, or you can use this table for solving your problem if the scenario is like this or like this or like this. One more thing is that if the uniformly distributed at the load is closed, it means you have to close. If it's not closed, you have to close. You will see in coming problem as well. Now there is a fourth scenario in which you can see that this is uniformly varying load, a linearly varying load. The load is increasing linearly, and it is acting at a distance of A from point O. So again the load equation or the load equation will be Wx. Now here it will be equal to k into x minus 1 power 1, because it is a linearly varying load, so it's a linearly, so that is why it is 1, and k is the slope of this line. And what will be the slope? Slope will be equal to W0. This, let's say this is W0 and this is the base, so tangent of theta will be equal to W0 over this length, and this length is this slope is equal to k. It is equal to W0 over this length. For example, let's say this length is b, so it will be b. You will also see it in problem. So this will be the load equation, and you can see the load is 1 degree. So shear force again will be the 2 degree, and it will be equal to Vx is equal to minus k over 2 into x minus a power 2. So if this is confusing that how this shear equation comes out, so you have to take integral on both sides, and so you will get this shear force equation. Now for x is less than a, if x is less than a, so here this term will be negative and it will be equal to 0, and anything 0 will be equal, multiplied by 0 will be 0. So from 0 to a it will be 0. And if x is greater than a, so this will be a positive number and its power is 2, so it will be a parabolic. So this will be the shear force diagram. Similarly, bending moment for this beam will be 1 degree higher. The bending moment equation will be 1 degree higher. So again you have to integrate it, and the bending moment equation is equal to mx is equal to minus k over 6 into x minus a की power 3, because it is 1 degree higher. So for x is less than a, so this will be 0, and for x is greater than a, so it will be a positive number and it will be cubic. So this will be like this. The fourth scenario is that if you have higher degree load, so if this is load and this is higher degree, clear? So W will be equal to again K into X minus A की power N, where N defines the degree of load. It can be 2, 3 or anything. And for this shear force will be equal to Vx is equal to minus K over N plus 1, because if you take the integral on both sides, so it will be minus K over N plus 1 X minus A की power N plus 1, and the bending moment equation will be equal to minus K over N plus 1 into N plus 2 into X minus A की power N plus 2, and this equation can be obtained if you take the integral of shear force on both sides. Here we are discussing how to draw the shear force and bending moment. So you can see if X is less than A, clear? So this term will be negative, so it means this will be 0. So from 0 to A it will be 0. And if X is greater than A, this region, so it will be a positive number and it will be higher degree equation, and as it is negative value, so it will be downward. And the same is the case for the bending moment. For X is less than A, it will be 0, and for X is greater than A, it will be a some value, and it is higher degree, so it will be a like curve. One more thing, if you have a you have distributed load, so end of the distributed load should be closed. So while discussing or while solving a problem, we will show you why it is necessary to close the load, because we have to make our problem same as the scenario given in this table. So you have to make your diagram or figure with any of the scenario that is available, and you can use their shear force and bending moment equation quickly in order to solve and to find out the shear force and bending moment diagram. Now you can see there is a beam that is given in this scenario. So there is from point O to A there is no load, so at a distance of point A there is a uniformly distributed load which is W naught, and it is acting from this point to this point, and again the total length of the beam is L. So this scenario is totally different from the scenarios that is available in this table, clear? So what we will do is that we will close the uniformly distributed load till end. So if we close it like this, so again in this portion we have to give opposite uniformly distributed load, so that will be minus W naught because it is upward, and this will be whole W naught. So in this portion you have added and then given the reaction distributed load. So you can see that it will be like this. The beam is now equivalent to this. You can see that load is from A till the end, and from there is a distributed load given below which is minus W naught, and it will be from at a distance of B from the origin, and it is a distance from. So now you can apply this scenario on the beam. You can use this equation of shear force and bending moment on this beam in order to quickly solve and to find out the shear force and bending moment diagram. In coming problem we will see how to tackle this problem, but also remember there will be a reaction forces at the end, and you have to consider this as well. Sample problem 5.9. The statement is given that for the beam and loading shown, determine the equation of defining the shear and bending moment at any point, and the second part is shear and bending moment at points C, D, and E. So this is the beam and the loading is shown. This is a simply supported beam with a uniform linearly varying load from point A to C, and then uniformly varying load that is decreasing from C to B. So it is given in part A that you have to find an equation that determine the shear and bending moment at any point. So you have to find out the shear force equation and bending moment equation, a single equation. So to find out the shear force and bending moment at any point. So definitely there will be a single shear force equation and bending moment equation from which you can find out the shear force and bending moment at any point in the beam. Again, note that there is nothing given to solve this problem using singularity function, but it is given that you have to find out a equation for bending shear force and bending moment in order to find the shear force and bending moment at any point. So definitely we will solve it by using singularity function. Next point is that if we get the shear force and bending moment equations, then we can find out the shear force and bending at point C and E. So let's solve this problem. First of all, for solving this problem, you have to find out the reaction forces at point A and at point B. So RB and RA, you have to find this, and you must be able to know how you will find the reaction forces at point B and point A. So I will just give you a clue that you can see that this is a uniformly varying load from point A to point C. Again, if you want to convert it to concentrated load, so it will be equal to half of W naught into its total length, and the total length from point A to point C is L by 2, because L by 4 plus L by 4 is L by 2. So this concentrated load will be acting, let's say, at this point. So and this will be equal to 1 over 4 W naught into L. Similarly here it will be again the same, and this will be this linearly varying load will be converted into half of 1 over 4 into W naught into L. So now you have the beam like this. This will be the reaction forces. This will be a concentrated load, and this will be again concentrated load. It is 1 by 4 W naught into L, and it is also 1 by 4 W naught into L. The length is given 1 by L by 2, and again the length is given L by 2. Now you can use the equilibrium conditions to find out the reaction forces at RA and RB. So when you solve it, so your RA will be the same, that is 1 over 4 W naught into L, and RB will be also 1 over 4 W naught into L. After finding the reaction force, you will use singularity function in order to find the shear force equation and bending moment equation. So these are the same things. So let's solve this. You can see the reaction force is represented as 1 over 4 W naught into L, and the reaction force at point B is 1 over 4 W naught into L. Again, if you look at the figure, so this scenario is also not available in this loadings. The only scenario is available like that. So you have to close this triangle. So you have to extend it in order to close it. So it is, let's say this was L by 2. So again you have to close it through again L by 2. So if you take it to this point and close the load, so W naught is up till L by 2. So 2 W naught will be for whole length, for this total length of the beam. So let's say we will convert this like this, and again
from this point you will have to given opposite. This will be also 2W naught, but it will be positive because it will be upward in order to cancel the effect. Now you can see we have converted this loading into this type that is shown over here. Initially it was like this. We have extended W naught to total length, which is equal to 2W naught, and there is this has been converted to this, which is shown above. Now you can see the scenario is available in the loading. So this is the same scenario. So this loading, at this loading, if you go back to this same thing. So for first loading, the A will be 0 for above, and for the below it will be, for this loading here A will be equal to 0, and for this loading this A will be equal to L by 2. Again, if you look, let me write again this thing as well. For this loading we can see that shear force equation is equal to minus K by 2 into X power 2, X minus A power 2. So let me write it minus K over 2 shear force is equal to minus K over 2 into X minus A की power 2, and the bending moment will be equal to minus K over 3 into X minus A की power 3. Let me confirm it as well. Oh, this is minus 6. This is minus 6 because if you integrate it, it will be 3 divided by 3, which is 6. So now we will use this equation. So in this case you can see K, we will find K for this as well as K for this. So slope for this line will be equal to this height, which is 2W naught, and divided by 2 base, which is length. So slope for this will be 2W naught over L, while slope for this will be equal to 2W naught divided by this length, and this length is L. So this slope will be equal to it is like this. So that is minus 2W naught divided by L by 2, which will be equal to minus 4 into W naught by L. So slope for the upper line K1 will be 2W naught over L, while K2 for this will be 4W naught into divided by L. So we will use this shear force linearity equation and bending moment to find out the shear force equation and bending moment equation. So you can see that as Vx is equal to minus K over 2, let me erase something so that it will be easily visible. So again you can see that this V shear force for this scenario will be equal to minus K over 2 into X minus A whole square for this loading, and this will be minus K over 2 into X minus A whole square. Now for first scenario, A will be equal to 0, that will be minus K over 2 into X minus A is if A is equal to 0, so it will be X whole square minus K over 2. In this scenario, this A will be equal to L by 2 for this loading. So that will be X minus L by 2 whole square. Again, this K is equal to 2W naught over L, so that will be equal to minus 2W naught divided by 2L into X square, and X square minus K over 2. This K2 will be, let me write its value, it will be minus W naught over L into x minus L by 2 whole square. So this is the shear force equation for this beam. Similarly, you can also find out the bending moment equation for this beam. Let me show you this. Let me clear this all these values. So you can see that now the beam will be this. This is how this load has been converted into this. Now the actual beam will have a reaction forces at both ends as well, and the beam is transformed into a new type of loading. Always remember that we will take the reaction forces or any forces that is available on the left side, because on right we start drawing the sections or we move from the left side to the right side. So anything on the right side will be neglected. So the loading equation for this type of beam, again if you move back, I will also clear this so it will be easy for us to move quicker. Erase all. So you can see the loading equation for this uniformly linearly varying rod is Wx is equal to k into x minus 1 power 1. So it is the same. This Wx will be equal to, for upper loading it will be k1 into x minus, let me write Wx is equal to minus k, it was minus, or it was positive in the equation. Let me show you, it is positive. So that is equal to k into Macaulay bracket x minus a ki power 1. So this was the general equation. Now there are two loadings, so that will be w into x, k into x minus 1 plus k into again x minus a ki power 1. So for this first loading, a will be equal to 0. So that will be equal to k1 into x minus 0 power 1 plus k2 into x minus, for this loading a will be L by 2. So that will be x minus 1 over 2 L power 1. So x minus 0 is equal to x, and power 1 will be equal to k1 into x, and the slope of this was 2w naught over L. So this will be 2w naught over L into x plus k2 is minus 4w naught over L into x minus 1 over 2 L. So this will be the loading equation. Then we will move toward the this is further simplified. So that is 2w naught L over x. This is the same which I have written, and that is minus w naught over L into x minus L. This is the loading equation for the given beam. Again, the shear force equation will be, I have written again, that is Vx is equal to minus k over 2 into x minus a ki power 2. Let me check it. The shear force k minus k by 2 into x minus a ki power 2. Again, so for both the load, again initially neglect this. So this is for concentrated load. There is a concentrated load at the start as well, so we have to encounter it as well. So Vx minus V0 is equal to minus W naught into L, W naught over L into x square minus 2 W naught over L into x minus 1 over 2 L whole square. So this was the general equation for the shear force. So if you use the second term, so that is also minus k over 2 into x minus a whole square. For the first loading where where a is equal to 0. So if you put a is equal to 0, that will be minus k over 2 into x square, and that will be minus k over 2 into x. X will be here, x minus A will be L by 2, which is x minus L by 2. Similarly, if you put the value of K, which was 2 omega naught over L, and K2, which is minus 4 omega naught over L. So if you solve this, so this will be minus W naught L over L into x square minus 2 W naught L into x minus 1 over 2 L square. Again, shear force at this point is 1 over 4 into W naught into L. So you have to take it as well. So when it will go to the right side, so it will be, this term will for the linearly varying load, and this will be a concentrated load. Again, if you do not want to write V naught, so you can write the equation for this, and at the last you can also use the shear force equation for the concentrated load. So you can see, let me show you it as well. So you can see load for the concentrated is minus P into x minus A ki power 0. So at that condition where the load is at this point, so A is equal to 0. So it means x minus 0 is equal to x, and x anything power 0 is equal to 1. So in that condition Vx will be equal to minus P, and the P was minus 1 over 4 W naught into L. So we have written minus W naught, so when it moves minus 1 over 4 W naught into L. Again, so since the force is positive, so you have to take it positive. So that's why if you do not interested to write it as V naught, so you can at the end you can place its function for the shear force for concentrated load. Also, the shear force at this point A, the shear force will be 1 over 4 W naught into L, but the moment at this point will be 0, and the moment will vary if you move along the length of the beam. So this is the shear force equation for the beam as shown. Similarly, the bending moment equation can also be found, and you know that the equation of bending moment will be equal to minus K over 6 into x minus A ki power 3. That is given, or that is taken from this loading. Minus K over 6 into x minus A ki power 3. So you have, this is for loading 1, and this is minus K over 6 x minus A ki power 3 for loading 2. For loading 1, A is equal to 0, so that will be equal to minus K over 6 x cube, and for loading 2, that is x will be L by 2. A will be L by 2. So L by 2 ki power 3. And again, if you put the value of K for first loading, that is 2 W naught over L, and K2 is minus 4 W naught over L in this equation, so it will be the same like this. Also, you can see due to this concentrated load at point A, the moment equation will be minus m naught into x minus A power 0. So if A is equal to 0, so mx will be equal to minus m naught into x power 0, and x power 0 is equal to 0. X power 0 is equal to 1, so mx will be equal to minus m naught. Clear? And this m naught will be again, sorry, I have used this, not this. You have to use this equation because the bending moment for the concentrated load is minus px, so do not consider this. So A is equal to 0, so it will be m of x will be equal to minus p into x power 1, and x power 1 will be x, so and p was 1 over 4 W naught into L and x. So movement due to concentrated load when you move from this point, from this point will be 1 over 4 W naught into Lx. So if you put all the values, so mx will be equal to minus m naught. This is the moment due to the concentrated load, and that is equal to, if you put the k1 and k2 over here, so this equation will be like this. Clear? The moment at point 0 is equal to 0, and the function of movement due to concentrated load is this. Clear? Which is given at the end. So mx will be equal to this equation. So this is the single bending moment equation for the loading, and this is the single shear force equation for the loading. And this is drawn, but before drawing this, let me clear that we have solved our first part of the problem, that is to define a single equation for the shear force and bending moment, or the equation from which we can find out the shear force and bending moment at any point in the beam. So you have to put the value of x at any point of x. You can calculate the shear force and bending moment. So this was the first part. Now for second part, in second part we have been asked to find out the shear force and bending moment at point D, at point C, at point E, and at point B, because C, D and E are given. So we will now look into that. So this was the basic equation. Let me delete all this thing in order to have a clear visibility. So this is the shear force equation and this is the bending moment equation. Now for shear force at point C, for example, so C is at a distance of L by 2. So if you put L by 2 over here, clear? So this L by 2 will be cancelled with this, so this term will be, the second term will be 0, and here similarly the second term will be equal to 0. So again, sorry, not here, this is the single equation. So this will be 0 and the remaining is given over here. So you can see at point C, if this will be 0 and if this will be minus W naught L square over 4L, and this is 1 over 4 W naught into L. So if you calculate or if you simplify, it will be minus 1 over 4 W naught into L, which will be cancelled with this. So shear force at point C is equal to 0. Similarly, bending moment at point C at L is equal to 1 over 2. So if you put L 1 over 2, so this term will be equal to 0, and the shear force, bending moment equation will be this, and if you further solve it, so bending moment at point C will be this. Similarly at point D, now you can see that point D is at a distance of L by 4, which was given earlier, so L by 4. So if you put, let me again erase all. So now for x at point D, this distance is L by 4. So if you put L by 4 over here, so if you subtract L by 4 from minus 1 over 2, it will be negative value, and anything inside the Macaulay bracket which is negative will be considered as 0. Similarly, this term will be also 0 in the bending moment, and when you solve this, so you will have shear force at point D and at point B, and bending moment at point B as this. At point E, if you put x is equal to 3 by L, so definitely this value will be positive, this will be positive, and this, and again this. So if you solve this, so the bending shear force at point E will be this, and the bending moment will be this. Now you have to plot them on the shear force. So at point A, you can see there was a shear force which is 1 over 4 W naught into L. Clear? Let me show you at point A there is a shear force. Now at point C, at point D, C and E, you have to determine this. So let's start with point C. So at point C, you can see that shear force was 0. So shear force at this point 0. At point D it was 3 over 16 into W naught into L, which is a positive value, and if you plot it, it will be like somewhat here. And as this shear force is second degree equation, so it will be a curve in the clockwise direction. Similarly, at point E, this is a minus 3 over 16 W naught into L. So this is 3 over 16, so again this will be minus 3 over 16, and you have to locate this. And at point B, the shear force will be the same as the 1 over 4 W naught. So you have to join them, and this will be a second degree curve or parabolic, and it will be like same. So this is the shear force diagram for the. So at point D you have calculated the shear force, at point C it is 0, and at point E it is minus 3 over 16 W naught into L. Now for bending moment diagram, as we know that at point A shear force is 1 over 4 W naught into L, but at point A there is no bending moment. At point D the moment is a positive value, which is 11 over 192 into W naught into L, as it is general. So if you have W naught and L square value, you can made it precisely. So at this point, from point A to C, it will be again a curve here, because it is cubic, so it will not be a straight line, it will be a curve. Again it will be a curve. At point C, you can see at point C the moment is greater than point D, 1 over 12 and 11 by 192. So this value is greater, so it will be above. So if you plot it, it will be somewhere at point C, it will be like this. Again this is a cubic, so it will be curve. Now at point E, the load is minus 3 over 16, and it is at point E, this is ME, which is 11 by 192, and it is same as D. So you can easily take this point. You can easily, let me choose the marker. So at point at point D and E, they have the same, which is 11 by 2. So you can project that point, and this will be your bending moment between point C and D, which is cubic. And similarly at point D, there will be no shear force, so it will be 0. At point B, there will be 0, and this will be also a curve. So this is the shear force and bending moment diagram, and we have calculated the shear force at point D and bending moment at point D, shear force at point C and bending moment at point C. Similarly, the shear force at point E and bending moment at point E. And these are the value of shear force and bending moment at their corresponding points. I hope you have enjoyed the videos. Now it's your duty to solve problem 5.108 and problem 5.104 on the basis of singularity function. Thank you for watching the video. If you like the videos, kindly subscribe, like and watch. Thank you. Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you. Bismillahirrahmanirrahim. Dear friends and students, today I will teach you chapter number 6, and the topic is sharing stresses in beam and thin wall member. I have divided this lecture into different parts. So let's start with part number 1. The course content of this lecture is that in this lecture we will discuss the introduction, then we will discuss share on horizontal face of beam, and then example 6.01. So these are the course content of part first of this
lecture. In previous lecture, chapter number 4 and 5, we have studied that if you have a beam and that beam is subjected to movement, and this movement is like that, so it will, and let's say the length of beam is, original length is L0, so it will bend like this. Clear? So the upper portion is in compression while the lower portion or lower surface in tension. Similarly, we have also studied that there is a axis which is known as neutral axis, which do not contract or extend, and the length of this neutral axis will remain same as that of original length. Clear? So the length below the neutral axis increases, and the length above the neutral of the surface of the above the neutral axis contracts. And we have also derived the equation that m sigma max is equal to mc over I, where m is the bending moment, c is the distance from neutral axis to the topmost or bottommost surface, I is the second moment of inertia. Similarly, we can also have equation my over I, that is minus, and this y is variable distance from neutral axis to the outermost, and this y is greater or equal to 0 and less or equal to c. So in this lecture, we find out how to calculate the maximum stresses and how to find a stress at any point above or below the neutral axis. Then in chapter number 5, we discuss how to find the shear force diagram and bending moment diagram. In this chapter number 5, we discussed how to find the shear force equation, and then how to draw the shear force diagram, and then how to find the bending moment equation, and then we derive the bending moment diagram. From this shear force diagram and bending moment diagram, we find out the maximum bending stresses and maximum shear forces, because we studied that along the length of the beam, the shear force and bending moment varies. So in how to find the maximum bending moment that is acting on the beam throughout the length and shear force, we discussed that, and we found how to calculate the maximum shear stress and bending stresses in the from the shear force and bending moment diagram, and how to calculate the maximum bending moment as well. Also, you know that whenever, let's say, we have a beam and that beam is applied with a load P, and this load is a transverse load because it is acting perpendicular to the axis of this beam. So if you cut the beam at any section, so definitely there will be a shear force that will be acting downward, and there will be a movement. Clear? So this shear force is vertical shear force. Now in this lecture, in today's lecture, we will discuss that due to this force, there are always shear force in horizontal exist as well, because you can see here that in this beam, if we divide it into layers, so each layer will slide over each other. So sliding of this layer over each other means that there exists a shear force, and that is known as horizontal shear force and represented by H. So in this lecture, we will discuss in detail how to find these horizontal shear forces or horizontal shear stresses. So previously we have studied that this was the beam that was sectioned at any point. So and this beam was acted upon by a movement. So if we slide, if we take a section of the beam, so definitely for transverse loading there will be a shear force that will be acting at this point, that is represented as V, and there will be a bending moment M. This is the
this x is the direction of the beam length. This x is in the direction of beam length. This is y is in height and z is in this direction. Clear? So from chapter number 4, we have find out that this is the movement that is acting in this xy plane or in z plane, movement about the z plane. And if we take a small differential area over this surface at a different points, let me zoom it as well. So if you take the small differential area, so we find out that there is a normal stress that is acting, and this normal stress is sigma x into dA. Also on any phase there are three forces acting. One is normal and two is the shear force. So one is this force that is acting in x direction and represented as sigma x into dA. The second force is in z direction. And similarly, if this is the small differential area, so in this direction this is tau of xz, shear force acting in the direction of z, and this is the x plane. This surface is in x plane. So there will be a shear force that will be tau of xz. Also there is a force in shear force in y direction, and this is represented as tau of x y, and that is shear stress that is acting in y direction. If we multiply these stresses with the differential area, we will get the normal stress in x direction, shear stress in y direction, and shear stress in z direction. This force is tau of xz into dA. All we have discussed these things. So transverse loading applied to a beam result in normal and shear stresses in transverse section. Distribution of normal and shearing stresses satisfies all these 6 equations of equilibrium. In previous we only discussed the sum of all forces acting on x direction is equal to 0, and the sum of all movement about the z direction is equal to 0. Clear? Now you can see if we apply these equilibrium equations on this surface. Sum of all forces along x direction must be equal to 0, and only force that is acting along the x direction is sigma x into dA. So if we integrate it over the surface, so total net force acting on this face and the force acting in x direction will be equal to integral of sigma x dA is equal to 0. Similarly, then in the direction of y there are forces, shear forces that is acting, and that this force is tau of xy into dA. So if sum of all forces along y direction is not equal to 0, because it is the net shear force that is acting in this direction. So this Fy is represented of integral of tau of xy dA, and it is equal to minus v because it is acting downward. So on this phase there is a shear force acting which is acting downward. Clear? So this shear force, the net of this shear force will be the net shear force. Similarly, in z direction there is also shear stress acting. So sum of all the forces along z direction will be equal to 0, because in this diagram, if I remove these things from this figure, so you will find out that there is only shear force acting downward. So that's why sum of all forces along y direction will be equal to the net shear force acting on this face. Similarly, if there is no force in x direction, therefore the sum of all force along x direction is equal to 0, and there is no force acting in z direction, therefore sum of all forces along z direction must be equal to 0. So if you take the integral of tau xz into dA, it must be equal to 0, because there exist shear stresses along the z direction, but their net effect must be equal to 0. Also, you can see that this movement
along the moment that is produced due to this normal stress, which is equal to sigma A, and perpendicular is distance is z. So moment about this y-axis is equal to integral of sigma x dA into perpendicular distance z, and that must be equal to 0, because we have studied that this is the plane where this moment, net reaction moment, is applied, and this y-axis and x-axis are lies in that plane. So if a moment is applied on a plane and the axis that is contained in that plane, so moment about that axis will be equal to 0. So moment about y will be equal to 0 and moment about x will be equal to 0. But you can see this moment is about z-axis. Clear? So it will be equal to, it will be not equal to 0, it will be equal to m. Here it is written as 0, but it's wrong. It will be m, because we have studied it earlier. Similarly, the stress is the moment produced due to the shear force in x direction is mx, and that is equal to, you can see this is in x direction, shear force is in x direction, in x plane. This is the shear force in y direction, and both are acting in x plane. So moment about x-axis will be integral of tau of xz into y minus z into tau of xy dA is equal to 0, because you can see that this is the force which is tau of xy into dA, shear stress force, and it is acting perpendicular to perpendicular distance from x-axis is z. So it will tend to rotate it in this force, that this force is acting like this. So it will tend to rotate in clockwise direction. So that is, it is why minus z into tau of xy, clear, into dA. And similarly, this shear force in z direction, tau of xz, is also producing a moment about this axis, and this is the tau of xz, and perpendicular distance from this x-axis is y, clear, and it is producing a clockwise counterclockwise movement. That is why y into tau z into dA, and their sum must be equal to 0, because we have already discussed that this axis lies in the plane containing moment. So moment about x plane will be equal to 0. Therefore, we have written that mx is integral of y tau of xz minus z into tau of xy into dA is equal to 0. Similarly, moment about y-axis will be also 0, and the only moment produced by about y-axis is due to this normal stress, and that is equal to 0. Similarly, moment about z is equal to net moment that is given over here as m, and it is equal to integral of minus y into sigma x. All these things have been discussed earlier also. Now you can see there is a shear force acting on this face, and this shear force is given over here, and that is tau of xy, because this plane is x plane and this shear stress is acting in y direction, so that is why tau of xy. Now there is a shear stress on this surface, so obviously there will be a shear stress on the other side of the face, clear, and by this you can see that this force is upward and this shear force is downward, so it tends to rotate this section in clockwise direction. So in order to counter react, or in order to make the equilibrium, these are the perpendicular faces, so the horizontal faces are vertical faces, so there will be also a shear force in horizontal faces, and this horizontal stresses will also produce a counterclockwise effect in order to keep it in equilibrium. So when shearing stress are exerted on the vertical faces of an element, so this was the
shearing stress that is acting on the vertical faces. Equal stresses must be exerted on the horizontal faces. So the same shear stress will be also exerted on the horizontal faces in order to keep it in equilibrium condition. So longitudinal shearing stress must exist in any member subjected to transverse loading. So again, these are longitudinal stresses, and that is acting in horizontal direction, and these are the shear stress due to transverse loading, and that is acting on the vertical faces. So this sentence is saying that longitudinal shear stresses must exist in any member subject to transverse loading, that if any member is applied with transverse loading, so definitely there will be a longitudinal stresses on the horizontal faces. Also, it is given in the book, you can see this is the top xy, so this will be the same as tau of yx, and it is also derived in the book that this tau of xy is equal to tau of yx. Similarly, again, if you have tau of xz, that will be equal to tau of zx. So if you have tau of xy is equal to 0, for example, so you can consider that the longitudinal stress on this horizontal face is also 0. If this is 0, vertical is 0, so it will be also 0. The next topic is shear on horizontal face of the beam. So you can see this is a simply supported beam, and that is acted upon by load. P1 is concentrated load, P2 is also concentrated, and W is uniformly distributed load. The cross section of the beam is shown here. This is, you can say, the side view of the beam. If you find out the horizontal shear force, so we take out a section that is under the uniformly distributed load. The beam is shown in this. Clear? Let this, the neutral axis is in longitudinal direction. Clear? That is longitudinal axis defined in this axis, in this section of the beam. Now, for our analysis purpose, we are going to take out a small portion of the beam, that is portion C, D, C dash, D dash, and the thickness of this portion is represented as delta x. Delta x is very small thickness. Clear? So the lower portion of this portion C, D, C dash, D dash, the lower face is at a distance of y1 from the neutral axis, and similarly the outermost surface or CD face is at a distance of C from the neutral axis, because C is the maximum distance from the neutral axis to the outermost surface. Clear? So we will find out the horizontal shear force. So if we separate this portion CD, C dash, D dash from this beam, so there are the forces that is acted upon on this portion. So as this beam is under the distributed load, so definitely there will be a distributed load W that will be acting on CD. Clear? Also, when you section the beam over these sides, so definitely there will be a shear force VD at the point D or at the face D, and there will be a shear force at this face C dash. Clear? Now remember one thing, that whenever a beam is subjected to transverse loading, so there will be a shear force at the cutout section, and there will be a bending moment. Clear? So in this case the shear force is represented, but bending moment is not represented over here. And also we know that bending moment is equal to my over I. Clear? Where m is the bending moment, y is the distance from neutral axis to the any point where you want to find the stress, and it's a variable, and I is the second moment of inertia. So instead of bending moment, we have represented the bending moment in terms of bending stress. So at point C, this bending stress will be equal to mc y over I, and at point D, the stress will be md y over I. So instead of showing the moment, we have represented the stresses on face C, C dash and D, D dash. Clear? Now you can see that this stress is the linear function of this y. So when y is maximum, means when y is maximum, or when it will be maximum, when it will be at this point. Clear? So stress will be maximum. Similarly, when y is decreasing, so stress is decreasing, and it is represented here in this figure. So the stress at phase C will be sigma C, and stress at phase D is sigma D. And generally we are finding out the horizontal shears, so we will convert this stress into force. So when you multiply this stress with their areas, differential area dA, so you will get the horizontal normal force. Also, when you slice or when you separate this section from the beam, so there will be a horizontal shear force that is represented as delta X, and we are interested to find out delta H, or horizontal shear force. So how we will find out this shear force? So we will apply the equilibrium condition, that sum of all force along x direction that must be equal to 0. Now you can see there are forces. One is horizontal force, and two are the horizontal shear force, and two are the normal stresses that are acting on this beam, or on this portion of the beam. So we will see there is a delta H force that is acting again, plus we have integral of sigma C minus sigma D into dA force that is acting over the area A. Their sum must be equal to 0. One is sigma C. Sigma C is acting in positive x direction, and sigma D is acting in negative direction. And we have integrated in order to find the net force acting on this face and this face. Clear? Now we know that delta H will be equal to delta H plus, it will be equal to integral of, instead of sigma C and sigma D, I will write mCyi over mCy over I, and minus md y over I, multiply by the differential area is equal to 0. Clear? So you can see y is common, so we can write them as delta H plus integral of mc minus md over I into y dA, that is equal to 0, and this integral over area A. Now you can see this is the constant term. mc is constant, md is constant, and I is constant, so we will take it out of the integral. So it will be mc minus md over I into integral of y dA is equal to 0 over the area. As y is variable, its value is changing from the neutral axis, so we cannot take it out of integral. Clear? Now we know that this integral of y into dA over the entire area is known as first moment of inertia, and it is represented as Q. Clear? So we will put the value over here. So delta H plus mc minus md divided by I into Q, that will be equal to 0. Clear? Also, we know that MC minus this delta H will be equal to, when it will move to the right side, the equation will become MD minus MC divided by I into Q. So we will use this equation further to carry out to find the horizontal shear stress. Okay, so this was the equation for horizontal shear force. Now we will move forward. As you know that this MD minus MC, the term, this term MD minus MC is actually that is equal to delta M. So if you divide both sides of the equation by delta X, and delta X is a thickness of the section, clear? So this equation will be MD minus MC over delta X is equal to delta M over delta X. So this MD minus MC will be equal to delta M over delta X into delta X. If this distance is very small, if delta X is very small, so we can write it as dm over dx into delta X. So MD minus MC will be equal to this term. So we will put the value of MD minus MC in the equation that we have derived here, that is delta H is equal to MD minus MC over I into Q. So we will put the value over here. So delta H will become equal to dm over dx, clear, into Q over I, clear. So now from our previous lecture in which we discussed the relationship between the bending moment and the shear force, so we wrote that dm is equal to V into dx, or dm over dx is equal to shear force. Because shear force is 1 degree lesser than the bending moment, so we take the derivative of bending moment in order to get the shear force. So if you have bending moment equation, so you can take the derivative. After that, the resultant equation will be the required shear force. So instead of dm over dx, we can also write delta H is equal to VQ over I. So delta Q is equal to Vx into I. Also, one more thing is that in MD minus, if we put the value of MD minus MC over here, so it will be dm dx into delta X. So again here this will be V, this is Q, and this is V, this will be delta X. So this is the equation for finding the horizontal shear force. Now there is another term that is represented as Q, and this Q is equal to shear flow. How we define shear flow? The shear flow is equal to shear stress over unit length, or length. So if you have shear force, horizontal shear force as VQ into delta X over I, and the length is also, length or the thickness is also delta X, so shear flow comes out to be equal to VQ over I. This is the by shear flow we means the shear per unit length, that how much the shear force acting on a unit length or length is known as shear flow, that is equal to small q. Clear? Okay, so this is the same thing. You can see all the derivation, delta H, Q, then MD minus MC, which is equal to V into delta X. Clear? And when you substitute, you will get the horizontal shear force and then shear flow. So this was all that about how to find the horizontal shear force on a beam element. Now the same thing is that we have discussed that this horizontal shear force that is acting here is delta H, and this delta H was calculated as delta H was equal to Q into delta X, and Q is equal to VQ over I into delta X. Clear? Now, and this is the shear force that is acting on face C dash D dash. Now, if we take the remaining portion, let me show you this thing. If you take the remaining portion of the beam section and you want to calculate the shear force on this, clear? This is the portion that is shown C dash D dash divided over C double dash and D double dash, and you can take it as for your analysis, and you will come to know that same horizontal force here it is represented as delta H. So in this section or on this face C dash D dash, because it is C dash D dash, same horizontal shear force will be acting, but it will be in opposite direction, and this will be delta H dash. So this delta H will be equal to minus delta H. They are the same, but only direction will change. Similarly, this Q is the first moment of inertia about y1, and I is the second moment of inertia, which is equal to integral of y square dA A plus A dash. A is this area and A dash is this area. Clear? And same result found for lower area. The shear flow will be also minus Q dash. We will solve a problem in which you will further learn how to find out the shear force in beam or in any portion of the beam. So you can see example 6.01. In this problem, a beam is made of 3 planks nailed together, knowing that the spacing between nail is 25 mm and that the vertical shear in the beam is 500 Newton. So determine the shear force in each nail. So these are 3 planks. This is 1, this is 2, and this is 3, and they are held together by nails. Clear? You can see over here, these are the nails. Clear? And the shear force is given as V100, and you have to determine the shear force in each nail. Also, it is given that the distance between the nail is 25 mm. So if I draw it in 3-dimensional, so you can see this is the beam. So there will be one nail, there will be another nail. Throughout the length of the beam, they are held together by nail, but it is given that distance between the nail is 25 mm. So this distance is 25, this distance is 25 mm. So this distance is actually delta X. Clear? Also, you can see that this is the nail and this is the first plank, and there will be a second plank. So the shear force will be horizontal shear force will be acting over this area of the nail where both planks are meeting. So we will find the horizontal shear force in the nail. So let's start with the solution. As we know that delta H is equal to Q into delta X, and Q is equal to VQ over I into delta X. So first we will find the shear flow, which is Q is equal to VQ over I. When you will find the shear flow, then you will convert it into horizontal shear force. So we have shear force value, we do not have Q, we do not have I. So for that we will calculate first Q. As we know that Q is the first moment of inertia, and this is represented as Q is equal to A into Y dash. Now what is A? A is that area which is above the horizontal shear force. So at this joint there was a horizontal shear force, so above that area is actually A area. Clear? And this area is 0.1 meter into 0.020 meter. Also one thing, that all the dimension of the beams are shown over here that are in millimeters. So we have converted them into meter in order to have consistency in our units. Clear? So this is thickness of the flange. This is the total, this is the thickness of flange. Similarly, the lower flange will also have a thickness. Total height of the beam is 140 millimeters. Thickness of web is also 20 mm. Clear? Now, what is Y dash? Y dash is actually the distance from neutral axis to the mid of this area. Now, the mid of this area is this. Clear? And distance from neutral axis to mid will be this. And what is this distance? So if you look, the half of it will be 0.010, and the half of this from this to this is 0.050. So 0.050 plus 0.010. So total distance will be 0.060 meter. So when you put the value, area is this one and Y dash is this one. So it will give you the first moment of inertia for this area. Clear? Now we have to find the second moment of inertia for this beam. So you can see these beams are comprised of 3 planks. Now plank 1, upper and lower plank, it is represented as 1. Both have the same breadth and thickness, and this is 2. This plank 2, the middle web is plank or portion 2. So we know that moment of inertia for this beam will be equal to I2 plus 2 times of I1, because the moment of inertia of this 1 and 1, that is 2 times, plus the moment of inertia of this 2. So by using this equation we can find out the second moment of inertia of this beam. Also you know that moment of inertia for rectangular beam is equal to, or rectangular section is equal to 1/12 BH cube plus AD square. Now B is breadth, H is equal to height, A is the area of that section, and D is the distance from neutral axis to the centroidal section, the section centroid. In our case, for second portion of the beam or web, you can see that neutral axis is passing through centroidal section of this part 2. So D will be equal to 0 for I2. So we will calculate I is equal to I2 plus 2 times of I1. Now 1/12, what is B of I2, which is equal to 0.020, and total height is 100 millimeter, that is 0.100. So 1/12 B, and this is H cube, plus, as D is equal to 0, so the remaining term will be 0, plus 2 times I1. Now what is the moment of inertia, second moment of inertia of I1? That is equal to 1/12 B. What is B? B is this distance, which is mentioned over here. And what is height? Height is this thickness, which is 0.020. So 1/12 BH cube plus AD square. Now what is the area of this? It is 0.100 into 0.020. That is written over here. And D square. D is the distance from neutral axis to the centroidal section centroid. So section centroid, it is 0.060. So all the values are now available. You can, if you calculate them, I will be equal to 16.20 into 10 raised to power minus 6 meter 4. Now we have V, we have Q, we have I. So you have to put the values. When you put it, you will have Q is equal to 3704 Newton per meter. So this is shear flow. In order to find the horizontal force delta H, so delta H will be equal to Q into delta X. So Q is also available, and delta X is the distance between two consecutive nails. So here they have represented horizontal shear force as F, and we have written delta H is equal to Q into delta X. So if we replace delta H with F, so F will be equal to Q into X. Clear? So Q is 3704 Newton per meter and X is 25 millimeter, which is equal to 0.025. So when you multiply this, so horizontal shear force comes out to be 92.6 Newton. So this was all about part first of the chapter number 6. I hope you have enjoyed the video. If you have any question, you can ask in comment section. Thank you. Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you. Bismillahirrahmanirrahim, and welcome back to the second part of the lecture, that is from chapter number 6, shearing stresses in beam and thin wall member. So in today's lecture we are going to discuss how to find the shear stresses in the beam and thin wall member. In our part first, we discussed how to find the shear force, that is delta H is equal to Q into delta X, where H is the horizontal shear force, Q is shear flow, and delta X is the length. And we also discussed Q is equal to VQ divided by I, where V is shear force, Q is the first moment of inertia about neutral axis, and I is the second moment of inertia about the neutral axis. So in this lecture we are going to find out shearing stresses in the beam and thin wall member. So this is the same thing that we discussed in our part first. So we came out with a conclusion that delta H is equal to Q into delta X. So this was a horizontal shear force. So how we can find the shearing stress? So definitely shearing stress will be equal to shearing force over shearing area. So this was the figure, and we find out the delta H that is acting on this space or in this area, that is represented as delta A. So horizontal shear force will be acting on this surface having area delta A. So we can find out the average shear stress by using equation delta H over delta A. So delta H is horizontal shear force and delta A is the area over this area that is parallel to this shear force. So if this area is represented as delta A and having thickness T, that is represented, and in this direction having delta length is equal to delta X. So tau average shear stress is equal to delta H over delta A, and we know that delta H is equal to Q into delta X over delta A. Now if we replace delta A with T into delta X, clear? So here I have represented A in terms of T into delta X. Q is also equal to VQ over I, and delta X will remain same. So delta X will cancel with delta X, and we will have the equation of average shear stress is equal to VQ over I into T, where V is the shear force, Q is the first moment of inertia, I is the second moment of inertia about neutral axis, and T is the thickness of the beam. Clear? So this will be the average shear stress that will be acting over the surface of this C dash, C2 double dash, D2 dash and D1 dash. Okay, if we take the whole beam, not this section, I am talking about the whole beam. So you can see that there is no external force, shear force acting on the surface. So on the upper and lower surface of the beam, top y axis is 0. So it follows that top xy is equal to 0 on the upper and lower edge of the transverse section. So you can see on the upper and lower portion of the beam, there is no external shear force. It means that the surface have no shear force top xy. So we have discussed that if there is no shear force on the top of the beam, so the upper and lower surface of the transverse section, so this top of xy will be also 0. Clear? One more thing is that we have calculated the average shear stress is equal to VQ over IT. Now this is the average shear force stress, not the shear stress. Clear? So this shear stress will be maximum at D2 and D2 dash and D1 dash, and it will be minimum at D. Why? The reason is that you can see that the thickness of this beam, which is D1, D2 dash, clear, or this surface, D1 dash, D2 dash is larger than the height or depth of the beam. So in this scenario, the shear stress will be maximum at D2 dash and D1 dash, and it will be less in D dash. So if the width of the beam is comparable or large relative to its depth, so you can see width of the beam is large, comparatively large or equal to the depth of the beam. Clear? So the shearing stress at D1 and D2 are significantly higher than D. So average shear stress at D1 and D2 will be higher than at D1. Now we will show you some example of shearing stresses in rectangular beam and wide flange beam. So you can see that we have a rectangular beam shown in this figure. Clear? Let the breadth of or width of this beam or thickness of this beam is B, and total height of this beam is H. Clear? So definitely the neutral axis will be passing through the mid of this, and that will be passing through H by 2. So this will be your neutral axis. Now from neutral axis to the topmost edge, the distance is represented as C, which is definitely equal to half of total height. Similarly, the lower C is also same, and that is equal to half of C dash. Clear? Now we take a small area above the neutral axis. Let this is the area A dash. This is the area A dash, in which we are going to find out the shear stress, that what will be the shear stress or what will be the distribution of shear stress. So as you know that shear stress is equal to VQ over I into T. So in this case, this T is equal to B, so it will be equal to VQ over IB. Now we have to find Q for this beam. Q is the first moment of inertia of this section A dash. I is the moment of inertia of this whole beam, rectangular beam, and B is the breadth. So we can find out the equation of shear stress in this rectangular beam. So as you know that this Q, which is the first moment of inertia, is equal to A into Y dash. A is the moment of inertia of this shaded area, and Y dash, what is the Y dash? Y dash is the distance from neutral axis to the mid of this area, to the mid or centroid of this area A dash, and this is Y dash. Clear? So what is A dash, or area of this shaded portion? So you can see it is B into this thickness, this height. So this is total is 1 over 2h, and this is h. The lower surface of this area is at a distance of y. So this distance will be equal to 1 over 2. Sorry, this distance will be equal to this distance minus y. So 1 over 2h minus y. Or you can simply say that it is equal to c over 2 minus y. Sorry, not c over 2. Let me write it. It can be written as c minus y. C minus y, because this total distance is c and this is y, so it will be equal to c minus y. So area is equal to b breadth, this breadth, and height is equal to c minus y. Now what is this y dash? Now this y dash is this distance, and it is equal to y plus this distance. So we can write it as y plus c minus y over 2. If you solve this term, so this term will comes out to be, let me write it, b into c minus y, and this term will come out to be 1 over 2 c plus y. Clear? So this is the first moment of inertia of this shaded area A dash, which is equal to b into c minus y into half of c plus y. Now what is the moment of inertia of this whole beam? And we know that moment of inertia of this whole beam is equal to 1 over 12 bh cube. Clear? So you can see that 1 over 2 h is equal to, total h is equal to 2c. Clear? So it will be 2c. So instant of this will be equal to 2c whole cube. And we will have I is equal to second moment of inertia about neutral axis comes out to be 2 over 3 bc cube. 2 over 3, this is 12. 2 over 3 bc cube. This is the second moment of inertia. So we have q, we have I, you can put it in this equation. So when you put it this equation and when you solve it, so you will have tau of xy, or this shear stress will be equal to 3 over 2 into v by a into 1 minus y square over c square. So this is the shear stress that will be acting on this beam, and it is written over here. Why it is tau of xy? So you can see this is, let me delete something so you can see that this is z-axis, this is y-axis. So this space is again this will be the x-plane and in the direction of y. So this shear stress will be tau of xy. So this tau of xy is basically written as vq over ib, and that is equal to, after further derivation, we come out with a formula that is equal to 3v over 2a into y, 1 minus y square over c square. Now this shear stress is a second degree equation. You can see it depends on y square. So it will be a parabolic. Now if we draw the distribution of this shear force over the beam, so if you put y is equal to 0,
So if this is equal to 0, any 0 divided by something will be 0, and we will have the shear force will be, which will be the maximum, and that will be equal to 3V over 2A. So let this point is the maximum shear stress. If y is equal to c, if y becomes equal to c, because y is the distance from neutral axis to the point where you want to find the stress. So if y is equal to c, so this term will be equal to 1, and 1 minus 1 is equal to 0, so whole term will be 0. So means shear stress will be 0 at this point. Similarly, shear stress below this point is also 0. Also, it is a quadratic equation, so the distribution will be a parabolic distribution. So this is the stress, shearing stress in rectangular beam, or distribution of shearing stress in the rectangular beam. Now we can also have a wide flange beam or W or short beams that is available in American standards. Clear? So you can see the figure over here. This is the thickness of this beam. This is total height, and distribution is shown. As we know that every shear stress is equal to VQ over IT. So you can see the shearing stress is maximum at the neutral axis because y is equal to 0, and shearing stress is 0 at the outermost. So for the first flange, it will take some shear stress, and then whole shear stress will be exerted on this web. This is the web, this is flange, this is also flange. So shear stress distribution in the thin wall member will be like this. This is the average shear stress. So maximum stress will be in the web portion. For American standard S and wide flange beam, average shear stress which is equal to VQ over IT. By average we means that the shearing stress available in flange and web, but most of the shearing stress will be in the web because the neutral axis is passing through the centroid and there is available in the web. So maximum shearing stress will be available in the web portion. This is the web portion. Clear? And that can be represented by using formula tau max is equal to shear force over area of the web. Okay, let's solve a design problem for the beam in which we will see how to design a beam that is given in this figure. So this is a timber beam. The statement of problem is that a timber beam is supported to support the 3 concentrated loads. So there is a timber beam that is supported by 3 concentrated load. We have given that knowing that for the grade of timber used, sigma allowable is 1800 psi and maximum shearing stress allowable is 120 psi. So you have to determine the minimum required depth of D of the beam. So in cross section of the beam is given that is 3.5 into D. So you have to design or you have to find out this depth D in order so that it can satisfy these conditions are maximum allowable stress and maximum allowable shearing stress for this load. So how we will design or how we will solve this problem? So first we have given sigma allowable, and as you know that sigma allowable can also be written as sigma max, and sigma max is equal to maximum bending moment into C divided by I, or we can also write as maximum bending moment divided by section modulus. So by using these forces we will find out maximum bending moment, and what we will do, we will have to draw the shear force and bending moment diagram. Once you draw the shear force and bending moment diagram, so you will get a maximum bending moment. We have the value of maximum bending stress. So we have this value and this value. Let me write it again. Is this maximum bending moment over section modulus.
So you will be have this value and this value, so you can calculate S. When you get S, and for rectangular beam, you know that S is equal to 1 over 6 BH square, 1 over 6, let me write, we will also check it later, BH square, where H is the depth, clear, D. So we have this value, we have B, so we can find this depth D. Let me write it as D square. So we can by using this method we can find the depth. Also, second, we will find we have given tau allowable, and that is equal to tau maximum. This tau maximum is equal to VQ over I into T. So again, here tau maximum will be equal to maximum shear stress. So maximum shear stress will be taken from the shear force diagram. Q can be calculated. I can for the beam can also be calculated, and thickness is 3.5. So you can calculate the maximum shear stress. Again, so you have maximum shear stress. Q is the first moment of inertia, cannot be calculated. So we have this, and for I, because I is the rectangular, so we can also calculate the value of area if we have maximum shear stress and maximum shear force. So let's move toward the problem and we will see. So first of all, you have to find out the reaction forces at point A and B, and I will not do that. You have to calculate it yourself. So you can see that these are the reaction forces at point A and at point C. Now if you draw the shear force diagram, so you have to draw the two lines from at end of the beam, and you have to join these two lines. These lines show you the length across the longitudinal stress. Now you can see there is a shear force of 3 kips, so it will go upward to 3 kips. Now from A to C there is no load, so it will be the same. So at point C there is 2.5 kilonewton concentrated load. So 3 minus 2.5 is 0.5. So at point C it will reduce to 0.5. Now from C to D there is no load, so it will be remain same 0.5. At point C there is a load of 1. So 1 is downward and 0.5. So that will be 0.5 is plus. So that will be minus 0.5. So it will go to minus 0.5. From D to E there is no load, so it will be minus 0.5. Now this is minus 0.5 and this load is also negative 2.5. So 2.5 and 0.5 is 3. So it will be minus 3. Again it will be the same till this. So you can see at the end there is 3 kips and this 3 kips. So this is the shear force diagram. Now you know for bending moment diagram we can find it easily by area under the shear stress. So from A to C the area is this one. So 3 into 2, which is equal to 6. That is written over here, plus 6. Now from area under the shear force diagram between C and D is, so this force was 0.5 and this distance is 3. So it is 1.5. Again this area from D to E, this area. So minus 0.5 into 3 is minus 1.5. And this area is, total is 3 and this is 2, which is minus 6. Clear? So you can also calculate it. This is 6, 1.5 minus 1.5 minus 6. So if you plot them, so at point A there is shear force but no bending moment, so it will be 0. So at point C the area, the shear bending moment is 6. So you have to plot 6. And since it is a 0 degree equation, it will be a straight line, a linear line. Now at point from C to D, this is 1.5. So this was 6 and this is plus 1.5. Total will be 7.5. So you have to plot 7.5, and again the line between C and D is 0 degree line, so it will be the bending moment will be the linear equation. Now when you move from here to here, so total is 7.5 minus 1.5, so it will be again 6, so it will be 6. Now it is the 0 degree line and it is negative, so it will be in linear line but slope will be decreasing. Similarly, from this is minus 6 and this 6, so it will be 0. Minus 6 plus 6 will be 0. So from this diagram, this is the bending moment diagram. From this diagram, we can see that the maximum bending moment is equal to 7.5 kips, and the maximum shear force is 3 kips. You can see this is 3, this is 0.5, this is minus 0.5 and this is minus 3. So maximum shear force is 3 kips and maximum bending moment is 7.5 kips into foot, which we have converted into inch. So that will be 90 kips into inch. Now we have given the maximum, we know that allowable stress is equal to maximum bending moment over section modulus. So maximum bending allowable stress was 1800 psi. Maximum bending moment we find out in previous slide, that is 19 to 10 power 3 lb into inch, and section modulus is equal to 1 over 6 bd square, because this is the depth section modulus. So you have, when you put the value of b, which is 3.5, and divide it by 6, so it will be 0.5833 into d square. So again d will be here and this 1800 will come down. So when you take the under root of d square, so it will be d, and this d is 9.26 inch. This is how we can find the depth by using the allowable shearing stress, allowable bending stress or normal stress. Now we will determine this depth based on the allowable shear stress. Now we know that maximum shear stress from this figure, this is for rectangular beam. So maximum shear stress is equal to 3 over 2 VA, which is equal to 3 over 2 V max over A. And this maximum shearing stress allowable is given as 120 psi. 3 over 2 V is also obtained by using the maximum shear force diagram, 3 kips. And area, you know that area of this beam is equal to 3.5 into depth. So 3.5 into depth, which is unknown. So you can calculate the value of depth. Now if you see that we have two value of depth, one is this one and one is this one. So for safety purpose, you have to choose the largest value of depth. So we will choose this depth, d is equal to 10.71 inch. Why we choose the largest? Because if we choose the smallest value, so maybe that is not supported by the allowable shearing stress or maximum bending stress. So if we use this depth, that will be that will satisfy the criteria of maximum allowable stress and maximum shearing stress. So this is how we have calculated the required depth of the beam, that is equal to the largest of two, and that is 10.71. Thank you for watching the video. If you like the video, kindly subscribe, like and share. Thank you. Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you. Bismillahirrahmanirrahim, and welcome back to the part 3 of chapter number 6. In this chapter we will discuss the shearing stress in beam and thin wall member. So the topic is again shearing stress in thin wall member. So consider a segment of wide flange beam subjected to vertical shear V. So you can see this is a wide flange beam and that is subjected to a vertical shear force V. The longitudinal direction is X, the vertical direction is Y, and transverse direction is Z. The thickness of this wide flange beam the width of this thin wall beam is delta X. So we are going to take a small segment of the flange, wide flange. Clear? So this is the section that we are going to take for our analysis purpose in order to show the shear stress in thin-walled member. So this is the member that is shown as B dash, B, A dash, B dash, B, A and A dash. The thickness of this flange is T, while the width is, or length is delta X. So there is a vertical shear force acting on the beam, and if we cut out this flange from or a segment of flange from this beam, so there will be a horizontal shear force also acting on beam. If you look into this figure, you can find out that this web is perpendicular to x direction, so this shear force V will be equal to tau of x, and it is in direction of y. So this shear force is tau of xy. Now this horizontal shear force is actually tau of zx. How? You can see this face is perpendicular to z. This face is perpendicular to z, and it is in the direction of x. So that is tau of xz. So the shearing stress in the flange is tau of xz, while shearing stress in the web is tau of xy. Now this shearing stress in the flange is equal to tau of xz, which is equal to horizontal shear force, which is delta H over the area. Now this area is equal to delta X into T, which is equal to delta H over delta X into T. This is the horizontal shear stress that is acting on this flange. Clear? So as we know that the longitudinal shear force on the element is delta X. This is the longitudinal or horizontal shear stress, shear force that is equal to VQI into delta X, as this delta H is equal to Q into delta X. So Q is equal to VQ over I into delta X, where Q is the shear floor, X is the length, V is the shear force, Q is the first moment of inertia, I is the second moment of inertia, and delta H is horizontal shear force. So this delta H is equal to VQ over I into delta X. The corresponding shearing stress is tau of xz. So due to this horizontal shear stress, the shear force, horizontal shear force, the shear stress tau of xz is equal to delta H over area, which is equal to T into delta X. So this delta H is equal to VQI into delta X. So if you put it, let me solve this, delta H is equal to VQI into delta X. Again, let this tau is equal to delta H over area, and this is equal to delta H over T into delta X, and again this delta H is equal to VQ over I into delta X. There, and again the area that was T into delta X. So delta X will be cut out, so we will have shear stress is equal to VQ over I into T, that is presented, and we also know that tau of xz is equal to tau of zx, so it will be the same. Previously we found out a similar expression for the shearing stress in the web, and the shearing stress in the web is tau of xy. I have already discussed why it is xy, because this surface is perpendicular to x, so this is tau of x and the direction of y. So first subscript is used for the face that is perpendicular to the axis. It is perpendicular to the axis, so tau of x-axis, so it will be tau of x, and the force is in direction of y. So this is tau of xy. Now this tau of xy is also again VQ over IT. Both equations are same, but the value will be different. Also note that we have already discussed that any surface will be having three forces. One will be normal force and two will be the shear force. So now in this condition, the only force that is acting, shear force that is acting on this surface is tau of xz, and there will be again tau of xy, but that will be equal to 0. Why it is 0? Because in flange you know that thickness is very small, so the shearing stress in this flange will be 0. Tau of xy will be equal to 0, and only the shearing stress will be tau of xz. Similarly, in web portion there is a shearing stress of tau of xy, but there will be tau of xz will be equal to 0, because the thickness of web is also very small in z direction, so this term will be equal to 0. So flange will experience only a shear stress that is tau of zx, and web only experience a shear stress of tau of xy. Now we will discuss something thing about shear flow on thin wall members. So you can see there is a hollow rectangular thin walled member. So the variation of shear flow across the section depend only on the variation of first moment of inertia, because we know that Q is equal to tau into T. How this is Q is equal to tau into T, as we know that Q is equal to delta H over delta X. Clear? And delta X is again this, that delta X is equal to VQ over I into delta X, and this delta X will be remain same. Clear? So this delta X will be cut with delta X, and Q will be equal to VQ. Q will be equal to VQ over I. If we multiply and divide it with delta T, so this VQ, sorry, not delta T. If you divide both with T, so we know that VQ over IT is equal to shear stress. So Q will be equal to shear stress, and this T will remain same. So Q is equal to T into T, which is equal to VQ over I. Now the shear flow in this box type beam will be represented as that the shear force that is acting at point A will come to point A. At this point A, shear stress will be 0, and this flow will split into two, from A to B dash and A to B, and the shear stress will flow toward this, and from B it will come towards C and C dash, and from C dash it is again coming toward point E, and they are merging, and at point E the shear stress will be 0. Now the shear stress or the shear flow is at point A is 0, and it is increasing and moving toward point C dash, where C shear flow will be maximum at neutral axis or C dash. It will be minimum. Q flow will be minimum over here, and again at point E, Q will be equal to 0. Clear? So for a box beam, Q grows smoothly from 0 at A to maximum at C and C dash, and then back to 0 to E. So from A to B or from A to C, C dash, it is increasing our maximum, and then from C to E or C dash to E, it is again coming back and decreasing, and at point E it becomes 0. The sense of Q in horizontal portion of the section may be deduced from the sense in vertical portion of the sense of shear force. So you can see that the shear stress flow is from point A, it is deduced, that is split into two, and then it is coming toward point C, and again it is merging. So if the force was like this, is the shear force will be like this. So again from point E it will be toward this, and it will be merging at point A, and it will give you 0. Also, why the shear force is or the shear flow is maximum at C. So we know that shear flow is equal to VQ over I, and that depend on the Q, where Q is the first moment of in area. Clear? So if you are taking the measuring the shearing stress or flow over here, so only the area will be this one. But if you are moving towards C, again the area is increasing. Clear? So Q is increasing, meaning the shear flow will be maximum toward the neutral axis, or it will be maximum at the neutral axis. Now we will discuss the shearing stress or shear flow in the W beam or short flange beam. So in our previous discussion, in which we discussed a box beam, and we find out that the shear flow at point will transfer to point A, and at point A it will split toward B and B dash, and then from B dash to B, and from B dash and B it will move towards C, and at the end it will come at point E, where the shear stress will be 0. Now in thin wall section it is completely different. That this is a thin wall section, and it is subjected to shear force. When you apply shear force, the shear flow will start from this position, A and A dash, and it will start from A and move toward point B, where point B it will be moved down toward point C. So the shear, let Q1 is the shear flow from A to B, and Q2 is the shear flow from A dash to B, and they meet at point B. The total flow will be Q1 plus Q2, and that will be maximum toward neutral axis. And when it moves from point B, from point C to D, again after reaching point C it will split into two, moving toward from D to E and D to E dash, and at point E dash and E the shear flow or shear stress will be 0. So for a wide flange beam, the shear flow increases symmetrically from 0 at A and A dash. It will symmetrically 0 and flow from A to A dash, and reaches a maximum at C, and then decreases to 0 at E and E dash, and then from E to E dash it is 0. And it is the same as the continuity of variation in Q and emerging from Q from section branches, and suggest an analogy of fluid flow. So it also follow the analogy of fluid flow, that from A and A dash and A it comes, and then it merge and flow towards C, and at reaching point D it moves toward E and E dash, and then it becomes 0. So this is how the variation of shear flow in the thin walled member or wide flange beam and short flange beam. I hope you have enjoyed this short video. If you like the video, kindly subscribe, like and watch.